Hi there, welcome to Complete Machine Learning Engineer full course. In today's AI-driven world, machines are no longer just following instructions. They are learning from data and improving over time. From recommendation systems to fraud detections to self-driving cars and intelligent chatbots, machine learning powers many of the technologies we use every day. Machine learning engineering goes beyond theory. It involves working with data, building models, optimization, performance, and also deploying solutions that can handle real-world scale and complexity. In this Complete Machine Learning Engineer course, you will learn how to move from foundational concepts to build and deploying machine learning systems. We'll start with the basics of Python, mathematics, statistics, and then progress into core machine learning algorithms, model evaluation, and optimization techniques. As you advance, you will also explore important areas such as feature engineering, deep learning, model deployment, and MLOps practices. You will also gain hands-on experience with industry tools and libraries used to build and manage machine learning workflows. By the end of this course, you will have a strong understanding of how machine learning models are built, evaluated, and deployed in production environments. Having said that, let's take a look at today's agenda for this course. We'll start off with Module 1, which is Introduction to Machine Learning and AI. Module 2 is Python Programming for Machine Learning. Module 3 is Mathematics and Statistics for ML. Module 4 is Data Collection and Data Preprocessing. Module 5 is Exploratory Data Analysis. Module 6 is Feature Engineering and Feature Selection. Module 7 is Supervised Learning Algorithms. Module 8 is Unsupervised Learning Algorithms. Module 9 is Model Evaluation and Performance Metrics. Module 10 is Introduction to Deep Learning. Module 11 is Model Deployment Basics. Module 12 is MLOps and Model Lifecycle Management. Module 13 is Real-World Machine Learning Projects. Module 14 is Interview, Question, and Career Guidance. Hope I made myself clear with this agenda. That said, if these are the type of videos you'd like to watch, then hit that subscribe button with the bell icon to get notified whenever we host. Also, just so that you know, if you want to upskill yourself, master generative AI, and land your dream job or even grow in your career, then you must explore Simplilearn's cohort of various generative AI training and professional certificate programs. Simplilearn offers a variety of master's, certification, and postgraduate programs in collaboration with some of the world's leading universities. Through our courses, you will gain knowledge along with work-ready expertise in skills like Python, agentic AI, AI automation systems, LLMs, and over a dozen others. And that's not all. You'll also get the opportunity to work on multiple projects led by industry experts working in top-tier service-based and product companies. After completing these courses, thousands of learners have transitioned into AI and machine learning role as a fresher or moved on to a higher paying job in profile. If you're passionate about making your career in this field, then make sure to check out the link in the pinned comments and in the description box to find an AI and machine learning program that fits your experience and areas of interest. So let's get started with our Machine Learning Engineer full course with a small quiz. Which type of learning uses labeled data? Is it unsupervised learning, supervised learning, reinforcement learning, deep learning? Please let us know your answers in the comment section below. Now over to our training experts.
We know humans learn from their past experiences, and machines follow instructions given by humans. But what if humans can train the machines to learn from their past data and do what humans can do and much faster? Well, that's called machine learning. But it's a lot more than just learning. It's also about understanding and reasoning. So today, we will learn about the basics of machine learning. So that's Paul. He loves listening to new songs. He either likes them or dislikes them. Paul decides this on the basis of the song's tempo, genre, intensity, and the gender of voice. For simplicity, let's just use tempo and intensity for now. So here, tempo is on the x-axis, ranging from relaxed to fast, whereas intensity is on the y-axis, ranging from light to soaring. We see that Paul likes the song with fast tempo and soaring intensity, while he dislikes the song with relaxed tempo and light intensity. So now we know Paul's choices. Let's say Paul listens to a new song. Let's name it as Song A. Song A has fast tempo and a soaring intensity, so it lies somewhere here. Looking at the data, can you guess whether Paul will like the song or not? Correct. So Paul likes this song. By looking at Paul's past choices, we were able to classify the unknown song very easily, right? Let's say now Paul listens to a new song. Let's label it as Song B. So Song B lies somewhere here with medium tempo and medium intensity. Neither relaxed nor fast, neither light nor soaring. Now can you guess whether Paul likes it or not? Not able to guess whether Paul will like it or dislike it? Are the choices unclear? Correct. We could easily classify song A. But when the choice became complicated, as in the case of song B, yes, and that's where machine learning comes in. Let's see how. In the same example, for song B, if we draw a circle around the song B, we see that there are 4 votes for like, whereas 1 vote for dislike. If we go for the majority votes, we can say that Paul will definitely like the song. That's all. This was a basic machine learning algorithm also. It's called k-nearest neighbors. So this is just a small example in one of the many machine learning algorithms. Quite easy, right? Believe me, it is. But what happens when the choices become complicated, as in the case of song B? That's when machine learning comes in. It learns the data, builds the prediction model, and when the new data point comes in, it can easily predict for it. More the data, better the model, higher will be the accuracy. There are many ways in which the machine learns. It could be either supervised learning, unsupervised learning, or reinforcement learning. Let's first quickly understand supervised learning. Suppose your friend gives you 1 million coins of 3 different currencies, say 1 rupee, 1 euro and 1 dirham. Each coin has different weights. For example, a coin of 1 rupee weighs 3 grams, 1 euro weighs 7 grams and 1 dirham weighs 4 grams. Your model will predict the currency of the coin. Here, your weight becomes the feature of coins, while currency becomes their label. When you feed this data to the machine learning model, it learns which feature is associated with which label. For example, it will learn that if a coin is of 3 grams, it will be a 1 rupee coin. Let's give a new coin to the machine. On the basis of the weight of the new coin, your model will predict the currency. Hence, supervised learning uses labeled data to train the model. Here the machine knew the features of the object and also the labels associated with those features. On this note, let's move to unsupervised learning and see the difference. Suppose you have cricket dataset of various players with their respective scores and the wickets taken. When we feed this dataset to the machine identifies the pattern of player performance. So it plots this data with the respective wickets on the x-axis while runs on the y-axis. While looking at the data, you will clearly see that there are 2 clusters. The one cluster are the players who scored high runs and took less wickets, while the other cluster is of the players who scored less runs but took many wickets. So here we interpret these 2 clusters as batsmen and bowlers. The important point to note here is that there were no labels of batsmen and bowlers. Hence, the learning with unlabeled data is unsupervised learning. So we saw supervised learning where the data was labeled and the unsupervised learning where the data was unlabeled. And then there is reinforcement learning, which is reward-based learning, or we can say that it works on the principle of feedback. Here, let's say you provide the system with an image of a dog and ask it to identify it. The system identifies it as a cat. So you give a negative feedback to the machine saying that it's a dog's image. The machine will learn from the feedback, and finally if it comes across any other image of a dog, it will be able to classify it correctly. That is reinforcement learning. To generalize machine learning model, let's see a flowchart. Input is given to a machine learning model, which then gives the output according to the algorithm applied. If it's right, we take the output as our final result. Else, we provide feedback to the training model and ask it to predict until it learns. I hope you've understood supervised and unsupervised learning. So let's have a quick quiz. You have to determine whether the given scenarios uses supervised or unsupervised learning. Simple, right? Scenario 1. Facebook recognizes your friend in a picture from an album of tagged photographs. Scenario 2. Netflix recommends new movies based on someone's past movie choices. Scenario 3. Analyzing bank data for suspicious transactions and flagging the fraud transactions. Think wisely and comment below your answers. Moving on, don't you sometimes wonder how is machine learning possible in today's era? Well, that's because today we have humongous data available. Everybody is online, either making a transaction or just surfing the internet, and that's generating a huge amount of data every minute. And that data, my friend, is the key to analysis. Also, the memory handling capabilities of computers have largely increased, which helps them to process such a huge amount of data at hand without any delay. And yes, computers now have great computational powers. So there are a lot of applications of machine learning out there. To name a few, machine learning is used in healthcare, where diagnostics are predicted for doctors' review. The sentiment analysis that the tech giants are doing on social media is another interesting application of machine learning. Fraud detection in the finance sector, and also to predict customer churn in the e-commerce sector. While booking a cab, you must have encountered surge pricing often, where it says the fare of your trip has been updated. Continue booking? Yes, please, I'm getting late for office. Well, that's an interesting machine learning model which is used by global taxi giant Uber and others, where they have differential pricing in real time based on demand, the number of cars available, bad weather, rush hour, etc. So they use the surge pricing model to ensure that those who need a cab can get one. Also, it uses predictive modeling to predict where the demand will be high, with the goal that drivers can take care of the demand and surge pricing can be minimized. Great! Hey Siri, can you remind me to book a cab at 6 p.m. today?
Okay, I'll remind you.
Thanks.
No problem.
Comment below some interesting everyday examples around you where machines are learning and doing amazing jobs. So that's all for machine learning basics today from my side. Keep watching this space for more interesting videos. Until then, happy learning.
Artificial intelligence, machine learning, and deep learning represent the evolution of computer science towards creating intelligent systems. AI is the broader concept, striving to build machines capable of human-like intelligence. ML is a subset of AI, emphasizing algorithms that learn from data to make predictions or decisions. DL in turn is a specialized branch of ML that employs deep neural networks to model complex patterns. Imagine an AI-powered voice assistant like Apple's Siri. It utilizes ML to understand and respond to user queries, learning from interactions over time. Deep learning comes into play when Siri recognizes speech patterns or interprets natural language, using neural networks to process intricate features. The better it becomes at understanding diverse accents or refining responses, exemplifying the continuous learning inherent in these technologies. AI seeks to emulate human intelligence, ML harnesses data for learning, and DL employs deep neural networks for intricate tasks. The integration of these technologies manifests in everyday applications, transforming how we interact with and benefit from intelligent systems. This technology enables voice interaction, allowing the device to play music, set alarms, present audiobooks, and provide up-to-date information on topics like news, weather, sports, and traffic reports, etc. Let's move forward and see what is machine learning. Machine learning is a subset of artificial intelligence that focuses on developing algorithms and models capable of learning and making predictions or decisions without being explicitly programmed. ML systems leverage data to recognize patterns, adapt, and improve their performance over time. There are several types of machine learning. Number 1. Supervised learning. The algorithm is trained on a labeled dataset where each input is associated with a corresponding output. Number 2 comes as unsupervised learning. Unsupervised learning deals with unlabeled data to find inherent patterns or structures within the information. And then comes the reinforcement learning. This type involves training agents to make sequences of decisions by interacting with an environment. And then comes semi-supervised learning. Semi-supervised learning combines supervised and unsupervised learning elements, typically using a small amount of labeled data and a larger pool of unlabeled data. Let us move forward and see what deep learning is. Deep learning, a branch of machine learning, focuses on algorithms inspired by the human brain structure and functionality. It excels in processing vast amounts of both structured and unstructured data. At the heart of deep learning are artificial neural networks, empowering machines to make decisions. The key distinction between deep learning and machine learning lies in data presentation. Machine learning algorithms typically demand structured data, while deep learning networks operate through multiple layers of artificial neural networks, allowing them to handle diverse data formats. So let's start with the difference between artificial intelligence, machine learning, and deep learning. And this will show in a tabular form. So starting with the definition. So definition of artificial intelligence. So broad field of machine learning or creating machines with intelligent behavior is artificial intelligence. And when we talk about machine learning, it's the subset of AI focusing on algorithms learning from data. And then comes the deep learning, that is specialized subset of ML using deep neural networks. And now we'll see the difference with the learning approach between all these three. So in learning approach, artificial intelligence can include rule-based systems, expert system, and more. And in machine learning, it learns from data patterns without explicit programming. And then comes the deep learning, where it learns hierarchical representation using neural networks. And if we talk about scope, it encompasses various techniques beyond learning from data. And in machine learning, it primarily focuses on learning patterns from data. And then the deep learning, it specifically utilizes deep neural networks for complex tasks. And now we'll move to the next difference and we'll start with an example. So in artificial intelligence, the example is autonomous vehicles, chatbots, or expert systems. And for machine learning, it's spam filters, recommendation systems, image recognition. And in deep learning, it is image and speech recognition, natural language processing. And now we'll see the difference for the data requirements. So it depends on the specific application and problem solving approach. And in machine learning, it requires labeled or unlabeled data or training. And for the deep learning, it relies on large amounts of labeled data for training deep networks. And now for the complexity, artificial intelligence addresses a wide range of tasks, including those beyond ML. And in machine learning, it deals with moderate to complex tasks depending on algorithms. And for the deep learning, it is well suited for intricate tasks, often requiring substantial computational resources. And now see the flexibility. So for the artificial intelligence, it can be rule-based, evolving, and adaptive. And for the machine learning, the flexibility adapts to patterns and the changes in data. And for the deep learning, it adapts to hierarchical representations and diverse data types. And then comes the training process. So in artificial intelligence, training process varies based on specific AI techniques used. And in machine learning, training involves feeding data and adjusting model parameters. And in deep learning, training involves optimizing neural weights and structures. And now we'll talk about the applications between all these three terms, that is AI, ML, and deep learning. So for artificial intelligence, the applications are robotics, natural language processing, game playing. And for machine learning, it's predictive analytics, fraud detection, and healthcare diagnostic. And for the deep learning, it is image recognition, speech synthesis, and language translation.
We have Rahul, who will take you through the various applications of machine learning and how you can be a machine learning engineer.
Machine learning has improved our lives in a number of wonderful ways. Today, let's talk about some of these. I'm Rahul from Simplilearn, and these are the top 10 applications of machine learning. First, let's talk about virtual personal assistants. Google Assistant, Alexa, Cortana, and Siri. Now, we've all used one of these at least at some point in our lives. Now, these help improve our lives in a great number of ways. For example, you could tell them to call someone. You could tell them to play some music. You could tell them to even schedule an appointment. So how do these things actually work? First, they record whatever you're saying, send it over to a server, which is usually in a cloud, decode it with the help of machine learning and neural networks, and then provide you with an output. So if you've ever noticed that these systems don't work very well without the internet, that's because the server couldn't be contacted. Next, let's talk about traffic predictions. Now say I wanted to travel from Buckingham Palace to Lord's Cricket Ground. The first thing I would probably do is to get on Google Maps. So, search it. And let's put it here. So here we have the path you should take to get to Lord's Cricket Ground. Now here the map is a combination of red, yellow and blue. Now the blue regions signify a clear road, that is you won't encounter traffic there. The yellow indicate that they are slightly congested and red means they're heavily congested. So let's look at the map, a different version of the same map. And here, as I told you before, red means heavily congested, yellow means slow moving and blue means clear. So how exactly is Google able to tell you that the traffic is clear, slow moving or heavily congested? So this is with the help of machine learning and with the help of two important measures. First is the average time that's taken on specific days at specific times on that route. The second one is the real-time location data of vehicles from Google Maps and with the help of sensors. Some of the other popular map services are Bing Maps, Maps.me, and here we go. Next up, we have social media personalization. So say I want to buy a drone and I'm on Amazon and I want to buy a DJI Mavic Pro. The thing is it's close to 1 lakh, so I don't want to buy it right now. But the next time I'm on Facebook, I'll see an advertisement for the product. The next time I'm on YouTube, I'll see an advertisement. Even on Instagram, I'll see an advertisement. So here, with the help of machine learning, Google has understood that I'm interested in this particular product. Hence, it's targeting me with these advertisements. This is also with the help of machine learning. Let's talk about email spam filtering. Now, this is the spam that's in my inbox. Now, how does Gmail know what's spam and what's not spam? So Gmail has an entire collection of emails which have already been labeled as spam or not spam. So after analyzing this data, Gmail is able to find some characteristics like the word lottery or winner. From then on, any new email that comes to your inbox goes through a few spam filters to decide whether it's spam or not. Now, some of the popular spam filters that Gmail uses is content filters, header filters, general blacklist filters, and so on. Next, we have online fraud detection. Now, there are several ways that online fraud can take place. For example, there's identity theft, where they steal your identity, fake accounts, where these accounts only last for how long the transaction takes place and stop existing after that, and man-in-the-middle attacks, where they steal your money while the transaction is taking place. The feed-forward neural network helps determine whether a transaction is genuine or fraudulent. So what happens with feed-forward neural networks are that the outputs are converted into hash values, and these values become the inputs for the next round. So for every real transaction that takes place, there's a specific pattern. A fraudulent transaction would stand out because of the significant changes that it would cause with the hash values. Stock market trading. Machine learning is used extensively when it comes to stock market trading. Now you have stock market indices like Nikkei. They use long short-term memory neural networks. Now these are used to classify, process, and predict data when there are time lags of unknown size and duration. Now this is used to predict stock market trends. Assistive medical technology. Now, medical technology has been innovated. With the help of machine learning, diagnosing diseases has been easier, from which we can create 3D models that can predict where exactly there are lesions in the brain. It works just as well for brain tumors and ischemic stroke lesions. They can also be used in fetal imaging and cardiac analysis. Now, some of the medical fields that machine learning will help assist in is disease identification, personalized treatment, drug discovery, clinical research, and radiology. And finally, we have automatic translation. Now, say you're in a foreign country and you see billboards and signs that you don't understand. That's where automatic translation comes of help. Now, how does automatic translation actually work? The technology behind it is the same as the sequence-to-sequence learning, which is the same thing that's used with chatbots. Here, the image recognition happens using convolutional neural networks, and the text is identified using optical character recognition. Furthermore, the sequence-to-sequence algorithm is also used to translate the text from one language to the other. And today I'm going to tell you how you can become a machine learning engineer. But before we begin, let me tell you what a machine learning engineer actually does. A machine learning engineer creates and maintains machine learning solutions to solve business problems. They constantly tweak and optimize the solutions for maximum performance and scalability. They solve business problems like reducing customer churn, running targeted marketing campaigns, and improving product experience. They also help with predicting whether a particular hypothesis will be profitable in the future. They contribute to cutting-edge research in AI and machine learning. Now, before you can start off on your journey to becoming a machine learning engineer, there's a certain number of steps that you need to follow. On this learning path, your first step is to improve your math skills. Mathematics plays a very important role in helping you understand how machine learning and its algorithms work. Among the many concepts that you need to understand, three of the most important ones are probability and statistics, linear algebra, and calculus. Now, let's have a detailed look at probability and statistics. Firstly, you have the Bayes theorem. This is used in the naive Bayes algorithm to help categorize your data. Then we have probability distribution. This helps you determine how frequently a particular event will take place. For example, you can determine what your premium for your insurance will be based on the probability distribution of expenditure pertaining to insurance claims. You must also learn how sampling and hypothesis testing works. Now, let's look at linear algebra. Now, linear algebra has two main concepts, matrices and vectors. They both used widely in machine learning. Now, matrices are used for image recognition, where the entire image that you're using is already in the form of a matrix. You need to be able to work with matrices, perform simple operations like addition, subtraction, multiplication, inverse, transpose, and so on. Now, the recommender systems that you see in applications like Netflix or Amazon actually work on vectors. This vector is the customer behavior vectors, and they use distance measures. Now, let's have a closer look at calculus. You have differential calculus and integral calculus. Now, these help in determining the probability of events. For example, in finding the posterior probability in a naive-Bayes model. In your next step to becoming a machine learning engineer, you need to develop good programming skills. And let me tell you, there are a huge number of options from which you can choose. There's Python, there's C, there's C#, there's Java, and so much more. Now here's a graph of the job postings from 2014 to 2017. And you can see that there are two languages that dominate since 2015, Python and R. Now these are one of the most wanted languages when it comes to machine learning engineers. These are closely followed by JavaScript and C. Hence, we would like to recommend that you learn Python and R as they're the best options when it comes to coding in machine learning algorithms. So here are a few things that you need to know about Python and R. Python is an object-oriented language, which means their main emphasis is on the object. R is a functional language, which means their emphasis is on creating and manipulating functions. Python relies on its many packages, and R is slightly faster than Python because it has inbuilt packages. Now Python is generic and is suitable if you need to integrate it with any other software. R works a little more closer with statistical analysis. Your next step is to get yourself some data engineering skills. Now these skills are important as they help you analyze and process your data as soon as you get it. Now there are three major steps when it comes to data engineering. Firstly, there's data preprocessing. Now these refer to all the steps that you need to perform before data can be processed by the machine learning algorithm. You have cleaning, parsing, correcting, and consolidating the data. Then you have ETL or extract, transform, and load. You need to know how data can be extracted from the internet or a local server. You need to know how to transform the data. For example, not all formats of data would be accepted by the program. So you need to convert the data into a format that is accepted by the program. Then you need to know how the data is loaded into your program. The final step is to have knowledge about database management softwares or DBMS. You need to be well versed with MySQL, the Oracle database, and NoSQL. Your next step is to learn machine learning algorithms. Now, among all the machine learning algorithms that you can see on screen, you can divide them into two different categories. Ones that fall under supervised machine learning and the others that fall under unsupervised machine learning. Even after such a division, you can further subdivide them into classification and regression algorithms. Now, all algorithms except linear regression fall under the category of classification, which is used to determine whether a particular data falls into a particular category. On the other hand, you have linear regression that falls under regression algorithms. This is used to predict a particular value. Then you have k-means clustering and hierarchical clustering. Now these fall in the category of clustering. This is used to group data into clusters based on certain similar attributes. Then you have the a priori algorithm that falls under the concept of association. Association is used to determine patterns of association among variables in large data sets. So now that you know about these algorithms, let me tell you where you can learn about them. Let's take a look at our Simplilearn channel and let's go to playlists. And on this, we have a dedicated set of playlists that talk about machine learning. Here you have videos on machine learning, how machine learning is different from deep learning and artificial intelligence, machine learning with Python, k-means clustering, decision trees, and so on. If you want to learn more, you could also go through some deep learning algorithms like convolutional neural networks, recurrent neural networks, long short-term memory networks, and so on. In fact, we have a detailed playlist that talks about the concepts of deep learning. Here you can find videos on what is deep learning, TensorFlow, what is a neural network, convolutional neural networks, and recurrent neural networks. Now, after you master these algorithms, you need to learn how you can select the right algorithm for your problem. Then you need to create a good model with one or more algorithms. After which you need to keep tweaking and optimizing the model so that you can get the maximum accuracy. For further reading, you can go through GitHub where there's more than 21,000 repositories under machine learning. You can also recreate published research papers, adding to your experience of working with machine learning. And now for your last step, learning machine learning frameworks. Machine learning frameworks help make the lives of developers as well as users a whole lot easier. They help remove the complex part of machine learning and make it available for everyone who wants to use it, be it developers or other users. Now let's look at the widely used machine learning frameworks. There's TensorFlow, Theano, Torch, Scikit-learn, and so on. Now let's look at some of them in detail. First, let's look at TensorFlow. TensorFlow is the most widely used machine learning framework. It's used for machine learning as well as deep learning. Now it's an open source software library which performs numerical computations, which is done with the help of data flow graphs. Google Translate is one of the most popular use cases of TensorFlow. Now let's look at Theano. Theano helps you define, optimize, and evaluate mathematical expressions. It was developed in the University of Montreal. Lasagne, Blocks, and Keras are its most popular libraries. Now let's look at Spark ML library. Now this is Apache Spark's machine learning component. It also provides libraries for machine learning which are built on top of RDDs or resilient distributed datasets. It's very good at providing iterative computation and provides very high algorithmic performance. Now let's look at Scikit-learn. Scikit-learn is able to provide a huge range of supervised as well as unsupervised algorithms for machine learning. It is built on existing libraries like NumPy, SciPy, and Matplotlib. Scikit-learn actually started off as a Google Summer of Code project and now has 23,000 GitHub commits. And that's it. Congratulations, you're now a machine learning engineer. Now let's look at the job opportunities in machine learning. Now if you have a look at this graph, it kind of speaks for itself. Before 2015, machine learning was much less popular than big data and cloud computing. But all of that suddenly changed. And right now, a machine learning engineer earns around $114,000 per annum. And this is a clear indication that organizations are ready to invest heavily in people who are skilled in the concepts of machine learning. You can also make the learning process easier by using Simplilearn's machine learning certification. Simplilearn's machine learning certification course provides 36 hours of instructor-led training, provides 25 plus hands-on exercises, gives you practical applications of 15 plus machine learning algorithms, and helps you master the concepts of supervised and unsupervised learning. It also introduces you to artificial intelligence, tells you the techniques of machine learning, data processing, regression, classification, and so much more. So if you want to take your first step to getting certified and getting ahead
offline, now machine learning systems are integrated into real-world operations and are capable of making decisions that impact the business immediately. Here's an example to make it clearer. In the past, an e-commerce website might use machine learning to predict what products a customer might want based on their past purchases. Now, the systems can constantly learn from new customer data, continuously refining those predictions in real time as customers' preferences are changing. The world of machine learning has evolved from theory to practice, and this has created a huge demand for machine learning engineers who can build scalable systems and make them work in real-world environments. The impact of machine learning is now directly tied to business outcomes, and machine learning engineers are at the center of that transformation. You might be thinking, okay, I get it, machine learning is impactful, but what exactly does a machine learning engineer do compared to other roles in tech? That's a great question. In the world of machine learning, you'll hear about a few key roles such as data scientist, machine learning, and AI engineer. Let's break them down so you know exactly where you fit in. Data scientists are like the detectives of data. They spend their time analyzing large data sets, finding trends, and trying to extract meaningful insights. They build models, but their main focus is usually on data exploration and experimenting with various algorithms. They don't typically focus on deploying those models into production environments. Machine learning engineers, on the other hand, these are architects. They take the models built by data scientists and build scalable, deployable systems. They work on creating solutions that will not only work in the short term, but can also scale to handle real-world data in massive volumes. The machine learning engineer is responsible for ensuring that machine learning systems are integrated into businesses that can work seamlessly with existing technologies. AI engineers focus more on the application side of things. They build AI-powered products like chatbots, voice assistants, and real-time systems. While their work often overlaps with ML engineers, they are typically more focused on the user-facing product and how machine learning fits into it. As an ML engineer, your primary focus is to take models and turn them into actionable solutions that are deployed in real-world systems. We shall now move on to why 2026 is the right time to enter machine learning. Now that you know the role of an ML engineer, let's talk about why 2026 is the perfect time for you to jump into the field. You've probably heard that machine learning is a hot topic, but what does that mean for you as someone starting out in this field? So I'll help you break that down for you. First, the demand for ML engineers has skyrocketed. The world is full of problems that need solving, and machine learning has proven to be one of the most effective tools to solve them. From predicting customer preferences to automating critical business functions, machine learning is changing how businesses operate. Secondly, the tools used to build machine learning systems are more accessible than ever before. In the past, machine learning was viewed as something experimental, something that required a lot of effort just to set up. But today, machine learning platforms and frameworks such as TensorFlow, PyTorch, and Scikit-learn have matured significantly. These tools make it easier to build and deploy models that can scale to handle real-world data. We shall now move on to why is this the right time for you to get started out as a machine learning engineer. So how do you get started? The first step is to build a strong foundation. You might be excited to start building models and diving into algorithms, but before that, you need to understand the core concepts that drive all the machine learning systems. These include mathematics, programming, and data handling. You don't need to be an expert in all of these areas, but you do need to understand the basics. Think of these as building blocks of everything that you will need to learn machine learning. Let's start with mathematics. You don't need to be a math genius, but you do need to understand the basics. There are three main areas of math that will help you get started out as an ML engineer, and those are linear algebra. This is the study of vectors and matrices which are used to manipulate and process data in machine learning models. If you've heard terms like feature vectors or matrix operations, that's linear algebra at play. This is the core of how machine learning algorithms operate. This is the math behind optimizing models. You'll use calculus to adjust the parameters of machine learning models and minimize the error between predicted and the actual values. Specifically, derivatives are used to find the best way to fit a model into the data. Statistics. Machine learning is all about working with uncertainty, and statistics will help you make sense of it. Whether you're dealing with probability distributions or hypothesis testing, statistics can help you understand patterns in data and make decisions with uncertain information. These mathematical concepts will help you build a more accurate model and optimize it effectively. Let's move on to programming stack. If you're new to programming, don't worry. Python is the language that you will want to learn. It's simple to get started with and has a huge ecosystem of libraries especially designed for machine learning. The key libraries that you will need to master include NumPy. This library is used to handle large arrays of matrices and data, which is the backbone of most machine learning algorithms. If you plan on working with large data sets, you'll be using NumPy a lot. Pandas. This library is great for data manipulation and analysis. You'll use Pandas to clean, organize, and transform data, making it ready for machine learning models. Scikit-learn. This library provides simple, easy-to-use tools for building machine learning models. It covers everything from data preprocessing models like regression and classification. Once you're comfortable with these tools, you'll be able to start building machine learning models and working with real-world data. Next up is SQL, which stands for Structured Query Language. As an ML engineer, you will be working on lots of data, and SQL will help you query databases to retrieve information that you need. You'll use SQL to extract data, filter it, and join tables together, making sure that you have the right data to your models. Once you have your data, the next step is data wrangling. Data wrangling is a huge part of your job, and if you master it, it'll save you a lot of time and frustration while building models. We shall now move on to types of machine learning. Let's talk about the different types of machine learning. There are three main categories, which are supervised learning, unsupervised learning, and reinforcement learning. Speaking of supervised learning, this is when you have labeled data. You train your model on data where the answers are already known. The goal is for the model to learn the relationship between inputs and outputs so it can predict the future outcomes. Unsupervised learning. In this case, the model works with unlabeled data and it tries to find hidden patterns and groupings in the data. This is useful for tasks like clustering or anomaly detection. Reinforcement learning. This type of learning involves training an agent to make decisions by interacting with its environment and receiving rewards or penalties based on its actions. This is often used in game AI or robotics. We shall now move on to feature engineering and evaluation. After cleaning your data, the next step is feature engineering. This is the process of transforming raw data into meaningful features that help your model make better predictions. Once you've engineered your features, it's time to evaluate the model. You'll use metrics like accuracy, precision, and recall to see how well your model is performing. Proper evaluation ensures that your model is ready for real-world applications and that it can handle data in production. We shall now move on to the 6-month learning plan in order to become an ML engineer in 2026. So how do you actually get started? Here's your 6-month learning plan to guide your journey. Firstly, focus on learning Python, mathematics, and SQL. Dive into machine learning algorithms and hands-on projects. Then, learn deep learning and work with frameworks like TensorFlow or PyTorch. By the 6th month, you can work on a capstone project that covers the full pipeline from data collection to deployment. We shall now speak about the ML engineer tool stack. So let's talk about the tools that you will need as a machine learning engineer. You must be wondering, what tools should I be learning to become a successful ML engineer in 2026? So let's simplify this. Git and GitHub are the first things on your list. At first glance, version control might seem like something that only coders need to worry about. However, it can be really crucial. Why? Because version control allows you to track every change that you make to your code, collaborate with teams, and roll back changes if something goes wrong. Imagine you're working on a huge project and you mess something up. Without version control, you could lose hours of work. But with Git and GitHub, you could go back and fix to any point and time. You might be thinking, okay, I get that Git is useful, but what about the tools that can actually help me build and deploy machine learning models? Now that's a great question. So let's talk about the cloud platforms like AWS, Google Cloud, and Azure. In the past, machine learning models were often built and tested upon local machines, but we quickly realized that it wasn't scalable. These cloud platforms give you the ability to handle large data sets, run models on high-powered servers, and scale them as your projects grow. Instead of relying on your personal laptop to do all of the heavy lifting, you can leverage the cloud to train models much faster and handle massive data sets without worrying about memory limitations. We shall now move on to the next topic, which is on MLOps lifecycle. You have now got all of your tools in place. But how do you go from all of these tools coming together in the MLOps lifecycle? So you must be wondering, what does all of the MLOps lifecycle tools even look like? And how do I manage the process from starting to finish? Well, here's the thing. MLOps is like a well-oiled machine. It involves a series of stages that ensure that your models remain reliable, scalable, and adaptable to new data over time. Think of it like a car assembly line. First, you train the car, and then you deploy it into the real world. After that, you need to monitor it and see if it runs smoothly. If it breaks down, you will have to retrain it. Let's break it down into key steps. Training your model. This is where you create the model using your training data. This is a very experimental phase where you try different algorithms, tweak parameters, and optimize the model for better performance. Deploying it to production. Now that your model is ready, it's time to put it into action. This means making the model available to users or clients. Whether it's in a mobile app or a web service, deployment is where the magic happens. Monitoring performance. Once your model is live, you can't just forget about it. It's like checking the car's tire pressure after it's been on the road for a while. You need to continuously track how well your model is doing. If it starts to slip or underperform, it's time for tweaks and adjustments. Lastly, we have retraining. Over time, your model may need to be retrained with new data to stay accurate. This is especially true in industries where the environment is constantly changing, like e-commerce or finance. Retraining ensures that the model stays relevant and continues to provide value. You may be wondering that this sounds like a lot of work. And that's true. That's where MLOps tools like MLflow help you streamline this process. By automating and managing this lifecycle, you can spend less time dealing with the backend and more time focusing on building innovative solutions. We shall now move on to experiment tracking. As you dive deeper into machine learning, you'll quickly realize how important it is to track your experiments. At first, this might seem a little overwhelming. You might be thinking, I can't just run a model and hope for the best, right? But trust me, tracking your experiments is one of the best habits that you can develop early on. Think of it like logging your workout progress. Even if you don't track the results, how will you know whether you're improving or not? The same goes for machine learning. By using experiment tracking tools, MLflow, and weights and biases, you can keep a detailed record of every model and every hyperparameter and every evaluation metric. Now imagine you're building a recommendation system for an online store. You try different adjustments, algorithms, and get different results. With experiment tracking, you can easily compare which configurations work best. And learn from the past mistakes. You'll always know which experiment gives you the best results and which needs tweaking. Tracking experiments also helps in collaboration. If you're working with a team, being able to see everyone's experiments in one place makes it easier to understand their approach and build on each other's work. We shall now move on to projects and portfolio. Now that you've got your tools and workflow in place, it's time to focus on building a strong portfolio. You might be thinking, how do I make my portfolio stand out to potential employees? That's a great question. The answer is simple: real-world projects. Think about it. Employers want to see what you can do in practice. They don't just want to see theoretical knowledge, they want to see that you can solve problems and build working systems that can make a difference. So for that reason, we have mini project examples. At this point, you're probably itching to start building something yourself. Well, Hands-on projects are the best way to solidify what you have already learned. For example, you could create a customer churn prediction model or a fraud detection system. These are practical, real-world projects that demonstrate your ability to build solutions from start to finish. Make sure you document your projects clearly on GitHub and always include a detailed explanation of your approach, challenges, and results. Remember, the goal is to show that you understand the problem and build a working solution. We'll now move on to Kaggle and open source. As you continue to build your portfolio, I highly recommend diving into Kaggle competitions and contributing to open source projects. Kaggle is an amazing platform where you can work on real-world data sets and solve problems that companies and research institutions are facing. Not only will you improve your skills, but you'll also have the opportunity to see how top data scientists and machine learning engineers approach similar problems. Contributing to open source projects is another excellent way to showcase your skills. It shows that you can work well with others, understanding existing systems, and contribute to the community. Plus, it's a great way to gain visibility and make connections with other engineers. We shall now speak about the resumes which work for you. Speaking about your resume, when it comes to landing a job as a machine learning engineer, your resume needs to be focused on real-world projects and practical experience. So be sure to highlight the projects that you've worked on, the tools you've used, and most importantly, the impact that your work has had. If you build a recommendation engine that boosted product sales by 20%, make sure that you include that. Employers want to see how your work contributes to solving real business problems. Don't forget to include links, Kaggle profile, or any other open source contributions that you've made. Employers love seeing code, and showing them your projects is the best way to stand out. We shall now speak about what interviewers test in 2026. By now, you must be wondering, what do employers actually look for in an ML engineer? So in 2026, interviews are not just about technical knowledge. Employers just want to see how well you can communicate your thought process and real-world problems. You'll likely face practical tests that challenge you to build a model or analyze data in real time. You'll also be tested on how well you explain your approach and justify the decisions that you made during the project. Prepare to discuss things like why you choose a specific algorithm for a problem, or how you handle issues like data imbalance or overfitting, along with what metrics you use to evaluate your model's performance. Being able to communicate clearly your process and how you arrive at your solution is a skill that will set you apart from other candidates. We shall now speak about the ML trends that you will need to follow. Machine learning is evolving fast, and staying up to date is key to remaining relevant in this field. So here are a few trends to keep an eye on in 2026. Generative models. These models can generate new data based on patterns they learn, and they're used for things like text generation, image creation, and even music composition. AutoML. Automated machine learning tools are making it easier for non-experts to build machine learning models. As a result, more people will be able to contribute to this field without needing to become experts. Privacy-first models. As privacy concerns grow, machine learning models are being designed to work securely and ethically, and these don't compromise on user privacy. Staying on top of these trends will help you remain competitive and innovative in the ever-evolving field of machine learning. So, in conclusion, I will say consistency is key in machine learning. You don't need to know everything right away, but you must stay committed to learning and building. Start small, keep experimenting, and keep improving. The road to become a machine learning engineer may seem long, but with the right tools and mindset, you can get there. Thank you for watching, and I'll see you in the next one. Thanks for watching the Machine Learning Engineer Roadmap for 2026. We hope that this video gave you a clear path to becoming a successful ML engineer. Ready to take the next step? Explore the Simplilearn's professional certificate in AI and machine learning in partnership with Purdue University. Gain hands-on experience and industry-recognized credentials to boost your career.
Welcome to Math Refresher, Probability and Statistics. In this lesson, we are going to explain the concepts of statistics and probability, describe conditional probability, define the chain rule of probability, discuss the measure of variance, identify the types of Gaussian distribution, basic of statistics and probability. Probability and statistics. Data science relies heavily on estimates and predictions. A significant portion of data science is made up of evaluations and forecast. Statistical methods are used to make estimates for further analysis. Probability theory is helpful for making predictions. Statistical methods are highly dependent on probability theory, and all probability and statistics are dependent on data. Data is information acquired for reference or research via observations, facts, and measurements. Data is a set of facts structured in the form that computers can interpret, such as numbers, words, estimations, and views. Importance of data. Data aids in seeing more about the information by identifying possible connections between two features. Data assists in the detection of distortion by uncovering hidden patterns. Based on prior information patterns, data may be utilized to anticipate the future or predict the current state of affairs. Also, data aids in determining whether two pieces of information have any instance in common or not. Types of data. Data might be quantitative. That is data that can be measured or counted in numbers. Or it may be qualitative, which is data which is generally divided into groups or, in simpler words, which cannot be counted or measured in numbers. Let's consider an example. A customer information data of a bank may contain quantitative and qualitative data. Consider this snapshot where we have customer ID, surname, geography, gender, age, balance, has C or card, is active member. Amongst these variables, we can see surname is mostly qualitative as it cannot be counted and measured in numbers. Geography and gender are also qualitative as they cannot be counted in numbers and are mostly groups. Has C or card, that is, has credit card, and is active member, although are containing numerical in form. But these are categorical. That means these have been divided into groups of 1 and 0 that represent yes and no as an answer. Hence, these two variables are also qualitative. Customer ID is again, although a numerical data. However, the significance or intuition behind customer ID is categorical. Hence, it may be kept in the qualitative data also. However, age and balance. These are numerical information which have been measured or counted, and numerical operations can be performed on them. Hence, these are under quantitative data categories. Introduction to descriptive statistics. Descriptive statistics. A descriptive measurement is a summary measure that quantitatively portrays the most important features of a set of data, allowing for a better comprehension of the information. Data can be measured as different levels. The levels of measurement describe the nature of information stored in the data assigned to the variables. Qualitative data can be measured as nominal or ordinal. Quantitative data can be measured in terms of interval and ratio type. Nominal data. The data is categorized using names, labels, or qualities. For example, brand name, zip code, and gender. Ordinal data can be arranged in order or ranked and can be compared. Examples include grades, star reviews, position and race, and date. Interval data is the data that is ordered and has meaningful differences between the data points, example, temperature in Celsius, and year of birth. Ratio data is similar to the interval level with the added property of inherent zero. Mathematical calculations can be performed on both interval as well as ratio data. For example, height, age, and weight. Population versus sample. Before analyzing the data, it's important to figure out if it's from a population or a sample. Population is a collection of all available items as well as each unit in our study. Sample is a subset of the population that contains only a few units of the population. Population data is used for study when the data pool is very small and can give all the required information. Samples are collected randomly and represent the entire population in the best possible way. Measures of central tendency. The central tendency is a single value that aids in the description of the data by determining its center position. Measures of central tendency are sometimes known as summary statistics or measures of central location. The most popular measurements of central tendency are mean, median, and mode. The normal distribution is a bell-shaped, symmetrical distribution in which mean, median, and mode all are equal. The curve over here shows the bell-shaped curve or the normal distribution of variable x. The point over here that is x1 is the point which represents the mean, median, and mode of this distribution. Mean. Mean is calculated by dividing the sum of all data values by the total number of data values. It gets affected when there are unusual or extreme values. It is sensitive to the outliers. Mean can be calculated as summation over all the values of x in a collection divided by the size of the collection. For example, we have a collection where we have values as 7, 3, 4, 1, 6, and 7. We find out the sum of these values, which is 28, and there are a total of 6 values. So 28 divided by 6 gives us a mean value of 4.66. Median. It is the middle value in the set of the data that has been sorted in ascending order. It is a better alternative to mean, since it is less impacted by outliers and skewness. It is closer to the actual central value. Median is calculated differently for different sizes of data. Differentiated as if the total number of values is odd, or if the total number of values is even, if the size of the data is odd. For example, in this case, we have 5 elements. After sorting, whatever middle value we get. That means n plus 1 by 2th term in this case. 5 plus 1 divided by 2. That is the 3rd term, which is 4 is the median value. In case when the total number of values is even like here, there are 6 values. The average or the mean of the 2 central values is considered as the median. In this case, the median is the mean of 6 and 4, which is 5. Mode. Mode represents the most common value in the dataset. It is not at all affected by extreme observations. It is the best measure of central tendency for highly skewed or non-normal distribution. Mode for categorical data is determined by estimating the frequencies for each categories, and then the category with the highest frequency is considered to be mode. Like in this case, 7 has the highest frequency, hence 7 becomes the mode value. However, in case of continuous data or quantitative data, the calculation of mode is slightly different. The first step in calculation of mode is dividing the data into classes which are equal with, then getting the frequency of data points lying within that range of classes, and finally selecting the class with the highest frequency. Using the range of that class and the frequencies, we can get the final mode value. Using the formula L plus fm minus f1 multiplied to h divided by fm minus f1 plus fm minus f2. Here L is the lower limit or the lower observation of the mode class. H is the size of the mode class. Fm is the frequency of the mode class. F1 is the frequency of the class proceeding to mode. And F2 is the frequency of the class succeeding to mode. This gives us the final mode value. Mean versus expectation. Now let's talk about mean versus expectation. So in general, we use the expected value or expectation when we want to calculate the mean of a probability distribution that represents the average value we expect to occur before collecting any data. And mean, on the other hand, mean is basically used when we want to calculate the average value of a given sample. This represents the average value of raw data that we may have already collected. We can understand this by using a simple example. Now, to calculate the expected value of this probability distribution, we can use a specific formula from the previous discussion. This is going to be the expected value, where x is going to be the data value, and this px is the probability of value. For example, we could calculate the expected value for this probability distribution to be as shown. So here, it will be 1.45 goals. So this represents the expected number of goals that the team will score in any given game. And then if you talk about calculating mean, so we typically calculate the mean after we have actually collected raw data. For example, suppose we record the number of goals that a soccer team will score in 15 different games. Now to calculate the mean number of goals scored per game, we can use the following formula, where sum of x is basically the sum of all the goals divided by n and the number of records, or we can say the sample size. It is as shown on the screen. So this represents the mean number of goals scored per game by the team. Measures of asymmetry. The difference between the three distinct curves can be studied in this image. The central curve is the normal or no skewness curve. Here mean, median, and mode all lie on the same point. This normal curve is symmetrical about its mean, median, and mode. That means the left-hand side of the curve is a mirror image of the right-hand side of the curve. However, in case of negatively skewed data, the tail is elongated on the left-hand side, and the mean is smaller than the mode and the median values, or is on the left-hand side of the mode, hence indicating that the outliers are in the negative direction. On the other hand, in case of positively skewed, the data is concentrated on the left-hand side of the curve, while the tail is elongated or longer on the right-hand side of the curve. The mean is greater than the mode and median, or is on the right-hand side of the mode and median, indicating that the outliers are in the positive direction. Let's consider an example. The graph here shows the global income distribution for the year 2013 and a projection for 2035. If we see the global income distribution statistics for 2003, it is highly right-skewed. We can observe in the previous graph that in 2003, the mean of $3,451 was higher than the median of $1,090. The global income is definitely not evenly distributed. The majority of people make less than $2,000 each year, while only a small percentage of the population earns more than $14,000. Measures of variability. Measures of variability. Dispersion. The measure of central tendencies provide a single value that addresses the full worth. However, the central tendency cannot depict the viewpoint entirely. The metric of dispersion helps us focus on the inconsistency in the data spread. Measures of dispersion describe the spread of the data. The range, interquartile range, standard deviation, and variance are examples of dispersion measures. Range. The range of distribution is the difference between the largest and the smallest amount of data. The range, for example, does not include all of a series' positive aspects. It concentrates on the most shocking aspects and ignores that aren't considered critical. For example, for a set 13, 33, 45, 67, 70, the range is 57. That is, the maximum of this, which is 70 minus the minimum over here, which is 13. Variance. Variance is the average of all squared deviations. It is defined as the sum of squared distance between each point and the mean or the dispersion around the mean. The standard deviation is used as variance suffers from a unit difference. Variance can be computed as sigma square summation over x minus mu square divided by n, where mu is the mean of the data, x is the individual data point, and n is the size of the data. This representation is for a population data. For a sample data variance can be computed as x minus x bar whole square summation over it divided by n minus 1. Here x bar is the mean of these sample data, and n is the sample size. The units of values and variance are not equal, so another variability measure is used. Standard deviation. Standard deviation is a statistical term used to measure the amount of variability or dispersion around a mean. The standard deviation is calculated as the square root of variance. It depicts the concentration of the data around the mean of the dataset. Standard deviation, as indicated previously, can be computed as square root of variance. For a population data, standard deviation sigma can be computed as square root of summation over xi minus mu whole square divided by n, where mu is the mean of the data, xi are the data points, and n is the size. Let's consider an example. Let's find out the mean, variance, and standard deviation for this data. The data values are 3, 5, 6, 9, and 10. To find out the mean, we first find the sum of all these data values. That is 33, and divide it by the count, which is 5. We get the mean of 6.6. To compute the variance, we start by computing the deviation. That is x minus the mean of x. Here 3 is one of the values of the data, and 6.6 is the mean. So 3 minus 6.6 square, and we do that to find out sum of all the deviations divided by the count, which is 5. We end up getting an overall variance of 6.64. Standard deviation, as we know, is measured at square root of variance. That is square root of 6.64, which amounts to 2.576. Measures of relationship. Measures of relationship. Covariance. Covariance is the measure of joint variability of two variables. It measures the direction of the relationship between the variables. It determines if one variable will cause the other to alter in the same way. Covariance between variable x and y can be computed as summation over the product of xi minus x bar and yi minus y bar the whole divided by n minus 1. Here x bar and y bar are the mean of x and y respectively. The value of covariance can range from minus infinity to a plus infinity. Correlation. Correlation is normalized covariance. It measures the strength of association between two variables. The most common measure for correlation is the Pearson correlation coefficient. Correlation between two variables, x and y, can be measured with respect to covariance as covariance between x and y divided by the standard deviation of x and standard deviation of y. The value of correlation ranges from a -1 to +1. Types of correlation. Correlation can be either a positive correlation, zero correlation, or a negative correlation. The first picture over here represents a perfect positive correlation, wherein a straight line with a positive slope is representing the relationship between the two variables. Zero correlation means that the line representing the relationship between the two variables is horizontal to the x-axis. Perfect negative correlation can be represented by a straight line with a negative slope. Correlation equals to 1 implies a positive relationship. That is when one variable increases, the other variable also increases. A correlation value of -1 implies a negative relationship. That is when one variable increases, the other decreases. The correlation coefficient of 0 shows that the variables are completely independent of each other. Let's consider an example. Here, we have two variables, height and weight. To compute the correlation between height and weight, we use the correlation formula as covariance of x and y divided by standard deviation of x and standard deviation of y. Here height is the x variable and weight is the y variable. First, to compute covariance, we compute the x minus x bar and y minus y bar values, and then the product of them. We then compute x minus x bar square and y minus y bar square values to compute the standard deviations of height and weight respectively. Correlation, as we know, has been defined as covariance of x and y and y divided by standard deviations of x and y. This can also be represented as summation over x minus x bar multiplied to y minus y bar divided by square root of summation over sum of squared deviations. That is x minus x bar square multiplied to square root of summation over y minus y bar whole square. That is sum of square deviations for y. Now, let's find out values to put into this formula. First, we find out the overall sum of height to get the mean of height, which is 5.14. Similarly, we get the sum of weight to get the mean of weight as 50. We now get the summation over x minus x bar multiplied to y minus y bar to get the numerator for the formula. Then we compute x minus x bar square summation and y minus y bar square. That is sum of squared deviation of x and y respectively. Now we put in the values in this final correlation formula to get a correlation value of 0.889. This indicates that height and weight have a positive relationship. It is evident that as height grows, weight also increases. In this module, we will be talking about expectation and variance. So the expected value, or we can say mean of a given variable, that we can denote by x is a discrete random variable where it is a weighted average of the possible values that x can take, and each value is going to be according to the probability of that specific event occurring. So usually the expected value of x is denoted by a simple formula where we can define the expectation based on the x parameter, which is going to be the sum of each possible outcome multiplied by the probability of the outcome occurring. So in more concrete terms, the expectation is what we would expect the outcome of an experiment to be on average. We can take an example for the coin. If a coin is being tossed 10 times, then one is most likely to get 5 heads and 5 tails. Same logic can be discussed if we talk about another example of rolling a die. So there are 6 possible outcomes when you roll a die. 1, 2, 3, 4, 5, 6. And each of these has a probability of 1 by 6 of occurring. So we can say that the expectation is going to be 1 multiplied by the probability of that happening, which is going to be 1 by 6, plus 2 by 6, plus 3 by 6, plus 4 by 6, plus 5 by 6, plus 6 by 6, and that is going to give us 3.5 as an output. The expected value is 3.5. So if you think about it, 3.5 is halfway between the possible values that I can take. And this is what we should have expected. Next, we talk about the concept of variance. So variance of a random variable allows us to know something about the spread of the possible values of the variable. So for a discrete random variable x, the variances of x is going to be denoted by using a simple formula that is going to be var x equals ex minus m, the whole square where m is basically the expected value of the expectation of x. So this is more like a standard deviation of x, which can also be represented by using this formula. So the variance does not behave in the same way as expectation when we multiply and add constants to random variables. So now there are 2 different types of variance that we can have a fair understanding on. First of all, we have low variance, and then we have high variance. So low variance simply means that there is a small variation in the production of the target function, with changes in the training data set, and at the same time, high variance, as we can see here. High variance shows a large variation in prediction of the target function, with changes in the training data set. So a model that shows high variance learns a lot and performs well with the training data set. And it does not generalize well with the unseen data set. And that's why, as a result, such a model gives good results with training data set, but shows high error rates on the test data set. And since the high variance a model learns too much from the data set, it leads to an overfitting of the model. So model with high variance will be having a couple of issues, like it may lead to overfitting, or it may also lead to increase in model complexities. Next, we have skewness. So skewness in simple terms is basically a measure of asymmetry of a distribution. So distribution is asymmetrical when its left and right sides are not the mirror images. Right now, this is a mirrored image, and a distribution can have right positive, or we can say negative, or it can have 0 skewness. So right skewed in this scenario is basically the distribution is longer on the right side of its peak. And a left skew distribution is going to be, we can say, where it is longer on the left side. So we can see we have this one as a part of right side. It is more elongated towards the right side, and this one is more elongated towards the left side. So we can think of skewness in terms of tails. A tail is long tampering and the end of a distribution. So it simply indicates that they are observations at one end of the distribution, but that they are relatively infrequent. So a right skew distribution has a long tail on the right side, as you can see here, so the number supports observed. Let's say we have a data on a per year basis. So again, we can have a more skewness towards the right side, where data is being dropping as we continue to increase the number of years. For example, we may have a high sales towards the beginning of year, suppose in 2022. But again, as we proceed to 2023, second half we are seeing the dip in performance. So that is rightly skewed. And same way, let's suppose if we started with the sales figure, it was really less in suppose 2002. But again, as we proceeded to 2023 now, our sales have been gradually increasing. So it's more like skew towards the left section as a part of negative skew. Next, we have kurtosis. So kurtosis is basically a measure of the tailedness of a distribution. So tailedness is how often the outliers occur, and excess kurtosis is the tailedness of the distribution related to a normal distribution. So a distribution with medium kurtosis is called as mesokurtic. A distribution with low kurtosis like this one. This is called as the platykurtic, and then distribution with high kurtosis like this one. This is called as the leptokurtic. So tails here, they are tapering ends on either side of a distribution like this. So they represent the probability or the frequency of values that are extremely high or extremely low to the mean. In other words, tails here represents how often the outliers occur. So there are three types of kurtosis. We have platykurtic, which is negative, leptokurtic, which is a positive towards the upper end, and then we have mesokurtic, which is a normal distribution. So mesokurtic is the medium tail, so normal distributions, they have a kurtosis of 3. So any distribution with a kurtosis of a prox value of 3 is going to be mesokurtic, and kurtosis is described in terms of excess kurtosis, which is kurtosis minus 3. And since normal distribution, they have a kurtosis of 3 axis kurtosis, makes comparing a distribution kurtosis to a normal distribution even easier. Introduction to probability. Probability theory. Probability is a measure of the likelihood that an event will occur. Let's consider an example of coin toss, where the chances of getting heads on a coin are 1 by 2 or 50%. The probability of each given event is between 0 and 1, both inclusive. Sum of an event's cumulative probability cannot be greater than 1. Hence, the probability of an event X lies between 0 and 1. This means that the integral of probability of distribution over X equals to 1. Conditional probability. Conditional probability of any event A is defined as the probability of occurrence of A, given that event B has previously occurred. Condition probability of event A given B can be estimated as probability of A intersection B, that is, probability of both A and B happening together, divided by the probability of B. It is also written as that probability of A intersection B equals to probability of A given B, multiplied to probability of B. Let's consider an example. In a coin, we are doing a 2-coin flip. Coin 1 gets heads, and tails in subsequent flips, while coin 2 gets tails, heads, and tails in the subsequent flips. Now the probability that coin 1 will get a head is 2 out of 4, while the probability that coin 2 will get heads is again 2 out of 4. The probability that both coin 1 and coin 2 will have a heads is just 1 out of the 4 flips. Hence, the probability that coin 1 will get heads, given that coin 2 is already heads, can be computed as probability of coin 1 edge intersection coin 2 edge. That is 1 by 4 divided by probability of coin 2 edge. That's a given that is 2 by 4. Which is going to be 0.5 or 50% based. Bayes theorem. Bayes theorem calculates the conditional probability of an event based on its prior probabilities. Basically, Bayes theorem incorporates the prior probability distribution to predict the posterior probabilities. Bayes theorem for conditional probability can be expressed as probability of A given B equals probability of B given A, divided by probability of B multiplied to probability of A. Bayes theorem allows updating the probability values by using new information or evidence. Here, probability of A is known as prior probability. That is the probability of event before any new data is collected. Probability of A given B is known as the posterior probability. It is the revised probability of an event occurring after taking into consideration the new information. Probability of B given A is known as the likelihood, and probability of B is probability of observing an evidence Bayes model. An example. Consider an example for calculating the likelihood of having diabetes based on frequency of fast food consumption. Here is the observed data. Let's say the fast food audience is 20%. Diabetes prevalence is 10%, and 5% is fast food and diabetes. The chances of diabetes given fast food, that is the conditional probability of D given B, can be calculated as probability of diabetes and fast food together divided by probability of fast food. That means 5% divided by 20%. That equals 25%. Define an analysis can state eating fast food increases the chance of having diabetes by 25%. The multiplication rule of probability. If events A and B are statistically independent and probability of A intersection B can be given as probability of A given B multiplied to probability of B. However, probability of A intersection B is also given as probability of A multiplied to probability of B. Here, probability of A given B equals to probability of A when we assume that probability of B is non-zero. Similarly, probability of B equals probability of B given A, assuming probability of A is non-zero. Chain rule of probability. Joint probability distributions over many random variables can be reduced into conditional distributions over a single variable. It can be expressed as probability of x1, x2, so on until xn equals probability of x1 intersection probability of xi, given probability of x1 till xi minus 1. For example, the joint probability of A, B, and C can be given as probability of A given B. C multiplied to probability of B given C multiplied to probability of C. Logistic sigmoid. The logistics function is a type of sigmoid function that aims to predict the class to which a particular sample belongs. Its outcome is discrete binary value, a probability between 0 and 1. The logistics sigmoid is a useful function that follows the yes curve. It saturates when the input is very large or very small. Logistic sigmoid is expressed as sigma of x equals 1 upon 1 plus e to the power minus x. The logistic sigmoid can be expressed as sigmoid function of x is given as 1 upon 1 plus e to the power minus x, where e is the Euler's number. Gaussian distribution. The Gaussian distribution is a type of distribution in which data tends to cluster around a central value with little or no bias to the left or right. It is often referred to as normal distribution. In absence of prior information, the normal distribution is frequently a fair assumption in machine learning. Equation. The formula for calculating Gaussian distribution is described as the normal distribution of x. That is the function of x given mean as mu and variance is sigma square can be calculated as 1 upon sigma square root of 2 pi e to the power minus half x minus mu divided by sigma whole square, where mu is the mean or peak value, which also is the expected value of x. Sigma is the standard deviation, sigma square is the variance. A standard normal distribution has a mean of 0 and a standard deviation of 1. Gaussian distribution can be univariate, which describes the distribution of a single variable x. It can also be multivariate, where it can just use to describe the distribution of several variables. It is represented in 3D of ND formats. Law of large numbers. Now let's talk about law of large numbers. The law of large numbers states that an observed sample average from a large sample will be close to the true population average, and that it will get closer in the larger sample. So the law of large number does not guarantee that a given sample, spatially a small sample, will reflect the true population characteristics, or that a sample does not reflect the true population will be balanced by a subsequent sample. This is for the law of large numbers to express the relationship between scale and growth rate. So there are multiple examples through which we can understand. And it is widely used in statistical analysis in working with the central limit theorem in terms of the business growth. So there are multiple real-time setup in which these are going to be used. So if you talk about tossing a coin, so tossing a coin in a number of times will give us two different type of outcomes. The result will spread evenly between head and tails, and the expected average value is going to be half. That means 50 times tails and 30 times heads. But again, if you toss a coin 1,000 times, then the result can be in different manners because out of 1,000, let's say 850 times it has been head and only 150 times it has been tails, and so on. So that's why the possibility of one event occurring is going to be changed in large sample sets as compared to a small sample sets, as in let's say 10 times. So the number of heads and tails unbalanced for lower number of trials, so we can see it is unbalanced. But again, as soon as we toss more number of coins, more leans towards the balanced value, or we can see the observed averages. Next, we have p-value. So p-value is basically a number calculated from the statistical test that describes how likely we are to have found a particular set of observations if the null hypothesis were true. So p-values are used in hypothesis testing to help decide whether to reject the null hypothesis. And the smaller the p-value, the more likely we are to reject the null hypothesis. So we have a term called as null hypothesis. So all statistical tests, they have null hypothesis. So for most tests, the null hypothesis is that there is no relationship between our variables of n first, or that there is no difference among groups. For example, in a two-tail t-test, the non-hypothesis is that the difference between two groups is going to be 0. So p-value is going to tell us how likely it is that our data could have occurred under the null hypothesis. It is done by calculating the likelihood of a test statistic, which is the number calculated by a statistical test using our data. So p-value tell us how often we would expect to see a test statistic as extreme or more extreme than one calculated by a statistical test if the null hypothesis of the test was true. So there are multiple limitations as well. So first one is the results can be significant, but again, they may not be practical as we have compared. It can be based on multiple hypotheses for a game, for the healthcare test. If the test is going to be positive or not, it may show even values of the effect of a variable, but not the magnitude in real life. What exactly is going to be the application of a drug test being failed in pharma company? Therefore, it is recommended to use confidence and levels in addition to the p-values to quantify, or we can say to give a solid figure to the reserve, which we are going to get. The p-values, they are interpreted as supporting, or we can say refuting, the alternative hypothesis. So p-value can only tell you whether or not the null hypothesis is supported. It cannot tell us whether our alternative hypothesis is true or why. So the risk of rejecting the null hypothesis is often higher than the p-value. So especially when we are looking at a single study or when using small sample sizes. So this is because the smaller frame of reference, the greater are the chance that as we stumble across a statistically significant pattern completely by accident. Key takeaways. Key takeaways. Probability and statistics structure the premise of the data. The data helps in anticipating the future or gauging in view of the past patterns of information. The central tendency is a single value that helps to describe the data by identifying these central positions. The mean, median, and mode are the measures of central tendencies. The distribution where the data tends to be around a central value with a lack of bias or minimal bias towards the left or right is called as Gaussian distribution.
My name is Richard Kirshner with the Simplilearn team. That's Get Certified, Get Ahead. We're going to cover mathematics for machine learning. So today's agenda is going to cover data and its types. Then we're going to dive into linear algebra and its concepts, calculus, statistics for machine learning, probability for machine learning, hands-on demos. And of course, thrown in there in the middle is going to be your matrices and a few other things to go along with all this. Data and its types. Data denotes the individual pieces of factual information collected from various sources. It is stored, processed, and later used for analysis. And so we see here just a huge grouping of information, a lot of text stuff, money, dollar signs, numbers, and then you have your performing analytics to drive insights. And hopefully you have a nice your shareholders gathered at the meeting and you're able to explain it in something they can understand. So when we talk about types of data, we have in our types of data, we have a qualitative, categorical. You think nominal or ordinal. And then you have your quantitative or numerical, which is discrete or continuous. And let's look a little closer at those data types. Vocabulary, always people's favorite is the vocabulary words. Okay, not mine. But let's dive into this, what we mean by nominal. Nominal, they are used to label label our variables without providing any measurable value. Country, gender, race, hair, color, etc. It's something that you either mark true or false. This is a label. It's on or off. Either they have a red hat on or they do not. So a lot of times when you're thinking nominal data labels, think of it as a true-false kind of setup. And we look at ordinal. This is categorical data with a set order or a scale to it. And you can think of salary range as a great one. Movie ratings, etc. You can see here the salary range. If you have 10,000 to 20,000, number of employees earning that rate is 150. 20,000 to 30,000, 100, and so forth. Some of the terms you'll hear is bucket. This is where you have 10 different buckets and you want to separate it into something that makes sense into those 10 buckets. And so when we start talking about ordinal, a lot of times when you get down to the brass bones, again, we're talking true-false. So if you're a member of the 10 to 20K range, so forth. Those would each be either part of that group or you're not. But now we're talking about buckets and we want to count how many people are in that bucket. Quantitative, numerical data falls into two classes, discrete or continuous. And so data with a final set of values which can be categorized. Class strength, questions answered correctly, and runs hit in cricket. A lot of times when you see this, you can think integer, and a very restricted integer, i.e. you can only have 100 questions on a test, so it's very discrete. I only have 100 different values that it can attain. So usually you're talking about integers, but within a very small range. They don't have an open end or anything like that. So discrete is very solid, simple to count, set number. Continuous, on the other hand, continuous data can take any numerical value within a range. So water pressure, weight of a person, etc. Usually we start thinking about float values where they can get phenomenally small in what they're worth. And there's a whole series of values that falls right between discrete and continuous. You can think of the stock market. You have dollar amounts. It's still discrete, but it starts to get complicated enough when you have jump in the stock market from $525.33 to $580.67. There's a lot of point values in there. It'd still be called discrete, but you start looking at it as almost continuous because it does have such a variance in it. Now, we talk about we went over nominal and ordinal, almost true-false charts, and we looked at quantitative and numerical data, which we're starting to get into numbers. Discrete, you can usually A lot of times discrete will be could be put into true false, but usually it's not. So we want to address this stuff, and the first thing we want to look at is the very basic, which is your algebra. So we're going to take a look at linear algebra. You can remember back when your Euclidean geometry. We have a line. Well, let's go through this. We have a linear algebra is the domain of mathematics concerning linear equations and their representations in vector spaces and through matrices. I told you we're going to talk about matrices. So a linear equation is simply 2x plus 4y minus 3z equals 10. Very linear. 10x plus 12.4y equals z. And now you can actually solve these two equations by combining them. And that's what we're talking about, a linear equation. In the vectors, we have a plus b equals c. Now we're starting to look at a direction. And these values usually think of an x, y, z plot. So each one is a direction. And the actual distance of like a triangle, AB, is c. And then your matrix can describe all kinds of things. I find matrices confuse a lot of people, not because they're particularly difficult, but because of the magnitude and the different things they're used for. And a matrix is a chart, or think of a spreadsheet, but you have your rows and your columns. And you'll see here we have A times B equals C. Very important to know your counts. So depending on how the math is being done, what you're using it for, making sure you have the same rows and number of columns or a single number. There's all kinds of things that play in that can make matrices confusing. But really it has a lot more to do with what domain you're working in. Are you adding in multiple polynomials where you have like ax squared plus by plus, you start to see that it can be very confusing versus a very straightforward matrix. And let's just go a little deeper into these, because these are such primary. This is what we're here to talk about, is these different mathematical computations that come up. So when we're looking at linear equations, let's dig deeper into that one. An equation having a maximum order of 1 is called a linear equation. So it's linear because when you look at this, we have ax plus b equals c, which is a 1 variable. We have 2 variable ax plus by equals c, ax plus by plus cz equals d, and so forth. But all of these are to the power of 1. You don't see x squared. You don't see x cubed. So when we're talking about linear equations, that's what we're talking about. In their addition, if you have already dived into, say, neural networks, you should recognize this ax plus by plus cz setup plus the intercept, which is basically your neural network, each node adding up all the different inputs. And we can drill down into that. Most common formula is your y equals mx plus c. So you have your y equals the m, which is your slope, your x value plus c, which is your y-intercept. They kind of labeled it wrong here. Threw me for a loop. But the c would be your y-intercept. So when you set x equal to 0, y equals c. And that's your y-intercept right there. And they just had a reversed value of y when x equals 0. It equals the y-intercept, which is c. And your slope gradient line, which is your m. So you get your y equals 2x plus 3. And there's lots of easy ways to compute this. This is why we always start with the most basic one when we're solving one of these problems. And then, of course, one of the most important takeaways is the slope gradient of the line. So the slope is very important, that m value. In this case, we went ahead and solved this. If you have y equals 2x plus 3, you can see how it has a nice line graph here on the right. So, matrices. A matrix refers to a rectangular representation of an array of numbers arranged in columns and rows. So we're talking m rows by n columns. Here, A11 denotes the element of the first row in the first column. Similarly, A12, and it's really pronounced A11 in this particular setup. So it's row 1, column 1. A12 is A row 1, column 2. First row and second column, and so on. And there's a lot of ways to denote this. I've seen these as like a capital letter A, small case a for the top row. Or, you can see where they can go all kinds of different directions as far as the value. you just take a moment to realize there needs to be some designation as far as what row it's in and what column it's in. And we have our basic operations. We have addition. So when you think about addition, you have two matrices of 2 by 2, and you just add each individual number in that matrix. And then when you get to the bottom, you have, in this case, the solution is 12, 10 plus 2 is 12, 5 plus 3 is 8, and so on. And the same thing with subtraction. Now again, you're counting matrices. You want to check your dimensions of the matrix. The shape. You'll see shape come up a lot in programming. So when we're talking about dimensions, we're talking about the shape. If the two shapes are equal, this is what happens when you add them together or subtract them. And we have multiplication. When you look at the multiplication, you end up with a very slightly different setup going. Now, if we look at our last one, we're like, why? This always gets to me when we get to matrices, because they don't really say why you multiply matrices. My first thought is 1 times 2, 4 times 3. But if you look at this, we get 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5, 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5. If you're looking at these matrices, think of this more as an equation. And so we have, if you remember, when we back up here for our multiple line equations, let's just go back up a couple slides where we were looking at 2 variable. So this is a 2 variable equation, ax plus by equals c. And this is a way to make it very quick to solve these variables, and that's why you have the matrix, and that's why you do the multiplication the way they do. And this is the dot product of 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5, 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5. And it gives us a nice little 14, 23, 21, and 33 over here, which then can be used and reduced down to a simple formula as far as solving the variables as you have enough inputs. And then in matrix operations, when you're dealing with a lot of matrices, now keep in mind, multiplying matrices is different than finding the product of 2 matrices. Okay? So when we're talking about multiplication, we're talking about solving for equations. When you're finding the product, you are just finding 1 times 2. Keep that in mind, because that does come up. I've had that come up a number of times where I am altering data and I get confused as to what I'm doing with it. Transpose, flipping the matrix over its diagonal. Comes up all the time, where you still have 12, but instead of it being 12, 8, it's now 12, 14, 8, 21. You're just flipping the columns and the rows. And then, of course, you can do an inverse, changing the signs of the values across this main diagonal. And you can see here we have the inverse a to the minus 1, and it ends up with, instead of 12, 8, 14, 12, it's now minus 22, minus 12. Vectors. Vector just means we have a value and a direction. And we have down 4 numbers here on our vector. In mathematics, a one-dimensional matrix is called a vector. So if you have your x plot and you have a single value, that value is along the x-axis and it's a single dimension. If you have 2 dimensions, you can think about putting them on a graph. You might have x and you might have y, and each value denotes a direction. And then, of course, the actual distance is going to be the hypothesis of that triangle. And you can do that with 3 dimensionals, x, y, and z. And you can do it all the way to nth dimensions. So when they talk about the k-means for categorizing and how close data is together, they will compute that based on the Pythagorean theorem. So you would take the square of each value, add them all together, and find the square root, and that gives you a distance as far as where that point is, where that vector exists, or an actual point value. And then you can compare that point value to another one. And it makes a very easy comparison versus comparing 50 or 60 different numbers. And that brings us up to igene vectors and igene values. Igene vectors, the vectors that don't change their span while transformation, and igene values, the scalar values that are associated to the vectors. Conceptually, you can think of the vector as your picture. You have a picture, it's 2 dimensions, x and y. And so when you do those 2 dimensions and those 2 values, or whatever that value is, that is that point. But the values change when you skew it. And so if we take and we have a vector A, and that's a set value, B is you have A and B, which is your eigene vector. 2 is the eigene value. So we're altering all the values by 2. That means maybe we're stretching it out one direction, making it tall, if you're doing picture editing. That's one of the places this comes in. But you can see when you're transforming your different information, how you transform it is then your eigene value. And you can see here vector after line transition, we have 3A. A is the eigene vector, 3 is the eigene value. So A doesn't change, that's whatever we started with, that's your original picture. And 3 is skewing it one direction, and maybe B is being skewed another direction. And so you have a nice tilted picture because you've altered it by the eigene values. So let's go ahead and pull up a demo on linear algebra. And to do this, I'm going to go through my trusted Anaconda into my Jupyter notebook, and we'll create a new notebook called linear algebra. Since we are working in Python, we're going to use our NumPy. I always import that as NP, our NumPy array. Probably the most popular module for doing matrices and things in. Given that this is part of a series, I'm not going to go too much into NumPy. We are going to go ahead and create 2 different variables, A for a NumPy array 10, 15, and B 29. We'll go ahead and run this, and you can see there's our 2 arrays, 10, 15, 29. And I went ahead and added a space there in between, so it's easier to read. And since it's the last line, we don't have to put the print statement on it unless you want. We can simply do A plus B. So when I run this, we have 10, 15, 29, and we get 30, 24, which is what you expect. 10 plus 20, 15 plus 9. You could almost look at this addition as being just adding up the columns on here coming down. And if we wanted to do it a different way, we could also do A dot T plus B dot T. Remember that T flips them. And so if we do that, we now get them, we now have 30, 24 going the other way. We could also do something kind of fun. There's a lot of different ways to do this. As far as A plus B, I can also do A plus B dot T, and you're going to see that that will come out the same, the 30, 24, whether I transpose A and B or transpose them both at the end. And likewise, we can very easily subtract 2 vectors. I can go A minus B, and we run that, and we get minus 10, 6. Now remember, this is the last line in this particular section, so I don't have to put the print around it. And just like we did before, we can transpose either the individual or we can transpose the main setup, and then we get a minus 10, 6 going the other way. Now, we didn't mention this in our notes, but you can also do a scalar multiplication. Let me just put down scalar so you can remember that. And what we're talking about here is I have this array here, U, and if I go A times U, we'll take the value 2, we'll multiply it by every value in here. So 2 times 30 is 60, 2 times 15. And just like we did before, this happens a lot because when you're doing matrices, you do need to flip them. You get 60, 30 coming this way. So in NumPy, we have what they call dot product. And with this is in a 2-dimensional vectors. It is the equivalent to matrix multiplication. And remember, we were talking about matrix multiplication, where it is well, let's walk through it. We'll go ahead and start by defining 2 NumPy arrays. We'll have 10, 20, 25, 6, or our U and our V. And then we're going to go ahead and do, if we take the values, and if you remember correctly, an array like this would be 10 times 25 plus 20 times 6. We'll go ahead and print that. There we go. And then we'll go ahead and do the np dot of u comma v. And we'll find when we do this, we go ahead and run this, we're going to get 370, 370. So this is a strain multiplication where they use it to solve linear algebra when you have multiple numbers going across. And so this could be very complicated. We could have a whole string of different variables going in here. But for this, we get a nice value for our dot multiplication. And we did addition earlier, which was just your basic addition. And of course, the matrix, you can get very complicated on these, or in this case, we'll go ahead and do, let's create two complex matrices. This one is a matrix of 12, 10, 4, 6, 4, 31. We'll just print out A so you can see what that looks like. Here's print A. When we print A out, you can see that we have a 2 by 3 layer matrix for A. And we can also put together, always kind of fun when you're playing with print values, we could do something like this. We could go in here. There we go. We could print A, we have it end with equals A, run, and this kind of gives it a nice look. Here's your matrix. That's all this is. Comma n means it just tags it on the end. That's all that is doing on there. And then we can simply add in what is A plus B, and you should already guess, because this is the same as what we did before. There's no difference. When we do a simple vector addition, we have 12 plus 2 is 14, 10 plus 8 is 18, and so on. And just like we did the matrix addition, we can also do A minus B and do our matrix subtraction. And we look at this, we have what? 12 minus 2 is 10, 10 minus 8, where are we? Oh, there we go. 8 minus, confusing what I'm looking at. I should have reprinted out the original numbers. But we can see here 12 minus 2 is of course 10, 10 minus 8 is 2, 4 minus 46 is minus 42, and so forth. So same as the subtraction as before, we just call it matrix subtraction. It's identical. Now if you remember up here we had scalar addition where we're adding just one number to a matrix. You can also do scalar multiplication. And so simply if you have a single value A and you have B, which is your array, we can also do A times B. When we run that, you can see here we have 2 times 4 is 8, 5 times 4 is 20, and so forth. You're just multiplying the 4 across each one of these values. And this is an interesting one that comes up. A little bit of a brain teaser is matrix and vector multiplication. And so when we're looking at this, we are, just do a regular arrays. It doesn't necessarily have to be a NumPy array. We have A, which has our array of arrays, and B, which is a single array. And so we can, from here, do the dot AB, and this is going to return 2 values. And the first value is that, you could say it's like we're doing this array, B array, first with A and then with a second one. And so it splits it up. So you have a matrix of vector multiplication and you can mix and match. When you get into really complicated back-end stuff, this becomes more common because you've got layers upon layers of data. And so you'll end up with a matrix and a set of vector matrices that you want to multiply. Now, keep in mind that if you're doing data science, a lot of times you're not looking at this. This is what's going on behind the scenes. So if you're in the Scikit looking at Scikit-learn where you're doing linear regression models, this is some of the math that's hidden behind the scenes that's going on. Other times you might find yourself having to do part of this and manipulate the data around so it fits right, and then you go back in and you run it through the Scikit. And if we can do up here where we did a matrix and vector multiplication, we can also do matrix to matrix multiplication. And if we run this where we have the 2 matrices, you can see we have a very complicated array that of course comes out on there for our dot. And just to reiterate it, we have our transpose matrix, which is your dot T. And so if we create a matrix A and then we do transpose it, you can see how it flips it from 5, 10, 15, 20, 25, 30 to 5, 15, 25, 10, 20, 30, rows and columns. And certainly with the math, this comes up a lot. It also comes up a lot with XY plotting. When you put it into PyPlot, you have one format where they're looking at pairs of numbers and then they want all of X's and all Y's. So, the transpose is an important tool both for your math and for plotting and all kinds of things. Another tool that we didn't discuss is your identity matrix. And this one is more definition. The identity matrix, we have here one where we just did 2. So it comes down as 1, 0, 0, 1, 1, 0, 0, 0, 1, 0. It creates a diagonal of 1. And what that is when you're doing your identities, you can be comparing all your different features to the different features and how they correlate. And of course, when you have feature 1 compared to feature 1 to itself, it is always 1, where usually it's between 0 and 1 depending on how well it correlates. So when we're talking about identity matrix, that's what we're talking about right here, is that you create this preset matrix and then you might adjust these numbers depending on what you're working with and what the domain is. And then another thing we can do to kind of wrap this up, we'll hit you with the most complicated piece of this puzzle here, is an inverse A matrix. And let's just go ahead and put the, it's a lengthy description. Let's go ahead and put the description. This is straight out of the website for NumPy. So given a square matrix A, here's our square matrix A, which is 2, 1, 0, 0, 1, 0, 1, 2, 1. Keep in mind 3 by 3, it's square. It's got to be equal. It's going to return the matrix A inverse satisfying dot A inverse. So here's our matrix multiplication. And then of course it equals the dot, A inverse of A, with an identity shape of A dot shape 0. This is just reshaping the identity. That's a little complicated there. So we go ahead and have here's our array. We'll go ahead and run this, and you can see what we end up with is we end up with an array 0.5 minus 0.5 and so forth, with our 2, 1, 1 going down, 2, 1, 0, 0, 1, 0, 1, 2, 1. Getting into a little deep on the math, understanding when you need this is probably really is what's really important when you're doing data science versus handwriting this out and looking up the math and handwriting all the pieces out. You do need to know about the linear algorithm inverse of A. So if it comes up, you can easily pull it up or at least remember where to look it up. We took a look at the algebra side of it. Let's go ahead and take a look at the calculus side of what's going on here with the machine learning. So calculus, oh my goodness, and differential equations, you got to throw that in there because that's all part of the bag of tricks, especially when you're doing large neural networks, but it also comes up in many other areas. The good news is most of it's already done for you in the back end. So when it comes up, you really do need to understand from the data science, not data analytics. Data analytics means you're digging deep into actually solving these math equations. And a neural network is just a giant differential equation. So when we talk about calculus, we're going to go ahead and understand it by talking about cars versus time and speed. So helps to calculate the spontaneous rate of change. So suppose we plot a graph of the speed of a car with respect to time. So as you can see here, going down the highway, probably merged into the highway from an on-ramp. So I had to accelerate, so my speed went way up. Stuck in traffic, merged into the traffic. Traffic opens up and I accelerate again up to the speed limit. And maybe it peters off up there. So you can look at this as the speed versus time. I'm getting faster and faster because I'm continually accelerating. And if I hit the brakes, it'd go the other way. So the rate of change of speed with respect of time is nothing but acceleration. How fast are we accelerating? The acceleration is the area between the start point of x and the end point of delta x. So we can calculate a simple, if you had x and delta x, we could put a line there, and that slope of the line is our acceleration. Now, that's pretty easy when you're doing linear algebra, but I don't want to know it just for that line and those 2 points. I want to know it across the whole of what I'm working with. That's where we get into calculus. So when we talk about the distance between x and delta x, it has to be the smallest possible near to 0 in order to approximate the acceleration. So the idea is that instead of, if you ever took a basic calculus class, they would draw bars down here and you would divide this area up. Let's go back up a screen. You divide this area of this time period up into maybe 10 sections, and you'd use that and you could calculate the acceleration between each one of those 10 sections kind of thing. And then we just keep making that space smaller and smaller until delta x is almost infinitesimally small. And so we get a function of a equals a limit as h goes to 0 of a function of a plus h minus a function of a over h. And that is you're computing the slope of the line. We're just computing that slope under smaller and smaller and smaller samples. And that's what calculus is. Calculus is the integral. You can see down here we have our nice integral sign. It looks like a giant S. And that's what that means, is that we've taken this down to as small as we can for that sampling. So we're talking about calculus. We're finding the area under the slope is the main process in the integration. Similar, small intervals are made of the smallest possible length of x plus delta x, where delta x approaches almost an infinitesimally small space. And then it helps to find the overall acceleration by summing up all the lengths together. So we're summing up all the accelerations from the beginning to the end. And so here's our integral. We sum of a of x times d of x equals a plus c. That is our basic calculus here. So when we talk about multivariate calculus deals with functions that have multiple variables. And you can see here we start getting into some very complicated equations. Change in w over change of time equals change of w over change of z. The differential of z to dx, the differential of x to dt. It gets pretty complicated. And it really translates into the multivariate integration using double integrals. And so you have the sum of f of x of y of d of a equals the sum from c to d and a to b of f of x of y dx dy equals the sum of a to b, sum of c to d of f x of y dy dx. Understanding the very specifics of everything going on in here and actually doing the math is usually calculus 1, calculus 2, and differential equations. So you're talking about 3 full-length courses to dig into and solve these math equations. What we want to take from here is when we're talking about calculus, we're talking about summing of all these different slopes. And so we're still solving a linear expression. We're still solving y equals mx plus b. But we're doing this for infinitesimally small x's, and then we want to sum them up. That's what this integral sign means. The sum of a of x d of x equals a plus c. And when you see these very complicated multivariate differentiation using the chain rule, when we come in here and we have the change of w to the change of t equals a change of w dz, and so forth. That's what's going on here. That's what these means. We're basically looking for the area under the curve, which really comes to how is the change changing? Speed's going up. How is that changing? And then you end up with a multiple layer. So if I have 3 layers of neural networks, how is the third layer changing based on the second layer changing, which is based on the first layer changing? And you get the picture here that now we have a very complicated multivariate integration with integrals. The good news is we can solve this mathematically, and that's what we do when you do neural networks and reverse propagation. So the nice thing is that you don't have to solve this on paper unless you're data analysis and you're working on the back end of integrating these formulas and building the script to actually build them. So we talk about applications of calculus. It provides us the tools to build an accurate predictive model. So it's really behind the scenes. We want to guess at what the change of the change of the change is. That's a little goofy. I know. I just threw that out there. It's kind of a meta term. But if you can guess how things are going to change, then you can guess what the new numbers are. Multivariate calculus explains the change in our target variable in relation to the rate of change in the input variables. So there's our multiple variables going in there. If one variable is changing, how does it affect the other variable? And then in gradient descent, calculus is used to find the local and global maxima. And this is really big. We're actually going to have a whole section here on gradient descent because it is really, I mean, I talked about neural networks and how you can see how the different layers go in there, but gradient descent is one of the most key things for trying to guess the best answer to something. So let's take a look at the code behind gradient descent. And before we open up the code, let's just do real quick. Gradient descent. Let's say we have a curve like this. And most common is that this is going to represent your error. Oops. Error. There we go. Error. Hard to read there. And I want to make the error as low as possible. And so when I'm looking at it is I want to find this line here, which is the minimum value. So we're looking for the minimum. And it does that by sampling there. And then based on this, it guesses it might be someplace here. And it goes, hey, this is still going down. It goes here, and then goes back over here, and then goes a little bit closer. And it's just playing a high-low until it gets to that spot, that bottom spot. And so we want to minimize the error. On the flip note, you could also want to be maximizing something. You want to get the best output of it. That's simply minus the value. So if you're looking for where the peak is, this is the same as a negative for where the valley is. I'm looking for that valley. That's all that is, and this is a way of finding it. So the cool thing is all the heavy lifting's done. I actually ended up putting together one of these a while back when I didn't know about Scikit and I was just starting. Boy, it's a long while back. And is playing high-low. How do you play high-low, not get stuck in the valleys, figure out these curves and things like that? Well, you do that, and the back end is all the calculus and differential equations to calculate this out. The good news is you don't have to do those. So instead, we're going to put together the code. And let's go ahead and see what we can do with that. So, guys in the back put together a nice little piece of code here, which is kind of fun. Some things we're going to note, and this is really important stuff because when you start doing your data science and digging into your machine learning models, you're going to find these things are stumbling blocks. The first one is current X. Where do we start at? Keep in mind, your model that you're working with is very generic. So whatever you use to minimize it, the first question is, where do we start? And we started at this because the algorithm starts at x equals 3. So we arbitrarily picked 5. Learning rate is how many bars to skip going one way or the other. In fact, I'm going to separate that a little bit because these two are really important. If we're dealing with something like this where we're talking about, well, here's the function we're going to use. Our gradient of our function, 2 times x plus 5, keep it simple. So that's the function we're going to work with. So if I'm dealing with increments of 1,000, 0.1 is going to be a very long time. And if I'm dealing with increments of 0.001, 0.1 is going to skip over my answer. So I won't get a very good answer. And then we look at precision. This tells us when to stop the algorithm. So again, very specific to what you're working on. If you're working with money and you don't convert it into a float value, you might be dealing with 0.01, which is a penny. That might be your precision you're working with. And then, of course, the previous step size, max iterations. We want something to cut out at a certain point. Usually that's built into a lot of minimization functions. And then here's our actual formula we're going to be working with. And then we come in and we go, while previous step size is greater than precision and iters is less than max iters. Say that 10 times fast. We're just saying if we're still greater than our precision level, we still got to keep digging deeper. And then we also don't want to go past 1,000 or whatever this is, 1,000,000 or 10,000 running. That's actually pretty high. We almost never do max iterations more than like 100 or 200. Rare occasions you might go up to 400 or 500 if it's depending on the problem you're working with. So we have our previous equals our current. That way we can track time-wise. The current now equals the current minus the rate times the formula of our previous x. So now we've generated our new version. Previous step size equals the absolute current previous. So we're looking for the change in x. Iters equals iterations plus 1. That's so we know to stop if we get too far. And then we're just going to print the local minimum occurs at x on here. And if we go ahead and run this, you can see right here it gets down to this point and it says, hey, local minimum is minus 3.3222 for this particular series we created. And this is created off of our formula here, lambda x2 times x plus 5. Now, when I'm running this stuff, you'll see this come up a lot in with the Scikit-learn kit. And one of the nice reasons of breaking this down the way we did is I could go over those top pieces. Those top pieces are everything when you start looking at these minimization toolkits in built-in code. And so from, we'll just do, it's actually docs.scipy.org, and we're looking at the Scikit. There we go. Optimize, minimize. You can only minimize one value. You have the function that's going in. This function can be very complicated. So we used a very simple function up here. It could be, there's all kinds of things that could be on there. And there's a number of methods to solve this as far as how they shrink down. And your x naught. There's your start value. So your function, your start value, there's all kinds of things that come in here that you can look at, which we're not going to. Optimization automatically creates, constraints, bounds. Some of this it does automatically, but the big thing I want to point out here is you need to have a starting point. You want to start with something that you already know is mostly the answer. If you don't, then it's going to have a heck of a time trying to calculate it out. Or you can write your own little script that does this and does a high-low guessing and tries to find the max value. That brings us to statistics. What this is kind of all about is figuring things out. A lot of vocabulary in statistics. So statistics, well, I guess it's all relative. It's definitely not an EDL class. So a bunch of stuff going on in statistics. Statistics concerns with the collection, organization, analysis, interpretation, and presentation of data. That is a mouthful. So we have from end to end, where does it come from? Is it valid? What does it mean? How do we organize it? How do we analyze it? And then you got to take those analyses and interpret it into something that people can use, kind of reduce it to understandable. And nowadays you have to be able to present it. If you can't present it, then no one else is going to understand what the heck you did. So when we look at the terminologies, there's a lot of terminologies depending on what domain you're working in. So clearly if you're working in a domain that deals with viruses and T cells and how does, where does that come from, and you're studying the different people, then you're going to have a population. If you are working with mechanical gear, a little bit different. If you're looking for the wobbling statistics to know when to replace a rotor on a machine or something like that, that can be a big deal. We have these huge fans that turn in our sewage processing systems. And so those fans, they start to wobble and hum and do different things that the sensors pick up. At one point, do you replace them instead of waiting for it to break, in which case it costs a lot of money. Instead of replacing a bushing, you're replacing the whole fan unit. An interesting project that came up for our city a while back. So population. All objects or measurements whose properties are being observed. So that's your population, all the objects. It's easy to see it with people because we have our population in large. But in the case of the sewer fans, we're talking about the fan units. That's the population of fans that we're working with. You have a parameter, a metric that is used to represent a population or characteristic. You have your sample, a subset of the population studied. You don't want to do them all because then you don't have if you come up with a conclusion for everyone, you don't have a way of testing it. So you take a sample. Sometimes you don't have a choice. You can only take a sample of what's going on. You can't study the whole population. And a variable, a metric of interest for each person or object in a population. Types of sampling. We have a probabilistic approach, selecting samples from a larger population using a method based on the theory of probability. And we'll go into a little bit more deeper on these. We have random, systematic, stratified. And then you have a non-probabilistic approach, selecting samples based on the subjective judgment of the researcher rather than random selection. It has to do with convenience, trying to reach a quota, or snowball. And they're very biased. That's one of the reasons you'll see this big stamp on it that says biased. So you got to be very careful on that. So probabilistic sampling. When we talk about a random sampling, we select random size samples from each group or category. So it's as random as you can get. When we talk about systematic sampling, we're selecting random size samples from each group or category with a fixed periodic interval. So we kind of split it up. This would be like a time setup or our different categories. And you might ask your question, well, what is a category or a group? If you look at, I'm going to go back a window. Let's say we're studying economics of an area. We know pretty much that based on their culture and where they came from, they might need to be separated. And so, and when I say separated, I don't mean separated from their place where they live. I mean, as far as the analysis, we want to look at the different groups and make sure they're all represented. So if we had like an 80% of a group that is, say, Hispanic or Indian, and also in that same area, we have 20% who are, let's call our expatriates. They left America and they're nice, and your Caucasian group. We might want to sample a group that is representative of both. So we're talking about stratified sampling, and we're talking about groups. Those are the groups we're talking about. And that brings us to stratified sampling, selecting approximately equal size samples from each group or category. This way we can actually separate the categories and give us an insight into the different cultures and how that might affect them in that area. So you can see these are very, very different, kind of depends on what you're working with as far as your data and what you're studying. And so we can see here, just to go a little bit more, we'd have selecting 25 employees from a company of 250 employees randomly. Don't care anything about them, what groups they're in, which office they're in, nothing. And we might be selecting one employee from every 50 unique employees in a company of 250 employees. And then we have selecting one employee from every branch in the company office. So we have all the different branches. There's our group or our categories by the branch. And the category could depend on what you're studying. So it has a lot of variation on there. You see this kind of grouping and categorizing is also used to generate a lot of misinformation. So if you only study one group and you say, this is what it is, then everybody assumes that's what it is for everybody. And so you got to be very careful of that, and it's a very unethical thing to kind of do. So types of statistics. When we talk about statistics, we're going to talk about descriptive and inferential statistics. There are so many different terms in statistics to break it up. So we're talking about a particular setup. So we're talking about descriptive and inferential statistics. The base of the word describe is pretty solid. You're describing the data. What does it look like? With inferential statistics, we're going to take that from the small population to a large population. So if you're working with a drug company, you might look at the data and say, these people were helped by this drug. They did 80% better as far as their health, or 80% better survival rate than the people who did not have the drug. So we can infer that that drug will work in the greater populace and will help people. So that's where you get your inferential. So we are predicting how it's going to affect the greater population. So descriptive statistics. It is used to describe the basic features of data and form the basis of quantitative analysis of data. So we have a measure of central tendencies. We have your mean, median, and mode. And then we have a measure of spread, like your range, your interquartile range, your variance, and your standard deviation. And we're going to look at all these a little deeper here in a second. But one of them you can think of is how the data differences, what's the max, min range, all that stuff is your spread. And anything that's just a single number is usually your central tendencies, measure of central tendencies. So when we talk about the mean, it is the average of the set of values considered. What is the average outcome of whatever's going on? And then your median separates the higher half and the lower half of data. So where's the center point of all your different data points? So your mean might have a couple really big numbers that skew it so that the average is much higher than if you took those outliers out, where the median would, by separating the high from the low, might give you a much lower number. You might look at it and say, oh, that's odd. Why is the average so much higher than the median? Well, it's because you have some outliers. Or why is it so much lower? And then the mode is the most frequent appearing value. This is really interesting if you're studying economics and how people are doing. You might find that the most common income, like in the U.S., was $1,24000 a year, where the average was closer to $80,000. And it's like, wow, what a difference. Well, there's some people who have a lot of money, and so that skews that way up. So the average person is not making that kind of money. And then you look at the median income, and you're like, well, the median income is a little bit closer to the average. So it does create a very interesting way of looking at the data. Again, these are all central tendencies, single numbers you can look at for the whole spread of the data. And we look at the measure of central tendencies. The mean is the average marks of a student in a classroom. So here we have the mean, sum of the marks of the students, total number of students. And as we talked about the median, if we have 0 through 10, and we take half the numbers and put them on one side of the line, half the numbers on the other side of the line, we end up with 5 in the middle. And then the mode. What mark was scored by most of the students in a test? In a simple case where most people scored like an 82% and got certain problems wrong, easy to figure out. Not so easy when you have different areas where like you have like the, let's go back to economy. A little bit more difficult to calculate if you have a large group that makes 30,000 and a slightly bigger group that makes 26,000. So what do you put down for the mode? Certainly there's a number of ways to calculate that, and there's actually different variations depending on what you're doing. So now we're looking at a measure of spread, range. What's the difference between the highest and the lowest value? First thing you want to look at, we had everybody in the test scored between 60 and 100%. Somebody got 100%, or maybe 60 to 90%. It was so hard that a lot of people could not get 100%. Then you have your interquartile range. Quartiles divide a rank-ordered data set into 4 equal parts. Very common thing to do as part of all the basic packages, whether you're working in data frames with Pandas, whether you're working in Scala, whether you're working in R. You'll see this come up where they have range, your min, your max, and then it'll have your interquartile range. How does it look like in each quarter of data? Variance measures how far each number in the set is from the mean and therefore from every other number in the set. So you have like how much turbulence is going on in this data. And then the standard deviation. It is the measure of the variance or the dispersion of a set of values from the mean. And you'll usually see, if I'm doing a graph, I might have the value graphed, and then based on the error, I might graph the standard deviation and the error on the graph as a background, so you can see how far off it is. So standard deviation is used a lot. So measurement of spread. Marks of a student out of 100. We have here from 50 to 63 or 50 to 90. So the range, maximum marks, minimum marks, we have 90 to 45, and the spread of that is 45, 90 minus 45. And then we have the interquartile range using the same marks over there. You can see here where the median is. And then there's the first quarter, the second quarter, and the third quarter based on splitting it apart by those values. And to understand the variance and standard deviation, we first need to find out the mean. So here's our calculating the average there. We end up at approximately 66 for the average. And then we look at that and the variance. Once we know the means, we can do equals the marks minus the mean squared. Why is it squared? Because one, you want to make sure you don't have like if you're putting all this stuff together, you end up with an error as far as one's negative, one's positive, one's a little higher, one's a little lower. So you always see the squared value and over the total observations. And so the standard deviation equals the square root of the variance, which is approximately 16. And if you were looking at a predictable model, you would be looking at the deviation based on the error. How much error does it have? And that's, again, really important to know. If your prediction is predicting something, what's the chance of it being way off or just a little bit off? Now that we've looked at the tools, as far as some of the basics for doing your statistics and what we're talking about, let's go ahead and pull up a little demo and show you what that looks like in Python code, so you can get some little hands-on here. For that, let's go back into our Jupyter Notebook in Python. Now, almost all of this you can do in NumPy. Last time we worked in NumPy. This time we're going to go ahead and use Pandas. And if you remember from Pandas on here, this is basically a data frame, rows, columns. Let's just go ahead and do a print df.head and run that. And you can see we have the name Jane, Michael, William, Rosie, Hannah, and their salaries on here. And of course, instead of having to do all those hand calculations and add everything together and divide by the total, we can do something very simple on this, like use the command mean in Pandas. And so if I go ahead and do this, print df, pick our column, salary, because we want to find the means of that column. We want to find the means of that column. And we go ahead and print this out, and you can see that the average income on here is 71,000. And let's just go ahead and do this. We'll go ahead and put in means. And if we're going to do that, we also might want to find the median. And the median is very similar, except it actually is just median. We're used to means and average. It's kind of interesting that they use the two different words. There can be, in some computations, slight differences, but for the most part, the means is the average. And then the median, whoops, let's put a median here, df salary, that way it displays a little better. We can see the median is 54,000, so the halfway mark is significantly below the average. Why? Because we have somebody in here who makes 189,000. Darn you, Rosie, for throwing off our numbers. But that's something you'd want to notice. This is the difference between these is huge, and so is what is the meaning behind that when you're studying a populace and looking at the different data coming in. And of course, we also want to find out, hey, what's the most common income that people make in this little tiny sample. And so we'll go ahead and do the mode. And you can see here with the mode, it's at 50,000. So this is very telling that most people are making 50,000. The middle point is at 54,000, so half the people are making more than that. What that tells me is that if the most common income is below the median, then there's a lot of high salaries going up, but there's some really low salaries in there. And so this trend, which is very common in statistics, when you're analyzing the economy and different people's income, is pretty common. And the bigger difference between these is also very important when we're studying statistics. And when you hear someone just say, hey, the average income was, you might start asking questions at that point. Why aren't you talking about the median income? Why aren't you talking about the mode, the most common income? What are you hiding? And if you're doing these analyses, you should be looking at these saying, hey, why are these discrepancies? Why are these so different? And of course, with any analysis, it's important to find out the minimum and the maximum. So we'll go ahead. It's just simply dot min will pull up your minimum, and then dot max pulls up the maximum. Pretty straightforward on as far as translating it and knowing what your lowest value and what your highest value is here, which you'll use to generate like a spread later on. And real quick on mode, note that it puts mode 0. Like I said, there's a couple different ways you can compute the mode, although the standard one's pretty good. We can of course do the range, which is your max minus your min. So now we have a range of 149,000 between the upper end and the lower end. And you might want to be looking up the individual values on all of these. But it turns out there is a describe feature in Pandas. And so in Pandas, we can actually do df salary describe. And if we do this, you can see we have that there's 7 setups. Here's our mean, our standard deviation, which we didn't compute yet, which should just be a .std. And you got to be a little careful because when it computes it, it looks for axes and things like that. We have our minimum value, and here's our quartiles, our maximum value, and then of course the name salary. So these are the basic statistics. You can pull them up and like just describe. This is a dictionary, so I could actually do something like in here I could actually go count and run, and now it just prints the count. So because this is a dictionary, you can pull any one of these values out of here. It's kind of a quick and dirty way to pull all the different information and then split it up depending on what you need. Now, if I just walked in and gave you this information in a meeting, at some point you would just kind of fall asleep. That's what I would do anyway. So we want to go ahead and see about graphing it here. And we'll go ahead and put it into a histogram and plot that graph on it of the salaries. And let's just go ahead and put that in here. So we do our matplot inline. Remember, that's a Jupyter's Notebook thing. A lot of the new version of the matplot library does it automatically. But just in case, I always put it in there. Import matplot library pyplot as PLT. That's my plotting. And then we have our data frame. I guess I really don't need to respell the data frame. Maybe we could just remind ourselves what's in it. So we'll go ahead and just print df. That way we still have it. And then we have our salary df salary, salary.plot history title, salary distribution, color gray, plot AXV line, salary the mean value. So we're going to take the mean value, color violet, line style dash. This is just all making it pretty. What color, dash line, line width of 2, that kind of thing. And the median. And let's go ahead and run this just so you can see what we're talking about. And so up here we are taking on our plot. So here's the data. Here's our data frame printed out so you can see it with the salaries. And we're looking at the salary distribution. And just look at this, the way the salary is distributed. You have our, in this case we did, let's see, we had red for the median. We have violet for our average or mean. And you can just see how it really, I mean, here's our outlier. Here's our person who makes a lot of money. Here's the average, and here's the median. And so as you look at this, you can say, wow, based on the average, it really doesn't tell you much about what people are really taking home. All it does is tell you how much money is in this, what the average salary is. So some of the things you want to take away in addition to this is that it's very easy to plot an AXV line. These are these up and down lines for your markers. And as you display the data, I mean, you can add all kinds of things to this and get really complicated. Keeping it simple is pretty straightforward. I look at this and I can see we have a major outlier out here. We can definitely do a histogram and stuff like that. But, picture's worth 1,000 words. What you really want to make sure you take away is that we can do a basic describe, which pulls all this information out, and we can print any of the individual information from the describe, because this is a dictionary. And so if we want to go ahead and look up the mean value, we can also do describe mean. So if you're doing a lot of statistics, being able to, it doesn't have the print on there, so it's only going to print the last one, which happens to be the mean. You can very easily reference any one of these. And then you can also, if you're doing something a little bit more complicated and you don't need just the basics, you can come through and pull any one of the individual references from the pandas on here. So now we've had a chance to describe our data. Let's get into inferential statistics. Inferential statistics allows you to make predictions or inferences from data. And you can see here we have a nice little picture of movie ratings, and if we took this group of people and said, hey, how many people like the movie, dislike it, can't say, and then you ask just a random person who comes out of the movie who hasn't been in this study, you can infer that 55% chance of saying liked, 35% chance of saying disliked, or a 10 or 11% chance of can't say. So that's real basics of what we're talking about, is you're going to infer that the next person is going to follow these statistics. So let's look at point estimation. It is a process of finding an approximate value for a population's parameter, like mean or average, from random samples of the population. Let's take an example of testing vaccines for COVID-19. Vaccines and flu bugs, all that, it's a pretty big thing of how do you test these out and make sure they're going to work on the populace. A group of people are chosen from the population. Medical trials are performed. Results are generalized for the whole population. So here's our small group up here where we've selected them. We run medical trials on them, and then the results work for the population. Nice diagram with the arrows going back and forth and the very scary COVID virus in the middle of one. And let's take a look at the applications of inferential statistics. Very central is what they call hypotheses testing, and the confidence interval, which go with that. And then as we get into probability, we get into our binomial theorem, our normal distribution, and central limit theorem. Hypothesis testing. Hypothesis testing is used to measure the plausibility of a hypothesis, assumption, by using sample data. Now, when we talk about theorems, theory, hypothesis, keep in mind that if you are in a philosophy class, theory is the same as hypothesis, where theorem is a scientific statement that is something that has been proven, although it is always up for debate, because in science we always want to make sure things are up to debate. So a hypothesis is the same as a philosophical class calling a theory, where theory in science is not the same. Theory in science says this has been well proven. Gravity is a theory. So if you want to debate the theory of gravity, try jumping up and down. If you want to have a theory about why the economy is collapsing in your area, that is a philosophical debate. Very important. I've heard people mix those up, and it is a pet peeve of mine. When we talk about hypotheses testing, the steps involved in hypotheses testing is first we formulate a hypothesis. We figure out the right test to test our hypothesis. We execute the test, and we make a decision. And so when you're talking about hypothesis, you're usually trying to disprove it. If you can't disprove it and it works for all the facts, then you might call that a theorem at some point. So in a use case, let's consider an example. We have 4 students who were given a task to clean a room every day. Sounds like working with my kids. They decided to distribute the job of cleaning the room among themselves. They did so by making 4 chits, which has their names on it, and the name that gets picked up has to do the cleaning for that day. Rob took the opportunity to make chits and wrote everyone's name on it. So here's our 4 people: Nick, Rob, Imlia, and Summer. Now Rick, Imlia, and Summer are asking us to decide whether Rob has done some mischief in preparing the chits, i.e. whether Rob has written his name on one of the chit. For that, we will find out the probability of Rob getting the cleaning job on first day, second day, third day, and so on till 12 days. The probability of Rob getting the job decreases every day, i.e. his turn never comes up, then definitely he has done some mischief while making the chits. So the probability of Rob not doing work on day 1 is 3 out of 4. There's a 0.75 chance that he didn't do work. 2 days, 3/4 times 3/4 equals 0.56. 3 days, you have 3/4, 3/4, 3/4, which equals 0.42. When you get to day 12, it's 0.032, which is less than 0.05. Remember this 0.05. That comes up a lot when we're talking about certain values, when we're looking at statistics. Rob is cheating as he wasn't chosen for 12 consecutive days. That's a very high probability when on day 12 he still hasn't gotten the job cleaning the room. So we come up to our important terminologies. We have null hypothesis, a general statement that states that there is no relationship between 2 measured phenomena or no association among the groups. Alternative hypothesis. Contrary to the null hypothesis, it states whenever something is happening, a new theory is preferred instead of an old one. And so the two hypotheses go hand in hand. So your null, this is always interesting in when we're talking about data science and the math behind it, it's about proving that the things have no correlation. Null hypothesis says these two have zero relation to each other. Where the alternative hypothesis says, hey, we found a relation, this is what it is. We have p-value. The p-value is a probability of finding the observed or more extreme results when the null hypothesis of a study question is true. And the t-value, it is simply the calculated difference represented in units of standard error. The greater the magnitude of t, the greater the evidence against the null hypothesis. And you can look at the t-value as being specific to the test you're doing, where the p-value is derived from your t-value, and you're looking for what they call the 5% or the 0.05, showing that it has a high correlation. So digging in deeper, let's assume that a new drug is developed with the goal of lowering the blood pressure more than the existing drug. And this is a good one because the null value here isn't that you don't have any drug. The null value here is that it's better than the existing drug. The new drug doesn't lower the blood pressure more than the existing drug. Now, if we get that, that says our null hypothesis is correct. There is no correlation, and the new drug is not doing its job. The alternative hypothesis, the new drug does significantly lower the blood pressure more than the existing drug. Yay, we got a new drug out there. And that's our alternative hypothesis, or the H1 or HA. And we look at the p-value, results from the evidence like medical trials showing positive results which will reject the null hypothesis. And again, they're looking for a 0.05 or 5%. And the t-value, comparing all the positive test results and finding means of different samples in order to test hypothesis. So this is specific to the test. What percentage of increase did they have? And this leads us to the confidence intervals. A confidence interval is a range of values we are sure our true values of observations lie in. Let's say you asked a dog owner around you and asked them, how many cans of food do you buy for your per year for your dog? Through calculations, you got to know that on an average, around 95% of the people bought around 200 to 300 cans of food. Hence, we can say that we have a confidence interval of 2-300, where 95% of our values lie in that data spread. And the graph really helps a lot, so you can start seeing what you're looking at here, where you have the 95%. You have your peak. In this case, it's a normal distribution, so you have the nice bell curve equal on both sides. It's not asymmetrical. And 95% of all the values lie within a very small range, and then you have your outliers, the 2.5% going each way. So we touched upon hypothesis, and we're going to move into probability. So you have your hypothesis. Once you've generated your hypothesis, we want to know the probability of something occurring. Probability is a measure of the likelihood of an event to occur. Any event can be predicted with total certainty and can only be predicted as a likelihood of its occurrence. So any event cannot be predicted with total certainty. It can only be predicted as a likelihood of its occurrence. Score prediction, how good you're going to do in whatever sport you're in, weather prediction, stock prediction. If you've studied physics and chaos theory, even the location of the chair you're sitting on has a probability that it might move 3 feet over. Granted, that probability is 1 in I think we calculated it as under 1 in trillions upon trillions. So the better the probability, the more likely it's going to happen. There are some things that have such a low probability that we don't see them. So we talk about a random variable. Random variable is a variable whose possible values are numerical outcomes of a random phenomena. So we have the coin toss. How many heads will occur in the series of 20 coin flips? Probably, on average they're 10, but you really can't know because it's very random. How many times a red ball is picked from a bag of balls, if there's equal number of red balls and blue balls and green balls in there. How many times the sum of digits on 2 dice result are 5 each. So, there's how often are you going to roll 2 5s on your pair of dice. So in a use case, let's consider the example of rolling 2 dice. We have a random variable outcome equals y. You can take values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a random variable and a combination of dice. And instead of looking at how many times both dice will roll 5, let's go ahead and look at total sum of 5. And you have, as far as your random variables, you can have a 1, 4 equals 5, 4, 1, 2, 3, 3, 2. So 4 of those rolls can be 4. If you look at all the different options you have, 4 of those random rolls can be a 5. And if we look at the total number, which happens to be 36 different options, you can see that we have 4 out of 36 chance every time you roll the dice that you're going to roll a total of 5. You're going to have an outcome of 5. And we'll look a little deeper as to what that means. But you could think of that at what point, if someone never rolls a 5 or they always roll a 5, can you say, hey, that person's probably cheating? We'll look a little closer at the math behind that. But let's just consider this is one of the cases, is rolling 2 dice and gambling. There's also binomial distribution. It is the probability of getting success or failure as an outcome in an experiment or trial that is repeated multiple times. And the key is bi, meaning 2, binomial. So passing or failing an exam, winning or losing a game, and getting either head or tails. So if you ever see binomial distribution, it's based on a true-false kind of setup. You win or lose. Let's consider a use case, and let's consider the game of football between 2 clubs, Barcelona and Dortmund. The teams will have to play a total of 4 matches, and we have to find out the chances of Barcelona winning the series. So we look at the total games, and we're looking at 5 different games or matches. Let's say that the winning chance for Barcelona is 75% or 0.75. That means that each game, they have a 75% chance that they're going to win that game. And losing chances are 25% or 0.25. Clearly 0.75 plus 0.25 equals 1. So that accounts for 100% of the game. Probability for getting K wins in N matches is calculated. And we're talking like, so if you have 5 games and you want to know if I play, how many wins in those 5 games should I get? What's the percentage on those? And the probability for getting K wins in N matches is calculated by Px equals K equals NCK, P to the K, Q to the N minus K. Here, P is the probability of success and Q is the probability of failure. And so we can do total games of N equals 5, where K equals 0, 1, 2, 3, 4, 5. P, which is the chance of winning, is 0.75. Q, the chance of losing, equals 1 minus P, which equals 1 minus 0.075, which equals 0.25. The probability that Barcelona will lose all of the matches can then just plug in the numbers, and we end up with a 0.0009765,625. So a very small chance they're going to lose all their matches. And we can plug in the value for 2 matches. Probability that Barcelona will win at least 2 matches is 0.0878. And of course we can go on to the probability that Barcelona will win 3 matches, the 0.26, and of course 4 matches, and so on. And it's always nice to take this information and let's find the cumulative discrete probabilities for each of the outcomes. Where Barcelona has won 3 or more matches, x equals 3, x equals 4, x equals 5. And we end up with the P equals 0.264 plus 0.395 plus 237, which equals 0.89. In reality, the probability of Barcelona winning the series is much higher than 0.75. And it's always nice to put out a nice graph so you can actually see the number of wins to the probability and how that pans out with our binomial case. Continuing in our important terminology, location. The location of the center of the graph depends on the mean value. And this is some very important things. So much of the data we look at, and when you start looking at probabilities, almost always has a normalized look, like the graph in the middle. But you do have left skewed, where the data is skewed off to the left, and you have more stuff happening off to the left, and you have right skewed data. And so when this comes up and these probabilities come up where they're skewed, it's really important to take a closer look at that. Mostly you end up with a normalized set of data, but you got to also be aware that sometimes it's a skewed data. And then the height. Height of the slope inversely depends upon the standard deviation. So you can see down here the standard deviation is really large. It kind of squishes it out. And if the standard deviation is small, then most of your data is going to hit right there in the middle. You're going to have a nice peak. And so being aware of this, that you might have a probability that fits certain data, but it has a lot of outliers. So if you have a really high standard deviation, if you're doing stock market analysis, this means your predictions are probably not going to make you much money. Where if you have a very small deviation, you might be right on target and set to become a millionaire. Which leads us to the z-score. Z-score tells you how far from the mean a data point is. It is measured in terms of standard deviations from the mean. Around 68% of the results are found between one standard deviation. Around 95% of the results are found between two standard deviations. And you read the symbols. Of course, they love to throw some Greek letters in there. We have mu minus 2 sigma. Mu is just a quick way. It's that kind of funky U. It just means the mean. And then the sigma is the standard deviation. And that's the O with the little arrow off to the right, or the little waggly tail going up, the O with the line on it. So mu minus 2 sigma is your 95% of the results are found between two standard deviations. Central limit theorem. This goes back to the skew. If you remember, we were looking at the skew values on this previous slide. Have left skewed, normalized, and right skewed. When we're talking about it being skewed or not skewed, the distribution of the sample means will be approximately normally distributed, evenly distributed, not skewed, if you take large random samples from the population with the mean, mu, and the standard deviation, sigma, with replacement. And you can see here, of course, we have our mu minus 2 sigma and the spread down here, the mean, the median, and the mode. And so when you're talking about very large populations, these numbers should come together and you shouldn't have a skewed value. If you do, that's a flag that something's wrong. That's why this is so important to be aware of what's going on with your data, where your samples are coming from, and the math behind it. And if we're going to do all this, we got to jump into conditional probability. The conditional probability of an event A is a probability that the event will occur given the knowledge that an event B has already occurred. And you'll see this as Bayes' theorem, B-A-Y-E-S, Bayes. And this is read, I mean, you have these funky looking little P brackets, A, B. This is the probability of A being true while B is already true. And you have the probability of B being true when A is already true, so P, B of A. The probability of A being true divided by the probability of B being true. And we talk about Bayes' theorem, which occurred back in the 1800s when he discovered this. This is such an important formula. And it's not, if you actually do the math, you could just kind of do xy equals jk, and then you divide them out, and you're going to see the same math. But it works with probabilities, which makes it really nice. And so if you have you might have 8 or 9 different studies going on in different areas. Different people have done the studies, they brought them together. If we look at today's COVID virus, the virus spread, certainly the studies done in China versus the studies the way they're done in the US, that data is different in each of those studies. But if you can find a place where it overlaps, where they're studying the same thing together, you can then compute the changes that you need to make in one study to make them equal. And this is also true if you have a study of one group and you want to find out more about it. So this formula is very powerful, and it really has to do with the data collection part of the math and data science, and understanding where your data is coming from and how you're going to combine different studies in different groups. And we'll go ahead and go into a use case. Let's find out the chance of a person getting lung disease due to smoking. And this is kind of interesting the way they word this. Let's say that according to medical report provided by the hospital, states that around 10% of all patients they treated suffered lung disease. So we have kind of a generic medical report. They further found out by a survey that 15% of the patients that visit them smoke. So we have 10% that are lung disease, and 15% of the patients smoke. And finally, 5% of the people continued smoke even when they had lung disease. Not the brightest choice, but it is an addiction, so it can be really difficult to kick. And so we can look at the probability of A, prior probability of 10% people having lung disease. And then probability B. Probability that a patient smokes is 15%. And the probability of B, if B then A, the probability of a patient smokes even though they have lung disease is 5%. And probability of A is B, probability that the patient will have lung disease if they smoke. And then when you put the formulas together, you get a nice solution here. You get the probability of A of B, probability that the patient will have lung disease if they smoke. And you can just plug the numbers right in, and we get a 3.33% chance. Hence, there is a 3.33% chance that a person who smokes will get a lung disease. So we're going to pull up a little Python code. Always my favorite. Roll up the sleeves. Keep in mind, we're going to be doing this kind of like the back-end way, so that you can see what's going on. And then later on, we're going to create, we'll get into another demo which shows you some of the tools that are already pre-built for this. Let's start by creating a set. So we're going to create a set with curly braces. This means that our set has only unique values. So you have a list, you have your tuples, which can never change, and then you have, in this case, the set. So 4, 7, you can't create a 4, 7, comma 4. It'll delete the 4 out. So it's only unique values. And if you use dictionaries, quick reminder, this should look familiar because it is a dictionary where you have a value, and that value is assigned to, or that key is assigned to a value. So you could have a key value set up as a dictionary. So it's like a dictionary without the value. It's just the keys, and they all have to be unique. And if we run this, we have a set of 4, 7. We can also take a list, a regular setup, and I'm going to go ahead and just throw in another number in here, 4, and run it. And you can see here, if I take my list 1, 2, 3, 4, 4, and I convert it to a set, and here it is, my set from list equals set, my list. The result is 1, 2, 3, 4. So it just deletes that last 4 right out of there. And with the sets, you can also go in there and print, here is my set, 3 is in the set, and then if you do 3 in my set, that's going to be a logic function. And 1 in my set, 6 is not in the set, and so forth. If we run this, we get 3 is in the set true, 1 is in the set false, because 3, 5, 7 is another 1. 6 is in the set, 6 is not in the set, so not in my set. You can also use this with a list. We could have just used 3, 5, 7, and it would have the same response on there. Is 3 in, usually you do if 3 is in, but 3 in my set still works on just a regular list. And we'll go ahead and do a little iteration. We're going to do kind of the dice one. Remember 1, 2, 3, 4, 5, 6. And so we're going to bring in an iteration tool and import product as product. And I'll show you what that means in just a second. So we have our 2 dice. We have dice A, and it's going to be a set of values. You can only have 1 value for each one. That's why they put it in a set. And if you remember from range, it is up to 7. So this is going to be 1, 2, 3, 4, 5, 6. It will not include the 7. And the same thing for our dice B. And then what we're going to do is we're going to create a list, which is the product of A and B. So what's A plus B? And if we go ahead and run this, it'll print that out, and you'll see, in this case, when they say product, because it's an iteration tool, we're talking about creating a tuple of the 2. So we've now created a tuple of all possible outcomes of the dice, where dice A is 1, 2, 3, 1 to 6, and dice B is 1 to 6. And you can see 1 to 1, 1 to 2, 1 to 3, and so forth. You can remember we had a slide on this earlier where we talked about all the different outcomes of a dice. We can play around with this a little bit. We can do in dice equals 2, dice faces 1, 2, 3, 4, 5, 6. Another way of doing what we did before, and then we can create an event space where we have a set, which is the product of the dice faces repeat equals in dice. And we'll go ahead and just run this. And you can see here it just again puts it through all the different possible variables we can have. And then if we wanted to take the same set on here and print them all out like we had before, we can just go through for outcome and event space, outcome and equals. So the event space is creating a sequence, and as you can see here, when we print it out, it stacks them versus going through and putting them in a nice line. And we'll go ahead and do something, let's go print. Since we have the end printing with a comma, that just means it's not going to hit the return going down to the next line. And we'll go ahead and do the length of our event space. That'll be an important variable we're going to want to know in a minute. And of course, if I get carried away with my typing of length, we'll print it twice and it'll give me an error. So we have 36 different possible variations here. And we might want to calculate something like, what about the multiple of 3? What if we want to have the probability of the multiple of 3 in our setup? And so we can put together the code for the outcome and event space of x, y equals outcome. If x plus y, remainder 3, so we're going to divide by 3 and look at the remainder, and it equals 0, then it's a favorable outcome. And we're going to pop that outcome on the end there. And we'll turn it into a set. So the favorable outcome equals a set. Not necessary because we know it's not going to be repeating itself, but just in case, we'll go ahead and do that. And if we want to print out the outcome, we can go ahead and see what that looks like. And you can see here, these are all multiples of 3. 1 plus 2 is 3, 5 plus 4 is 9, which divided by 3 is 3, and so forth. And just like we looked up the length of the one before, let's go ahead and print the length of our F outcome, so we can see what that looks like. There we go. And of course, I did forget to add the print in the middle because we're looping through and putting an end on the setup on there. So we're going to put the print in there. And if I run this, you can see we end up with 12. So we have 36 total options. We have 12 that are multiple that add up to a multiple of 3. And we can easily compute the probability of this by simply taking the length of our favorable outcome over the length of the event space. And if we print it out, let me put that in there, probability, last line, so we can just type it in, we end up with a 0.3333 chance. And it's roughly a third. And we might want to make this look nice, so let's go ahead and put in another line there. The probability of getting the sum, which is a multiple of 3, is 0.3333. We can compute the same thing for 5 dice. And if we do this for 5 dice and go ahead and run it, you can see we just have a huge amount of choices. So it just goes on and on down here. And we can look at the length of the event space. And we have over 7,776 choices. That's a lot of choices. And if we want to ask the question like we did above, what is the sum, where the sum is a multiple of 5 but not a multiple of 3, we can go through all of these different options, and then you can see here D1, D2, D3, D4, D5 equals the outcome. And if you add these all together and the division by 5 does not have a remainder of 0, but the remainder is also of a division by 3 is not equal to 0. So the multiple of 5 is equal to 0, but the multiple of 3 is not. We can just append that on here, and then we can look at that favorable outcome. We'll go ahead and set that, and we'll just take a look at this. What's our length of our favorable outcome? It's always good to see what we're working with. And so we have 904 out of 776. And then, of course, we can just do a simple division to get the probability on here. What's the probability that we're going to roll a multiple of 5 when you add them together, but not a multiple of 3. And so we're just going to divide those two numbers, and you can see here we get 0.116255, or 11.62%. And so you can really have a nice visual that this is not really complicated math right here on probabilities. It's just how many options do you have, and how many of those are you possibly going to be able to come up with the solution you're looking for. And this leads us to a confusion matrix. A confusion matrix is a table which is used to describe the performance of a classification model on a set of test data for which the true values are known. And so you'll see on the left we have the predicted and the actual. And we have a negative, false negative, positive, true positive, and then we have false positive and true negative. And you can think of this as your predicted model. What does that mean? That means if you divided your data and you used 2/3 of it to create the model, you might then test it against an actual case for the last third to see how well it comes out. How many times was it true positive versus false positive? It gave a false positive response. And you can imagine in medical situations, this is a pretty big deal. You don't want to give a false positive. So you might adjust your model accordingly so you don't have a false positive. Say with a COVID virus test, it'd be better to have a false negative and they go back and get retested than to have 30% false positives where then the test is pretty much invalid. So in a use case like cancer prediction, let's consider an example where a cancer prediction model is put to the test for its accuracy and precision. Actual result of a person's medical report is compared with the prediction made by the machine learning model. And so you can see here, here's our actual predicted, whether they have cancer or not. You know, cancer, a big one. You don't want to have a false positive. I mean, a false negative. In other words, you don't want to have it tell you that you don't have cancer when you do. So that would be something you'd really be looking for in this particular domain. You don't want a false negative. And this is, again, you know, you've created a model. You have hundreds of people or thousands of pieces of data that come in. There's a real famous case study where they have the imagery and all the measurements they take, and there's about 36 different measurements they take. And then if you run a basic model, you want to know just how accurate it is. How many negative results do you have that are either telling people they have cancer that don't, or telling people that don't have cancer that they do. And then we can take these numbers and we can feed them into our accuracy, our precision, and our recall. So accuracy, precision, and recall. Accuracy metric to measure how accurately the results are predicted. And this is your total true, where you got the right results, you add them together, the true positive, the true negative, over all the results. So what percentage of them were accurate versus what were wrong. When we talk about precision, is a metric to measure how many of the correctly predicted cases are actually turned out to be positive. So we have a precision on true positive. Again, if you're talking about like COVID testing with the viruses, you really want this to be a high number. You want this true that to be the center point, where you might have the opposite if you're dealing with cancer, where you want no false negatives. So this is your metric on here. Precision is your test positive, true positive plus false positive. And then your recall, how many of the actual positive cases we were able to predict quickly with our model. So test positive is the test positive plus the false negative on there. And we'll want to go ahead and do a demo on the naive Bayes classifier. Before I get too far into naive Bayes classifier, because we're going to pull it from the Scikit-learn or the Scikit, let's go ahead. Kind of an interesting page here for classifiers. When you go into the Scikit-learn kit, there's a lot of ways to do classification. And I'll just zoom up in here so you can see some of the titles. There's everything from the nearest neighbor, linear, but we're going to be focusing on the naive Bayes over here. And this is just a sample data set that they put together, and you can see how some of these have a very different output. The naive Bayes, remember, is set up as probably the most simplified calculator or set of predictions out there. And so what we've been talking about with the true false and stuff like that, where there's a a belief that there is a independent assumption between the features, where the features are very assumed to have some kind of connection, then we can go ahead and use that for the prediction. And so that's what we're using as a naive Bayes classifier versus many of the other classifiers that are out there. For this, we're going to use the social network ads. It's a little data set on here. And let me go ahead and just open that up, the file. Here we go. It has user ID, gender, age, estimated salary, purchased. And so we have, you can see the user ID, male, 19, estimated salary, 19,000, and purchased 0. So it's either going to make a purchase or not. So look at that last one, 0, 1, we should be thinking of binomials, we should be thinking of simple naive Bayes classifier kind of setup. So if we close this out, we're going to go ahead and import our NumPy as NP. We're going to have a good visual of our data, so we'll put in our matplot library. Here's our pandas, our data frame. And then we're going to go ahead and import the data set. And the data set's going to be, we're going to read it from the social network ads.csv. Then we're going to print the head just so you can see it again, even though I showed you it in the file. And x equals the data set iLocation, 2, 3 values, and y is going to be the 4, column 4. Let me just run this so it's a little easier to go over that. You can see right here we're going to be looking at 0, 1, 2 is age and estimated salary, so 2, 3. And that's what iLocation just means, that we're looking at the number versus a regular location. Regular location, you'd actually say age and estimated salary. And then column 4 is, did they make a purchase? They purchased something. So those are the 3 columns we're going to be looking at when we do this. And we've gone ahead and imported these and imported the data, so now our data set is all set with this information in it. And we'll need to go ahead and split the data up. So we need from the Scikit-learn model selection, we can import train test split. This does a nice job. We can set the random state so it randomly picks the data. And we're just going to take 25% of it's going to go into the test, our X test and our Y test, and the 75% will go to X train and Y train. That way, once we create our model, we can then have data to see just how accurate or how well it has performed with our prediction. The next step in pre-processing our data is to go ahead and do feature scaling. Now, a lot of this will start to look familiar. If you've done a number of the other modules and setup, you should start noticing that we bring in our data, we take a look at what we're working with, we go ahead and split it up into training and testing. In this case, we're going to go ahead and scale it. Scale it means we're putting it between a value of -1 and 1, or someplace in the middle ground there. This way, if you have any huge you don't have this huge setup. If we go back up to here where salary is 20,000 versus age 35. Well, there's a good chance with a lot of the back-end math that 20,000 will skew the results and the estimated salary will have a higher impact than the age, instead of balancing them out and letting the calculations weigh them properly. And finally, we get to actually create our naive Bayes model. And then we're going to go ahead and import the Gaussian naive Bayes. And the Gaussian is the most basic one. That's what we're looking at now. It turns out, though, if you go to the Scikit-learn kit, they have a number of different ones you can pull in there. There's Bernoulli, I've never used that one. Categorical, complement, and here's our Gaussian. So there's a number of different options you can look at. Gaussian, when you come to the naive Bayes, is the most commonly used. So we're talking about the naive Bayes. That's usually what people are talking about when they're pulling this in. And one of the nice things about the Gaussian, if you go to their website, to Scikit-learn, the naive Bayes Gaussian, there's a lot of cool features. One of them is you can do partial fit on here. That means if you have a huge amount of data, you don't have to process it all at once. You can batch it into the Gaussian NB model. And there's many other different things you can do with it as far as fitting the data and how you manipulate it. We're just doing the basics. So we're going to go ahead and create our classifier. We're going to equal the Gaussian NB And then we're going to do a fit. We're going to fit our training data and our training solution. So X train, Y train. And we'll go ahead and run this. It's going to tell us that it ran the code right there. And now we have our trained classifier model. So the next step is we need to go ahead and run a prediction. We're going to do our Y predict equals the classifier.predict X test. So here we fit the data, and now we're going to go ahead and predict. And now we get to our confusion matrix. So from the Scikit-learn metrics, you can import your confusion matrix. Just as saves you from doing all the simple math, it does it all for you. And then we'll go ahead and create our confusion metrics with the Y test and the Y predict. So we have our actual and we have our predicted value. And you can see from here, this is the chart we looked at. Here's predicted, so true positive, false negative, true negative. And if we go ahead and run this, there we have it, 65, 3, 7, 25. And in this particular prediction, we had 65 were predicted the truth as far as a purchase. They're going to make a purchase, and we guessed 3 wrong. And then we had 25 we predicted would not purchase, and 7 of them did. So there's our confusion matrix. At this point, if you were with your shareholders or a board meeting, you would start to hear some snoozing if they were looking at the numbers. And you say, hey, here's my confusion matrix. So let's go ahead and visualize the results. We're going to pull from the matplot library colors, import listed color map. And this is actually, my machine's going to throw an error because this is being, because of the way the setup is. I have a newer version on here than when they put together the demo. And we need our X set and our Y set, which is our X train and Y train. And then we'll create our X1, X2, and we'll put that into a grid. And we set our X set minimum stop and our X set max stop. And if you come all the way over here, we're going to step 0.01. This is going to give us a nice line, is what that's doing. And then we're going to plot the contour, plot the X limit, plot the Y limit, and put the scatter plot in there. Now let's go ahead and run this. To be honest, when I'm doing these graphs, there's so many different ways to do that. There's so many different ways to put this code together. To show you what we're doing, it's a lot easier to pull up the graph and then go back up and explain it. So the first thing we want to note here when we're looking at the data is this is the training set. And so we have those who didn't make a purchase. We've drawn a nice area for that. That's defined by the naive Bayes setup. And then we have those who did make a purchase, the green. And you can see that some of the green dots fall into the red area and some of the red dots fall into the green. So even our training set isn't going to be 100%. We couldn't do that. And so when we're looking at our different data coming down, we can kind of arrange our X1, X2 so we have a nice plot going on, and then we're going to create the contour. That's that nice line that's drawn down the middle on here with the red-green. That's what this is doing right here with the reshape. And notice that we had to do the dot T. If you remember from NumPy, if you did the NumPy module, you end up with pairs, X1, X2, X1, X2, next row, and so forth. You have to flip it so it's all one row. You have all your X1s and all your X2s. So this is what we're kind of looking for right here on this setup. And then the scatter plot is, of course, your scattered data across there. We're just going through all the points. That puts these nice little dots onto our setup on here. And we have our estimated salary and our age. And then, of course, the dots are, did they make a purchase or not? And just a quick note, this is kind of funny. You can see up here where it says X set, Y set equals X train, Y train, which seems kind of a little weird to do. This is because this was probably originally a definition. So it's its own module that could be called over and over again. And which is really a good way to do it, because the next thing we're going to want to do is do the exact same thing, where we're going to visualize the test set results. That way we can see what happened with our test group, our 25%. And you can see down here we have the test set, and if you look at the two graphs next to each other, this one obviously has 75% of the data, so it's going to show a lot more. This is only 25% of the data. You can see that there's a number that are kind of on the edge as to whether they could guess by age and income they're going to make a purchase or not. But that said, it still is pretty clear. It's pretty good as far as how much the estimate is and how good it does. Now, graphs are really effective for showing people what's going on, but you also need to have the numbers. And so we're going to do from Scikit-learn, we're going to import metrics, and then we're going to print our metrics classification report from the y-test and the y-predict. And you can see here we have precision. Precision of zeros is 90. There's our recall, 0.96. We have an F1 score and a support. And we have our precision, the recall on getting it right. And then we can do our accuracy, the macro average, and the weighted average. So you can see that it pulls in pretty good as far as how accurate it is. You could say it's going to be about 90% is going to guess correctly that they're not going to purchase. And we had an 89% chance that they are going to purchase. And then the other numbers as you get down have a little bit different meaning, but it's pretty straightforward on here. Here's our accuracy, and here's our micro average and the weighted average and everything else you might need. And if you forgot the exact definition of accuracy, it is the true positive, true negative over all of the different setups. Precision is your true positive over all positives, true and false. And recall is a true positive over true positive plus false negative. And we can just real quick flip back there so you can see those numbers on here. Here's our precision, here's our recall, and here's our accuracy on this.
Welcome to this exciting journey into the world of statistics for data science. Have you ever wondered how data transforms from raw numbers into powerful insights that drive decisions? Well, statistics is the magic behind it all. Today, we will uncover how statistical methods help us summarize data, model uncertainty, test hypotheses, and find relationships that can predict the future. So, buckle up. We are about to turn numbers into knowledge. Without any further ado, let's get started. Now, to start off, here's a key question. What are statistics in data science? Now, statistics is the science of collecting, analyzing, and interpreting data. By applying statistical methods, we can uncover patterns in the data and make informed decisions. Now, as we continue, you notice how these essential concepts will form the backbone of many data science practices. Let's explore the key functions of statistics in data science. First, statistics help summarize data using measures like mean, median, and variance. Next, it models uncertainty with probability and distributions, so we can better understand risk and variability in our data. It also tests hypotheses, such as when we use A/B testing to compare different outcomes. Statistics finds relationship through methods like regression and correlation, revealing how variables impact each other. And finally, all these tools enable data-driven decision-making, turning raw numbers into actionable insights. Now let's talk about why does statistics matter in data science. Statistics form the backbone of data science, providing the mathematical framework needed to make sense of data and draw reliable conclusions. Without statistics, it would be impossible to turn raw data into meaningful insights or make confident, evidence-based decisions. Now, let's have a look at the main branches of statistics: descriptive statistics and inferential statistics. So first, let's talk about the definition. Then we have got methods and measures. Now in the case of descriptive statistics, now let's have a look at the main branches of statistics. So basically there are two core branches: descriptive statistics and inferential statistics. Descriptive statistics summarizes and describes data using measures like mean, median, mode, range, and standard deviation. Its purpose is to organize and present data, typically with charts, graphs, or summary tables. The scope of descriptive statistics is limited to the sample data itself. Now, on the other hand, inferential statistics makes inferences about populations based on samples. It uses methods like hypothesis testing, confidence intervals, and regression. The purpose here is to draw conclusions and make predictions with common examples including A/B testing and survey analysis. The scope of inferential statistics extends beyond the sample to the larger population. Understanding both these branches is essential for analyzing and interpreting data in any data science project. Now, let's take a closer look at the descriptive statistics, starting with measures of central tendency. The first measure here is mean, which is the average of all the values simply calculated as the sum of all the data points divided by the total count. Next is the median, which represents the middle value when the data is sorted from lowest to highest. This is especially useful when dealing with skewed distributions. And finally, the mode is the most frequently occurring value in the data set, helping us identify common patterns or repeated outcomes. Let's continue our deep dive into descriptive statistics by looking at the measures of variability. First, we've got the range. This is simply the difference between the maximum and minimum value in a data set, showing us the spread of our data, which measures the average of the squared differences from the mean. This tells us how much the values in our data set differ from the average. Closely related is the standard deviation, which is the square root of the variance. It gives us a more intuitive sense of how much the values typically deviate from the mean. And finally, we've got the interquartile range, or we say IQR. This shows us the range of the middle 50% of our data, helping us understand how data is distributed across the center and avoid the effect of outliers. Understanding these four measures allows us to summarize not just the center of our data, but how spread out and varied our data set is. Now, let's look at some practical applications of descriptive statistics. One major use is the data exploration and summarization, where we quickly get an overview and basic understanding of complex data sets, helping track performance and detect problems early in fields like manufacturing or operations. And finally, they are central to business reporting and dashboards, where concise summaries are essential for managers to review trends and make data-driven decisions. So in short, descriptive statistics help transform raw data into clear, actionable information across many business, scientific, and operational contexts. Let's explore the first type of data in statistics, qualitative or categorical data. This type of data includes descriptive information that cannot be measured numerically, such as categories or labels, and yes or no responses. These are all about qualities or characteristics rather than quantities. Qualitative data can be further divided into two types: nominal, where the categories have no specific order, and ordinal, where the categories do have an order or ranking. Recognizing and classifying qualitative data is very important, as it affects how information is analyzed and interpreted in statistics. Now let's discuss the second main type of data in statistics, which is quantitative or numerical data. This type of data includes information that can be measured and expressed with numbers, making it ideal for mathematical analysis. Quantitative data is further divided into two main categories. First, there is discrete data. These are countable values with specific fixed points, such as the number of students, cars sold, or website clicks. Second, there is continuous data, which includes infinite possible values within a given range. Examples of continuous data include height, weight, temperature, or time. Understanding the distinction between discrete and continuous data is very important, as it determines which statistical methods and visualizations will be most appropriate. Now let's dive into the fundamentals of probability. Probability measures the likelihood of an event occurring, and it's always expressed as a value between 0 and 1. Here are some key concepts. If the probability or P equals to 0, that means the event will never occur. If P is equals to 1, the event will always occur. And if p is equals to 0.5, the event has an equal chance of occurring or not occurring. It's truly a 50-50% scenario. Now, understanding these basic principles help us quantify uncertainty and make informed predictions about future outcomes. Now, let's look at the different types of probability. First, there's classical probability. This is based on equally likely outcomes such as flipping a fair coin or rolling a balanced die. Next, empirical probability, which relies on observed frequency. It's calculated from actual data, such as the proportion of rainy days over the past month. Let's say, for example, the probability of it's raining today given that it's cloudy. Understanding these three types help us choose the right approach for different situations, whether we are predicting outcomes, analyzing data, or making decisions under uncertainty. Now, probability has a wide range of powerful applications in data science. First of all, it is used in predictive modeling and machine learning, where algorithms estimate future outcomes based on existing data. Probability also plays a key role in risk management and decision making, helping businesses and researchers evaluate the likelihood of different scenarios and plan accordingly. Conditional probability, calculating the chance of one event given that the another has occurred. This is crucial in fields like healthcare, fraud detection, and marketing analytics. And finally, probability is foundational in A/B testing and experimental design, allowing us to measure the effectiveness of new strategies or products. These applications show how probability enables smarter, evidence-driven progress in modern data science. Let's look at one of the most common probability distributions, the normal distribution. This distribution is famous for its bell-shaped symmetric curve, which shows that most values cluster around the mean, with fewer and fewer values appearing as you move away from the center. Now, many natural phenomena like heights, test scores, and measurement errors tend to follow this pattern, making the normal distribution a key concept in statistics. It's characterized by two main parameters, the mean, which determines the center of the curve, and the standard deviation, which controls its spread. Recognizing the distribution helps analysts make predictions, calculate probabilities, and apply statistical techniques to real-world data. Next, let's explore the binomial distribution, which is another common probability distribution. The binomial distribution is discrete and is used for situations with binary outcomes like success or failure. It is based on a fixed number of trials where each trial has a constant probability of success, such as flipping a coin a certain number of times or tracking pass-fail rates. Examples of binomial experiment includes coin flips and measuring how many students pass or fail a test. This distribution helps us model and analyze outcomes when only two possibilities exist in each trial. Now, let's focus on the Poisson distribution, another key type of probability distribution. The Poisson distribution is a discrete distribution specifically used to model rare events. It's particularly helpful for modeling events that occur independently over a fixed interval of time or space. For example, it predicts how many times an event, like a customer arriving on a website receiving a visit, might happen in a certain period. Typical examples include customer arrivals at a store, defect rates in manufacturing, or counts of website visits over a set period. This distribution is a great tool for understanding and predicting random independent events that don't happen very often but are important to track. It's a branch that allows us to make inferences, predictions, or generalizations about a larger population using sample data. Here are some key concepts. First is the population versus sample. The population represents the entire group we want to know about, while the sample is the subset we actually collect data from. Next concept is sampling distribution, which refers to the distribution of a statistic across multiple samples from the same population. Standard error measures how much the sample statistic is expected to vary due to random sampling. And finally, margin of error tells us how much we can expect our estimates to differ from the true population value. Together, these concepts form the foundation for drawing reliable insights from sample data in inferential statistics. Let's review some of the main techniques used in inferential statistics. First, we've got hypothesis testing. This method allows us to test claims or ideas about population parameters based on sample data, helping us determine if observed results are statistically significant and reliability of our estimate. Next are confidence intervals. These provide a range of likely values for a population parameter, giving us a sense of possible variation, reliability of our estimate. And lastly, regression analysis is used to model and analyze the relationships between variables, allowing us to make predictions, uncover trends, and understand how changes in one factor might affect another. Now, let's walk through the hypothesis testing process. The first step is to formulate hypothesis. Start with null hypothesis, represented as H0, which states that there is no effect or difference. Then, there's the alternative hypothesis, represented as H1, which suggests that an effect or difference does exist. Now, after setting up the hypothesis, the next step is to choose a significance level noted by alpha. Common choices for significance levels include 0.05, 5%, 0.01, 1%, 0.010, which is 10%. The significance level is important because it controls the likelihood of making a type 1 error, also known as false positive, and now each step in the process is critical for ensuring that statistical results are both meaningful and reliable. The next step is to collect and analyze sample data. Ensure the data is represented by choosing a good sample. Then calculate the appropriate and test statistic for your hypothesis test. Once that's done, it's time to make a decision. Compare the p-value to the chosen significance level alpha. Now, if the p-value is less than or equals to alpha, you reject the null hypothesis. If the p-value is greater than alpha, you fail to reject the null hypothesis. And finally, interpret your results. Draw your conclusions with respect to the context and problem at hand, always keeping the bigger picture in mind. Following these steps helps ensure your hypothesis test is robust, clear, and meaningful. Let's review the common types of hypothesis test used in statistics. The one sample test compares the mean of a sample to a known value, and the one sample Z test is used when the population standard deviation is known. Next, we have two sample test. The independent samples t-test compares to the means of two different groups, while paired samples t-test compares before and after measurements for the same subject. For categorical data test, the chi-square test checks for the independence or goodness of fit. And Fisher's exact test is useful for small sample sizes. And lastly, non-parametric tests such as the Mann-Whitney U-test and Wilcoxon-signed rank test serve as alternatives to the t-test when data doesn't meet certain parametric assumptions. Choosing the right hypothesis test depends on your data type and the specific question you want to answer. Let's explore the central limit theorem, or CLT, a foundation for inferential statistics. The central limit theorem states that as the sample size increases, the distribution of sample means approaches a normal distribution, even if the original data isn't normally distributed. This sample works for any population distribution, making it incredibly powerful. Now, for good results, the sample size should typically be 30 or more. What's interesting is the sample mean distribution, which will have the same mean as the population. The standard error, which measures variability by the sample mean, equals sigma divided by the square root of n, and this gets smaller as the sample size grows. And finally, the formula shown here, which is z is equals to x minus nu divided by sigma over the square root of n. Let's standardize and compare sample means.
The CLT makes most parametric statistics possible and is the backbone for many statistical tests. Let's review the main types of regression analysis which are used to model and understand relationships between variables. First up is linear regression. This technique analyzes the relationship between a continuous variable and another variable, resulting in a straight line. It's commonly used in predicting sales or prices. Next is logistic regression. Unlike linear regression, this method is used for binary outcomes, helping estimate probabilities such as whether an email is spam or a patient has a disease. Moving to multiple regression, this allows us to account for the effect of several variables at once, modeling more complex relationships like determining house prices. Lastly, polynomial regression, which is used for non-linear relationships. The resulting curve, rather than a straight line, lets us capture growth trends and other patterns that aren't linear. Understanding these types of regression help analysts choose the right model for the data and business's problem at hand. Let's clarify the important differences between correlation and causation. Correlation is statistical measure of how two variables move together. Correlation values range from -10 to +1. But remember, correlation does not imply causation. On the other hand, causation means that one variable actually causes changes in another. Establishing causation requires controlled experimentation and is much stronger relationship than simple correlation. Always be careful when interpreting results. Just because two variables move together doesn't mean one caused the other. Let's look at some common problems with interpreting correlation and causation. First is the third variable problem, which happens when a hidden variable affects both variables in a question, leading to a misleading connection. There's also this directionality problem where it's unclear which variable is causing others to change. But both are actually caused by a third variable, which is the hot weather. This demonstrates that correlation does not mean one variable causes the other, so always look for hidden factors before assuming causation. Let's talk about statistical errors, specifically type 1 and type 2 errors. Type 1 error, also called as false positive, occurs when we reject the true null hypothesis. In other words, we wrongly conclude there's an effect when there's actually isn't. The probability of making this error is equal to the significance level alpha. For example, concluding a drug works when it actually doesn't. On the other hand, type 2 error is false negative, means failing to reject a false null hypothesis. That's when we miss a real effect or difference. The probability of type 2 error is beta. For example, missing the real effect of a drug and saying it doesn't work when it actually does. Understanding these errors is key for designing good experiments and interpreting statistical results properly. Let's look at 3 common sampling methods used in statistics. The first one is random sampling. Here, every individual in the population has an equal chance of being selected. Where every nth individual is chosen, random sampling is crucial for ensuring representative sample. Next is stratified sampling. The population is divided onto homogeneous subgroups or strata, and then a random sample is drawn from each group. This approach makes sure all the groups are represented in the sample. And finally, cluster sampling divides the population into clusters, often based on geography. Entire clusters are then randomly selected. It's cost effective and useful for large, spread out populations. Choosing the right method ensures the data truly represents the whole population and strengthens the study's conclusions. So guys, let's wrap up with some real-world applications of statistics. In business analytics, statistics are used for A/B testing to optimize websites, customer segmentation, and targeting, sales forecasting and demand planning, and quality control, and also process improvement. These techniques help businesses make smarter, data-driven decisions every day. Statistics play a vital role in healthcare and medicine as well. They are key for analyzing clinical trial results, conducting epidemiological studies, evaluating treatment, effectiveness, and identifying risk factors. By using these approaches, healthcare researchers and practitioners can improve patient outcomes in public health. From businesses to medicine, statistics transform raw information into actionable insights that create real impact. Statistics has a huge impact in technology, data science, and finance, and power recommender systems that personalize what users see. In finance, statistics help with risk assessment and management, optimizing investment portfolios, determining credit scores, and supporting market research and analysis. Now, these applications show how statistical techniques help make smarter decisions and solve complex challenges across high-impact industries.
Are you one of the many who dreams of becoming a data scientist? Keep watching this video if you're passionate about data science, because we will tell you how does it really work under the hood. Emma is a data scientist. Let's see how a day in her life goes while she's working on a data science project. Well, it is very important to understand the business problem first. In our meeting with the clients, Emma asks relevant questions, understands and defines objectives for the problem that needs to be tackled. She's a curious soul who asks a lot of whys, one of the many traits of a good data scientist. Now, she gears up for data acquisition to gather and scrape data from multiple sources like web servers, logs, databases, APIs, and online repositories. Oh, it seems like finding the right data takes both time and effort. After the data is gathered comes data preparation. This step involves data cleaning and data transformation. Data cleaning is the most time-consuming process as it involves handling many complex scenarios. Here, Emma deals with inconsistent data types, misspelled attributes, missing values, duplicate values, and whatnot. Then, in data transformation, she modifies the data based on defined mapping rules. In her project, ETL tools like Talent and Informatica are used to perform complex transformations that helps the team to understand the data structure better. Then understanding what you actually can do with your data is very crucial. For that, Emma does exploratory data analysis. With the help of EDA, she defines and refines the selection of feature variables that will be used in the model development. But what if Emma skips this step? She might end up choosing the wrong variables, which will produce an inaccurate model. Thus, exploratory data analysis becomes the most important step. Now, she proceeds to the core activity of a data science project, which is data modeling. She repetitively applies diverse machine learning techniques like KNN, decision tree, naive Bayes to the data to identify the model that best fits the business requirement. She trains the models on the training dataset and tests them to select the best performing model. Emma prefers Python for modeling the data. However, it can also be done using R and SAS. Well, the trickiest part is not yet over: visualization and communication. Emma meets the clients again to communicate the business findings in a simple and effective manner to convince the stakeholders. She uses tools like Tableau, Power BI, and ClickView that can help her in creating powerful reports and dashboards. And then finally, she deploys and maintains the model. She tests the selected model in a pre-production environment before deploying it in the production environment, which is the best practice, right? After successfully deploying it, she uses reports and dashboards to get real-time analytics. Further, she also monitors and maintains the project's performance. Well, that's how Emma completes the data science project. We have seen the daily routine of a data scientist is a whole lot of fun, has a lot of interesting aspects, and comes with its own share of challenges. Now, let's see how data science is changing the world. Data science techniques along with genomic data provides a deeper understanding of genetic issues in reaction to particular drugs and diseases. Logistic companies like DHL, FedEx have discovered the best routes to ship, the best suited time to deliver, the best mode of transport to choose, thus leading to cost efficiency. With data science, it is possible to not only predict employee attrition, but to also understand the key variables that influence employee turnover. Also, the airline companies can now easily predict flight delay and notify the passengers beforehand to enhance their travel experience. Well, if you're wondering, there are various roles offered to a data scientist, like data analyst, machine learning engineer, deep learning engineer, data engineer, and of course, data scientist. The median base salaries of a data scientist can range from $95,000 to $165,000. So that was about the data science. Are you ready to be a data scientist? If yes, then start today. The world of data.
Picture this, you're shopping online and suddenly you see a product that feels like it was made just for you. How did they know? It's not by chance, it's data science. Data science helps businesses understand what you like, predict what you need next, and improve the way we shop and use technology. And here's the best part. Data science isn't just about watching Netflix. It's one of the fastest growing careers in the world right now. In fact, the US Bureau of Labor Statistics says that data science jobs are expected to grow 36% by 2033, way faster than most of the other jobs. Companies everywhere are using data to make smarter decisions. That means the demand for data scientists is huge. And let's talk about the salary. You're probably wondering, how much can I earn actually? Well, for entry-level position, data scientists in the US are earning around $152,000 per year right now. And by 2025, some can make as much as $230,000. And in India, starting salaries range from 50,000 rupees to 1 lakh per month, and the experienced professionals can earn more than 5 lakh rupees per month. That's impressive, right? But the best part is, as a data scientist, you won't just stop here. The skills you develop in this role, like machine learning, data visualization, and statistics, are highly transferable and crucial for moving into AI roles. So whether it's becoming an AI engineer or an AI specialist, the foundation you build in data science will help you level up and pursue exciting, high-paying opportunities in the AI field. Now, if you're thinking, this sounds great, but where do I even start? Well, that's exactly what the Professional Certificate course in Data Science from IIT Kanpur and Simplilearn is designed to do. It will get you started and make sure you're ready for this booming industry. In this 11-month live online interactive program, you will learn the skills you need to become a data science professional. No more theory, no more fluff. You get hands-on projects, live classes, and mentorship from IIT Kanpur faculty, plus real-world industry expert who will help you build your skills. So this course comes with exciting, amazing features that makes learning even more impactful. 8 times higher interaction in live online classes with industry expert. Regular live online classes conducted by experienced professionals who bring real-world knowledge into every session. You'll also get to master 13 plus key skills including generative AI, prompt engineering, ChatGPT, explainable AI, conversational AI, NLP, and many more. These are the skills that top companies use every day, and you'll gain hands-on experience with 14 plus industry tools like Python, SQL, Tableau, DALL-E 2, Midjourney, TensorFlow, and more. And by the end of this course, you will be ready to tackle real-world challenges using these powerful tools and techniques. But we are not just talking about textbook and theory. You'll work on 25 plus real-world projects, giving you hands-on experience with the tools and skills you'll use in the industry. For example, our first project would be about sales analysis. You'll use Python to analyze a clothing company fourth quarter sales data across Australian states, helping the company make informed decisions. The next project would be about employee performance analysis, where you learn how to build machine learning models to understand the factors influencing employees' turnover. Our third project would be about e-commerce, which will help Amazon improve its recommendation engine to offer better recommendation to customers. Upon successful completion, you'll receive a program certificate directly issued by the ENICT Academy IIT Kanpur within 45 days of completing your cohort. This prestigious certificate will help you boost your resume and show potential employers that you have mastered the skills needed to succeed. You'll also benefit from masterclasses delivered by distinguished IIT Kanpur faculty who bring their deep expertise in this course. Plus, you will be exposed to trending tools like ChatGPT, GenAI, and prompt engineering. Now, if you're wondering who will be teaching all of this, then the IIT Kanpur faculty is here for you. These experts have been in this field for years and have worked with the top companies. You'll also get masterclasses from them, and they will guide you through the learning process. You're not just learning from a textbook, you are learning from the people who have been there and done that. And the best part is, once you have learned the skills, Simplilearn's career assistance team will help you take to the next step, which will help you to build a killer resume, show you how to stand out top recruiters, and even give you access to mock interviews. Plus, you will also gain access to exclusive networking events and hackathons to connect with industry professionals. Along with Simplilearn's job assistant, you'll also get access to IT Kanpur's career services, helping you connect with top recruiters and land interviews with leading tech companies. So upon finishing this course, you'll be ready for top data science roles like data scientist, machine learning engineer, AI specialist, and business analyst. The good news is top companies like Amazon, EY, Fidelity Investment, Johnson & Johnson, Vodafone, Accenture, Infosys, and Nvidia is looking for professionals just like you. And with salaries in the US hitting around $230,000 plus and in India reaching up to 5 lakh per month, your career outlook looks great. So what will you be actually learning in this course? So here's a sneak peek of the syllabus which you'll be learning in this course, which is the foundation in Python, SQL and mathematics, core data science like machine learning, data visualization, NLP, special topics like GenAI, ChatGPT, prompt engineering, and you'll also work on industry projects which we have already mentioned before. You'll also have the option to choose electives like data storytelling with Power BI and business analytics with Excel to tailor your learning experience and focus on the areas that interest you the most. So don't wait, hurry up and enroll now and find the course link in the description box below and in the pinned comments.
Have you ever wondered how your favorite online store seems to know exactly what you are looking for? Every time you browse, add to cart or wishlist an item, you are leaving clues about your style, favorite colors, brands, and even shopping times. Data scientists jump in, analyze these patterns, and create a super personalized shopping experience. Suddenly, the store is showing you just the right pieces at just the right time, almost like it's reading your mind. That's data science, turning your clicks into a shopping spree crafted just for you. Hello everyone, welcome back to Simplilearn's YouTube channel. If you're already a data science enthusiast or just got curious about this exciting field, you're in the right place. Today in this video, I am diving into 10 essential steps to help you become the next in-demand data scientist and land that dream job. No more waiting, let's dive right in and get you on the path to your future in data science. So let's see the 10 essential steps to become the next data scientist in demand. Step number 1 is programming languages. Starting with Python as a beginner is a great move because it's simple, versatile, and widely used in data science. Python's straightforward syntax makes it beginner-friendly, helping you grasp programming basics quickly and dive into data science libraries like Pandas, NumPy, and Matplotlib with ease. Adding R to your skill set is valuable because it excels at statistical analysis and data visualization, two essential parts of data science. You can be comfortable with Python and R within a month or two. So, moving on to the next step, that is version control system. Learning a version control system like Git is essential because it allows you to track, manage, and collaborate and code effectively. With Git, you can save different versions of your work, making it easy to backtrack if something goes wrong or to experiment without losing progress. This is especially useful when working with complex data science projects where you might try out different models of analysis techniques. 1 or 2 weeks of practice along with Python and R is good to get started. Now moving on to the third step, that is data structures and algorithms. Learning data structures and algorithms is crucial for becoming a data scientist because they provide the foundation for efficient data handling and problem solving. Data structures like arrays, stacks, queues, and trees help you store and organize data in ways that make it easier and faster to access, process, and analyze. Algorithms, on the other hand, give you strategies to perform tasks like searching, sorting, and optimizing data operations, which are essential for handling large data sets. While many candidates struggle with DAC, mastering it gives you an edge, helping you stand out in the interviews and shine as a skilled data scientist capable of tackling the toughest data problems. Spend about 2 months in this, you will get in the shape for sure. Now moving on to the step number 4, that is SQL. Learning SQL is essential for data scientists because it enables you to access, manage, and manipulate data directly within databases where most real-world data resides. With SQL, you can create new tables, alter existing ones, delete unnecessary records, and run queries to filter, sort, and aggregate data. These abilities allow you to retrieve, clean, and organize data effectively, core skills needed for any data science role. It's easy and you don't have to spend more than a month to have a deep understanding of it. Now, moving on to the fifth step, that is mathematics and statistics. Mathematics and statistics are essential for data science because they form the backbone of data analysis, model building, and interpretation. Topics like linear algebra, calculus, probability, and statistics gives data scientists the tools to understand data patterns, perform accurate analysis, and make data-driven decisions. Mastering these areas enables you to build robust models, validate results, and tackle complex problems confidently, making you a well-rounded and skilled data scientist. Make sure you spend 2 months to grasp these topics. Now moving on to the step number 6, that is data pre-processing and visualization. Learning data pre-processing and visualization is essential for a data scientist because these skills make you data accurate, insightful, and easy to understand. Python libraries like NumPy and Pandas are crucial for manipulating and creating data, enabling you to handle missing values, filter out noise, and prepare data for analysis. Once the data is ready, visualization lets you uncover patterns and communicate results effectively. Libraries like Matplotlib and Seaborn help create clear, impactful visuals, allowing you to interpret trends and convey insights in a way that's easily understood by others. Together with these tools, make data pre-processing and visualization fundamentals for effective data science. If you have a solid foundation on Python and mathematics, you will get a good understanding of data pre-processing and visualization in a month or two. Now moving on to the seventh step, that is machine learning fundamentals. Machine learning fundamentals involve understanding how algorithms enable computers to learn from data and make predictions on decisions without explicit programming. The two main categories are supervised learning and unsupervised learning. In supervised learning, models are trained on labeled data to make predictions, while in unsupervised learning, models find patterns in unlabeled data. Popular tools like TensorFlow, PyTorch help build and train complex models, especially for deep learning, while Scikit-learn is essential used for simpler machine learning algorithms and data pre-processing. These tools make it easier to implement machine learning fundamentals effectively and build intelligent data-driven decisions. Dedicate about 3 months to understand the core of machine learning. Now coming to the next step, that is deep learning. Deep learning is a subset of machine learning that focuses on algorithms inspired by the structures of the human brain called neural networks. Deep learning uses neural networks with multiple layers, often dozens or hundreds, to learn complex patterns from large data sets. Specialized types like convolutional neural networks, that is CNNs, are great for image processing, while recurrent neural networks RNNs are used for sequence data like text or time series. Essential tools like TensorFlow, PyTorch make building, training, and deploying deep learning models more accessible, allowing you to create powerful AI solutions across various domains. I think it will take about 2 months to have a good hold on deep learning concepts and how to implement them. Now moving on to the ninth step, that is specializations. Once you have grasped the deep learning, it's like reaching a new level as a data scientist. Just as doctors specialize in areas in nephrology and cardiology, data scientists often choose to specialize in fields like natural language processing or computer vision. Natural language processing focuses on teaching machines to understand and generate human language, enabling applications like chatbots, sentiment analysis, and language translation. It's about making computers read, write, and even interpret human emotions through text or speech. Computer vision, on the other hand, is all about enabling machines to see and interpret images or videos. This field powers innovations like facial recognition, object detection, and autonomous driving. Now, you don't need to learn both. You can choose what interests you the most. Now, spend 1 to 2 months diving deep into one of these areas. Now moving on to the last but not the least step, that is big data. Big data refers to extremely large volumes of data generated rapidly from sources like social media and sensors. For data scientists, learning to handle big data is crucial, as it requires specialized tools like Hadoop and Spark to analyze and extract insights effectively. With companies relying on data-driven decisions, big data skills make you a highly in-demand professional in the field. Focus for about 2 months and you will be able to spot trends and patterns from datasets very easily. Once you are ready, it's time to build a killer resume packed with projects that showcase your new skills. Start applying to jobs on platforms like Naukri and Indeed and supercharge your LinkedIn. Connect with data scientists, see what skills they are mastering, and learn from their journeys as well. Keep sharpening your own skills, and when the time comes, you will be ready to crush those interviews and land your dream data scientist role in 2025.
Yeah, step by step, we will go through all of this, and we'll make sure that we learn everything and we bring everything together towards the end, right? Without further ado, let me just straight away deep dive to business, right? To learn data science, right? And with this data science, there is also something which is prefixed, which is applied data science. And suffix for this is with Python, right? Applied data science with Python, right? So there are two key concepts which are going to be a part of this course. The first one is the knowledge about data science, that what data science is. And then because we are doing an applied course, right? We are doing an applied course. I will try to tie up these concepts which we will understand in data science with a tool, right? Which is Python for you, right? We already know about 65% of Python, right? Which is the fundamental Python. And now we will be moving to the next step, to advanced Python, right? And using Python, right? Leveraging Python, we will be solving a lot of problems of data science, right? Using this. Okay. So the first few sessions, right? The first few sessions will be about making you abreast with Python, what Python is, right? What packages do we have? How do they work in reality, right? And all those things. And then we will be coupling it up with data science concepts. And then finally, towards the end of the session, in the last few classes, we will be doing, we will be taking a real data set. And on that data set, we will be applying all these concepts, right? To understand the data better, and we will be drawing inferences from that to convert that into information to take actionable insights. Using that actionable insights, taking a better decision, right? We'll do all of that in the actual way. Okay. So now, guys, if you understand this, then the next point of contention is data science, right? One of the most famous keywords on the planet right now, right? One of the most famous keywords in the planet right now. Do you think that these two things, okay, let me put it different way. What do you think that can be the possible explanation about this term data science? You know data, you know science. What do you think is going to follow in these sessions? What is data science to you as per these two words? Okay, so this is people made up of two words, right? Data and science, right? So what we are trying to do is we are trying to understand data, right? We are trying to understand data, right? And then do something to it, right? Understanding its science, understanding the nature, the behavior of this data, and converting it in something called as information, right? Do we know difference between data and information? Data is something which is completely raw, okay? It is completely raw. It has no meaning, right? It has no meaning, isn't it? For example, I give you the stats of some player, like suppose say Dhoni. I give you stats of Mahendra Singh Dhoni, right? That what were his scores, what is his name, what is his age, and you know, all those things. Now, everything is there, right? But we don't know what to do about it, right? Do you think the score of Dhoni has any context, people? It has any context? No, right? But when I deep down, when I go and deep dive about it, right? What is the first thing you find out of scores? What is the first thing you find out of scores? You try to find the average of score, isn't it? that in last 10 innings, right, in last 10 innings, before this also, you need something which is called as a problem statement, isn't it? Now, for example, the problem statement is selectors wants to understand that whether Mahendra Singh Dhoni should be picked up. So there's a problem now, right? Selectors want to see that whether Dhoni is fit for the next tournament or not. So what we will do, we will now try to take the mean of the scores, right, for last 10 innings. And if the score is suppose X, we will try to compare this with Y. What is Y? Y is a reference, right? Y is a reference that we want to compare it against. Now, when you are doing this comparisons, when you are applying these techniques to the score, this is now slowly becoming information, right? And at the end of the day, once you have the strike rate, once you have the mean score of Dhoni, once you have his age, once you have his fitness score, all those things will now help you to take this particular decision, because now what you have is called as information, right? Because this has context, right? This has meaning, and this is usually processed, right? This is usually processed, right? This is usually processed. Now, what did we do? Now, what did we do here? If you will go and read about data science says, it is the art of collecting, right? Cleaning, analyzing, modeling, improving, right? And visualizing, right? Visualizing the data, right? If a person is adept in doing all these things, this person, people, is cumulatively called a data scientist, right? That person is called a data scientist, right? So before going to the definition of data scientist now, I will give you some more examples, right? I'll give you some more examples. Data science people, as I said, is a combination of these things, right? You have to collect the data, right? You have to collect the data, right? And this has a lot of things. Data can be collected from two types. One is primary, and the second one is secondary, right? What is the primary way of collecting data? From your IoT devices, right? From sensors, from your inbuilt machines, right? Then from your surveys, which you float, right? Questionnaires, right? All these things are primary ways. What is the secondary way of collecting data? Purchasing data, right? Using internet data, because you have not generated it. You are just using someone else's data, right? Something like transfer learning. What is transfer learning? Transfer learning is a technique where suppose I am bank A and you are bank B, right? So bank A has created some model, right? Trained on their data. Now you are going to use the exact same model, right? You're going to use the exact same model, right? Maybe you're not seeing the data, but you are just using the property of data, like mean, median, mode, and a lot of modeling things, which will come, we will learn about them. And you use this model on your particular data, right? So in a way, you did not have enough data to create the model yourself, but you are now using someone else's model to run your data on it, right? So this is called as transfer learning. So this kind of collection is basically secondary data collection. So you can collect the data, right? Then you can perform data analysis, right? You can perform data analysis, right? How will you perform this data analysis? Using complex algorithms, right? Using complex algorithms, right? Some statistics, right? You can use artificial intelligence, right? Artificial intelligence. You can use machine learning, right? Right? You can use all these things for data analysis. Then you can transform the patterns into predictions, right? You can transfer these patterns into predictions, right? Which can be used for business decision making, right? For business decision making. Then you can validate the results, right? And present the results, right? So this is like a complete life cycle of a data scientist, right? So before going further, let me give you what combinations do you need to have to become a data scientist. The first one is domain knowledge, right? So what is domain knowledge? First of all, I told you, right, there will be a problem, right? You'll be solving a problem. In any project of data science, you'll be trying to solve a problem, right? And the problem will be belonging to a particular domain. Even if you're working for yourself, right? Even if you're an entrepreneur, then also you'll be solving a problem. So this domain knowledge part includes things like understanding. It's a very important diagram. Understanding client requirement, right? Understanding the client requirement, right? Important criterions, right? Important criteria knowledge, right? For example, to give an example, suppose we have created a machine learning model, okay? Understanding the data, we have created a machine learning model whose accuracy is 90%, right? Is 90% a good accuracy? Yeah, fairly decent accuracy. Yes. Suppose you have to predict sales, right? You're selling something. Suppose you're selling clothes and you want to predict what will be the sales for the next week. When you use this model, whatever the output model gives you, what is going to be the accuracy of your output using this model? How much accuracy? 90%. But my question is, model is 90%. But my question to you is that if 90% accuracy is on sales data, a person like me will be very, very happy. Okay, very, very happy. I'll be probably dancing, right? But if you try to apply the same model, right, for a medical diagnosis case, will you be interested in getting operated in such a hospital or an institution where the accuracy is coming as 90%? Domain knowledge, right? Domain knowledge. We need to understand what are the exact requirements. We need to understand what are the exact expectations, right? And we need to know how much do we need to pivot, right? So the first thing in data science is these accuracies and everything are subjective, right? They are subjective. So for that, you need domain knowledge. Domain knowledge part, very important, guys. Very important, these three things, which I'm going to tell you. Second part is people, the game changer, right? The second part is computer science. Now, if I take you back in history, okay, if I take you back in history in 1980s or somewhere, then okay, how many of you think that data science is a new concept? How many of you think that data science is a new concept? I hope you all know it's not a new concept. Everyone knows that. Yeah, it has been happening for ages. Just like you guys will be shocked if you already don't know, AI was coined in the year 1956. 1956 at the University of Dartmouth, AI was coined by Paul McCarthy, right? And we saw the boom of AI in the year 2010, right? Such a long journey. Same case with data science, because people back in the day, data science was called as data mining. Everyone heard about it? Data mining, knowledge databases. Yeah. We used to mine the data. Now, what were the problems? What were the hiccups of data mining? The hiccups for data mining was that we were doing everything manually, right? Now, if I give you 100 points, can you calculate the mean? Or let's say, if I give you 2 points to multiply, 2 multiplied by 3, how much time will you take? 2 seconds? Yep. How much time a computer will take? 2 seconds. If I give you to multiply 2, 2489 multiplied by 200, how much time will you take to calculate this? Say 5 seconds. How much time computer will take? 2 seconds. Now, if I give you to multiply 2489 into 1954386, how much time will you take to calculate this manually? Maybe say 1 minute, 80 seconds, 1 minute. How much time a computer will take? Still 2 seconds, right? Still 2 seconds, right? And if I give you to calculate this over 200 times, you will take 200 minutes, right? Using parallel computing, computer will still take about 3 to 5 seconds, right? So are you understanding the power of computer? Do you understand this concept in this relationship? What was happening back then? What computer science did, people, was it revolutionized the way data mining was happening. And that thing now is called as, that thing now is called as data science, in which computer science is one of the most important contributors. So this is just one reason. Now, manually, right? Manually, if I give you, say, 1 million rows of data, right? 1 million rows of data, right? So how many pages will you need to store this data? Suppose your notebook is like this, right? These boxes, and here you are storing the data, 1 million. So maybe you can buy n number of notebooks. But now, do you think it's as easy in storing something in computer? Because back in the day, people, we had memory issues, isn't it? Memory constraints. So there is something called as Murray's law, right? Which says as the advancement in microprocessors will increase, the price of microprocessor will decrease, right? So this is what is happening right now. Back in 1980s, if I show you, right, guys, right? Yeah, 2.5 kg exactly, right? It was size of a fridge, hard disk, but now it fits in your palm, right? So this was enabled, the storage techniques, right? The processing techniques, the infrastructure, right? Things like big data. What kind of data do you think we will be dealing with, people, in data science? You all know the term, very famous term, the kind of data, big data, right? Everyone knows about big data. What is big data? Yes, a data which is fast, right? It has velocity, veracity, variety, right? So this kind of data needs to be stored. This kind of data needs to be processed. So which thing brought all these things into data science? It was given to us by computer science, right? So computer science, people, included things like database management, right? Data validation, right? Data infrastructure, right? Data infrastructure, right? Then we had languages, computer languages, which is Python right now for us, right? Again, do you think when you do this thing manually, right? Suppose you do this thing manually, how easy do you think it will become using something like Python or any other computer language to create complex models? How easy it will be to do that? To create the complexity in models, right? Where you can capture the non-linear nature. Isn't it, people? Isn't it? For example, let me tell you this. 2, 4, 6, 8, 10, dash. What do you think is the next number, guys? 12. If I tell you to define this to me in, okay, leave that. What do you think is going to be the next number here? What is the next number? 11. Next number. 25. Perfect. Now guys, if I ask you to write these numbers, right, the way you predicted them, can you give me a function? F of x is equal to, what is the f of x here? It's 2x, right? It's 2x. F of x is equal to 2x. If I tell you to create a function, it will be f of x is equal to 2x. What will be the function here, guys? F of x will be equal to x plus 1. Yeah, x plus 1. Yeah. And here, f of x will be equal to x square. Yeah. Now, the last example, right? Last example. What is the next number here? I don't want the number. I want the function. I want this so that I can generalize. Isn't it? How did you reach this figure? How many of you think it's not possible to determine this? How many of you think it is not possible to determine this? Yeah. How many of you think? What if I just change this question and ask you, how many of you think it is not possible to determine this manually? Same response, but now I say, how many of you think it is not possible to determine this with computers? Will your answer still remain no? Do you think I cannot approximate this function using computers? We have something called as deep neural networks, and they are called as universal function approximators, right? So this is the problem, people. This is the problem, right? I will show this to you when the time comes, right? I will remember this example and I will show this to you. But now what I'm trying to tell you is the things which seemed impossible manually was solved by what? It was solved by computers. The distribution of this is like this. Can you figure it out yourself? No, right? We cannot, isn't it? We cannot do that. So this kind of approximation will be given by what? It will be only given by machines, right? And this is, people, what data science is all about, right? It is what computer science did inside data science, right? I hope this is clear. I'm assuming a lot of you will be going for interviews and everything after this course, right? So this will be a very, very important thing for you to know, right? Often it is asked why data science is having computer science in it, right? The reason is this. Okay. So this is the role of computer science inside data science. Now, people, the third thing, the third circle, which is one of the most parts, is maths and stats, right? Mathematics, statistics, which was optimization, right? Optimization of your models, right? Design of model, right? Now, guys, if you look carefully, in order to approximate this, what will you be playing with? You will be playing with a lot of data. You will be playing with a lot of mathematical concepts and statistical concepts, isn't it? What do you call this? This is maths, right? This is statistics and mathematics. Finding mean, median, mode, standard deviations, probability, statistics, all these will lead to this kind of result, isn't it? So this becomes the third wheel of this particular of this particular diagram, and this point of intersection, right? The sweet point of intersection is basically data science. Yeah, is particularly data science, right? So now, people, this point, okay, this point is basically representing data engineering, right? Data engineering, right? Data engineering is, people, the part of data science which enables us to capture the correct data, right? how the data will flow, how the data will be stored, how the data will be cleaned, right? All this is done by whom? It is done by data engineering. Just because, so am I right, guys? You will go for interviews, right, after this and try to fetch yourself jobs in this domain, data science, AI, ML, if my understanding is correct. Is that the aim? Yes. So now, guys, there will be three types of companies. Or let's say, to simplify it, let's say two types. One is small and the other one is big, right? So in a small organization, if you become a part of small organization and you are the data scientist there, you can be involved in all of these things, right? All of these things. Possible, right? Your bosses and your management will expect you to construct all these flows, right? No computer science, you should know maths and stats, and you should have the domain knowledge, and you will be asked to do all of this. But if you are going to become a part of a big organization, usually all these roles are fragmented. All of these roles are fragmented, right? There is a separate data infrastructure team. There's a separate data governance team. Now, guys, when you go on to collect the data, can you collect any sensitive data about? Is it possible? Ethically, it's not right, and legally also it's not right. My question to you is, who will look after this compliance? Whose responsibility indeed it is to look after this compliance? Data scientist. So this is about fragmentation. If you are part of a big organization, this thing will be taken by someone else, right? But if you are a part of a small organization, you will be expected to do this all by yourself. If you are part of a big organization, then do you think you need to have this domain knowledge? The answer is no. Why? Because there will be separate set of people who are called as what? Who are called as business analyst. Have you heard about this position, people? Business analyst. What is a business analyst role? It is basically a technical translator, right? Who knows technical, who knows domain. And that person goes and talks to the client in a layman language, convert it into technical requirement, coupled with the domain knowledge, and give you the document. This is basically a medical engineering problem. So we need this, and you need to fulfill this criteria. But again, if you're part of a small organization, who needs to take care of that? Who needs to make sure that you know everything about a domain? You yourself, right? You yourself, right? Then people, this area usually represents whom? This area represents research and analysis. Why? Because we have people who have domain knowledge and we have people who are knowledge of math stats. Have you heard about a position called as actuary in the world? Actuarial science. Actuaries are people who are basically dealing with domains which are very, very heavily data intrinsic, right? For example, finance domain, right? Finance is all about numbers. So there we go, actuarial science, and we have math, stats, optimization, model development, all of those things happening there. We are also at this point of time, people belonging to which section? Research and data analysis, right? And then people, there is the third intersection, right? There is the third intersection, which is this part, and this people is called as machine learning, right? Machine learning. Why machine learning? If you can combine the power of maths, stats, right, and you can combine the power of computer science, you will find yourself to be in a position where you can call yourself a machine learning engineer, right? How does a machine learning engineer becomes a data scientist? When they couple it up with the domain expertise, right? So in this course, people, in this course, we will teach you computer science. We will teach you a little bit about math stats, but what we cannot teach you is domain knowledge. Yeah. And making the base of what we are about to do very, very important to understand, right? If you understand this, then half the battle is won, right? So now to answer the question which was posted earlier, there are different things in the world of data science, right? So you can pick and choose anything, or you can do everything by yourself. If you guys are engineers, then I think you can be at this sweet spot going forward in life. If you choose a domain for yourself, for example, you choose to be a part of automobile industry, you choose to be a part of medical industry, you choose to be a part of, say, retail industry, you choose to be a part of aeronautics industry, right? You choose to be a part of finance industry, right? So whatever you will choose, this thing will get developed over time, right? This is the most difficult out of these three. I'll try to give you the example, right? My domain was agricultural industry, right? The agri products. I have worked extensively in agricultural industry, right? So again, for now, in my current role, this is something which I don't have. I have this expertise, I have this expertise. So same will be with you, and you guys will develop this knowledge over the time. Now I will try to give you an example, right? Elections to make you understand how data science can be used in one particular use case, okay? Maybe we can extend that to a lot of other use cases and examples, right? Talking about election season, right? Talking about the election season, right? We will try to understand how do we use data science, because it is very extensively used in this data science, right? Now, let me talk about the first phase. Let's say this is pre-election phase, right? Right, this is pre-election phase. In this pre-election phase, what do you think will be the tasks with which an agency like Election Commission of India will be doing? The first task can be that they will be doing the voter registration, right? Voter registration and data management, isn't it? Yeah, it will start with that. And what will be the things inside this? The first thing will be data collection, right? First thing will be data collection. So you will collect the data from all the registered voters, right? Maybe it can be their demographic information, where they live, what is their age, what is their gender, right? What is their past polling behavior? Have they turned out previously or not, right? All these details we can collect. Then can we also do data cleaning? Because I've told you, right, that there can be a lot of redundancies. Some person's name can appear twice, right? Some people can be mismatched. Suppose, for example, we have learned this in Python. Raghav, 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 right? Right? All these are what people? This is belonging to the same name, right? This is me. But for a computer, how many Raghavs are there? Different ones, all are different, right? So example like these, right? Some people might have died, they might not be existing anymore, right? So all this part will be taken care where people in the data cleaning process, right? Removing the duplicates, updating the new addresses, right? Correcting the information about every voter, all those things, right? And now, lastly, we can also include a flavor of data analytics, right? What will data analytics include in this? We can analyze the demographic data to identify eligible voters, isn't it? Yeah, people, till now we haven't understood this. Why it is not automated? How will you pick up all the how will you pick up all the details and nuances? Suppose you're filling a form, right? By mistake, you have, suppose you are 25 years of age. Suppose you have written 250. So does that mean I remove this? I remove this entry of yours? Because by mistake, you have written your age as 250. Is age 250 possible in our current world? Never, right? So I will have to tell the machine that because this is a mistake, please convert it to 25, isn't it? This is called as imputation. So this is mostly a manual task, not manual, but you have to understand the problem manually and then code it on computer. Suppose someone has written their state as EDLHI, right? And country as IDIN, right? So what is this state referring to? What is this country referring to? The humans are very smart. India, right? We can say this is India. And if this is India, then what is this pointing out to? Delhi? Just because you said, and it's a leading question, I wanted to explain this. Tell me, is it possible to do this automatically? No, right? We have to employ manual rules. right? We have to tell, because who's more intelligent? Humans or machines? Humans, right? Machines are just more optimized, right? So we know through human intelligence that this is pointing to Delhi and this is not EDLHI. So this is data cleaning, right? Lastly, we have data analytics. So do you think people, based on these data points, we can understand that who are the eligible voters and maybe who are not registered yet, maybe who have not voted in the past? Can we do all those analytics and reach out to those peoples and persons? That's the first part. This is just the first part, pre-election phase. Now, moving on to the second part, right? Moving on to the second part. Let's say we say public opinion regarding the polling, right? The polling which is about to happen. The first thing will be you want to collect information about people, right? So can you go out and reach all 1.8 billion people in this country? That what is their likable vote for which party? Is it possible? 1.8 billion. Do you think it's possible for 1 billion? Do you think it's possible for 500 million? Do you think it's possible for 100 million? No, right? So basically, I'm talking about what I have something which is called as a population, right? And if I have to study about this population, which is 1.8 billion people, which is impossible, which you just said, what do I need to do? Should I stop my process? No, right? I will go and collect something which is called a sample, right? We always work in samples, right? Suppose someone says that a Coca-Cola bottle does not contain 500 ml of liquid, which it claims, right? Suppose someone has put this allegation. Possible that Coca-Cola bottles do not have 500 ml liquid, which they promise. Now, there are two ways to deal with this, right? There are two ways to deal with this. Either I go and collect all the bottles of Coca-Cola in the world. Possible? Never, right? So what will I do? I will go and pick up handful of bottles, right? Handful of bottles. So what is that handful of bottles? Those are called as samples. One last thing. Suppose someone says that because of an industry, all the fishes of the lake are dying or they are infected. Is it possible to go and collect and check all the fishes in the pond or lake? No, right? What will we do? We will collect again handful of fishes and we will test them, right? Again, samples. Now, how does the raw data collected? Raw data as in, I hope you understand this. This is no more about population. With this step being told, now you're dealing with samples. So now do you want to ask me how is sample created? Yeah. Now I'm coming to that. Now guys, there are a lot of, second point is how to sample, right? How to sample, right? So we have sampling techniques, people. One is called as probabilistic and one is called as non-probabilistic, right? I will not go in detail right now. I just want to tell you an overview. Probabilistic is, suppose you are manufacturing t-shirts, right? You are manufacturing t-shirts, right? And suppose you created 100 lots of 1,000 t-shirts, right? So this is box 1, box 2, box 3, box 4, up to 100, right? 100 boxes. And in each box, how many t-shirts are there? 1,000, right? Now, suppose you are a quality inspector. You're a quality inspector. Is it possible for you to go over all the 100 lots with all checking all the 1,000 t-shirts one by one? No, right? What will you do? You will sample. Again, you will sample. Now, the most common way of sampling these kind of problems is probabilistic sampling. What is probability? What is the probability of getting heads or tails when you flip the coin? Equally likely, 1 by 2 and 1 by 2. What is the probability of getting 1, 2, 3, 4, 5, 6 on a roll of a dice? 1 by 6. Now, what is the probability of picking any t-shirt from this first lot out of 1,000 t-shirts? 1 by 1,000. Yes. So do you think all the t-shirts have equal probability of being picked up without any bias? If you decide to draw 5 t-shirts, right, from each of this box, right, and suppose say 2 are defective and 3 are not defective, what will you do? Will you accept the lot or reject the lot? We have majority of t-shirts of non-defective, or let's say we will reject the lot. Let's say we will reject the lot. Okay, though this is basically subjective as per the company policies, but let's say we reject it. Now, people, my question to you is, what if this entire batch had only 2 defective t-shirts? But now what will happen? The entire batch will be rejected. Yes. Let's say you sampled 1 t-shirt. Let's change the use case. I say you sampled only 1 t-shirt and that t-shirt was defected. Now you will reject the batch, and that is equally likely case. So this is called as probabilistic sampling, people. And there is no way you can go back. There is no way. You cannot say that, hey, sir, please allow this batch to pass because there is a chance that rest of the t-shirts are not defective. No, it is not the way that happens. It happens randomly. So, right, this is called as random sampling. Right? Random sampling. Now, suppose you are doing a cancer research, right? You're doing a cancer research, right? So for your cancer research, people, what kind of people will you need? People who had cancer in the past, isn't it? To know more about their problem, to know more about their medical condition. So is it possible, people, that in this use case, you can go and pick up any person from the population and ask them questions? No, right? That is not possible. So now, is the probability equally likely or it has changed when you pick the sample? It has changed. Now there is a bias which is introduced that you only want people who had cancer, right? So that kind of sampling, people, is called as non-probabilistic sampling, right? Non-probabilistic sampling. Clear? Now, sampling technique, right? Now, third thing in this same scheme can be, people, what? It can be the data collection, right? Data collection mode, right? That how do you collect the data? You can float a survey on, say, internet. You can go and stand outside a mall or office, isn't it? How will you can probably interview someone, right? Interview someone, right? You can have a group discussion. Yeah, all these techniques. Yes, no, maybe, right? In the same part, public opinion polling, right? Now, guys, so this was a brief introduction, right? And this can be extended to any industry, right? As of now, you can have example in the medical science, right? You can have an example in automobile, right? You can have an example in retail, right? Right? Then you can have example in manufacturing, right? You can have example in education, right? You can have example in sports, right? IPL analysis, cricket analysis, all these sports analysis, right? These are the most famous domains, right? They are the most famous domains. They are not topics, they are domains, right? In which data science is used extensively. So I'm just going to check, guys, in automobiles, there's a biggest example, self-driving cars. Yeah, autonomous driving. How do you think that's possible? Data science, again, like Tesla. Absolutely. Tesla is level 3. We have 5 levels. Level 3 is narrow AI. Level 4 is AGI, and level 5 is super AI. We are going to move first, right, with the technical aspect, right, with the technical aspect in our data science course, right? Right, which is based on Python, right? Because that is our base language, which we have learned so far, right? So in Python, people, we will start and cover 4 of the packages right now. And as we move on to machine learning and other deep learning and everything, you will explore more and more packages. The first package we have to cover will be NumPy, right? I'll explain you in detail what NumPy is. Then we will cover Pandas. Then we will cover Matplotlib. And then finally, we will cover something called as Seaborn, right? We will cover something called as Seaborn. So these 4 packages inherently we have to cover in Python to make sure we are able to reduce the time in coding, right? We are able to reduce the time in coding, and using these packages immediately help us in getting the desired results, right? I hope you all remember the concept of modules we have covered in Python. Do you all remember functions and modules? You can use Jupyter Notebook. If your Jupyter Notebook is not installed, you can use something which is called as Google Colab, right? Go to Google, type Colab, right? Let's say you write Colab, right? And then you will see this option. Click on Google Colab and it will allow you to code in Python, right? So we are now going to discuss about the NumPy package in Python. Okay, NumPy package in Python. So NumPy is a fundamental package for data science in Python, right? It is one of the most fundamental packages for practicing data science in Python, right? Why is that? Why is NumPy so fundamental? What is so special? NumPy package gives us a new data type for handling data in Python called as ND arrays, right? ND arrays, which stands for n-dimensional arrays, right? N-dimensional arrays, right? This stands for n-dimensional arrays. So till now, we have studied about list, integer, tuples, strings, right? Out of which the data types such as list, tuples have been used to store data, right? Store data, right? And range used for generating new data, which is primarily sequential, right? Now there is one problem, right? There is one problem, and there should be a question. That there should be a question. Why do we need a new data type to work with data science, right? Why do we need this? Yep. So the answer to this question, people, the answer to this question lies in a small explanation, right? Yep. Lies in a small explanation, which is that Python is a high level language, right? Python is a high level language, right? And a high level language is usually very distant from hardware? A high level language is close to hardware or distant from the hardware? Did you not attend the Python programming essentials? What is the type of programming language which is closest to hardware? A low level language? If this is my hardware, yeah, this is my OS, this is my application layer, right? So hard level language, high level languages here and low level languages here, right? Which is closest. So binary languages, assembly languages, right? All these are closest to the hardware, because where is the processing happening? Where is the processing happening of the data? At the hardware, isn't it? Processing of data is happening at hardware. No hurry, actually it is happening at hardware, right? What is processing? Processing is signals of zeros and ones, right? What are zeros and ones? These are electric signals. These are the electric signals, right? Which is basically on and off, right? And it is communicated to the hardware through the help of resistors and microprocessors, right? Isn't it? Right? Why a computer only knows zeros and ones? Because zero is off and one is on, which is the electric current, right? Electric current to activate or deactivate certain things, right? True and false, gates, right? So it is happening at hardware. So now people, if you understand this part, then try to logically connect it to what I'm going to say. When you are studying data science, what kind of data you will be dealing with? Big data, right? And as the name suggests, it will have a lot of volume, right? It will have a lot of volume other than a lot of other things, right? It will be very, very big. And on this large volume of data, you will be doing processing. You will be doing processing. What does processing means? What does processing means? Operations. So where is this operation happening? This is happening in hardware. And for hardware, which is the closest language to hardware? A low level language. But now, people, we have a situation in front of us. What is the situation? That what are we trying to do data science with? What are we trying to do data science with? Python, right? And Python is what? A high level language, isn't it? Yeah. So there's a discrepancy. Yeah, a big one. Because high level language, these are slow in processing, right? These are very slow in processing, right? So for these kind of languages, to handle this kind of data and these kind of operations, yeah, is very difficult, right? So let's keep this part aside if you understand this. Now let's go to the second point, right? When you learned Python, on a scale of 1 to 10, how easy was it? The ease of use of Python? It's relatively a higher number, right? Relatively a higher number. So now guys, when I talk about data science, right? When I talk about data science, okay? Right? When I talk about data science, my thing is that this will be used by masses, right? Will be used by masses, a lot of people, managers, programmers, business analysts, data analysts, possible, right? Who are from non-technical background, who don't know coding, they also can do data science, because data science is a general thing, isn't it? Understanding the data. It should not be limited by your capability to understand the technicalities of a very complex language. So for these people, which language is suitable? Which is Python. right? It is easiest to understand. It's a high level language, almost like English. Yeah. So Python is a simple language. So in this part, people, Python fits the bill, right? Which is a bigger thing. In the second part, when we talk about the operations, in this part, there is a problem, right? Python fails, right? Python fails, right? Because it's a high level language. We said that, okay, there is a language called as C, right? Which is a middle level language, right? And C language, people, is used to create OS, operating systems. It is used to create networks, networking applications. It is used to create games, right? All the things which are close to hardware, C is used, right? So C fits this bill, right? C fits this bill. Python said that, okay, if C fits the bill and Python is written in C, written on C, right? It's written on top of C language. Now what happened was Python said, okay, if my intrinsic data types, my intrinsic processing is not suitable for data science, but my high level nature is, let's do one thing. Let's take C language and use its power, right? Use its power that it is very close to hardware, and let's create a new data type, right? Let's create a new data type which is written on top of C and which can integrate with Python seamlessly. And people, this new data type was called as array. And this was given to you by something called as NumPy package, right? NumPy package. It defined a new data type, which was array. And along with defining the array, it gave various operations, right? It gave various operations one could perform on arrays, right? One could perform on arrays. It's simple, right? The power of processing lied with C, right? It was lying with C. So we developed a new data type using C on top of Python, and that new data type was called as array. And this array was defined in a new module, which was called as NumPy module, which told you how to create the arrays and then how to manipulate those arrays for doing data science. We had options like Java, we had options like C, right? We had options like Fortran to be used for data science, but we chose Python because of its simplicity and the simple syntaxes, so that people from non-programming background could also use Python to do data science, right? Now, the limitation was that because it is slow, because of being high level, we needed something which could make it fast, and that was using an external data type, which is not internal to Python, and that was array. And this array is defined inside a new module or a library called as NumPy, which is numerical Python, right? Numerical Python. Back to the programming, right? Where we have understood, right, about this question, right? So NumPy essentially is built on top of C language, which is compatible with Python. It leverages the power of closeness of C with hardware, right? C with hardware, which eventually makes the processing faster in Python, right? So this is what the first part is, right? This is what a first part is, right? Now the second thing is people, so this is about the performance bit, right? This is the performance bit. The above is about the performance of Python, right? Now coming to the next part, which is the memory efficiency, right? Memory efficiency, right? So arrays created by NumPy in Python are less memory exhaustive than lists in Python, right? And I will prove these points later on to you through code, right? In list, right? In list, each item is an object, right? Each item is an object, right? I hope you remember this, guys. Each item is an object, right? And it holds, right? It holds meta information like references and types, right? Etc. Right? A lot of information it holds, right? This makes list consume more memory, right? But arrays in NumPy are contiguous, which means that they do not create objects, but rather directly store the data in continuous memory blocks, one after another, right? Also, the arrays are homogeneous in nature, right? You can only store the homogeneous data in array, unlike lists. In lists, you could store different data types, right? But in arrays, you cannot, right? You have to store the same kind of data in the array, homogeneous. So it's a contiguous memory block, which is meaning that you can store data in continuity, right? One after another in the memory block. So the access is faster, the memory location and the memory efficiency is very higher, right? As compared to the native data type like lists or tuples in Python. Arrays are basically vectorized operations, right? I'll talk about to you with vectors. What are vectors, right? They are the vectorized operations and they are way more convenient to deal with as compared to list in Python, right? In list, you have to go through a lot of loops, right? We saw that you have to go through the list comprehension, but you will see in Python Pandas, sorry, in Python NumPy, the vectorized operations are very simple, right? They are very simple, right? Again, for all this, I will give you examples, but it will take some time because you have to understand what arrays are first, right? Okay. Then the most important other packages, which are Pandas, Matplotlib, Cbond, Scikit-learn, SciPy, all are written on top of NumPy package. That's the reason, for this reason, it's called as fundamental package. All the other packages which make your life easier as a data scientist, where you don't have to worry about code, all these packages make our data science journey smooth because we have to worry less about code and more about logic. Yes. So for for the understanding of these packages, it's very important that we understand NumPy first and then we move forward. Right? Now, then let's get started. So the first step, right? The first step which you have to see, right? The first step which you have to see while using NumPy package is basically from where will you import the package, right? From where will you import the package? So to import the package NumPy, we write import NumPy as NP, right? Where NP is an alias, right? It's an alias, right? So please do this, import NumPy as NP, right? If you don't get any result for this, then you can write pip install NumPy, right? Pip install NumPy and just execute this, right? When you will execute this, it will give you this message or it will download this package for you, right? Pip stands for Python index package, right? It is basically like Play Store, App Store, right? Or Windows Store for Python, right? So you are just going to these Play Store, Windows Store, App Store of your Python and asking them to download this for you, right? It is also called as the package manager, right? Pip. If it is done, you can also check the version. You can say np dot underscore underscore version underscore underscore, and it will give you the version of NumPy, right? NumPy is an open source package, right? Yeah, that's about it. Yeah, it's an open source package, people, right? Open source package. And if you want to see the code, you can go to GitHub. Go to Google, write the code for NumPy. It will show you it on GitHub, right? Done. So let's say okay. So I say we have, okay. Before this, let me come to a little bit of theory before I do this with you. So now guys, I said that NumPy has arrays as data type, right? And this is written on C, which runs directly on hardware. Also, this NumPy array is basically a vector, right? It's basically a vector. Now, what is a vector, people? What is a vector? A vector is a quantity which has sign plus magnitude, right? It has a sign and magnitude. If I say this is a Cartesian space, this is I, this is J, and I say this is 3I and 4J, right? 3I cap, 4J cap. So this is a vector, right? And this is the direction, guys. If you have studied elementary maths, you would know this. Yes, people, this is a vector. If I draw another like this, then this is another vector. So I will call this, say, 2I and 5J. Yep, this is another vector. And this is the theta. right? This is the direction. This is the direction. And what is the magnitude? 3i, 3 square plus 4 square, which is 9 plus 16, which is 25 under root, which is 5. So the magnitude of vector is 5 and direction is equal to theta. This is a vector quantity. Now, what is this? What is this? This is a scalar. This is a scalar. Yeah. Only magnitude. Isn't it? This is scalar, only magnitude. And then I have 2, 3. Right? This is what? This is a vector. It has 2 dimensions or 1 dimension. Only 1 dimension. Right? This is 1 dimension vector. Yep, 1 dimension vector. Now, if I say this 2, 3, 4, 5, what is this called? This is called a matrix. Right? This is called a matrix, which is what? Collection of vectors. And this collection of vectors matrix is called as 2-dimensional. Right? It is called as 2-dimensional. Now, if you have this, so these are stacked behind each other. This is 1, this is 2, this is 3, right? So we have 3 layers in matrix. So how many dimensions will be this, people? 1 dimension, 2 dimension, and 3 dimension. This is a 3-dimension matrix, right? Or 3-dimension vector, or 3-dimension array. I'll repeat once again. What is a single value? A single value is called as a scalar, right? It only has magnitude. Now, when you have multiple values, right? This is called as a vector. It has a direction, it has a magnitude, and this is single dimension. Now, multiple vectors, right? Like this, or maybe you can say like this, right? Are you understanding why I'm calling it 1 dimension? It can be either this dimension or it can be this dimension. In any dimension, you stack 2 vectors, you will get yourself a matrix, right? You will get yourself a matrix, which is now 2 dimensions. It has rows and it has columns, right? Now, if you stack multiple such matrix, one after another, right? This becomes a 3-dimensional matrix. And this can go up to how many dimensions, people? How many dimensions this can go up to? It can go up to, this can go up to n dimensions, right? N dimensions, right? So now do we get it? Why do we call it ND arrays? Yeah, n dimension arrays, right? That why are we calling something what? Right? N dimension arrays. We are only capable of viewing 3 dimensions, people. It can go up to 100 dimensions, 500 dimensions, 1000 dimensions, any dimensions. Scalars are least important. Vectors are more important. So now we have multiple dimensions in arrays, namely 0D, 1D, 2D, 3D, and so on till the ND, right? ND arrays, right? Now, let's create our first array, right? Let's create our first array. And this will be a 0-dimension array, right? 0-dimension array. How will you create this? You will say ARR0 is equal to np dot array and you will mention what a scalar value is. What is a scalar value? It is a simple value. I say 2, right? np.array equal to 2. And when you will now check or print the type of ARR0, it will tell you class numpy nd array, right? It is a 0-dimension array. And if you want to check the dimension, you just have to write ARR0.ndim, right? And it shows you that there is 0 dimensions present. So what is this in short? This is a scalar. I have entered a single value, people, 2, 200, 500, whatever you want to enter. And the syntax is np.array. np.array. You are instructing numpy package to fetch the function array on method array and convert this into that particular data type, right? Array 0. And when you check the type is nd array. But what is the dimension of this nd array? This is 0, which is nothing but a scalar, right? We have created this. This is what we have created, right? Now, guys, if I created this list, right? Say lis is equal to, yeah. So this was a list, right? This was a list, and this is what, people? What is this that we have just studied? According to that, what dimension is this list? So what I'm trying to do is, I will create a 1D array with a, or let's say from a list, right? Let me show you how do we do that. Okay. So I say, Hari, read the error. Name ARR not defined. Why? Because you have created array from AAR0. Come on, Hari. Right? I will create a 1-dimensional array. How will I do that? People, I will say ARR1 is equal to np.array. And can I pass 1D list inside this? Or can I say I can pass lis inside this? When I do this, people, now see what will happen. ARR1 will be equal to this, right? And if you say, let me say print ARR1, it will be like this. Okay. This is your ARR1.ndim. You will see that it gives you 1, right? This is a 1-dimension array, right? 1-dimension array. Yes. So for example, when I say scalar, right? When I say scalar, I say 35, right? When I say vector 1D, I say, so these are suppose my marks, right? Now I say 35, 40, 50, right? So now what are these? My marks in 3 subjects. Yeah, marks in 3 subjects. This is my, say, Hindi, this is English, and this is maths, right? Or let's say science, because not everyone has Hindi. Science, English, and maths, right, guys? Now, if I have to create a matrix of 2 dimension, what will I write? So that means this is 1 student. This is 1 student, people. Isn't it, guys? Yes, no, maybe. So now in matrix, we will have what? We will have multiple students. Yes, no, maybe. In a matrix, people, we will have multiple students. Suppose this was S1. Now you will have S1, S2, S3, S4, like this. And each student will have their own individual list of marks. So can I say that I'm making a nested list? Can I say that, people? I'm making a nested list. So now let's make it, okay? From a nested list, okay? A nested list. So I'll say ARR2 is equal to np.arraylist. I will have to create a list first. LIS2 is equal to, so this is my first bracket. What is this bracket representing? This bigger bracket. Now I will put another bracket inside this and I will write 1, 1, 2, 2, 3, 3. I'll put a comma again, right? A comma. Then I will say 4, 4, 5, 5, 6, 6, comma 7, 7, 8, 8, 9, 9. Right? I'll do this. Right? Now I will say list 2. When you will do this, you will see that an array like this has been created, right? Like this, ARR2, right? This has been created, right? When we check the dimension, it is 2-dimension array, right? Yep. Marks of 3 different students in 3 different subjects. And this is the same technique you can create a 3-dimension array. How will you create a 3-dimension array, people? If I go here, how will you create a 3-dimension array now? Now, suppose I have data in this, and this is my master list. Okay, this is my master list. In this, I have data, and this can be represented like this. This is my first matrix, isn't it? And this is the vector inside this. V1, V2, V3. Then this can be called as M1. And now to create a 3-dimension setup, how many M1s do you need? You need multiple M1s, isn't it? You need M1, M2, M3, multiple matrix like this, people, like this, matrix 1, matrix 2, matrix 3. So what will you do? You will have what, people? You will have another yellow, right? And you will have inside this yellow multiple purples, isn't it? Right? Again, like this. Yeah, like this you will have it, people. So can I say, people, can I say that as I am increasing the dimensions, as I am increasing the dimensions, I am putting 1D, sorry, 0D, right? And okay, again in this V1, do you think you will have multiple scalars, people? Can I say that? Can I say multiple scalars create a vector, multiple vectors create a matrix, and multiple matrix create one 3-dimensional matrix? Can I say that? Let me talk to you about an image, right? Image, right? What is an image made up of, people? What is an image made up of? Pixels? Yes or no? No, not frames. Frames is basically videos. Pixels are creating an image, right? So we have how many pixels here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? Suppose this is one vector, right? This is one vector, and this is one scalar, right? Scalar 1, scalar 2, scalar 3, scalar 4, and this will make vector v1. This is v2, v3, v4, and together, can I call this m1 and call this blue? So for a colored image, how many channels are there, people? How many channels are there? What do we call it? We call it the image as RGB image. That means red, green, blue. So this is blue part. So similarly, you will have a red part in front of it. Then you will have a green part. And then finally you will have a blue part. Yeah. Are you understanding, guys? Why do we require three-dimensional arrays? Yes. Suppose now you want to make a change at this pixel. So you will go to the third layer, which is the blue layer. Then you will go to the third column, which you will go to the third column and third row. And this is how you will reach this pixel. Everyone? Yes, no, maybe? Yes. So this is the reason why we need to create a 3D array, right? To ingest information like this, right? To ingest information like this. So we can create a 3D array also, right? Right? And how did I tell you? How many brackets will I have? Squared brackets? I will have 3 squared brackets. So now this is just one student, right? Now I'll put a comma here, right? I'll put a comma here and I will start. Right? I'll do this. I'll say this list 3, ARR 3, list 3, ARR 3, ARR 3, ARR 3. Right? And now you will see that there is a 3-dimensional array. Right, guys? Right? This is a 3-dimensional array. Yep. Moving on, there are multiple ways to create arrays, right? The first one we have done. So we have done from lists. From list we have done. Then second will be from we can create a 0 array, right? We can create ones array, right? Then we can create custom array, right? I will show this all to you, right? I'll show this all to you. So let's start with the ones array, sorry, zeros array, right? What do you have to do? You have to write, so let's say 0 underscore ARR 0, okay, a 0 dimension 0 array. So you say np dot zeros, right? And you create a 2, right? A 2, right? And if I say 0 dot endim, right? You will see it is a 1-dimension array, right? It is a 1-dimension array, right? So 2 is by default taken as, so let me just show this to you. It will look like this, right? It is taken as horizontal. What is the dimension of this, guys? A vector. What is the dimension of this vector? No. It's 1. It is basically 2 cross 1, right? 2 comma 1. Sorry, 1 comma 2. My bad. 1 comma 2. Isn't it? Now, what if you had to create a 2 cross 1? What if you had to create a 2 cross 1? Right? So let me just show that to you. So I say Wait. Like this, okay? Now when I do this, I say ARR 1 and I say here 2 comma 1, right? I say 2 comma 1. Now you will see, people, what will happen to this. Now, because you have created, right, specified 2 dimensions, right? What will this be converted to now? What will this be converted to? This will be converted to a 2-dimension vector. By default, it was this, right? Which was this vector, right? By default, it was this vector, right? What is the dimension of this vector? 1 cross, how many values you put here, right? 1 cross 2, like this. So we call this only 1 dimension. We call this only 1 dimension. But now when I will run this one, you will see, yes, 2 cross 1. And now you will see this is 2 dimension, right? You see this is 2 dimension now. Clear, people? Just the orientation has changed, but now you see the brackets. There are 2 brackets now. Because what have you now instructed? You have now instructed Python and rather NumPy to create the vector as 2 cross 1. So you have said, give me this 0 and give me this 0 here. So the moment you do this, you are now specifying the rows and columns. Now this 2, 1, right? Let's say this is 2, 1. Now let me create another 2 dimension matrix for you. Let me call this 10, 10, right? So how many rows and columns will it have, people? How many rows and columns will it have? I will say 2, 1, 0. It will have 10 rows and 10 columns like this. You saw this? Yeah, 10 rows and 10 columns, right? By default, it is 1 cross 2 like this. It is a 1-dimensional vector and this is a 2-dimensional vector. What about a 3-dimensional vector? 0 dot 0 underscore ARR3 is equal to NP dot zeros, right? NP dot zeros, right? Should I just write 3 comma 3 comma 3 and I should check for this? Yep, you will have a 3 cross 3 vector, 3 cross 3 matrix with 3 matrices stacked behind each other, right? If I say 4, this will be 4. So how do we read this? Number of layers, number of rows, and number of columns. So can you help me with a syntax? Can you help me with a syntax which can create me a 3D matrix of 5 layers, 3 rows, and 3 columns? What will I write? 5 layers, 3 rows, and 3 columns. What will I write? 5, 3, 3. Yeah, you'll get 5 layers, 1, 2, 3, 4, 5, right? Like this. Suppose you have to represent an image with say RGB channel and say 256 and 256 pixels. How will you create this? So I'll say img, right, image is equal to np dot zeros, and I will say inside this 3 channel 256 cross 256, right? And when you will just run this image, it will be like this, right? It will be like this. This is 1 channel, this is 2 channel, and this is 3 channel. And we understood that NumPy is a fundamental package for data science in Python, right? This package gives us a new data type to work with, which is called as n-dimensional arrays, right? Now, what are arrays? What are arrays? Arrays are nothing but vectors, right, which are stored in a contiguous block of memory, which means they are stored continuously one after another, and they do not get converted into the object, unlike the list, and they are way faster. They are more memory efficient than list. I will prove this fact to you today with the help of example, through the help of code, right? So why NumPy arrays? Because NumPy is a package which is built on top of C language, which is compatible with Python. And C, being a middle level language, interacts directly with the hardware. So whatever operation you run, in a fact, that is getting directly executed on the hardware itself, right? That is the reason why the performance is way better when we try to use the n-dimensional arrays. Along with this, these syntaxes, the type of syntaxes we used to type in list, I will show that to you also today with the help of example, are way simpler when you try to do them with ND arrays, right? So arrays are basically vectorized operations, right? And they're also very convenient to deal with as compared to lists and other native data types in Python, right? And the most important part is that in our data science journey, whatever other packages we will use, right? Again, what are packages? They have predefined things stored for you so that you can leverage them and focus less on code and more on logic, right? You need to be aware about the logic more than the knowledge of the code, right? So we have packages for that, which contains methods inside them, which you can use, and without any further calculations, you can work with them directly, right? So that is how we started with NumPy, right? And the syntax to import NumPy was import NumPy as NP, where NP was an alias, right? You could do pip install NumPy if someone did not have access to NumPy. If NumPy was not coming by default, you can use pip install NumPy, which is Python index package, right? And this is like Play Store, App Store, Windows Store for Python. All the packages are stored in pip, and you can call pip, you can ask pip to download that package for you so that you can use that, right? It's basically the package manager. So NumPy is an open source, and if you want to see the code, you can go to GitHub and check the code out for yourself, right? In NumPy, we have n-dimensional arrays. Now the question arises, people, that why do we need NumPy, right? So my answer to this particular question is that when you will deal in data science, right? When you will become a data scientist, you will be dealing with data, right? Now my question is, how will you make the machine ingest the data, right? There has to be a way, right, for you to input the data to the machine, right? To make manipulations to the data, to read the data. So all this is started as the base package of NumPy arrays, right? Other than that, it becomes very difficult and cumbersome for us to deal with that. And this provides us a lot of ease and flexibility to deal with such massive amounts of data, which you will see along with me as we will move forward in this particular course. Yep, perfect. Now, people, let me just pull up the PPTs. This is what we're discussing, people. We start with something which is called as scalar, right? We start with something which is called as scalar, which is a quantity which only has magnitude, right? In NumPy language, this is also called as 0D, right? It is called as 0 dimension. Then, people, we have vector, right? And vector has a constant dimension. It has only one dimension, right? You can interpret it as a row or you can interpret it as a column. It doesn't really matter because this is only one single dimension, right? So usually it will be written as 5 comma blank, right? There will be nothing written in front of it. So this in NumPy terminology and nomenclature is called as one dimension, right? When you move on, then you get combined couple of vectors, you get a shape, and now that is called as a matrix. And in NumPy terminology, it is called as two dimension, right? And when you try to stack multiple two-dimension matrices, one after each other or one before each other, then they become something called as three-dimensional. And now in my capability, I don't know what four-dimension looks like, but there is a high possibility that you have n-dimensional data, right? It has n, we are dealing with n-dimension data, right? Suppose with this, I also add time, right? At t equal to 1, at t equal to 2, that will serve as the fourth dimension for this data. But how does it look like? I don't really know that, right? Because humans are only capable of visualizing 3D. 3 dimensions at max, right? So you can go to n dimensions, and hence the name n dimensional arrays, right? ND arrays. Post this, we moved on to create certain things, and I tried to explain you the data, right? So the data will look to you like this, right? You might have a scalar quantity, which is marks, right? 1 marks, right? Now, if I go on to vectors in 1D, it can be marks of one student, right? Marks of one student in science, English, and maths, right? 35, 40, and 50 out of say 50, right? 3 subjects. So this will be characterized as a vector, right? What will be the dimension written for this? It will be 3 comma nothing. This will be 0, right? Shape will be 0. For this matrix, suppose we have 1, 2, 3, 4 students, and each student will have 3 marks. Right? Each student will have 3 marks. So what will be the shape of this? We have 4 rows and 3 columns, right? So this will be the shape, right, of this 2D matrix, right? And now if you stack images, right, one behind each other, then it will be like this, right? RGB image, I give you an example. So this has 4 cross 4 pixels. So the shape will be 3 cross 4 cross 4, right? This will be the shape for this particular 3D matrix, right, guys? So this is how you input the data. Just to tell you a little bit more, since generative AI is very popular these days, right? So what if I tell you the fact that the chat GPT, which you use or you might have used, right, has never seen a single word in its lifetime, right? All it sees is numbers, right? Only numbers. How do we see numbers? Suppose I say, my name is Raghav. Raghav is a nice name, right? So these are 2 data, right? These are 2 data points. Now, we all know that computers do not understand these, right? Computers do not understand these, right? There is no understanding for computers to know what text is, right? It only knows 0 and 1. Yes, Dharnika, right? It only knows 0s and 1s. So see how we will convert this. So there is something called as vocabulary, right? So vocabulary are nothing but the unique words, right? How many unique words do I have in this? My name is Raghav 4. This is not unique. This is repeating. This is repeating. 5, 6, and this is repeating. So I have 6 words. So now, guys, I will do something called as word to vec, right? Where I will convert these words into vectors. How will I convert them? Look at this. So I will have, suppose this is S1, this is S1, and this is S2, right? So I will represent S1 as, right? I will have a vector of size 6. How? I will say 1, 0, 0, 0, 0, 0, right? 1, 0, 0. How many elements does it have? 6 elements, right? Name will be 0, 1, 0, 0, 0, 0. Is will be 0, 0, 1, 0, 0, 0. And Raghav will be 0, 0, 0, 1, 0, 0. Right? This is S1. My name is Raghav. Now, when it comes to S2, right? When it comes to S2, how will I enter this? S2, 0, 0, 0, 1, 0, 0, Raghav. What is here? 0, 0, 1, 0, 0, 0. What is a 0, 0, 0, 0, 1, 0? A nice is 0, 0, 0, 0, 0, 1. And name will be 0, 1, 0, 0, 0, 0. Right? Now, this will be the vector representation of these 2 sentences. Just to tell you a fact, GPT-3, right? GPT-3 model, right? GPT-3 or GPT 3.5, they have vocabulary of 30,000 words, right? 30,000 words, and each word, right? Each word has a dimension of 12,500 numbers, right? What do I mean? Suppose I say Raghav. So it will be one word and it will be represented by 11,500 different numbers, right? And like Raghav, there will be 30,000 words in this GPT model, right? 30,000 words in this GPT model, right? And this total number of parameters which get trained in the neural network, which we will learn later on, neural networks, they are almost close to 1.75 billion parameters, right? 1.75 billion parameters. So why I'm telling you all this? Because to showcase to you that what is the importance of vectors, right? In the entire machine learning and data science. Yeah, people. So this is the reason, people. Now my question is, how will you create these vectors? How will you read these vectors, right? The answer is through NumPy package, because it is the base package. Clear, people? Yeah, I hope today's class will be interesting for you, because you will know the context. Why are we doing it? Yeah, so I'll try to show that to you, how we convert things to vectors, right? Okay, let me go here now, right? Let me go here. So people, we started using NumPy. So I started with the zero dimension arrays, right? Zero dimension arrays. So zero dimension is nothing but a scalar. So I created ARR0, which was np.array, and I entered a single element inside this, which is nothing but a scalar. And then I checked the type of ARR0 also, right? And then I checked the dimension also. So the answer was 2. Class was numpy nd array, and the dimension was 0, right? Exactly what I had mentioned in my PPT, right? It will be having a 0 dimension like this, right? Same thing has been proven, right? Because it's a scalar. Now coming on to one dimension, right? Coming on to one dimension, I create a list which is nothing but a one dimension data type, right? Now I create an array which is ARR1 from array from this particular list, LIS, and then I check the type of print ARR1, check the type of ARR1 and the dimension, right? So when I execute, right, then you will see that it was this numpy array and the dimension was 1, right? Exactly like this. So if I show you something else, say print ARR1 dot shape, you will see it's 4 comma empty, right? And I show it to you here. It will be empty, right? Empty. And this will be comma 1, right? So this means that it has only 4 elements, right? If I increase these elements to say 55, 66, 77, then it will become 7 comma blank, right? Which means it has 7 elements as a vector. Now we create something with a nested list, right? Which is like this. So with the nest, I want one bracket which is running outside, right? Then inside this, I have 1, 2, and 3 lists inside one list, right? So this is the nested list. This is marks of first student, second student, and the third student, right? So I do this and you see it is this, right? And I will show you the shape also. Right? It will be 3 cross 3, 3 rows and 3 columns, 3 rows and 3 columns, right? Now, similarly, we can also create a the 3D matrix, right? With 2 levels, right? Level 1 and level 2 and 3 cross 3. So The shape will be what, people? Can someone guess the shape? What will be the shape of this? I've shown you here, right? If this is 3, 4, 4, then what will be this? 3 rows and 3 columns, right? So when you will execute, you will get 2, 3, 3, right? 2, 3, 3, right? Right now, people, there are multiple ways, right? There are multiple ways to create arrays, and we should know them because all of these comes very, very handy. Not right now. I don't have enough context to give you right now, but later on, you will see with me or with some other trainer that how these will be used in deep learning specifically, right? They are the key of deep learning algorithms, right? Where we initialize some weights, we initialize some biases, and those initializations are nothing but multi-dimensional NumPy arrays, right? NumPy arrays. Okay. Right. For example, suppose I have this. I have to multiply this with some random numbers, right? So how will you generate these random numbers? You will generate them through NumPy, and you can generate them in a specific kind of shape, right? Which is 2 cross 3, and then you can multiply them. You can multiply the matrices, and you can get your output for yourself, right? So this is the way they are used. So we saw the first thing from list we have already covered. Then now we are moving on to creating zero arrays, right? So I create a zero array of one dimension, right? Of one dimension, which is 0, 0. They are represented in floats, right? They are represented in floats, 0.0, right? Now you can create a two-dimensional zero array, right? You can create a two-dimensional zero array, which is you have to mention just the shape inside 2 cross 1. So it will have 2 rows and 1 columns, right? 2 rows and 1 columns. The difference here is that these are 1 dimension and these are 2 dimensions, right? You have explicitly mentioned the rows and columns. So you can expand this to 10 cross 10 also. Right? You can expand in 10 cross 10 or 10 cross 6, whatever you feel like yourself, right? It will have 10 rows and 6 columns, right? Now you can also create the 3D arrays, 3D zero arrays, right? Which is 5, 3, 3. What does 5 means? What does 5 means? First element represents the number of layers. So you have 5 layers, right? It's 5 layer deep. Then you have 3 rows and 3 columns, right? So it will look something like this. One, two, one, two, three, four, five, right? Like this, something like this, right? It will look like this. Stack 1, 2, 3, 1, 2, 3, 1, 2, 3, right? 5, 3, 3. Okay. Yes, the number of matrices, Hari, what I represented, right? Layers, rows, columns, right? Layer, rows, and columns. Clear? So now when you execute this, you will get an arrangement like this. Okay. I try to show you this thing with another example, right? Which is I created an image of an RGB image of 256 cross 256 pixels, right? Which have all zeros inside them. And this is how it was created, right? 3 layers RGB 256, 256. So this is how the image will look like, right? This is how it will look like. Now you can also create arrays with ones, right? Exactly the same way you created it with zeros. I'll give it to you. I'll give you 5 minutes time to create them. I'll show you one. So I say A1 is equal to NP dot ones, and inside I pass 2. I check A1. So this is a array like this, right? It is an array like this. Now you create 2 dimension and 3-dimension arrays of 1. It is basically as a float. Hari, it's represented as a float, right? It's represented as a float. Okay, right? Perfect, right? Also, guys, with this, right? Also with this, you can create the custom arrays, right? You can create the custom arrays, right? How do we create custom arrays, people? How do we create the custom arrays? You have created now zeros. You have created now ones. Now what is left that you create? The custom arrays. Forget about this. I will come to this later on, right? Let's create custom arrays, right? So the syntax remains the same, right? I say cust underscore arr is equal to np dot full, right? This is the syntax, np dot full, right? And you will say 6 cross 6, and suppose you want an array of all 4s, right? This is the dimension 6 cross 6, and this value after comma is basically the value which you want. You execute this and you copy this, paste this, and you will get the arrays of 4s for yourself, right? If you want of 10, you will get of 10. If you want 10.3, you will get 10.3, right? Anything which you want. If you want case, you will get case, right? All the examples. So let me just show that to you. Yep, like this. Now, guys, how did we create or how did we use range in Python? Can you use range to generate numbers between 20 to 50, right? 20 to 50. Can you give me the syntax quickly? How did you do that in range? How do we do that? We said R is equal to range 20 to 51, right? And then I said I in R, print I, right? And this is how I got the numbers, right? So similar to range in Python, we have a range in NumPy, right? How do we use a range? I say a range underscore arr is equal to np dot a range, right? And then same syntax, I will say 20 to 51, right? 20 to 51, and that's it. And when I will check my arr range arr, you will see I have generated myself numbers between 20 to 50 and a range in NumPy, right? A range in NumPy. Yes, if you want a interval, so you can use this, say a range 1, and after comma you pass the third argument, suppose it's 3. So now it will jump 3 times, right? 20, 23, 26, 29, 32, 35, like this, up till 50. Now, guys, there is something which is called as linspace, right? What is linspace? It stands for linear spacing, which means between two given numbers, this function will fit the required number of numbers, right? For example, we need to create an interval from 0 to 1. People, there are infinite numbers I can have between 0 to 1, isn't it? Infinite numbers I can have between 0 to 1. 0.0000000000001, 0.000000101, right? I can go in the infinite manner, right? Now, for example, you need to create numbers between 0 to 10, right? And you want to create and want to have 10 numbers in it, right? So how will you do this? It's not float, it's about the number theory, right? Between 0 and 1, you have infinite numbers, right? So you say linspace is equal to np dot linspace, right? np dot linspace. You mention from 0 to 10, you want to have 10 numbers, right? And when you will create linspace, you will see that these are the numbers are there which have been created, right? These are the numbers which have been created, right? 9 numbers. Now I say 100 numbers I want. Evenly spaced 100 numbers, right? Evenly spaced 100 numbers. How are they even? You can simply subtract one number from another and the difference for all the numbers will be exactly the same. 0.010101. Subtract any two numbers, it will be 0.010101, right? Where do we need this? We need this to plot the axes, right? When you will plot graphs, you will need axis. Between this interval, you need 5 values. That works like this, okay? Suppose you want from 0 to 10, 5 different values, right? You will have 5 different values like this, right? Between the gap of 0.5, right? If I say 1 to 10, you will have values like this, right? Like this. Clear? 100 values like this. Yeah. Clear, guys? How do we use linspace? Suppose you want from 0 to 10, interval from 0 to 10, and 10 will be included, 0 will not be included, right? We'll start from 1. So I go to 1, it will be from 1. Why is 0 not included then? Yeah, 0 is included, right? 0 is also included and 10 is also included. 100 numbers between them, right? Clear? This is what linspace is. Now, guys, now suppose you Logeshwaran, linspace is basically used if you want to create n numbers between the range of numbers, right? Between 0 to 1, right? Suppose between 0 to 1, you are trying to plot a graph, okay? And your values are 0 0.2, 0 0.3, 0 0.6, right? And you want to draw a graph. So you will have to mark the axis, right? The x-axis and the y-axis. So you can use linspace there. And what will it do? It will take the range, it will take the interval in between. You want to add the equal space numbers. And then the third argument here will be that how many numbers do you want between them? So this syntax tells you that from 0 to 1, give me 100 numbers. How are these numbers? Equally spaced numbers, equally spaced numbers, right? So when you will execute this, you will see that there are 100 numbers which have been generated, right? 100 numbers, and all the numbers are equidistant from each other because difference of every single number from the next number is 0.010101. Yep, that's what it does, right? Now, guys, now suppose we want to generate random numbers, right? We want to generate random numbers, right? Now we are interested in generating random numbers. So we have something called as random dot random, right? What will it do? Random dot random will generate random float numbers between 0 to 1. Random float numbers between 0 to 1. How will this happen? You will say rand underscore rand is equal to np dot random, and inside you will mention what is the dimension that you seek. Suppose I want 6 cross 6. So when you will check this, you will have all numbers for 6 cross 6 dimension, right? 6 cross 6 matrix, right? Now, every time you rerun this, the numbers will change because all of these are random numbers, right? All of these are random numbers. Now I say 100 multiplied by rand underscore rand, you will see all of them, all these numbers will be multiplied by 100, right? All of them in one shot. Now, just like this, we can also create random integers, right? How will we create random integers, guys? I say rand int underscore rand int is equal to np dot random dot rand int, right? And here you will specify that what is the range of numbers you want from. So I say between 20 to 25. I need random numbers and then I want it from in a 3x3 format, right? And now when you will check your random, you will get random numbers generated like this. Okay, random numbers generated like this. Right? If you say 3x3x3, you will get a 3x3x3 matrix. Even if you will only say 3, you will get a 1D. Right, guys? You can change the dimension. So this is the range from which you want to choose the random numbers, and this is the dimension you want this matrix or vector to be in. Now, guys, we'll move on to the next part, which is basically properties. And again, there are a lot of operations. You'll have to see it yourself, right? Properties and attributes of NumPy arrays, right? Property and attributes of NumPy arrays. Okay. Now, guys, the first one in this scheme of things is shape of array, right? Shape of array. What is shape of array? It tells you the dimensions of the array stored in a tuple, right? For example, I say ARR 0, right? ARR 1, ARR 2, ARR 3, right? And then I say print this dot shape, right? Like this. And you will see that it will give you the shape of each array, right? 0D, 1D, 2D, and 3D, right, people? Shape of the array. Please try it out. We have used it 1 or 2 times, but this is what shape of array actually means. Second is, people, ndim, right? Is ndim, right? Ndim of array, right? It tells you the rank of the array, whether it's 1-dimensional, 2-dimensional, 0-dimensional, 3-dimensional, 4-dimensional. So again, I will do the same thing. Right, I'll say ndim, and you will see it will give you 0, 1, 2, 3. 0 dimension, 0 rank, 1 rank, 2 rank, and 3 rank. And it can go all the way up to n rank. Right. Before this, I should have also printed these arrays. Right, these are the arrays. Yep. These are the arrays which we have, and these are the subsequent things, right? Rank of the array. Then, guys, the third thing is the size of array, right? It tells you the number of elements inside. How many elements do we have inside this array? In ARR1, how many elements do we have? 1, 2, 3, 4, 5, 6, 7. How many elements do we have in this 2x2 AR2? 1, 2, 3, 4, 5, 6, 7, 8, 9, which is rows multiplied by columns, 3 multiplied by 3, right? And how many elements do we have in this 3D? Which is 2 multiplied by 3 multiplied by 3, which is 18, right? So now, when you copy this, right, you can use this and say size, right? So it will say 1, 7, 9, 18. Yep. Fourth is people. The D type of array tells you the data type of the array, right? And I've told you we place only homogeneous data in array, right? What will happen if we don't do this? I will show that to you also, right? So we do this, right? And we say D type, and you will see in 64, all of them are integers, right? All of them are integers. That's the reason we are getting in 64, right? Suppose I create a new array, arr underscore new, right? Let me say head, right? Heterogeneous, and I say it is like np dot array. Let's say like this. Right, like this. Now, people, when you will check arr dot d type, you will see it will give you float. Just because of one floating point number inside this entire array, it gets converted to float. Right? Between all the integers, if you put one float, then it will be taking float directly. Right? Now, let me just copy this and let's say heterogeneous 1, and let me add another value which is string and say Raghav. Right? And when you will execute this, it will give you U32. U32 here is representing strings, right? It is all called as objects, right? These are all string values, right? So precedence is strings, greatest, then float, and then your integers, right? If you place the heterogeneous data inside the numpy array, right? You only need to put homogeneous data in the array. Now, fifth is the item size of array, right? What is item size? It gives you the byte occupied by each element of an array, right? Because we assume that elements will be homogeneous, it will give you the byte occupied by each element of the array, only one element, okay? So how will it happen? So let's say arr 0, or let's say arr 1 dot item size, right? And you will get 8, right? So why 8? Because each data point, right? Each data point is occupying, the result is 8 bytes. Let me put this here. Right, 8 bytes, because each element in ARR1 is occupying 64 bits, which are equivalent to 8 bytes, right? 1 byte is equal to 8 bits. So 64 bits will be equal to 8 bytes, right? That is how it is giving you the result. Now, if you are interested in knowing the entire bytes, right? Entire bytes, then you say n bytes will give you the total bytes occupied by the elements of the array, right? You say print arr1 dot n bytes, right? And write bytes. It will be 56 bytes, right? Why? Because how many elements do we have in our arr1? 1, 2, 3, 4, 5, 6, 7, right? 7 8s are 56, right? 56 total bytes are being occupied with by arr1. Now, guys, the seventh one is as type, right? In array. This will help you change the data type of the array, right? Change the data type of the array. Suppose I have arr1 dot d type, which is so I say print d type, right? This is int64, right? And now what I do is I say print wait, let me give you a structured way. Print arr1, right? Let me say array arr1 right? D type of array. Now arr1 is equal to arr1 dot as type, right? Dot as type. And let's say I want to convert this in np dot, right? np dot int 32, right? I want to convert this in arr int 32, right? When I do this, and now when I will copy these same things, you will see for yourself, right? Now the D type was int 64 and now the D type is int 32, right? If I want, I can do this conversion in float also, float 64, right? And then I will just copy this and I will paste it here, right? And now you will see now the floating point has been activated, right? It has been now activated. We can go till int 8, right? I can go to 16, right? And I can do this. I can go to int 8 also. Yep, like this. Int 8 also. 64, 32. So first one has to be, yeah, 32 load this. Whatever, right? Like this. Okay. You can convert this. Also, people, this is later on conversion. You can define the data type of the array while creation time also. How would you do that? Suppose you are creating arr11 and you say np dot array, right? And suppose you take it from a list and then you just put a comma and say d type. So what will be the default data type here, people? If I just do this, if I just execute this, what will be the default data type? Int 64 is the default, isn't it? But now suppose I want to change it right here. I say data type is equal to float 32, right? Sorry, float 64. np dot, sorry, my bad. Float 64, right? And I say arr11 and this will be float 64. If you want float 32, it will also become float 32, right? Right here, while you define. Instead of using as type, you can do it right here. right? These things will come in very handy, people, because you will have to save memory, because when your data becomes very, very big, you will be always in a crunch for memory. Like this, you want integers, then integers will be like this, random.randint, like this. Suppose you want to generate 0 to 6, right? And suppose you want to generate, say, 100 numbers, like this, 0 to 6, the scores 1 to 6, like this, randomly, right? Suppose you want to generate 100 scores for 5 different batsmen randomly. It will be like this: batsman number 1, batsman number 2, batsman number 3, 4, and 5th, right? Yep. Understand the data, guys. Now it's the time to understand the data. Yep. Now, guys, we have methods in NumPy arrays, right? Methods in NumPy arrays. So what are these methods now? The first method we have to learn is called as reshape, right? Reshape. Yeah, so reshape is you can use this to create a new shape of the array. Very, very powerful, guys. Very powerful. One of the most powerful methods in NumPy is the reshape, right? And how do we use reshape? Suppose we have a 1D array of 20 elements, right? Now to reshape it, we need to find the factors, right? Factors of 20. They are what? 1, 20, 4, 5, 2, 10, right? These are the factors. These are the factors. Now see what will I do, right? Now see what will I do. Let me create a, say, random array, right? Random array. I say random underscore arr is equal to np.random.randint, right? And let me say I want to create it from 1 to 50, right? And I want it to be having 20 elements, right? So I say random.arr. So you will have random values inside this, right? Random 20 values. Now see. Now reshape. First, I will reshape in 1 cross 20, right? 1 comma 20. How will I do that? You just have to write print arr, sorry, random underscore arr dot reshape, and you just pass in the dimension. I say 1 comma 20, right? And when you will do this, you will see it is coming now in 1 comma 20 format, right? So let me just also write print right 2D 1 comma 20, right? And now what I'll do is I'll copy this and I will paste this and say 20 comma 1, right? You will see it will be like this 20 comma 1 immediately with reshape, right? Let me copy this. Let me say 2D. I'm still at 2D. Let me say 2 comma 10, right? And you will see this is 2 comma 10. Now I can reshape it in 10 comma 2, right? 10 comma 2, right? Then I can reshape the same thing in 4 comma 5, and I can reshape this in 5, 4, right? Like this. Guys, are you able to see the power? One dimension, I'm able to create 2 dimensions. And now I will take it a step further and I will write it in 3 dimensions, right? How will I write it in 3 dimensions? Let me say this 1, 2, 10, right? This will also be 3 dimensions. 2, 2, 5. Let me say this. And now you will see I can have this in 3 dimensions, right? Yep. I can also say in 3 dimensions like this. I want to have 5 layers with 2 rows and 2 columns, right? So you will have it like this also, right? So this is how we can reshape the array. Very powerful, very, very powerful, right? Very, very powerful, right? And you can take this and say print random dot this, and you can say print dot shape, right? So this was the first one. Yep, like this. Also, people, if you want to visualize, we can also go this route. We can have 10, 2, 1, right? It will look like this, right? 10 layers, 10 layers you can have, right? 10 layers you can have. Great. Now, second method which we have to learn is called as transpose, right? Transpose method, right? What does that do? It interchanges the dimensions like rows and columns, right? Yes, absolutely, right? Suppose you have a matrix, right, which is 22, 33, 44, 55, 66, 77, right? This is A. So now when you will A transpose it, right, the dimension right now, the shape right now is 3, 2. Now this will become 2, 3. And how this will happen? Rows will now become columns and columns will now become rows, right? So let's make column the rows, right? Sorry, columns the rows. It will be 22, 44, 66, 33, 55, 77, right? So people, in transpose, no information is lost. It is just a change in the view, right? Which is happening, right? 22, 44, 66, 33, 55, 77. Why do we need transposition? Suppose we have two matrices. This is 11th class mathematics, right? One has a dimension of n cross m, and the second has dimension of a cross b. If you want to multiply these two matrices, say m1 and m2, right? There needs to be a satisfaction of condition. M should be equal to A, right? M should be equal to A, right? M should be equal to A. This should be equal to this. And the resultant vector, the resultant matrix which you will get will be of n cross B dimension, right? So oftentimes, suppose this is n cross m. This is n cross m, right? M cross n. And you know that m is equal to A. So what will you do? You will transpose this matrix, right? You will transpose this matrix. Then it will become n cross m, and then m can be equivalent to A, right? For example, what I'm saying, we have one matrix which is 2 cross 3, and this matrix is 2 cross 5, right? So can you multiply these matrix, people? Is 3 equal to 2? The answer is no, right? The answer is no. So what will you do? You will just transpose this, and this will become 3 cross 2, and this is 2 cross 5, and now you can multiply this and the resultant will become 3 cross 5 matrix, right? So for operations like these, we need transposition, right? So how do we transpose it? How do we transpose it? So let's say again, ARR2, right? This is ARR2 and I want to transpose it. So I say ARR2 underscore T is equal to NP dot transpose. Sorry, ARR2 dot transpose, right? And now when you will see ARR2 underscore T, you will see rows and columns have interchanged, right? Rows and columns have interchanged with each other. Or let me give you one more example. If this is not clear, let me pick up this again. Right now I say dot reshape into say 2 cross 10, right? So this is 2 cross 10. And now when you want to transpose this, so I'll say this underscore T is equal to this dot transpose TRANS, and you can check this now and it will be this. Sorry guys, so this is going to be, it will be like this, right? Transposed. And now if you want to see this, this was the original shape, right? Rows and columns have now been interchanged, transposed with each other. Now guys, the third method which is there with us is called as flatten, right? It is called as flatten, right? What does flatten do? It reduces the dimension to one dimension, right? Any dimension you have, it reduces it to one dimension. For example, I have this, right? And now when I say this dot underscore F, this will become this dot flatten. And when you will check this up, you will see that it has now become one dimension. No matter how many dimensions you have, it will become one dimension, right? Let me take this again to show you one more example, right? And here I say dot reshape into 5 cross 2 cross 2, right? I do this. My random ARR is this, right? It has 5 layers, 2 rows and 2 columns, right? So now I say this underscore flatten is equal to this dot flatten. And if you will check it now again, you will see it has now flattened it up. Yep. Now, why do we need this? We need this for a lot of statistical operations. We need this to feed the data into the algorithms, right? As we will move forward, you will understand the use of flattening, right? Now, guys, moving on, and as discussed, let me now show you the power of NumPy, right? NumPy over lists and other data types, right? I will not take a lot of examples. Just a second, guys. Yeah. Okay. Now, guys, I told you that lists take up much more memory as compared to NumPy arrays, right? And I'm going to prove this to you. right? Now, let me create a random sequence of random numbers using range in Python, right? And say I create range of 10,000 numbers, right? Range of 10,000 numbers. So what will this give me? This will give me numbers from 0 to 9999, right? Continuous numbers, right? So this is range. I will use a range in NumPy to create a similar series of numbers, right? So let's say array is equal to np dot arange, right? Same thing, same done by both, right? I've shown you above also. Now let me import sys library, right? Sys package, and I will use something called as get size of, right? Get size of. What does this do? Get size of. It's a method which calculates the bytes occupied by a single element in vanilla Python. What is vanilla Python? It is the traditional Python, right? Vanilla Python. So let me just show that to you. I'll use this and I will say print. Now guys, if I get size of any random number from this range, right? Any random number, say I get size of 5, right? And I then multiply that bytes with the length of random, right? With the length of random, this ran, right? Right? With the length of random, do you think I will get the bytes for the entire data structure? What am I saying is, suppose I used range 5. So what will this give me? 0, 1, 2, 3, 4, right? This will be the output. So now I say get size of, say I say 2, right? So suppose 2 is x, and then I multiply this with the length of this series, which is 5. So do you think I will get 5x, which will represent the number of bytes occupied by the entire data type? Anything randomly, any random number. This can be 3, right? Why not, Hari? Why not? All of these are integers. So integers, all of 64 bits, assuming. So if you calculate the size of this, and if you multiply with the total number of numbers, you will get the total size, isn't it? Huh? Index is in Tavern? No. It's not about that. It's about the element, right? Homogeneous elements inside this. I am saying when you use range 5, what is going to be the output? 0, 1, 2, 3, 4, right? Now all these are elements of range, right? All of them are elements of range, right? Now I'm saying if I fetch the size of one element and multiply it with the length of the entire range, will I get the bytes occupied by the entire range? For example, if I do this, right? If I do this, this is 28, right? 28 bytes, people, 28 bytes are occupied by one element of range, right? One element of range, right? Now, if I just, I'm just saying, if I multiply to find how many numbers range has, how many numbers range has equal to 10,000, right? So total memory occupied will be how much? It will be 28 multiplied by 10,000, which will be equal to 28,000. Yeah, and how will you find this? You will say print this multiplied by length of RAM, right? 28,000 bytes. Clear now? Yes. Now this is for the range. Now let me use another thing. So how will you calculate the length of this array? What property and attribute will you use, people? N bytes, right? N bytes will give you total bytes occupied by the elements of the array, right? We will use N bytes here. So I come back down and I say using N bytes for arrays, right? And you will see what the result comes. Print array dot N bytes, right? And I say bytes. Are you ready to see the result? Do you see what has happened? How many bytes this was taking? It was taking 28,000 bytes. How many bytes this is taking? This is taking 80,000 bytes. This was taking 2,80,000. This is taking 80,000. 2 lakh extra bytes of memory is taken by range. RAN is range. Yep. And if I just go to million numbers, right? Million numbers in both. See the difference it becomes, right? This is now 28 million bytes it is taking, and it is taking 8 million bytes. 20 million extra bytes are occupied, right? Now, people, do you believe me? Yep, that NumPys are way more efficient in memory management as compared to the traditional data types of Python. Yes? Okay, that's the first part. Now, second is, people, performance, right? Performance. So what I'm going to do is, I am going to import time, right? It's a module in Python, right? Suppose I say x is equal to range this much, right? Okay. And then I have y is equal to range, say, this to this, right? Both of them will have equal amount of numbers, same numbers, both of them will have, right? This will have, say, 1, 2, 3, 1, 2, 3, 10 million values, 10 million values. This will also have 10 million values, right? Both of them will have 10 million values. Now, what I'm trying to do is I want to add them up, right? Bit by bit, I want to add them up, right? I want to add first element of this to first element of this, second of this to second of this, third of this to third of this, like this. Okay, I want to do this. Now, what I'll do is I will run a counter, right? I will run a counter, which is the start time, right? And this is given by time dot time, right? Which will give you this will give you the current time, right? After this, I will run the operation. I will say C is equal to x plus y for x comma y in zip x comma y, right? In zip x comma y, right? Add x plus y bit by bit, element by element for x and y in zip. Zip is a function, right? Which allows you to do this operation sequentially, right? Sequentially, right? Add the elements of x and y element by element, right? Element by element, right? Element by element, right? And then I am going to print, right? So start time will start, and now I will say time dot time, which is now the end time, minus start time. So this will give me the time taken for execution, isn't it, guys? Will give me delta of time, which is equal to time taken for operation, seconds, right? These many seconds will be taken, right? So let me run this, and it takes around, say, 4.3 seconds, right, to do this, right? 4.3 seconds. Now, guys, see what happens. You had to write this complex syntax in the traditional Python. Now, let me show this on arrays, right? What will happen on arrays? I will say A is equal to np dot arrange, right? And inside arrange, I will pass the same values, what I've taken above, right? And I will say B is equal to np dot arrange, and I will pass the same values inside, right? Exactly the same. Now, what I'll do is I will say same thing, right? Just I will change the execution of C, will now simply become people A plus B. What is simple? This or this? This or this? 2, right? Do you see the power? If not, I will show this to you again, right, later on, and let me run this. And you see the difference. Now, let me just increase a couple of zeros, right? A couple of zeros. 2 zeros I am increasing in both the use cases. It is going on and on, right? Let's see how much time it will take to add, say, 2 million, 1 billion numbers. 1 billion numbers I have asked my system to add, and I want to see how much time it takes. Running. Yeah, kernel has died. Kernel has died, people. I'll have to restart, right? I will have to import NumPy as NP. So let me just remove 1 0 from both. It is taking 4 seconds, removing 1 0 from here also, right? And when I do this, it takes 1 second. Do you see, guys? What is the difference in performance also, right? For both of these, yep. And if you didn't understand this, let me give you an example. Range 5, this is 5 to 10, right? And this is basically adding elements, right? 5, 7, 9, 11, 13, right? So this will be, what will be the output of this? This will be 0, 1, 2, 3, 4. And this will be output what? 5, 6, 7, 8, 9, right? So 0 plus 5, 5, 6 plus 1, 7, 7 plus 2, 9, 8 plus 3, 11, 9 plus 4, 13. And the same thing, if I do here, then what will happen? I say 5, and 10, right? And I say C is equal to A plus B, and I say C. Same thing you get here, right? We can move on, right? The next bit, guys, which we have to understand, is called as the indexing in NumPy arrays, right? Indexing in NumPy arrays, right? How do we index the elements, right? How do we index the elements? Indexing in NumPy arrays, right? Indexing in NumPy arrays. So again, you know indexing from basic Python. So let's start with 1D. For 1D arrays, right? I will use ARR1. Yeah, this is ARR1 now, right? This is ARR1. Okay. Now, people, what I want to do is, I want to fetch, right? I want to fetch, right? You can slice and dice. Let's say dice 33, right? So again, as per our normal indexing of list, what is 33? What is the index of 33, people? It's 2. So you will say the same thing, print, right? ARR1 squared bracket 2, and you will get 33 for yourself, right? If you wish to slice, same thing, right? 33 to say 66. What is the index? 33 is 2, 2, which one? 3, 4, 5, and 6, right? You will write 3 to 6, not 5, hurry. 5 is not included, remember? Say print ARR1, 2 is to 6, and you will get 33, 44, 55, 66. Right? Simple indexing. Please try it out. Please try it out. And if you want, you can have this code also. You can write this code. You will always have clarity that why do we use it. Moving on, people. Moving on. Let's see indexing in a 2D array, right? And before I explain this to you, let me take you here, right? So a 2D array will be what? Right? This is a 2D array. It has 3 rows and 3 columns, right? Rows, columns. So now for rows, indexing will start from 0. So if you have to fetch this particular row, right? So what will be the index? It will be row 0. If you have to fetch this particular row, the index will be 1. And if you have to fetch this particular row, the index will be 2. Similarly for column, if you have to fetch this particular column, right? You will have column is equal to 0. This particular column equal to 1. This particular column equal to 2, right? Indexing will start from -1 again, right? 0, 1, 2. So let me just show that to you, right? Let's say I call ARR2. This is my ARR2. Now, indexing first row, right? How will I do that? I will say print ARR2, and I will write how? How will I write this? I will write row 0, right? Row 0. So what will this give me? This will give me this, right? The syntax is row space column, right? So now if you just pass 1, it will give you only rows, right? Row 1, row 2, row 3, right? Similarly, if you want to create it for columns, right? What will you say? Sorry. For columns, it was zero. Column 1, column 2, column 3, right? Right? So what is my column 1? 76, 89, 98. 76, 89, 98, right? And if you want column 2, sorry. If you want column 2, this is the column 2 and this is column 3, right guys? 90, 99, 99. Independently. Now, if I ask you to fetch me a particular element, right? Say I want you to fetch me 78, right? How will you fetch 78? You will say print ARR2. What is the row for 78? Which row does it belong to? 0, 1, 2. To which row 78 belongs? 1 row. Which column it belongs to? 0, 1, 2. 1. Hari, check again whether it belongs to 0 column, first column or second column. Right? And you will get, 0, 1. So this is 2. Right? 78. Right? Second row, first column. Right? Second row, first column. How to define it as in? Right? This is your matrix, right? Now, what are the index positions for this? This row is 0 row, first row, second row. This is your 0th column, first column, second column. Yeah. Yes, no, maybe. Are we understanding this? This much is clear. The indexing of rows and columns. Now, if you have two, so the syntax is, say this is matrix A. So you will say A, in this A matrix, you will write row, comma, column, right? Suppose I want to access only 0th row. So there will be no column. So what will you get? Row number 0, right? Row number 0, and you will just put it like this, or you can put a comma and put colon. Colon means what? Take everything. So I want all 3 columns together, 0 row and all 3 columns. So this will be your, let me show that to you. Right? See this? 0th row and all the columns. So what will be your answer? 76, 88, 90, right? Then if you want to access the second row, 89, 90, 99, 89, 90, 99, 1 and like this. Clear? Now similarly for columns, what will happen? You will take all the rows, comma, which column do you want? If you say 2, what will be the result for this? What numbers will you get for this? Colon, comma, 2. You will get 33, 66, 99. Now, coming to the element, right? Suppose now you want to fetch 55, right? So what will you write? You will write which row does it belong to? Follow this syntax. It belongs to the first row. Which column does it belong to? First column. So what will you get? 55. Come to this example. Now you want 78 in this particular array or matrix, right? Where is 78? Which row does it belong to? Is it first row? Check carefully. 0th row, first row, second row. Yeah. So I put 2 here. Now which column does it belong to? First column, second column, 0th column, first column, second column. Belongs to the first column. So I put 1 here. So when you put this syntax, you will get 78. Clear? Now, the third thing is slicing through the array, right? Now, for this, I want 90, 99, 78, 99. That means what? I want this, 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 and this. Let me take you to the PPT first. Now, what I'm asking you to fetch me? I'm asking you to fetch me these 4 numbers, right? These 4 numbers. So here, what will you write? Which rows are included in this, people? Which rows are included in this? Row 1 to all, right? 1 to all. Yeah, not 2, 1 to all, right? And you leave everything like this. If you have the last row, you leave it empty after the colon, comma. Which columns do you want for this? 1 and 2, right? And when these will intersect, you will get this area, you will get this shaded area, green shaded area. So I will say, I need from column 1 to all the columns, right? So what will this fetch you? What will this fetch you? This will fetch you 44, 55, 66, and 77, 88, 99, right? What will this fetch you? This will fetch you 22, 55, 88, 33, 66, 99. What are the commonalities between both of these? Access, both of these slices, what are the commonalities? It is only this much, right? 55, 66, 88, 99, right? So do you think you will get your result? Yeah, let's check it here, right? I say print ARR2, right? And this I say I need row 0, sorry, row 1 to empty and then column 1 empty, and you will get 90, 99, 78, 90. Indexing. Yeah. Now guys, let's check it for 3 dimensions, right? 3D. I say ARR3, right? This is my ARR3, right? So let me just put an example here. Suppose my arrays are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, right? This is my first. Then behind this, I have another matrix, which is 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5, 6, 6, 6, 7, 7, 7, 8, 8, 8, 9, 9, 9, right? And in my third one, I have 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, 4, 4, 4, 4, 5, 5, 5, 5, 6, 6, 6, 6, 7, 8, 8, 8, 8, 9, 9, 9. Is it qualifying for a 3D array? Can you access anything on this particular array if given a chance separately, like this one? Now people, if you want to move between layers, right? If you want to move between layers, do you think I have told you one particular access, which is what? Which is the layers. So what number will be given to this layer? Layer number 0, layer number 1, and layer number 2. So now if you have to access this 555, which layer you will go to first? You will go to first layer. Then which row will you go to? You will go to first row and first column. So if you pass this syntax, what will you get? You will get 555, right? Problem solved. The only bottleneck was the layers part, and you have additional parameter or argument for this layer. So if I come back to my example, and if you have to access this 555, right? How will you do that? I say print ARR2, ARR3, right? And this I say, and in this I say what? I have to access this 555. Which layer number is this? This is layer number 0, right? This is layer number 0, and this is layer number 1. So I say layer number 1. Which row is this? In this particular layer, it is layer number, sorry, it is row number 1 and column number 1. And when you do this, you will get 5 by 5. Right? If you want 999, what you will do? You will change this to 2, 2. Right? If you want 777, or let's say if you want 98, what will you do? For 98, layer number 0, row number 2, column number 0. And you will get this 98. Clear, guys? Yep. Layer, row, column. In the same way, you will slice it. Right? You will slice it. Yep. Right? I'll write the syntax so that you don't get confused. It is array, squared bracket, layer, row, column. Right? Layer, row, column. Right? This is the syntax. Perfect. Right? Great. We can also perform some operations, right? Plus, minus, multiplication, division between two arrays very, very easily, right? It should not pose any problem to us, right? We can do all the operations which we want to, right, between two arrays, right? For example, right, you have, right, operations on arrays. So let's say, let's see as a list, right? List. So we have list is equal to 1, 2, 3, 4, 5, right? Now suppose you want to square each element of the list, right? What will you do? You will say sq underscore l is equal to x to the power of 2 for x in L, right? And then you will say print sq underscore L and you will get the squared of list, right? Original list, squared list. Now, in array, what will happen? Suppose I say A1 is equal to np dot array and L, I create the same array out of this list. I say print original array, right? I say A1, right? This is my original array, same as this. Now, I want to square it. Square the elements of arrays. Very, very simple. Nothing you require. You just say sq underscore A1 is equal to sq underscore A1 is equal to A1 to the power of 2, right? A1 to the power of 2, right? And then you print the right, you get the squared array. Suppose you want to find the mean of numbers using list, right? So what will you do? You will say mean is equal to sum of L, right? List divided by length of list, right? And you will get the mean, right? Which is 3 for this one, right? This original list. Now, let me show you in arrays, right? How will you do this? You will say mean is equal to np dot mean and you will just pass A1, right? And when you will check mean, you will get 3.2, right? Nothing like this, direct, right? Direct like this, right? I've already showed you add, I've already showed you square, and then I believe you can understand that what all operations are possible using the arrays, right? Leveraging the power of arrays, right? Also, guys, in the arrays, right? In the arrays, what you can do is you can perform some string operations, right? Very powerful string operations, right? So, for example, let's say I have a array, right? I have an array of names of people, right? So I say names is equal to np dot array, right? And I say Raghav. Then I say Dinesh, right? And then I say Madhu, right? These three names I had, right? So you can check the names. They will be like in the array, right? And the data type will be U6, which is a representation of strings, right? Now, guys, suppose you want to capitalize. You wish to capitalize the names, right, of people. What will you do? You will say print me np dot char, right? Np dot char dot capitalize, right? Capitalize. And inside this, you will pass names and you will see all the names have been capitalized, right? You see this? R has been capitalized, D has been capitalized, M has been capitalized, right? You can convert them into upper if you want. Print np.char.upper names, and you will have all of them in caps lock. You can say print np.char.lower, you will have them in lower, right? You can put the title, right? Suppose I say title, title is equal to np.array, and I say Raghav Goyal, right? Then I say Dinesh Senapati, right? And I say Madhu Verma, right? I say these three things. Now, if I say print np.char.title, right? And I say title, you will see that all the words will be in capitalized mode. Raghav Goyal, D and S of Dinesh Senapati, M and V of Madhu Verma are now capitalized. I can also replace something if I wish to. Suppose I want to replace Madhu with say Surbhi, right? I will say print, right? np dot char dot replace, right? And you will say where you want to replace. I say title, and in this I want to replace Madhu with Surbhi, right? And you will say it will be Surbhi underscore Surbhi Varma, right? Madhu has been replaced with Surbhi, right? Right? If you want to calculate the characters of strings, right? You can do that. Print np.char dot str underscore length of titles, and you will get 11 characters are there in here, 15 are there here, and 11 are here in this particular thing, right? You can do much more powerful things also. Let me show you one complex function, right? Suppose I have f name is equal to np dot array, right? And we have Raghav, Dinesh, Madhu, right? And we have L underscore name array, Goyal, Ganapati, Verma, right? We have these two things. Now I can create a new array, full underscore name, by simply, right? By simply saying np dot char dot add, right? And I say f name, right? Comma L underscore name, right? Plus yep, repeat it, full name. Yeah, Raghav Goel. I just was trying to add a space in between. Anyway, right? We can do that. Right? You can also people search in arrays, right? Very powerful again. Search in arrays using where, right? Right? You can say, suppose A2 is equal to np dot array, right? And I say 1 1 2 2 3 3 4 4 5 5 6 6, right? And now you have to say A is equal to np dot where, right? And in this you say A2 greater than 20, right? And when you will check A, it's giving me the index. Why is it giving me the index? Why is it giving me the index? Does it always return index? One more thing is you can find an letter, right? Through a letter. You can find an element through a letter. Guys, these are all some tricks which you should know because you will be dealing with data and you need to pull data, right? You need to pull data a lot, right? Based on conditions and based on things. Suppose you want to find out the names which have G in them, right? Or RA in them. So how will you do this? I will say print, right? And I will say np dot char dot find, right? And I will say find this inside full underscore names, right? And find me RA, right? RA. True, false, false. Right? It returns true because it has found it here, right? So I don't want to tell you indexing through this, but anyway, you should know this. Just assume this that I am telling you to write this, okay? Because this is much easier when we will go to pandas, right? Just write it as a syntax, okay? Greater than equal to 0. I hope this is clear.
So let's start with the data science interview questions and answers. And the number one problem we will be facing is real world problem solving. And the question one is handling missing data in predictive modeling. So imagine you have given a data set where 30% of the data for a key predictive variable is missing. This variable is crucial for a predictive model. How would you handle this situation to ensure the integrity and performance of your model? And please describe your approach step by step. So starting with the answer, you can start with handling missing dataset is a common challenge in data science, and it's important to address it carefully to maintain the accuracy of your model. And here's how you could approach this situation. The number one point could be identify the missing data. So first you need to understand where the missing values are in your dataset. You can do this by using a simple code in Python with libraries like Pandas. For example, you can use the data.isNull.sum function that will show you the count of missing values in each column. Then you can analyze the pattern, determine if there's a pattern to the missing data. Is it random or is it missing for a reason? This can affect your approach. If the data is missing at random, the methods you use might be different than if the data is missing systematically. So choosing a method for imputation. Let's see the next method, that is choosing a method for imputation. So if the missing data is numeric, you might replace missing values with the mean or median of that column. This is simple and effective, but can be used primarily when the data is missing completely at random. Then comes model-based imputation. Sometimes you can use other variables in the data to predict missing values using a regression model. This can be more accurate but is also more complex. Then we'll use the k nearest neighbors can algorithm. But before that, we have a code snippet here that could be used for the implementation of imputation. You could use Python or R. And now moving on, we'll see the k nearest neighbors algorithm. So this method predicts the missing values based on how closely related the data points are to each other. So after imputation, it's crucial to check how your changes have affected the overall dataset and model performance. Sometimes filling in too many missing values can introduce bias. And then we have visualization. To help understand before and after the imputation, you could visualize the distribution of the variable using histograms or box plots. This helps in seeing how the imputation has changed the statistical properties of the data. And by following these steps, you can handle missing data thoughtfully and maintain the integrity of your predictive model. Now moving to the question number 2, that is based on evaluating model overfitting. So the question is, you have developed a predictive model, but you suspect it might be overfitting the training data. How would you test and address the issue? Please explain your steps and the techniques you would use. So you could start the answer by explaining what is overfitting. So overfitting is a common problem where model performs well on training data but poorly on unseen data, indicating it's too closely fitted to the training data's specific details and noise. So now we'll see a step-by-step guide on how to address this. The number one step is cross-validation. So one effective way to test for overfitting is by using cross-validation technique. Cross-validation involves splitting your training data into multiple smaller sets, that is faults, and then training a model on some of these sets and validating it on the others. So this helps you understand if the model's good performance is consistent across different subsets of data. For example, in Python, you can use the cross_value_score function from sklearn.model_selection. So this is the code, and this is the code snippet of Python that you can use for the cross-validation. And here we are importing from sklearn, that is the module, and we are importing cross_val_score. And here we have used the cross_val_score function, and then we have printed the average cross-validation score. And the next step we will do is running cross-validation model. So this is your predictive model that you have already built using Scikit-learn. And here's the X train. These are the X input features of your training data, and Y train, these are the output labels of training data. So we are running cross-validation model here. This is your predictive model that you have already built using Scikit-learn. So X train here, that means these are the input features of your training data. And Y train here means these are the output labels of training data. And CV equal to 5. This parameter tests the function to split the data into 5 parts, that is faults, and the model is trained on 4 of these parts, and the remaining part is used for testing. So this process rotates until each part has been used for testing once. And the printing results, that is score.mean. So this calculates the average of the scores obtained from each cross-validation fault. This average score gives you an idea of how well your model is likely to perform on unseen data. A consistent score across different faults suggests your model is generalizing well rather than overfitting to the training data. So now moving to the next point, that is training versus validation error. So plot the training and validation errors as a function of training epochs or complexity of the model. A model that overfits will show a low error on training data and a high error on validation data as it trains further. Then we have pruning the model. If you confirm that the model is overfitting, consider simplifying it. This might mean reducing the number of parameters by selecting fewer features, using regularization techniques like lasso or ridge, or choosing a less complex model. After this step, we will move to regularization technique step. So these techniques add a penalty to the loss function used to train the model, which can discourage complex models that overfit. Then we have common methods that include L1, that is lasso, and L2, ridge regularization. And here's how you can add L2 regularization in Python. So this is the code snippet here. And what we have done here is we are creating the ridge model, and we have applied alpha equal to 1.0. So this parameter controls the strength of the regularization. A higher alpha value increases the regularization effect, which helps reduce model complexity and combat overfitting. The alpha value can be tuned to find the optimal balance between bias and variance. And now coming for the fitting the model. So model.fit, and in that we have X train and Y train that trains the ridge model on the training data. It adjusts the weight of the feature in X train to predict the Y train while also considering the regularization term. This helps prevent the model from fitting too closely to the noisy aspects of the training data. And then we are re-evaluating the model. After making adjustments, it's important to re-evaluate the model again using the same cross-validation technique to see if the issue of overfitting has improved. And then we have visualization. To help illustrate overfitting, you could create a plot showing the training and validation errors over the number of epochs or model complexity. So by using these techniques, You can identify if a model is overfitting and take steps to correct it, ensuring it performs well not only on the training data but also on new unseen data. So now moving to the next question, that is question number 3, and it is based on real-time data stream processing. And the question is, you are tasked with building a model to predict stock prices in real time. The data comes in every second and you need to update your predictions accordingly. Describe how you would set up your system to handle this type of data effectively, and what tools and techniques would you use and why. So you could start answering this question with handling real-time data. So handling real-time data, especially for something as volatile and fast-paced as stock prices, requires a robust system that can process and analyze data quickly and accurately. So here's how you could approach this. We'll set up such a system and we'll have some steps. So starting with the steps. So the first step is choosing the right tools. The right tool would be Apache Kafka. So this is a popular tool for handling real-time data that streams because it allows you to publish and subscribe to streams of records, that is data. And it can handle high throughput with low latency. Kafka acts as a buffer and manages the flow of data, ensuring that your system doesn't get overwhelmed. And you can also use Apache Spark. Especially Spark streaming is excellent for processing the data. It can process data in real time and perform complex operations like windowing, grouping data into chunks of a specified time period, and aggregating, that is summarizing data. So you can modify it and perform the predicting of stock prices. And then the step is data processing pipeline. And the first step comes here is ingestion. Data first enters the system, typically through Kafka, which collects data sent from the stock market. And then we do the processing. So Spark streaming takes over here. Here you can apply transformations and run your predictive models on the data. For example, you might calculate moving averages or other indicators that feed into your stock price prediction model. And then comes the output. Finally, the predictions are outputted. This could be to a dashboard for traders, an automated trading system, or even stored for further analysis. And then we develop the model. Now comes the model development. You would likely use a machine learning model that can update quickly and incorporate new data as it arrives. Models such as ARIMA for time series forecasting or more complex machine learning models like recurrent neural networks (RNNs) can be suitable. The model should be retrained or fine-tuned periodically with new data to ensure it stays accurate. Now we'll come to scalability and reliability. So ensure your system can scale as data volume increases. This might mean adding more servers or optimizing your data processing code. Implement monitoring to catch any issues early, like delays in data processing or model performance drops. And now we'll see the step, that is visualization and monitoring. Consider setting up a real-time dashboard that shows key metrics like prediction accuracy and processing time. This helps in quickly spotting when something goes wrong. By setting up your system with these tools and strategies, you can effectively handle the challenge of predicting stock prices in real time. So now we'll move to the next question, that is question number 4, and this will be based on scalable data analytics. So we have covered 2 questions that were a bit code-based questions, and now we'll see other questions that would be based on scalable data analytics, or they might be on different areas. And with the 13th question, we will start again with the coding ones. So moving with the question 4, that is based on scalable data analytics. And the question is, given a scenario where your organization suddenly needs to scale its data analysis capabilities due to an influx of data that would be 10 times the normal volume, how would you handle this situation to ensure your data analytics processes remain efficient and accurate? What technologies would you consider and what steps would you take? So you can start answering this question with, handling a sudden increase in data volume requires a strategic approach to scaling your analytics infrastructure without compromising on efficiency or accuracy. So we'll see some steps from that you could effectively manage this scenario. That you would start answering the interviewer that we can start by evaluating the current infrastructure's ability to handle increased loads. This includes assessing your databases, servers, and analytical tools to identify potential bottlenecks or limitations. Then you could move to next step, that would be choosing scalable technologies. To manage the increased data volume, consider leveraging cloud-based solutions such as Amazon Web Services, Google Cloud Platform, or Microsoft Azure. These platforms offer scalable resources which can be adjusted accordingly to the data load, ensuring you only pay for what you use. Integrate big data technologies like Apache Hadoop for distributed storage and Apache Spark for fast data processing. These tools are designed to handle massive volumes of data efficiently and can scale up to meet standard increased demands. Now we move to the next step, that would be optimizing data processing. So implement data partitioning and indexing strategies to improve the efficiency of data queries. This will help in managing large data sets by breaking them into smaller, manageable chunks and speeding up search operations. And use real-time data processing frameworks like Apache Kafka or Apache Flink, which can handle high throughput and provide timely insights from large data streams. And the next step would be automation and monitoring. Automate routine data processing tasks to reduce the manual effort and speed up the analysis. This can be done through scripting or using workflow automation tools. Set up comprehensive monitoring systems to track the performance of your data processes. Tools like Prometheus for system monitoring and Grafana for analytics and monitoring dashboards are useful here. They help ensure that the system is running smoothly and alert you to potential issues before they become critical. And the next step will be regular evaluation and scaling. Continuously evaluate the performance of analytics infrastructure. As your data grows, keep adjusting and scaling your resources to maintain optimal performance. Plan for periodic reviews of your technology stack and infrastructure to ensure they remain aligned with your data needs and organizational goals. By following these steps, you can ensure that your data analytics processes are prepared to handle sudden surges in data volume effectively, maintaining the integrity and speed of insights. So this was all for the question 4. Now moving to the question 5, and this is based on integrating machine learning models into production. And the question is, you have developed a machine learning model that performs well in testing environment. Now you need to integrate it into your production environment where it will be used in real-time applications. What steps would you take to ensure the successful deployment and operations of the model in production? So we'll start answering this by successfully deploying a machine learning model into production involves several critical steps to ensure it performs as well in real-time operations as it does in testing. So you would have a clear pathway to make the interviewer understand. We will start with the pathway with the first step, that would be model validation. So before moving anything into production, revalidate your model's performance using a separate validation dataset. This helps confirm that the model generalizes well to new, unseen data. The next step will be preparing the production environment. Ensure that the production environment is ready to handle the model. This includes setting up the necessary hardware and software, ensuring that it can handle the expected load, and that all dependencies are correctly installed and configured. Then the next step comes, that is model wrapping. Wrap your model in an API, that is application programming interface, making it accessible to other parts of your software infrastructure. Frameworks like Flask for Python can be used to create a simple web server that listens for data inputs and provides model outputs. Then comes the next step, that is deployment strategies. Consider using containerization tools like Docker, which can help encapsulate your model and its environment, ensuring that it works uniformly across different development and production settings. And then we'll use deployment strategies like blue-green deployment or canary releases to minimize downtime and reduce the risk of introducing a faulty model into production. And then comes the next step, that is monitoring and logging. Implement logging and monitoring to track the model's performance and health in real time. Tools like Prometheus for monitoring and ELK, Elasticsearch, Logstash, Kibana for logging help in quickly identifying and diagnosing issues in production. And then comes the next step, that is performance tuning. Monitor the model's performance over time. If the model's performance degrades, or if new data shows different patterns, you may need to retrain or fine-tune the model to maintain accuracy. And after this step, there's a step for feedback loop. Set a feedback loop where predictions and outcomes can be compared. This feedback is crucial for continuously improving the model and catching any drift in data or changes in external conditions that affect the model. And after this comes a last step, that is legal and compliance checks. Ensure all the data used by the model in production complies with privacy laws and regulations. This is crucial for maintaining trust and legality, especially when handling sensitive information. So by carefully planning and executing these steps, you can smoothly transition your machine learning model from a testing environment to a fully functional component of a production system. So this was all about the question number 5. Now moving to the question number 6, that would be based on data-driven decision making. And the question is, your company wants to shift towards more data-driven decision making. You have been tasked with developing a strategy to implement this. What steps would you take to ensure that the data at all levels of the organization is utilized effectively to make informed decisions? And what challenges might you face and how would you address them? So you can start answering this by implementing a data-driven decision-making strategy. that will require a comprehensive approach to ensure that reliable data is accessible and effectively used across all levels of the organization. And now we can develop and deploy this strategy, and similarly you could tell this strategy to the interviewer. So the number one step will be assessing current data infrastructure. Start by evaluating the existing data infrastructure to understand what data is available, how it is stored, and how it is currently used. This assessment will help identify gaps in data collection, storage, and access that need to be addressed. Now we'll move to the next step, that is developing a data governance framework. Implement a data governance framework that defines who can access data, how it can be used, and who is responsible for maintaining its quality. This framework ensures data integrity and security, which are critical for making reliable decisions. Now we'll move to the next step, that is training and empowerment. So train employees at all levels on the importance of data-driven decision making and provide them with the tools and knowledge necessary to analyze and interpret data. This might include training sessions, workshops, and ongoing support to ensure everyone can use data effectively. Now moving to the next step, that is implementing analytical tools. So deploy user-friendly analytical tools that can integrate seamlessly into the daily workflows of employees. Tools like Tableau, Microsoft Power BI, or even advanced Excel techniques can provide powerful data analysis capabilities without requiring extensive technical knowledge. After this, we'll move to the step that would be creating a centralized data platform. Develop a centralized data platform where all organizational data can be accessed and analyzed. This platform should be scalable and secure, providing a single source of truth for the organization. And then we have the promoting a data-driven culture. So foster a culture that values data-driven decision making. Encourage experimentation and learning from data-driven initiatives. Celebrate successes and learn from failures to continually improve the use of data-driven in decision making. And there would be some challenges and solutions for that. So one major challenge we know here is resistance to change, as some employees may prefer traditional decision-making methods. So address this by demonstrating the tangible benefits of data-driven decisions through pilot projects and success stories. So data silos can also hinder effective data use, promote cross-department collaboration, and integrate disparate data sources to overcome this challenge. After that, you can monitor and do continuous improvement. So by systematically implementing these steps, you can transform your organization into one that leverages data at all levels to make informed and effective decisions. And after answering in these steps, you could make the interviewer have a truth and a faith in you that you could make these models. Now move to the next question, that is question number 7, and that is based on handling large data set. And the question is, your project involves analyzing extremely large data sets, potentially exceeding terabytes in size. What strategies would you use to manage and analyze such large data sets effectively? Describe the tools and techniques you might employ. And you could start this with answering that working with large data sets, especially those in terabyte range, presents unique challenges in terms of storage, processing, and analysis. So we'll have a structured approach to handle these challenges effectively. We'll start with the data storage, that would be use distributed file systems. Consider using a distributed file systems like Hadoop Distributed File System, HDFS, or Amazon S3. These systems are designed to store vast amounts of data across many servers, offering high availability and fault tolerance. And then comes the next step, that is data processing. Leverage big data processing frameworks. Tools like Apache Spark are ideal for processing large data sets because they handle distributed computing effectively. Spark can perform data processing tasks much faster than traditional disk-based processing due to its in-memory computing capabilities. And next we could start with efficient data sampling. So there are many sampling techniques that we can use. So when the data set is too large to handle, even with powerful tools, consider using data sampling techniques to reduce the size to a manageable level without losing significant insights. Ensure that the sample represents the whole data set accurately. And then comes optimization of data queries. Indexing and partitioning. Optimize your data queries by implementing indexing and partitioning. This can drastically reduce the time it takes to perform queries by limiting the amounts of data scanned. And then we can do scalable analytics. And then we'll move to the next step, that is scalable analytics. And in that we could start with the parallel computing. Use parallel computing capabilities of frameworks like Spark or Dask to analyze data across multiple nodes. This helps in scaling up your analytics operations to handle large data sets effectively. And now we'll move to the cloud-based analytical tools. So consider using cloud services like Google BigQuery or AWS Redshift which are designed to handle massive datasets and complex analytics with ease. And after this step, we will move to data cleaning and pre-processing. Here we will automate pre-processing tasks. We'll use automated tools to clean and pre-process data. This includes handling missing values, normalizing data, and removing duplicates, which can be particularly challenging with large dataset. And after this step, we'll move to the step that will visualize large dataset. So we'll use specialized tools. That tools could be Tableau or Power BI that can handle large dataset by aggregating data and using efficient backend technologies. For more detailed exploration, tools like Plotly or Bouquet can be used as they offer capabilities to interactively visualize large volumes of data. And after that, there would be step for regular maintenance and updates. That could be continuously monitoring the data quality. As new data comes in, you can continuously monitor its quality. And after this step, you could integrate all these strategies and tools into your workflow, and you can effectively manage and extract valuable insights from extremely large datasets, thereby supporting robust data-driven decision making. And you could answer the whole strategy to the interviewer. Now moving to the question number 8, that is based on optimizing machine learning models. And the question is, during model development, you have noticed that your machine learning model is underperforming. What steps would you take to diagnose the problem and optimize the model's performance? What techniques and tools would you use? So you can answer this by starting with the optimizing. And optimizing a machine learning model that is underperforming involves several steps to diagnose and improve its accuracy and efficiency. And here we will have structured approach to tackle this issue. And you could start this with the number 1 step, that is diagnosing the problem. Evaluate model metrics. Start by thoroughly evaluating the performance metrics of your model. For classification task, look at accuracy, precision, recall, and the F1 score. For regression task, consider R squared, mean squared error, that is MSE, and mean absolute error, that is MAE. And then you can move to the next step. That is, use plots like ROC curves for classification models and residual plots for regression to visually assess where the model is going wrong. After that, we'll move to the next step, that is data quality and quantity check. Inspect the data. That is, sometimes the quality and quantity of data can be the root cause of poor model performance. Ensure the data is clean, well pre-processed, and sufficient. Look for issues like missing values, outliers, or imbalanced classes. And after this, we'll move to the feature engineering step, that would be experiment with creating new features or transforming existing ones to provide better predictive power. And then we have the next step, that is model tuning and configuration. After feature engineering, we'll move to the next step, that is model tuning and configuration. So hyperparameter tuning. Use techniques like grid search or random search to find the optimal settings for your model's parameters. Tools like Scikit-learn's grid search CV or randomized search CV can automate this process. And there's a cross-validation that would implement cross-validation to ensure that the model's performance is consistent across different subsets of the dataset. And then we have the next step, that is trying different models. So experiment with algorithms here. If initial models are underperforming, try different algorithms that might be better suited for the problem. For instance, if you started with linear regression and it's not performing well, consider more complex models like random forest or gradient boosting machines. And after this, we have ensemble methods that we can use techniques like bagging, boosting, or stacking to combine the predictions of multiple models to improve overall performance. After this step, we have feature selection that includes reduce dimensionality. Use techniques like principal component analysis, that is PCA, to reduce the number of features, which might help in improving model performance by removing noise and redundancy. And then we have select important features. So use model-based technique to identify and keep only the most important features that impact the outcome. And then comes the last step, that is regular updates and retraining. So here you can monitor and update, that could be continuously monitoring the model's performance over time. As new data becomes available, update and retrain the model to adapt to any changes in underlying patterns. And after that, you could have a consultation and collaboration work with the other teams. And by methodically addressing each of these areas, you can diagnose why your machine learning model is underperforming and can take steps to optimize its accuracy and efficiency. So this was all about question number 8. So let's start with the question number 9, and this is based on handling unstructured data. So the question is, you are given a large amount of unstructured data, including text, images, and videos. What strategies would you use to manage and analyze this type of data effectively? Describe the tools and techniques you might employ. So you can start answering this question by describing that dealing with unstructured data can be challenging due to its lack of predefined format or structure. However, with the right strategies and tools, you can effectively manage and analyze it to extract valuable insights, and there will be an approach how you can do that. So we will discuss the approach here, and starting with the steps. So the number one step will be data categorization and organization. So the number one step in this step will be sorting and tagging. We will begin by categorizing the data into types, that will be text, images, or videos. Use tagging to add metadata, which helps in organizing the data and makes it easier to access and analyze later. Then, and after that, particularly for text data, we'll use natural language processing, NLP. We will employ NLP techniques to extract useful information from text. Tools like NLTK, Spacey, or even more advanced models like BERT can help you perform tasks such as sentiment analysis, entity recognition, and topic modeling. After that, we will do text indexing. We can use Elasticsearch or Apache Solr to index large volumes of text. These tools provide powerful search capabilities and can handle complex queries efficiently. And after that, we'll move to image data. And to structure image data, we'll use image processing. We'll use libraries like OpenCV for basic image processing tasks such as filtering and transformations. For more advanced image analysis, consider deep learning models using frameworks like TensorFlow or PyTorch. And then we'll feature extraction. Apply techniques to extract features from images, such as edges, textures, or key points, which can be used for further analysis or machine learning. And then we'll come to video data. And here we'll do video processing, and we'll use the tools like FMPEG that can be used for basic video processing tasks such as format conversion or extracting frames. For analyzing video content, look at machine learning models that can classify or recognize activities in the video. And after this, we'll move to temporal analysis. For videos, temporal components are important. Techniques like sequence modeling or recurrent neural networks, RNNs, can be useful to analyze sequences of frames for activities or events. And then we'll move to data storage and management. Here we'll use the given volume and complexity of unstructured data and use big data platforms like Hadoop or cloud services like AWS S3 for storage. These platforms can scale up to handle large data sizes and provide the necessary infrastructure to store and retrieve unstructured data efficiently. And then we have visualization and reporting. Custom dashboards that we'll create here. We will develop custom dashboards using tools like Tableau or Power BI, which can integrate different data types and provide a unified view of the analyzed data. And after that, we will do data summarization. Tools that provide summarization capabilities can help in considering large volumes of unstructured data into more manageable and interpretable forms. And after that, we will leverage these strategies and tools and can effectively manage, analyze, and derive insights from unstructured data, which can be crucial for making informed decisions in various applications. And this is the path that you can explore and explain to the interviewer if this question has been asked. Now moving to the question number 10, and that will be based on scaling AI solutions in enterprise. And the question is, your company wants to scale its AI operations from a few initial pilot projects to enterprise-wide implementation. What are the key considerations and steps you would take to ensure the successful scaling of AI solutions across the organization? And what challenges might you face and how would you address them? So you can start answering this question with the scaling AI solutions. You could answer him that scaling AI solutions across an enterprise requires careful planning and strategic implementation to ensure success and alignment with business objectives. And there should be a strategic approach to implement this. So starting with the approach, and the number one step will be strategic alignment. So identify business objectives. Start by identifying the business objectives that the AI solutions are intended to support. This ensures that the AI initiatives are aligned with the company's strategic goals and can demonstrate clear business value. And then comes the stakeholder engagement. So engage stakeholders from various departments early in the process to gather input and build support. This helps in understanding diverse needs and ensures broader acceptance of the AI solutions. And after that comes the infrastructure and technology. So there's an option that is assess and upgrade infrastructure. Evaluate whether your current IT infrastructure can support the expanded use of AI. You might need to upgrade hardware, invest in cloud solutions, or adopt technologies that facilitate AI processing and data handling. And after that, we have standardization of tools. Standardize the tools and platforms used for AI development to ensure compatibility and ease of maintenance across the organizations. And after that, we'll move to data management. So robust data governance, that is to implement a strong data governance framework to manage enterprise data effectively. This includes policies for data quality, security, and compliance, especially important when scaling AI solutions that rely on vast amounts of data. And after that, we will come to data accessibility. So ensure that data is accessible across the organization, but also secure against unauthorized access. This involves setting up secure data lakes or warehouses that centralize data while allowing controlled access. And then we come to the next step, that is talent and training. So build AI competency, that is develop in-house AI expertise through training programs and hiring. So this builds the necessary skills within the organization to develop, manage, and scale AI solutions. And after that, you can also perform cross-functional AI teams. That could be forming cross-functional teams that include data scientists, IT professionals, and domain experts. So this fosters collaboration and ensures that AI solutions are developed with a comprehensive understanding. And after forming these collaborative teams, we'll move to scalable deployment models. So pilot test and phased rollout. Before a full-scale rollout, conduct pilot tests to gauge the AI solution effectiveness and integration capabilities. Based on feedback, adjust, and then gradually deploy the solutions across the organization. And then we have modular and flexible design. So design AI systems to be modular and scalable, allowing for adjustments and expansions as needs. And then we'll monitor and do the continuous improvement. So there will be performance metrics that would establish metrics to regularly assess the performance of AI systems. We will monitor these systems to ensure they met expected outcomes and adapt as necessary. And after that, we have next step, that is addressing challenges. So there could be cultural resistance, that there could be employees that would be resisting to the changes, but we have to address this through continuous education and by showcasing successful AI use cases within the organizations. And by carefully considering these aspects and methodically implementing steps, you can successfully scale AI solutions across your enterprise, driving significant business value and innovation. And that's all for question number 10. Now we'll move to question number 11, and that is based on ethical considerations in data science. So the question is, in your data science projects, how do you ensure that ethical considerations are addressed? Describe the steps you take to identify and mitigate ethical risk in your projects. What frameworks or guidelines do you follow? So you could start answering this question with ethical considerations, that they're crucial in data science to ensure that the solutions and analyses do not advertently cause harm or bias. Here's how you can ensure that. So there are some steps and we will discuss those steps, starting with the number 1, that is educate on ethical standards. So stay informed about the ethical standards in data science, such as fairness, accountability, transparency, and privacy. Organizations like the Data Science Association and the ACM have codes of ethics that we refer to as guidelines. And then we have ethical risk assessment. Identify potential ethical issues. That would be at the beginning of each project, conduct a thorough assessment to identify any potential ethical risk, such as biases in data or impact on vulnerable groups. This involves reviewing the source of data, the methodologies used for data collection, and the intended use of the data analytics results. And then we have stakeholder analysis. Engage with stakeholders to understand the diverse perspectives and potential impact of the project. This helps in identifying ethical issues that may not be apparent from a purely technical standpoint. And then we'll move to mitigation strategies. Implementing bias mitigation techniques, we will use statistical and machine learning techniques to detect and mitigate biases in data. This might involve techniques like resampling, reweighing, or using algorithms designed to be fair. And then we have privacy preserving methods. Employ methods such as data anonymization, encryption, or differential privacy to protect individual privacy when analyzing sensitive data. Then we have other methods, that is transparency and explainability. There we have model explainability, and after that coming to documentation and reporting. So we have to maintain thorough documentation of data sources, model decisions, and methodologies. And then we have continuous monitoring and feedback. There you have to monitor outcomes and the feedback mechanisms should be applied. And then we have the panels, that is collaboration and advisory panels. There we have ethical review boards. So for complex projects, setting up or consulting with an ethical review board can provide oversight and diverse perspectives on the ethical implications of project methodologies. So by proactively addressing ethical considerations through these steps, you can ensure that your data science projects uphold high ethical standards and positively contribute to society while minimizing harm. So this was all about question 11. Now moving to question number 12, that is based on time series forecasting for business decisions. So the question number 12 is, you are tasked with forecasting monthly sales for a retail company using time series data from the past 5 years. What steps would you take to prepare and analyze this data to make accurate forecast? What specific tools or techniques would you use and why? So we can start answering this by time series forecasting. And we could address them that it's a powerful tool for predicting future events based on past data, especially in business context like retail sales. So we will have a structured approach here, and we'll start with data collection and cleaning. First, we will gather data and ensure that you have collected all relevant data, including monthly sale figures from the past 5 years, and also considering including external factors that might affect sales, such as economic indicators, holidays, and promotional activities. And then we'll proceed to clean data. We'll check for and handle any inconsistencies or missing values. And then we have data visualization. Here we will plot the data. We'll use plotting libraries like matplotlib or seaborn in Python to visualize the data. This will help in identifying patterns, trends, and seasonality. And then we have decomposition of data. So there's a seasonal decomposition, and we'll use statistical techniques to decompose the data into trend, seasonally, and residuals. So this can be accomplished with tools like the seasonal decompose function from the stats models library in Python. And we'll understand these components separately and can improve the accuracy of our forecast. And then the next step is model selection and forecasting. So there are two models, that is ARIMA and SARIMA models. So we have to choose appropriate forecasting models based on data's characteristics. For instance, ARIMA, that is Autoregressive Integrated Moving Average. It is effective for non-season data, while SARIMA, that is Seasonal ARIMA, that is suitable for data with seasonal patterns. And after choosing the model, we'll move to cross-validation. We will implement time series specific cross-validation techniques like time-based splitting to evaluate model performance. And this will ensure your model generalizes well on unseen data. And then we have model fitting and diagnostics. We will fit the model, that is by using the Cynimax class from stat models that will fit your model to the data. And then we will carefully select parameters based on AIC, that is Archaic Information Criterion, that scores or thorough grid research technique. And then we can do the diagnostics and forecast and validation. And after forecast validation, we'll move to iterative improvement. So there's a feedback loop that should be mandatory, and there should be a regular update for the model with new sales data and refining the model as needed. So this continuous improvement cycle helps adapt to changing patterns in sales data. And by following these steps and using these tools, you can create robust forecasts that help the retail company plan better and make informed decisions. So this was all about question number 12. Now moving to question number 13, that is based on customer segmentation using machine learning. So the question is, you are given a data set containing demographic and purchasing behavior data for a group of customers. Your task is to segment these customers into distinct groups based on similarities in their purchasing behavior and demographics. So what steps would you take to perform this segmentation, and can you provide a sample Python code snippet to illustrate the initial stages of data handling and model application? So we can start this by explaining customer segmentation, that it's a powerful approach to tailor marketing strategies and improve customer service by identifying distinct groups based on their behavior and characteristics. And here also we have a detailed approach for this task. So we'll start with number one step, that would be data exploration and preprocessing. So there will be initial exploration, that is beginning by examining the data set to understand the features available such as age, income, purchase frequency, etc. Then we will look for missing values or anomalies and decide how to handle them. That could be using imputation. And then we'll move to feature engineering. We will create new features that might be useful for segmentation, such as customer lifetime value or average transaction amount. We will also use normalization, that is normalize the data to ensure that one feature doesn't disproportionately influence the model due to its scale. We'll use standard scaling or min-max scaling as appropriate. So then we'll come to the next step, that is choosing the segmentation technique. And here we have k-means clustering. So this is a popular method for customer segmentation. Here we will decide on the number of clusters by using techniques like the elbow method or silhouette analysis to determine the optimal cluster count. And then we have model implementation. And in that we will use data preparation, and we'll prepare the data by selecting the relevant features and applying any final transformations. And then we have model fitting. will fit the k-means clustering model to the data and evaluate and interpret analyzing clusters. And after analyzing clusters, we'll move to the next step, that is strategic insights. We'll provide actionable insights based on cluster characteristics such as targeted marketing strategies for each segment. And then we have iterative refinement, that is feedback incorporation, and we'll use business feedback to refine the segmentation. If additional data becomes available, incorporate it to enhance the model. And now we'll see the sample Python code. So for this, first we'll import the libraries and modules. As you can see on the screen, we have imported Pandas, random forest classifier, train test split, standard scalar, classification report. And after that, we'll load the data. And for that, we have used the Pandas to read the data, that is read underscore SSV. And after that, we are processing the data, that is data pre-processing. We are handling missing values and using the forward fill or FIL to fill missing values in the data set. And then we are featuring scaling, that is normalizing the selected features, that is feature 1, feature 2 and feature 3 using standard scalar. And then we'll move to the next step, that is data splitting. We'll split the data set into training and testing sets. So that test size equal to 0.2 parameters specifies that 20% of the data will be used for testing. And then we'll train the model. We'll initialize and train a random forest classifier with 100 trees and a random state for reproducibility. And then we'll evaluate the model. We'll make predictions on the test set, that is x underscore test, using the trained model, and print a classification report showing precision, recall, F1 score, and support for each class. So this code demonstrates the process of loading, pre-processing, training, and evaluating a machine learning model, that is random forest classifier, for predicting equipment failures in a manufacturing plant. The use of techniques such as data pre-processing and splitting along with the random forest classifier highlights a standard flow for building predictive maintenance models. So this was all about the question number 13. So now moving to the question number 14, that is based on predictive customer churn. And the question is, you are tasked with developing a model to predict which customers are likely to churn from a subscription service. So what steps will you take to build this model, and can you provide a sample Python code to illustrate the data preparation and model training process? So we'll start answering this question about depicting what is predicting customer churn. So predicting customer churn is crucial for businesses to implement retention strategies proactively. And we'll have a detailed approach for building a predictive model for this purpose, starting with data collection and exploration. And in this, we will collect data. And after that, we will perform the exploratory data analysis, that is EDA. We'll perform an initial analysis to understand patterns and trends. And then we have feature engineering. We will create new features and derive new features that might influence churn, such as change in usage pattern or service upgrades. And then we'll handle the missing values if we found any. And then we'll encode categorical variables. We'll use techniques like one-hot encoding or label encoding for categorical variables. And then we have scale features to normalize or standardize numerical features to ensure they contribute equally to the model's performance. And then we'll select the model, that is, we'll choose the appropriate model and start with for the knowing handling binary classification task. That could be with logistic regression, random forest, or gradient boosting machines. And after selecting the model, we'll train the model and evaluate it. So fit your model on the training data, and after that, evaluate the model using appropriate metrics like accuracy, precision, recall, F1 score, and ROC to gauge its performance. And then we'll optimize the model using hyperparameter tuning. We'll optimize the model parameter using grid search or random search to improve performance. And then we have feature importance, that is analyze and rank features by their importance in predicting churn to refine the model further. And then the last step is deployment and monitoring. We'll deploy the model. Once validated, deploy the model into a production environment where it can predict real-time churn. So after deploying the model, regularly monitor the model to ensure it remains effective over time as new data comes in. So now we'll see the sample Python code for this example. So starting with the importing of libraries, we will import Pandas, NumPy, Scikit-learn, sklearn, TensorFlow, and the TensorFlow keras and callbacks. And after importing the modules, we'll start with data loading. We'll load the dataset from a CSV file named equipment_data.csv, and that too with the Pandas data frame. And after that, we'll do the data preprocessing. We'll handle missing values. And for that, we'll use forward fill to fill missing values in the data set. And then we have feature scaling that will normalize the selected features, that is feature 1, feature 2, feature 3 using standard scaler. And after that, we'll use the data splitting. We'll split the dataset into training and testing sets, and the test size will be equal to 0.2. And this parameter specifies that 20% of the data will be used for testing. And after that, we'll start with building the model. First, we'll see sequential model that initializes a sequential model technique. And then we have dense layers that adds 2 dense layers with 64 units and ReLU activation function. Then we have dropout layers that adds 2 dropout layers with a dropout rate of 0.5 to reduce overfitting. After that, we'll do the model compilation. We'll compile the model using the Adam optimizer and binary cross entropy loss function for binary classification. And there will be an early stopping that will define an early stopping callback to stop training when the validation loss metric has stopped improving after 3 epochs. And after training the model, we will evaluate the model and evaluating the model on the test data and print the loss and accuracy metrics. So this code demonstrates the process of loading, pre-processing, building, compiling, training, and evaluating a deep learning model using TensorFlow and Keras for predicting equipment failures in a manufacturing plant. So the use of techniques such as data pre-processing, dropout, regularization, and early stopping helps in building a robust deep learning model for predictive maintenance. So that's all with question number 14. Now we'll start with question number 15, that is based on deep learning and NLP. And your question is, you are tasked with developing a sentiment analysis model using deep learning to understand customer opinions from reviews. So what steps would you take to build this model, and can you provide a sample Python code snippet to illustrate how you would pre-process data and train a simple deep learning model? So we'll start answering this with sentiment analysis. That sentiment analysis using deep learning allows businesses to gauge customer sentiment from text data like reviews or comments effectively. And we'll have a detailed approach for building a sentiment analysis model. We'll start with data collection and cleaning. We will collect the data, gather a substantial data set of text reviews and their associated sentiments, typically labeled as positive, negative, or neutral. And then we'll clean the data, pre-process the data by removing noise such as HTML tags, special characters, and stop words. And we'll normalize the text by converting it to lowercase. And then we have text pre-processing. We'll convert text into tokens, words, or phrases. And then we have vectorization that transforms tokens into numerical format using techniques like word embeddings or TF-IDF, that is term frequency in verse document frequency. And then we'll use the padding. And then we have the option of model selection. We'll choose a model architecture based on a basic approach and use a RNN or more advanced architecture like LSTM, that is long short term memory, or GRU, that is gated recurrent units, which are effective for sequence data like text. And then we have model training. We'll compile the model, define the model architecture, and compile it with the loss function suited for classification like categorical, cross entropy, and an optimizer like Adam. And then we'll train the model, we'll fit the model on our pre-processed data. We'll evaluate and optimize it. Evaluating model performance, here use the metrics such as accuracy, precision, recall, and F1 score to assess the model. And then we have hyperparameter tuning. We'll optimize the model by adjusting parameters like learning rate, number of layers, and units per layer. And then coming to deployment. We'll deploy the model and integrate the model into the existing review processing pipeline so it can automatically classify new reviews. So let's see the sample Python code, and we'll have a basic approach for that. Here we'll import NumPy, TensorFlow, Sequential, embedding LSTM, dense dropout. So embedding converts positive integers, that is indexes, into dense vectors of fixed size. And LSTM, that is long short term memory layer, that is used for learning dependencies in sequence data. And then we have dense, that is a regularly densed connected NN layer. And then we will import pad underscore sequences. And after that we have the data set and the sample text data representing customer reviews that will store in variable text. And then we have labels that has binary labels indicating sentiment, 1 for positive, 0 for negative. And now we'll start with the pre-processing of data. Here we have declared that tokenizer. We will initialize a tokenizer that will help only the top 1000 most frequent words. And then we have fit underscore on underscore text, that is update the internal vocabulary based on the list of text. It essentially creates a dictionary of word to index pairs. And then we have text to sequences that will transform each text in text to a sequence of integers. And then we have pad sequences that will ensure all sequences have the same length by padding shorter sequences with zeros up to the maximum length. And then we'll start building the model. Here we have sequential model that will set up a linear stack of layers, and then we have embedding layer that will map each word index to an embedding vector of size 64. So the input length is set to 10, that is the length of the input sequences. Then we'll start with LSTM layers. So two LSTM layers are added. The first one returns sequences to allow the next LSTM layer to process these sequences. And after that, we have the dropout layer that applies dropout with a rate of 0.5 of the first LSTM layer to reduce overfitting. And after that, we'll come to dense layer that has output of a single scalar that represents the predicted sentiment and using sigmoid activation to output a probability. And now we'll start with model compilation and training. So we'll configure the model for training and we'll use binary cross entropy as the loss function that is suitable for binary classification, and the Adam optimizer and tracks constantly accuracy as a metric. And then we have the fit that trains the model for a specified number of epochs, that is iterations or the entire data set. And then we'll predict the model, that is after training the model can predict the sentiment of the reviews in the data set. This is useful for checking how the model performs on the training data itself. So this breakdown explains each step of the coding process, detailing how the data is prepared and how the model is configured. And then we'll compile it and use for training and prediction. So its detailed explanation should help in understanding how to implement a simple LSTM model for sentiment analysis in TensorFlow. Now moving to the question number 16. So let's start with question number 16, that is based on anomaly detection in transaction data. So the question is, you are tasked with identifying unusual transactions in a company's financial data that might suggest fraudulent activity. So what steps would you take to develop an anomaly detection model, and can you provide a sample Python code snippet to illustrate how you would pre-process the data and apply an anomaly detection technique? So we'll start answering this with anomaly detection technique. That is, anomaly detection is essential for preventing fraud by identifying transactions that deviate significantly from typical patterns. And now we'll see the structured approach to building an anomaly detection model for transaction data. We'll start with data collection and cleaning, and we'll collect all the compiling transaction data, which should include details like transaction amount, time, user ID, and transaction type. Then we'll move to feature engineering and develop features that capture the essence of transactions, such as time of day and the day of the week. And then we have data normalization. We'll use scaling techniques such as min-max scaling or standardization to ensure that the model is perfectly normalized. And then we have choosing the anomaly detection technique. So here we have to choose the technique which is effective for high dimensional data sets and works for isolating anomalies instead of profiling normal data points. After choosing the anomaly technique, we'll train anomaly identification. We'll fit the chosen model to the data, and the anomalies that would have been chosen will be those transactions that the model identifies. And after this, we come to the last step, that is review and action. Here we have manual review, that is transactions flagged as potential anomalies should be reviewed manually to confirm fraudulent activity. And then we have continuous improvement. That is, we can regularly update the model with the new data and feedback from the review process to improve accuracy. And now moving to the prediction, that is after training the model, we can predict the sentiment of the reviews in the dataset. And this is useful for checking how the model performs on the training data itself. Now we'll see the Python code to see how you can set up this model for anomaly detection. We'll start by importing the libraries and module, and after that we'll load and prepare data. That is, we'll load transaction data from a CSV file into the Pandas data frame. And after that, we'll convert the transaction time column to date time format, which allows the extraction of additional time-based features. And after that, we'll perform feature engineering that will extract the hour of the day from the transaction time column. This feature can be important as transactions occurring at unusual hours may be indicative of fraud. And then we'll move to the normalization of data. This will apply standard scaling to the amount and hour of the day feature. This normalization process involves subtracting the mean and dividing by the standard deviation for each feature, ensuring that the feature contribute equally to the analysis and improving the performance of many machine learning algorithms. And after that, we'll start with anomaly detection with isolation forest, That's a technique. We will initialize an isolation forest model with 100 trees, that is n estimators equal to 100, setting the proportions of outliers, that is contamination, to 1% of the data. So this parameter is crucial as it influences the threshold of marking an observation as an anomaly. Then we'll fit the model to the scaled amount and R of the D data and predict the anomaly status for each transaction. And then we'll start with filter and display anomalies. We'll filter out transactions identified as anomalies, that is anomaly equal to -1. We'll display these transactions which can be reviewed manually to determine if they represent actual fraudulent activity. So this code snippet provides a systematic approach to detecting anomalies in transaction data, leveraging the isolation forest algorithm's ability to handle complex and high-dimensional dataset effectively. So the pre-processing steps ensure that the data is appropriately formatted and normalized for optional model performance. So this was all about question number 16. Now moving to question number 17, and that is based on integrating machine learning models into web applications. And your question is, you have developed a machine learning model to predict real estate prices based on various features like location, size, and amenities. How would you integrate this model into a web application to allow users to get real-time price predictions? Can you provide a sample Python code snippet to illustrate how you would prepare the model for integration and handle user requests? So starting with the approach, that is integrating a machine learning model into a web application, this will involve several steps to ensure the model is accessible and perform well in a live environment. So here's how you can approach this task. We could divide into steps, and we'll start with number 1 step, that is model preparation. We'll finalize and save the model. So once your model is trained and validated, save it using a format that can be easily loaded into a web application. So Python's pickle module or TensorFlow's save model format are commonly used for this purpose. Then we can use web application backend setup. For this, select a suitable web framework. So Flask is popularly known for its simplicity and effectiveness in integrating Python-based machine learning models. And after that, we'll develop the API. After developing the API within your Flask app, that you can receive user inputs for model features, load the model, make prediction, and return the result. And after this, we'll develop the UI. We'll design a user-friendly interface. We'll create a simple and intuitive UI that lets users input the feature like location, size, and submit them for prediction. And after that, we'll move to the deployment phase. We'll use a cloud platform like Heroku, AWS, or Google Cloud to deploy your Flask application. And then we have the maintenance and updates. We'll monitor and update regularly for the performance and use the model as needed based on user feedback. So now moving to the Python code and see how this model can be created. So here we'll start importing the libraries and module, and we are using Flask, Pickle, and JSONify. And we will start with app initialization. We'll initialize a new Flask web application. That would be a special variable which gives Python files a unique name to differentiate between them when they are imported into other scripts. And after that, we'll load the model. So loading a pre-trained machine learning model from the file system. So this model is assumed to be saved in the same directory as this script. So the model is loaded in RB mode, which stands for read binary. And after that, we'll move to API route and prediction function. So we will define an API endpoint at predict that listens for post request. This is the URL that the front end of the web application will call to send data to the backend. And after that, we'll start with predicting the function. And here we have extract features that retrieves data sent into the JSON format from the post request. That is request.get_JSON, and the force we have set it as true here, and forcefully formats the request data into JSON, ensuring compatibility. And then we'll extract the relevant features, that is location, size, and amenities from the JSON object and store them in a list as expected by the model. And after preparing the features, we'll make the prediction. We'll use the loaded model to make a prediction based on the provided feature. And then we have the return prediction method. Here we will convert the prediction result into JSON format using JSONify and send it back to the client, and this will ensure that the response can be easily handled by the client application. So this was all about the question number 17. Now moving to the question number 18, that is based on analyzing. And now we'll move to the question number 18, that is based on analyzing geospatial data. And your question is, you are tasked with analyzing geospatial data to help a city improve its public transportation system. The data includes GPS coordinates of bus stops, ridership numbers, and traffic patterns. What steps would you take to analyze this data, and can you provide a sample Python code snippet to illustrate how you might visualize bus stop location and ridership? So you can start answering this question that geospatial data analysis can provide critical insights into how effectively a public transportation system serves its city and guide improvements. And there's a detailed approach for this, and we can start with data preparation. And in this, we will do data collection and data cleaning. And after this step, we will move to the next step, that is exploratory data analysis. And in this, we will have statistical summary, we will generate descriptive statistics, and then we have correlation analysis. And after moving that, we have geospatial visualization, that is mapping bus stop. We'll plot the locations of bus stop on a map to visually assess their distribution across the city. And after that, we have heat maps that will create ridership data to identify hotspots and areas with potential service gaps. And after geospatial visualization, we'll move with spatial analysis. We have proximity analysis that will analyze the proximity of bus stop to key areas like commercial centers or residential areas. And now moving to the fifth step, that is optimization and recommendation. So we'll have a route optimization that will suggest modifications to route based on traffic patterns and ridership demand, and the policy recommendations that will provide actionable recommendations for improving bus frequencies. Now moving to the sample Python code where we can define this model and use it accordingly. And here we will start importing the libraries and modules, and here we'll start with importing GeoPandas and matplotlib.pyplot. And after importing, we'll start with data loading. So we will declare a variable bus underscore stops and load the bus stops data from a shapefile. So shapefiles are popular geospatial vector data formats for geographic information system software. And then we have the ridership that will load ridership data from a CSV file, which includes columns for longitude, latitude, and ridership levels. And after that, we'll create geodata frame that will convert the ridership data frame into a geodata frame. And this step involves creating a geometry column from the longitude and latitude columns. And then we have the plotting one. Here we will plot the graphs that would be figures and axes and create a figure for the single subplot with a specified size that is 10 cross 10 inches. And then we have city underscore map.plot. It is assumed that there is a base map of the city loaded as a geodata frame named city map. This is plotted first with the light gray color to serve as a background for the other layers. So this was all about question number 18. Now moving to question number 19, that is based on predictive maintenance using machine learning. And the question is, you are tasked with developing a predictive maintenance system for a manufacturing plant that relies heavily on automated machinery. So the data available includes machine operational parameters, maintenance history, and failure incidents. What steps would you take to develop a predictive model, and can you provide a sample Python code? So you can start with predictive maintenance that is essential in manufacturing as it helps prevent equipment failures, reducing downtime and maintenance cost. And here you would have a detailed approach or predictive model for this, starting with data collection and integration. Then you can do EDA, that is exploratory data analysis, and then we can perform feature engineering, and then move to data preprocessing task, and then the selection model and training. And after that, we have model evaluation and deployment technique that we can do for the model using appropriate metrics such as precision, recall, and F1 score. So this was all about question number 19. So now move to question number 20, that is based on personalization using machine learning. And your question is, you are tasked with developing a machine learning model to personalize content recommendations for users on a media streaming platform. The data available includes user demographic details, viewing history, and ratings. So what steps would you take to build a model for personalized recommendations? And can you provide a sample Python code for that? So you can start answering this with creating a personalized recommendation systems. This would be essential for engaging users by providing content that is relevant to their interest. And there will be a systematic approach or personalized content recommendation. We'll start with data collection and integration. And after that, we'll perform EDA, that is exploratory data analysis. And then we have feature engineering. In this, we'll interact features, and the temporal features will include time-based features to capture trends and seasonality in viewing behavior. And then we'll select the model, that is by collaborative filtering and hybrid models. And then we'll train the model and validation and implement and monitor them. And after that, we'll deploy the model.
Be your mentor or trainer for this course of machine learning. And I hope we have this wonderful, interactive, exciting journey. All right, so let's begin with this journey and try to understand what is machine learning and why is there so much buzz around it. Let me go through what all we would be covering in this particular course, and then we begin the discussion. So if we talk about a learning path, the first, topic that we will be covering today is Introduction to Machine Learning, which focuses on the basics of machine learning. Second is Supervised Learning, Regression and Application, which focuses on supervised learning with an emphasis on understanding and implementing different types of regression models. Third is Supervised Learning, Classification, Applications, like basically we're trying to cover that what are the different learning techniques available in the machine learning. So first technique that we would be covering up is supervised learning. Under supervised learning, we would be covering up regression as well as classification. Then we would be moving on to the ensemble learning method, which focuses on advanced ensemble methods to enhance the performance and robustness of the models. Then we would be moving on to unsupervised learning and finally recommender system along with the application. What is machine learning and why is there so much of buzz? Why are you here to learn machine learning? Let me put this in another way. So basically, we want the machine to get trained with our data. We want the machine to learn from the data so that it can predict data. What kind of data that we want to predict? Why do we want these predictions? Right? Because now are we living in the digital technology where data is all around us? Even this, session is data, right? When all the material that has been sent to you is data, anything on the news which is coming is data, anything doing for entertainment is data, e-commerce is data, your work profile is data, because we are living in huge amount of data. Data is all around us. Do you think, is there any escape from data now? No, not now. When I used to take sessions 5 years now, and 7 years before, the scenario was a little different, trying to adapt. But I don't think so. There is now any survival without data. Can you survive without this data? Not moving on social media. And, one day, as it says, if the internet stops, do you think your life also stops? Your mobile phone is lost. Everything is lost. Isn't it? The data has become a lifeline, and now we see several applications which are working or the concepts that are being based on data. Now it automatic translation. Translation has not become difficult if you want to convert something from English to German, German to Spanish, any language translation is right there. We speak to the machine and we get the translation. Virtual personal assistants are there, image recognition, email spam filtering. That's actually comes under the domain of machine learning. That it, based on the algorithm or the pattern or the text or the words which are there, it is able to filter out whether the mail is a spam or not. So what do you think would be the criteria? Generally, the mails with spam are saying that you have a lottery system, other system, or there is a bonus. So that becomes your email spam filtering. Then we have the text and the speech recognition, medical diagnosis, online fraud detection is there, where we want to detect how is the online fraud happening, web search and recommendation engines, and of course, what is going to be the traffic prediction. Not only the traffic prediction on the roads, but it also related to the traffic going on to a particular website, whether that website is going to get crashed or not. Data becoming now difficult to handle because it's digital data. Understanding data, everything numerically is difficult. Earlier the data was this much, it could be handled. Now it's become like this much and this much and this much, and it's increasing. So we need certain algorithm, we need technologies which can help to analyze so that we can improve our performance. But if we look at on the overall scenario, still there is a lot of confusion about the AI, the machine learning, and the deep learning. Yeah, what is the subset or the issues, like what is artificial intelligence, machine learning, and deep learning? Are you able to distinguish between the three? So this is one of the initial chess, developed by the computers. IBM Deep Blue chess program developed in 1997. When was it developed? It was developed in 1997 by IBM. And this particular program was strong enough to defeat the world chess champion at that particular point. His name is Gary Kasparov. Okay, he was capable of defeating the world chess champion. Getting my point? Right? And then we have this IBM Watson under machine learning. So AI is the bigger branch. All right. Artificial intelligence is the bigger branch, right? Under which we have the machine learning subset, right? Which we are going to study. In machine learning, basically, it works on statistical algorithm. That is why we say that before learning machine learning, it is important to have a good concepts and knowledge of statistics that helps to understand. So based on statistical foundation, statistical algorithm, the machine is capable of doing Google search algorithm, Amazon recommendation, and email spam filtering. How, like we just saw, that it is capable of filtering the email. And then finally, we have the deep learning, which is also under machine learning, in which we have the AlphaGo, the natural speech recognition, and the level 4 automated driving system. The scenario has changed and we are into the AI revolution. So the bigger branch is still AI. We are witnessing this revolution in front of us. Under AI, we have the machine learning. Under machine learning, we have the deep learning. And under deep Gen AI task, right? So when we talk about the Gen AI task generation fine tuning, we have the agents, automation, and the virtual assistants. And this Gen AI is now capable of even doing a lot of text generation that we see. We ask a lot of things to the Chat GPT, other models like Gemini, Copilot also. We want to generate images, video generation. All these things are being possible. AI that we are talking at the moment is only and only related to the software. Through software, we are able to provide or give intelligent answers. But what is basically the difference between a traditional programming and a machine learning programming? So let me explain you with this particular example. So in traditional programming, again, we have this data, right? That this is my data, which is 1, 2, 3, and 4, right? And over here, we have machine learning algorithm where we have 1, 2, 3, and 4. Okay, the data has not changed. I'm giving you a very simple, example. Now, if we talk about the program, initially the program, and we talk about C, Pascal, Fortran, even C++ and Java, and even Python, they are capable of giving logic. Now, if I want to distinguish that, what are the numbers, what is the logic behind that these, numbers are even or odd? So simply we understand the logic that if I talk about Python, I percentage 2 is equal to 0. That means if the remainder divided by 2 is 0, then the number is, it is odd, right? Else it is odd. Getting my point? Yes or no? This point is getting clear. So now, even if a number 10, it would automatically give me that this is going to be an even number. And if I give the number 57, it is going to be odd. But now, machine learning, how things happen, I give the output along with it. I say that 1 is odd, 2 is even, 3 is odd, and 4 is even. Got it? Now the computer, based on certain statistical concepts, algorithm will try to detect that when I feed the number 10 over here, that it is going to be even. Can it predict me as odd also? Yes, the prediction can be wrong also. Clear? But if the algorithm has to be good enough that it is predicting that 10 is even and 57 is odd. So, coming on to the concept, the first kind of learning is known as supervised learning. What is it known as? Supervised learning. That if this is my known data, this is already now images, that this is my input, and I also feed the output. When I feed the input as well as output to the machine, it becomes my labeled data, right? That means this is an image of an apple. I feed it into the machine, and when I feed this apple, it says, predicts that is this apple or not, and it predicts it's an apple. But it can predict wrong also. So might have seen sometimes the chat GPT also predicts, gives wrong answer. The image development, Ghibli and all give wrong answers. It's the biggest fear, that these, if a wrong or a incapable data is set to them, then it can give false and nonsensical and fabricated information also. So this is the fear that we are now moving ahead. Right, Ajay? Charan? Hardik? But if we talk about clear system, if we talk about the traditional systems, expert systems were working that we have a user, we are trying to give the query and then try to get the output out of it, right? If this is my query and this is how I get the output out of it, and then I try to infer what is it. But inference is not coming from the data, but this data, it's coming from data, but this data is created from an expert. Now, what do I mean by that? Let me explain this to you. Expert can be a cardiologist, a lawyer in different domains, right? A cardiologist, a lawyer, somebody from in the finance domain, maybe for 30 years, 30 plus years of experience. And we created if else knowledge, inference knowledge, that whether you are capable of getting a loan or not. And if I have a cardiologist, some information has been fed that maybe your BP rating is this much, or your terms. If that is matching to the inference engine, that's how it will give the output. So what happens? For example, if you are a user and you enter to the user interface, maybe all your blood reports, your BPs and your test reports, all things are given as the user interface, right? And then we do the inference engine, and based on this knowledge base, we get the output, right? So what has been replaced now? Rather than knowledge base, it is completely based on the original data, and things have become complicated on images, on non-structured data. So do we understand supervised learning now? Can I say more the data, more my system becomes intelligent? It is only capable of recognizing hexagon, triangle, and square. And if I add a shape of a circle, maybe a parallelogram, maybe a rectangle, it's capable of analyzing that. So that is where, the systems are getting modeled, because the data is becoming huge day by day, right? So this is supervised learning. So under supervised learning, we have the label data. What is label data? We have the input as well as the output, where we try to train the model. After the model has been trained, based on the test data, we try to do the prediction whether it is a square or a triangle. Clear? We will initially start with supervised learning, that we have the input, the output. We will try the model. So where will we do the model? That means now the data, the 70% of the data will be used for training, and 20 to 30% will be used for testing. Then it will predict the output. Okay. And as I've been telling you, there is a very strong relationship between machine learning as well as statistics part of it, right? So statistics is a field of mathematics, but when it is combined with computer science, the machine learning, it becomes statistics and machine learning. The idea of statistics is that it helps us to draw inferences, relationship between variables, whereas machine learning gives optimization, prediction, accuracy, etc. Right? And then we have prior assumptions about the data, some knowledge about the population usually required. This is none. Dimensionality of the data usually applied to the low dimensional data. And knowledge overlap, there's no ML knowledge required when we study statistics. But in machine learning, some statistics knowledge is usually needed, as it becomes the foundation for few algorithms. So if you do not know much about statistics, there is nothing to worry. It's not very difficult. Definitely concepts of probability would be required. So I would just request you, the learners, to get familiar with the concepts of probability, conditional probability, Bayesian theorem, and probability distribution. So this is what I expect from you all. Got it? Right? And to make the picture a little more clear, the boundaries are not very crisp now because there is data everywhere. But to make the picture a little more clear, that, when we start with initially Python course, we are doing visualization, exploratory data analysis, maths, and statistics. And when we try to do overlap between AI, machine learning, deep learning, we get this data science. So data science becomes the foundation for AI, ML, and deep learning. If I technically ask you what is learning, and now you might have been hearing this word agent, it could be a human agent, it could be a robotic agent, it could be an AI agent. So if we talk about a little more technical definition of learning, basically we are trying to improve the behavior based on the experience. When we say you are a very learner thing, you experience, that means different types, years of knowledge. The range of behaviors is expanded. The agent can do more, right? The range of behavior is expanded and agent can do more. The accuracy on the task is improved. The agent can do things better. And the speed is improved. The agent can do things faster. So what is the idea of learning? If you see this, means that DS, okay. So if we talk about learning from the machine as well as from the human point of view, this definition is valid. That it is the ability to improve our behavior based on our experience, right? It's not always about acquiring new skills. That's one of the things, that range of behavior, that you are, driving, swimming, stitching, cooking. Of course, the range is increased, but also accuracy. By doing the thing again and again, doing learning increases my accuracy as well as speed. And if we now see technically in machine learning, the different types of learning techniques are supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. So all these kinds of actually learning come from the fact that how we as humans also learn. So do you also agree? Only agree through training and testing? Training and testing happens when we are going to school, we are trained and then we are tested in universities, colleges, or even this session. Is there any other way we learn also? Do we learn through observations? Do we learn through our mistakes? Do we learn? There are different kinds of learning also possible. And exactly the same thing we also try to replicate in our machines also. So one of the learning method is observation. So one basic difference between supervised learning and unsupervised learning. What do we mean by supervised and unsupervised learning? Supervised learning says that this is my data, right? Are my apples, right? And I tell them that this is my image, these are apples. 70% of my data is used for training and 30% of the data is used for testing. Label data is given in, so absolutely correct, Mega. Label data means supervised learning. And then the model predicts me that it is an apple. And what is unsupervised learning? Do I have a label data? No, I have not told that this is an apple or this is a banana or this is a peach. But the model or the algorithm, sorry guys, is capable enough to distinguish between the three of them, that this is my apple, this is my peach, and this is my banana, right? So initially we will, build concepts on this supervised as well as unsupervised learning. The machine is given huge sets of data that are not labeled as inputs to analyze. The machine needs to figure out the output on its own, where it identifies the patterns. And the two types of algorithm which come under unsupervised learning are association and clustering. And K means for clustering problems and a priori algorithm for association rule learning problems, right? And then we have supervised learning. The input is in the form of raw data that is labeled. The machine is already fed with the required feature set to classify inputs, divided into two types of problems, regression and classification. And then we will try to understand different regression algorithms. This is the first stage that we are going to work on. Clear? So now let's understand what is self-supervised learning. Here we have the input data. Is it labeled? No, this is not labeled data, but we have partial labeled data, that this is an orange and this is a banana and its quantity is less. And here both the types of data are mixed. Machine learning model, and this is my unlabeled data to predict the output. So it's an apple. So this is my input data, right? This is my partial data. And when I combine them together, prepare the model, I get the output. Clear? And reinforcement learning, the most effective way of learning from which we as humans learn a lot. That means from our mistakes, from our feedbacks, from our punishments, from our rewards, right? So if this is the input given to the machine and the machine predicts that it is a mango and I give a feedback, wrong, it's an apple, it notes it down, and now when I feed the apple again to the machine, it says that it is an apple. So making the overall picture a quick recap, that basically, if we talk about machines, there are three types of learnings. We have the supervised learning, where we have the input and output. And this supervised learning is capable of calculating error, that is output minus the input. And what is because why are we capable of calculating error in supervised learning? Because we have the actual output over here, right? And based on the actual output, is my machine predicting the correct result? That if it is an apple, is it actually telling me an apple or not? Or is it telling me this is a cherry? So I can calculate my error. So the biggest advantage or the simplest way to learn is supervised learning, where we are capable of calculating the errors, right? Here we have unsupervised learning, where we do not know the output. It's just trying to do the clustering and association between the objects. And the other type is reinforcement learning, that is not going to be part of this journey. That's generally taken into deep learning concepts, that where the machine learns from its, punishments and rewards, right? And of course, that we are capable of calculating error. Again, I'm telling you, in this particular course, we are going to try to cover supervised and unsupervised learning, concepts, algorithms in detail. Now, moving ahead to supervised learning. There are two types of supervised learning. We have regression, and then we have classification. We have regression as well as classification. Now, what is the difference between the two? Please try to understand. Under supervised learning, if the output, it's all about output. If the output is numerical, then this is known as regression. And if the output is categorical, then it is known as classification. Getting my point, learners? What we are trying to achieve, that what is going to be the temperature tomorrow? So if it gives me that tomorrow it is going to be 84 degrees Fahrenheit or any other value, then this kind of algorithm is regression. But if I want to predict whether the temperature is going to be cold or hot, this is known as categorical data. Clear? So the regression works on numeric and classification works on variable and categorical. Two types of numerical data. One is discrete, another one is continuous. Do we understand that? And if we talk about categorical data, do we understand nominal and ordinal data? This is what is covered in data science class. So basically, data types are divided as qualitative and quantitative. Very, very important. When you divide the data as qualitative, it's categorical. Ordered data is something, like rating, ranking, they come under order. Feedbacks of movies. Nominal is that there is no order as such, the color of the eyes or nationality. And quantitative is numerical values. Continuous, which can be divided, such as distance, salary, price. And something which cannot be divided is example, cats, etc. So now I hope the concept of regression and classification is clear to everybody, right? So making your concept more clear, that regression is something when the task of predicting a continuous, quantity, that I want to predict the price of the house. That price of the house in 2014 was this much. Then in 2024, it is this much, right? And then what will happen? What will be the price in 2034? Clear? So since price is a numerical quantity, it comes under regression. And classification, as I told you, that if I want to separate whether the mail is a spam or not, that comes under a classification problem. Clear? So now we will begin our journey in this machine learning through supervised learning. First, we will try to complete algorithms which are like simple linear regression, multiple linear regression, polynomial, support vector, decision tree, random forest. We are not covering neural network. All the others will be covered. Similarly, in classification, we will cover logistic, K nearest neighbor, support vector machine, naive Bayes, decision tree, random forest. Again, neural networks are not covered. Yeah, so with this, we come to the end of the introduction. And if you will now look at your slide, the ebooks, that is lesson number 2. Now we can begin with lesson number 2. So just have prepared the foundation for that. So let me show you the lesson number 2. All right, so we are now starting with this. I hope now you would be able to locate this particular file in your LMS, in your material. Please look at that. So analyze the distinctions and applications of machine learning, deep learning, artificial intelligence through the real world examples of various technical applications. Differentiate among various machine learning models and explore each model learns from data to predict outcomes. Explore Python libraries for effective data manipulation, visualization, implementation, and machine learning algorithm. So the business scenario says that ABC is an e-commerce company which is struggling with a surge in fraudulent transactions on its website. The manual review process for transaction has caused delays in order processing and led to negative customer experience. To address this, ABC will use machine learning algorithms to detect real-time fraudulent transactions. So machine learning algorithms are capable for detecting the fraud transaction. And these algorithms will be integrated into the company's transaction processing systems to flag suspicious transactions and prevent fraud. Additionally, the company will use these algorithms to predict the customer behavior on the past purchase history, thereby improving the recommendation engine's performance. Now everybody is using mixture. Everybody wants the best. The more you learn, the best output you get. And when I say best output, you want the prediction to be highly accurate. So when your report goes to a machine learning or an AI machine, it has to give accurate result that whether you are, that predicting that, it should be accurate enough to predict that, yes, you are, you know, uh, you have a tendency to have cancer or not, So no, not only one technique will be used, it will try to use mixture of techniques to get the best results. Got it now? So now are we clear what is machine learning? So machine learning is a subset of AI that assists systems to learn and improve automatically from the experience without being explicitly programmed. Arthur Samuel coined the term machine learning in 1959. It enables programs to learn automatically, making computers more intelligent without human intervention. But human feedback is extremely, extremely important because, see, ultimately, machines are not genius. We have to tell them that this is, an acceptable result or not. So who is known as the father of machine learning? It's Arthur Samuel, and he coined the term machine learning in 1959. Father of AI, that's John McCarthy in 1956. Yes, John McCarthy in 1956. Are we now more clear what is the difference between the traditional approach where we had the data and where we were programming explicitly the output, right? And the machine learning approach based on the algorithm, based on the data, the patterns it understands, it predicts the output. That is why statistical techniques, algorithms are the foundation for machine learning. It automatically learns the features and reduces the need of manual featuring. Clear? It handles complex and unstructured data such as images, text, audio without requiring extensive pre-processing. Performance improves with more data and learning iterations, enhancing accuracy and generalization, right? And now do we understand this Venn diagram also, that machine learning, deep learning, AI are often used interchangeably? So AI encompasses simulation of human intelligence in machines. So self-driving cars are, AI. All the robotics come under the category of AI. But machine learning, Amazon Alexa, where we are giving it specific instructions and it gives us output. And when I talk about deep learning involves neural network, which is going to be your next stage after machine learning to understand how neural network, work, how are they capable of understanding complex pattern recognition, such as recognizing patterns in images, speech, text, etc. So, what are the examples of machine learning? In a chess game between a computer and a person. So why do you think that? Why is this chess game always coming into the picture? Why do you think is the chess game always coming into the picture? Well, when we talk about human beings, a person who plays chess well is said to be intelligent. It's an intelligent game. Agreed? Is said to be intelligent, and even if the results go wrong, there's no harm. There are no catastrophic results, Even if the person is winning and says the machine is winning, it is not that harmful. Yeah. So that is why, was one of the way where AI exploded in, intelligent gaming systems, theorem solving. That is why chess, AlphaGo, these are the games which you will, read or see when we talk about a little history of AI. So in a chess game, between a computer and a person, the computer uses AI to analyze the game, predict moves, decide its decision. AI uses machine learning to figure out the opponent is a beginner, intermediate, and an advanced level. How the AI uses machine learning to identify whether you are a beginner, intermediate, or an advanced player by predicting our moves, based on our moves, it will immediately judge, that you are a beginner or intermediate or an advanced level, right? And you might be playing a lot of games where there is AI and other, graphics games over there, especially the young generation, right? Well, I don't, but you can, how smartly, they are capable of hiding things and they become smarter. The level changes, as you are also becoming smart, the level of the game becomes smarter, right? We all observe that. So AI decides its next move against the opponent using a complex neural network that learns various features, patterns from the data, right? Then, of course, many applications are there. We see machine learning all around us in spam filtering. Spam filtering actually use knife-based classifier, social media analysis, customer service chatbots, now a lot of available online recommendation. We all see that. Sentiment analysis. How does the sentiment analysis happen? Anybody who has an idea based on the words and especially the emojis? Is it a smiley? Is it a angry face? Is it a sad face, crying face? All these things are taken into account. So these processes allow computers to learn patterns from the data, make predictions, predict outcomes, classify target, feature, and improve performance. So that's what we want. Machine learning, that they help to predict the outcome, what is going to be the price of the house or any other thing after 10 years down the line, classify target features based on the similarities and improve the overall performance of the system. And we have seen, is there a very, very strong relationship between the data and the output? Yes. The amount of data, if it is more, of course, the output or the quality or the prediction also increases. Where the red line is the quantity, and if it is high quality data, we get better results, better insights, and better predictions of the output. So, of course, maintaining the quality, authenticity, and removing the errors, all these points have to be taken into account when we are talking about the data and the machine learning algorithms. Clear? Right? So when we talk about types of machine learning, ML can be divided into 4 main categories, each characterized by its capacity to predict the conditions or identify the patterns to produce outcomes, such as what is supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. Now, I think the distinction is clear. Supervised learning, we've done this. What are the 3 main points under supervised learning? First is the label data. What do we mean by label data? It will have the input as well as the output. Second point is splitting of the data into training and testing, right? Generally, training happens on most of the data and testing on the rest of the data. And third is calculation of the error. Because in supervised learning, we know the actual output also and whether it is predicting it right or wrong. Clear? And some commonly known, supervised learning algorithms are linear regression, decision trees, logistic regression, support vector machines, etc. So some examples of supervised learning are predicting temperature rise based on the yearly temperature trends. Predicting why supervised learning? Again, predicting temperature rise. It comes under regression because it's a numerical problem. Right? Numerical output. Predicting crop yield based on the seasonal crop quality changes, again regression. Sorting waste based on the known waste items corresponding to the waste type. This type comes under classification or filtering. So under supervised learning, calculation of error is also going to be an important aspect of machine learning because we have to be very clear that the output of machine learning will always not be 100% correct. Clear? Now these examples making the picture more clear? And if we talk about unsupervised learning, very much used to identify different parts of the object, image segmentation for object detection, identification of user groups based on commonalities, identification of anomalies over geographical landscapes based on the data patterns. The unlabeled data set is provided to an unsupervised learning algorithm to discover hidden patterns and to recognize their relationship. So it's not that unsupervised learning is not important. It is equally important to analyze different features, different relationships in the data, right? Rather, this is the algorithm which helps us to discover the hidden patterns and discover the relationships. Clear? And now coming on to the unsupervised learning example, it automatically groups the images based on the similarity that this is unlabeled data. Based on that, it is capable of distinguishing the middle-aged people, old-age people, the young, the infants, the teenage, etc. Got it? And what is semi-supervised learning? As I've already told you, it uses a combination of small amount of labeled data. Sometimes, the data is, that's one of the constraints that we see in data is not completely labeled. A large amount of unlabeled data is used for training. Like supervised learning, it aims to learn from a function that can accurately predict the output variable from the input variable. It uses the unlabeled input to assist the learning process by collecting more information, improving model generalization. So it falls between supervised and unsupervised learning. So suppose this is my raw data and I have partial that this is adults and these are kids. Then the machine automatically distinguishes between babies, teens, and tweens, and also distinguishes between the senior citizens, youth, and adults. Got it? So it automatically learns the correct, groupings of the kids or the different people into teens, tweens, and babies, and the adult ones into these category. Clear? And another example of semi-supervised learning, which we see it practically, that was your question, Megha, that Google Photos is popular example of semi-supervised learning, that when a picture is taken, it gets stored in the Google Cloud platform. And from slowly, the Google tracks, whose picture it is, at what place it was taken. So in various instances, uploaders label images. Despite Google's lack of knowledge regarding image names, its algorithm can identifying by analyzing visual features and shapes and colors. And it does that. It does a lot for me. It's able to identify my friends, my family, in which location I was and where. And reinforcement learning is a type of machine learning where algorithms learn from the environment by performing actions and receiving either rewards or penalties as feedback. If the program finds correct solution, the interpreter rewards the algorithm. If the outcome is incorrect, the algorithm is penalized for incorrect predictions. It must reiterate until it finds a better result, right? So ultimately, reinforcement learning involves an agent. It interacts with an environment, learning from the rewards and states to choose from, and then based on the output, it gives the best action. And if it is an error, it learns it again. All right. So this is my input raw data based on the environment, reward, state, and action. It's capable of detecting them separately. Okay. So the example is this type of learning is seen in YouTube recommendation where the user searches for a particular song. The program shows the list of available songs. So when a user selects a specific song, the system trains itself to remember and deliver similar results for future searches based on the user's interaction, like views, shares, etc. So this is the concept on which recommendation systems work. So other examples of reinforcement learning are game where players can play with bots, autocorrect tools, search recommendation engines, self-driving cars. And then the Python packages that we would be doing in for machine learning. We are aware about NumPy. It's a very powerful tool for numerical Python computing. Matplotlib for drawing data visualization. Pandas. So I hope you all are aware about NumPy, Matplotlib, Pandas. But we will be working more on the Scikit-learn, file, which consists of different algorithms. But the pre-processing, the other part is also being taken care before we feed into the algorithm. So a quick recap. So machine learning refers to the machine's ability to learn from the data and replicate human behavior. AI includes machine learning, deep learning, each with unique capabilities for simulating intelligence. There are four main types of machine learning: supervised, unsupervised, semi-supervised, and reinforcement learning. Python packages are folders with modules that organize code for easy reuse and maintenance, improving the development efficiency. Now, clear? So now let's go in for a knowledge check. Question number 1. Yes, learners, are you there? Which of the following best describes the machine learning? A, B, C, and D. Question number 2. Which example illustrates the use of machine learning to enhance customer experience in an e-commerce company? What distinguishes between deep learning, machine learning, and AI? Yes, it is a subset of ML that uses multiple layers for complex pattern recognition, such as recognizing patterns in images, speech, and text. Right. So with this, we come to the end of the very introduction and basics of machine learning. Yeah. So what I'm looking forward is, this is the overall picture of statistics that we have. The learners who have already done data science are aware about it. The ones who are not aware about it, the different types of statistics that we have is descriptive. Under descriptive, we have measures of central tendency and measures of variability. Under measures of central tendency, we have the mean, mode, and median. Under measure of variability, we have the range, variance, and dispersion. And here we have the inferential statistics, how we infer the results. So this is the important part that we are looking at, that includes confidence interval, hypothesis testing. So you can do a lot of search on inferential statistics. And this is what I am saying, that statistical inference, constructing confidence and intervals on population, hypothesis testing, that is what I'm looking. And what is the advantages of these particular program? Because ultimately, probability in data science and AI play a very, very major role in understanding uncertainty, predicting outcomes, how probable the correct the output is. Even the LLM models, the chat GPT is predicting on the probability. Okay, this is the next word. So if it is 70% above, then let's predict the output. How do we model complex system? Enhancing AI. And it is the statistics and the probability together which help in exploratory data analysis and give meaningful insights and features. So as we are going through this flow, we understand we are going to start with supervised learning. What is supervised learning? Before supervised learning, I would like you to cover, cover the basic concepts of machine learning, which I've prepared through my PPT, and then we will move on to what they have shared. Okay. So the first thing is regression, What are the two main algorithms which come under supervised learning? Yeah, regression and classification. What is the difference between regression and classification? Basically, regression happens when the output is numerical and classification happens when the output is categorical. All right, so I start with my PPT again so that it helps and it gives you strong foundation, clear concepts so that we can move along with that. So if we talk about the first knowledge check, what is machine learning? Correct answer, it is C, that it is an autonomous acquisition of knowledge through the use of computer programs. Second question, what is the key difference between supervised and unsupervised learning? A and B are both correct. What's the key benefit of using deep learning for tasks like regression? How do I, okay, you've written yes, okay. What's the key benefit of using deep learning for tasks like recognizing images? Yeah, they can learn from complex details from data on their own. That's the idea of deep learning. That's the use of neural network. Absolutely correct. All right. So now we start with the concepts of machine learning under supervised learning, which are valid for regression and classification algorithms. Whenever you will say, machine learning, these are the basic questions that will be asked, right? So if I talk about machine learning or supervised learning, what are we trying to, do in supervised learning? What is the main aim? What is our main objective of supervised learning? But prediction of the data. Okay. We would call it prediction of the data, future based on given data, right? We want to predict. And is this prediction always correct or it can be wrong? Can be wrong. They can be errors, right? Right. And so they should be a limit of accepting the errors or rejecting the result, right? There should be some way of accepting and rejecting the results. We all understand this very in a conceptual, subjective matter. Now let's try to understand it on the basis of mathematical functions, right? So here we have the plus over here and here we have the minus over here, right? This is my data set. This is my x-axis and this is my y-axis. These are given as my data, right? And what are we trying to do over here? We are trying to predict the output. So what are we trying to predict? The data, that what is the value of this question mark? What is the value of this question mark? All right. And what is the value of this question mark? Right? Is this question mark a plus sign or a minus sign? Can you tell me? What is this question mark, a plus or a minus sign? What about this? What about this? So this is my first question mark, second question mark, third question mark, and fourth. So based on your observation, can you tell me what is this first? Do you think it is a plus or a minus sign? What does this particular data point represent? Is it a plus or a minus? Because this particular data point is more close to the plus. So if there are chances that this is going to be plus sign, more chances. Yes, it can be negative also, but we can say 70 to 75% or 90 to 95% chances are that this is going to be plus. What about the fourth one? This is negative. Now, what about the second and the third one? What about the second? What about the second and the third? This is going to be a little difficult to say that this can be plus, this can be minus, based on the way the neighbors I am selecting, what will be my output. Agreed? But if technically now, if I use a straight line function, mathematically, how do we use a straight line function? That y is equal to mx plus c. So in all the points which lie on the left side of this line, they all are known as plus. They all will come under the category of plus. And the data points, now all the points which are lying on the right side of the line, they will be all negative because most of the points are minus or the red points. Can I say that all the points which are lying on the left side are plus and all the points which are lying on the right side are negative? There are very few. There is only one plus sign, and if you see, all the points belong to the red negative class. One way I have to do something. But again, the question is, why this straight line? Then how do I decide the straight line? So one point to understand is that when data points are given, that is known as a hypothesis space represented by capital H, and the line is represented by small h. Right? And it is going to be this red line which is going to divide the data points into two different classes. So they can be more than one solutions to a problem or infinite solutions. I can draw infinite straight lines. But which one to accept? The line which will be accepted is going to be one with gives me the minimum error. Right? The error word will be different for different algorithms, but I will accept that straight line which will give me the minimum error, or I can say the maximum accuracy. Clear? We will calculate, as I told you, in supervised learning, we keep the track how we can have maximum accuracy and minimum error. So what is the capital H over here? Hypothesis space is the set of all possible legal hypotheses. This is the set from which the machine learning algorithm would determine the best possible only one, which would best describe the target function. And small h is a hypothesis function that best describes the target in supervised learning algorithm. So now, technically, what does supervised learning mean? That the hypothesis or the small h, they can be several small h that an algorithm would come up, depends upon the data, also depends upon the restrictions bias that we have imposed on the data. So next thing is, we need to find out mathematical functions which give relationships between the data points, right? So basically now the idea is that we want to find a mathematical function where, we want the error to be minimum or the result to have maximum accuracy. Again, I am repeating, we want to find a simple mathematical function which gives me minimum error or maximum accuracy. Clear? Thank you, Atul. Thank you for your understanding. Thank you, learners. So now, what are the different stages that we are looking at? Now, suppose data points can be of any kind. So if this is my data points over here, and if I want to solve it with a simple linear function, see, straight line function is a simple mathematical form, calculation that y is equal to mx plus c. Okay. So when y is equal to mx plus c, right? And if these are my data points, now how do I calculate my error? This is going to be actual minus the predicted. It will have very high error. And this particular concept is known as underfitting. Do you think that this straight line is consistent covering all the data points? No. Right? So the simple straight line equation or function is not capable of covering all the data points. That is known as underfitting. Other way is that if I draw a function which passes through all the data points, so it makes it a very, very highly complicated mathematical function with high degree, right? So it makes a complicated function with high degree mathematical function. That also we don't want. Why we don't want? Because if the data point is out of all the data points, then this is going to give me my maximum error. So we want a mathematical function which is simple and which covers all my data points. So something like this exponential, right? And this gives me a good fit or a good balance. Now clear? So Ajay says no. So the model even fails to predict labels, what it learned, right? It will predict the labels, but with very low accuracy. The error will be high. So we will not accept models with high errors or low accuracy. So overfitting is a situation. How do I know the error is high? Overfitting. So one way is that error is equal to, if I talk in technical terms, so how do we know that if it is underfitting, overfitting? So that's what I'm telling you. Generally, the formula for error is bias square plus variance. What is it equal to? It is bias square plus variance. But the equation is in good balance, not linear. Yeah, it's not necessary that it has to be a linear equation. No. We want an equation which is simple and nice. So how do we know? So now if I say that error is equal to bias square plus variance over here, right? And this is, so how do I know whether it's overfitting or underfitting? It's not about the straight line, but when I have variance, if the variance of the data goes very high, then I know that it is an overfitting model. If the bias of my data goes very high, I know it's an underfitting model. And to keep my error low, I want the bias as well as variance to be low. Getting my point? Right? Now, what do we mean by bias and variance? A very, very typical example. A bias means how far are we away from the original data points. So bias means we are close to the center. Variance, what does variance mean? The spread of the data is also low. So this is the ideal situation we always want the data points to be in. This is where we will say, okay, a good fit has been achieved, where we have the low bias and low variance. Okay. And when we have the low bias and when we have the high variance, low bias means that the data points are near to my actual target points but spread out. So what is the case? Happens over here. This is known as the overfitting case. And what is high bias and low variance? That over here, these are my data points. And this is high bias. So this is underfitting situation. So in whole of machine learning, we don't want underfitting. We don't want overfitting. Of course, this is a worst case where the bias is more, variance is both. The idea is to have low bias as well as low variance. Clear? Okay. Now, I'll explain the previous example with this explanation after this, Puneet. I think so this will make things more clear. So these are my data points over here. A linear model is not a good fit, underfit. That means over here, what is more? My bias is more. What is bias? That my data points are very far away from the actual points. Bias means we are far away from the actual points, right? This is high bias. And what is variance? Variance is when the spread of the data is more, right? And when spread of the data is more or my mathematical function is too complex, then it is overfitting. When my mathematical function is too simple, it is underfitting. And when it is a balance, it gives me the right data. So now when I talk about complexity, now when I say overfitting means more complexity, that generally linear models give me underfitting, right? We start with simple models, but generally they do underfitting. Then we will move on to non-linear models, support vector machines, tree-based models, deep learning models. Why are we doing this? Because they give me more results, better results, more accurate result, less of error. But what is the cost? That my model has become complicated. I'm losing the interpretability of the model. What do I mean by interpretability? That if this is my input, right, how do I know that this is going to be my output? That's possible in linear model because I know y is equal to mx plus c, that if this is my input, I will get this output, otherwise I will not. Clear? And to make it more clear, the overall picture that I was talking about, please look at this slide. So ultimately, where is the trade-off? Where are we fighting in the whole of machine learning models? If life was so easier, wouldn't have the problems be solved by now? But no, there is still a trade-off which is going. So how will I know it is underfitting though it is showing in diagram? Is there any? Yes, they are mathematical way. But first, let's get the grasp of the thing, okay? That ultimately the idea is to get highest accuracy, right? And interpretability is also important. Why? Because we want to see why am I getting this output. So we always start with linear regression or logistic regression problems. That is what we do. That is what we are going to do in our whole of this journey. And why linear regression? Because they are linear and smooth, well-defined relationship, easier to compute. And as we move along this journey, decision trees provide good accuracy with high interpretability. KNN clustering. Clustering and KNN algorithm are mid-range. Interpretability is okay and accuracy is also okay. But if I want really good accurate results, that is why new algorithms, complex algorithms were built with kernel-based approach for support vector machines, ensemble methods, and of course, neural networks. Now clear? Is this slide getting clear to everybody? That is why complicated neural networks are capable of solving non-linear relationships, non-smooth relationships, and long computation time. Clear? Okay. If I want interpretability of the models, then I might go in for decision trees, but I will have to compromise on my accuracy. But if I am not interested in interpretability, that we are not, we always want best result. That is why neural networks, deep learning have taken the market. It is we as users who will decide. What is the difference between accuracy and interpretability? Interpretability is how am I going to find out the relationship of output given a particular input? So if I know a mathematical equation, okay, this is related with beta naught x1, beta 2 x1, I know why am I getting the result. But if it is some integratable model like neural networks working in layers, in different layers, in some layer differentiation, integration, addition, subtraction is happening, I will not be able to interpret the result, but it is giving me highest result, then of course I will use it. If I have a very mathematical complicated system. See, now try to understand the whole story again. Let me just repeat the story because this is very important. in the whole of machine learning, and these concepts are valid for deep learning also, okay? The story says that we want to predict the output or the data. We are clear? The first point says we want to predict the output of the data with minimum error or maximum accuracy. First 2 points are clear? The threshold, Simon, is maximum accuracy and minimum error. That point is clear, right? And which is the simplest mathematical function that we have? We always talk about a straight line. If that straight line is giving me minimum error, is it that only we will always apply one algorithm, or is it a different algorithms or a different hit and trial methods that we have to apply? It is different hit and trial methods, algorithm that we will try to get the output. It's not just, oh God, regression and decision tree is working. Okay, this is the end of it. No, you might go in for advanced algorithms, and that's where the research is going. Why do you think that the problems are not solved? Because every time, every algorithm will have its own pros and cons, and the research is going at each and every level. And it's still going, we are just trying to improve on the algorithms every time. Why? Because we still see the LLMs, the chat GPT giving us wrong answers, wrong predictions. So there is still a lot of scope of improvement, where we have to work. Clear? So life was, if the thing was so easy, I think so by now, everything would have been solved by AI and machine learning algorithm. No. Why is it not simple? First, data is variable, uncertain. It keeps on changing. Secondly, every algorithm has its pros and cons. So the errors, the accuracy, my requirements upon the product, on the data or the algorithm keeps on changing. And that is why this change happens. Right? So they are plethora of algorithms which have been built. As in machine learning, we will always start with linear regression algorithms because of the simple mathematical function and high interpretability, but they have minimum accuracy. But as we move along with the journey of decision trees, clustering, kernel-based, we want maximum accuracy, but the trade-off is that we decrease on the interpretability of the model, right? So as I have been telling you, splitting the data for machine learning in supervised learning, we always want to select the data randomly. So there is a function train underscore test underscore split that we would be using to split the data. Train underscore test underscore split, which is part of the Scikit-learn library. This is my data. And we will be randomly selecting it and dividing into training and testing data. Now clear? And most of you see this is around 70 to 80% of the data. And this is around 30 to 20% of the data. Puneet is just wondering if interpretability is more important as we go to complex problems. Not really. Not really, ultimately, Puneet, not really, because we are always interested in the final result. It's something like, as I give my example, suppose, you have a magician and, the magician turns a pigeon into a flower. Are we interested how does it does, or are we interested in the output as a flower? Okay. So we are always interested in the output. Got it now? Better? Yeah. So if logistic regression is having minimum accuracy, then it is a no, Nanda. No. The accuracy is less over here. It doesn't mean that it's a wrong prediction. Logistic regression might not give you the best results for the prediction, and maybe using a neural network would give you, it's something like, using logistic regression is giving you 70% of accuracy, and neural network is giving you 97%. So that's the difference. But of course, neural networks are better. That means, right? Got it? So yeah, there are a lot of terms which you have to be associated. You have to understand it in the correct sense. I understand I'm giving you time for doing that. Yeah, now coming on to the part that you all are interested that, ma'am, what is the mathematical equation? How do we know the mathematical term which is used to see the output? Now, first of all, we are going to calculate error, right? In regression, the error is known as mean square error. Now, let's start understanding this. So, we have this mean square error, okay? The error name is that I'll explain you technically when we move on to regression. Now, in supervised learning, whether it's classification or regression, we know the data is divided into training and testing. Now, tell me which error is more important. Now, let me put it in this way, that you go to a class, and you are pursuing some course, you do errors, you are learning, and you do errors while training, right? And still you don't perform well in the test. And there is somebody who doesn't attend even one single class and performs well in the test. So which error is more important? It is the training error which is important, or the testing error? Among the two. Of course, both are important, but among the two, which one is important? So what is more important, to have the training error less or the testing error less? The training error is less, but the testing error is very high. Is it a good thing? It's an even big failure. So again, I'm asking you this question. Is the training error important or the testing error important? Of course, the final test, if you're not performing well on the final day of the test, then the whole training is useless. Agreed? So when my training MSC is high, of course, I can reduce my training by giving in more data, and my testing MSC is less. What is this case? This is the case of underfitting. Of course, the training error should not be high than the testing MSC. The model is too simple for it to solve, and then I will say the model is underfitting. Now clear? That was the question, I think so. So now clear mathematically. So this is how I will judge based on my training and testing that my model is underfitting. So I will now not use a straight line to solve my data points. I will not use. Okay. Other is my training MSC is 0. Excellent. But my testing MSC is so high. Absolutely not acceptable case. So this is the case of overfitting, which is high variance. And what do you think the data or the model goes through? Is it more of underfitting problem or an overfitting problem? What do you think? Most of the models in machine learning face which kind of problem? Reducing the training error is easy, but failing on the testing is a total failure, and that is what we will look at most of the algorithms, that how to prevent overfitting in the models. That is why I was telling you these concepts are very, very common to machine learning, deep learning models. So are you getting a grasp of it? And I don't straight away start with regression. Come on, let's start doing it, other things. You have to have good foundation of machine learning concepts, so that, you understand other materials, the in-depth knowledge, how we accept and reject the particular model. Training and testing, that we will decide, because when the data is there, we will split the data into training and testing, and then we will calculate the training error separately and the testing error separately. Okay, we will have suppose I said 1000 rows, 700 rows will be used for training. Then we will have 300 rows used for testing. Then calculate the errors for training and testing separately, and then decide whether it's underfitting or overfitting. So what will be the best case? Where my training error is also low testing error is also low or almost equal to each other. So again, looking at the concept x-axis, we have the model complexity and then we have the predictive error. So over here on the x-axis, this is my underfitting over here. And if what is overfitting? That when I start with my model, simple model, my errors are high, both the bias and both the test and as well as the training. As my training increases, the training error or the model complexity increases, the training error decreases, but the test error will dip and then increase because of high variance. So we want to find out a model. How do I decide which model is best for my data? Where the training and the testing error are minimum or close to each other. So this is what I'm trying to explain you. Please try to understand that as the model complexity is less, here we have the bias more. As the complexity increases, the bias decreases. When the interpretability is high, the variance is low, and as the complexity increases, the variance increases. But we are looking at a point where these two intersect to find the optimal model complexity. The variance is the spread of the data. Variance is a statistical term which means the spread of the data. So as my model complexity is going to increase, the complexity, as the complexity of the model increases, the variance or the spread of the data also increases. Got it? That's the relationship. Again, I am telling you, we are trying to create a graph between error or accuracy is going to be opposite of this. And this is my model complexity. We always start with minimum complex model. This is the case of underfitting. Agreed? When my model is simple, but my bias is high, as the complexity of the model increases, my bias decreases, but my variance increases. So I don't want the overfitting situation or the underfitting situation. I am looking at a situation where my error is minimum. So the test error is U-shaped in curve, and where the value is minimum, that becomes my optimal model complexity. Now clear to everyone? Okay. Now, now since the topic has been taken, now let's do one thing. If you have downloaded the ebooks material, I want everybody to make a folder in the desktop and move under lesson number 3. Something like this. See, what I would see is, let me share my screen. In work and data break, how do I understand that? So once you are into, now we're starting with lesson number 3. So do you see this 3.1 and 3.2 learners? So how do you go about opening it? Open the Jupyter notebook environments, install and open the file along with me. So chapter number 3, we have to start with lesson 3. Lesson 3 is supervised learning, regression and its application. Yeah, are we all able to open this? Let me guide them that how do we go about it. See, the prerequisite for the course I've been telling it is Python. So we like there are a lot of tools like PyCharm, VS Code. You can do it through other tools, but generally we use Anaconda Navigator download. Please go ahead and go to the Anaconda, fill in your like the details, the email ID, and I want everybody to download the Anaconda, right? And based on your system, whether it's Mac, Linux, or Windows, and go in for a full distribution. Don't go for mini Conda. Google Colab. If you're aware about Google Colab, that's also one of the online tools available, which helps you to run the code in the Jupyter kind of environment. Let me show it to you. Anaconda distribution, go and download it, install it. Or the other one is go to Google Colab over here. Just log in through your Google account. That's the another way to go about it. And from here, I will upload the file. Which file? The file which I have already downloaded on my ebooks. That's there on my desktop. Machine learning, third chapter, 3.1. And I open it. Yeah. So there are 2-3 methods, whichever one you are comfortable with. That's not an issue. If you're clear, you're comfortable, Anush, on VS Code, that's not an issue. Got it now? Everybody is there with me now. So this is one of the very safest tool. You don't need to, download the Anaconda on your desktop through the Google Colab, through your good internet connection, you will be able to run the code. Yeah, so this particular file is, basically if I talk about 3.1, again, I'm repeating, go on to your learning management system on the reference material. Please download the ebooks, the Jupyter notebooks, and then try to open. So if we talk about, if we are back to 3.1, let's quickly go through the file. That file is completely theoretical. Okay, nothing great in that file. It talks about what supervised learning is and what are the two types of algorithms in supervised learning. It's regression and classification. What is the difference between regression and classification in supervised learning? In regression, the output is always numeric. And classification, output is always categorical. So when the target variable is categorical, we do classification. So this example, we are very clear. So when it's predicting numerical value, right, that is regression. When we are predicting a categorical outcome, determining the whether tomorrow it is going to be hot or cold, visualization, the same thermometer scale divided into two colored regions, cold and red for hot, with the threshold separating is classification. And if you look at the applications of supervised learning, do you think HR people use machine learning to identify the different job profiles, shortlisting of the resumes? HR is also using machine learning now. Yeah. In finance, what is the use of machine learning in predicting of fraudulent data? Are you ready for that loan approval or not, right? And this is similar to how a credit card company determines your credit worthiness before issuing a card. Then emails, this is about spam filtering, whether it's a spam or not. Manufacturing, anybody in manufacturing? So in manufacturing, supervised learning is also used to inspect the quality, classify the products into different grades. For example, a factory might use a machine learning model to check for defects in products and ensure they meet quality standards, much like the quality control inspector. Maritime industry, it helps in forecasting the historical events, weather condition. So precautionary accident, it's capable of predicting any kind of, weather. It might get wrong also, which we have seen. And supervised learning techniques like regression model can be used to predict tidal currents, forecast demand and supply, reducing inventory losses. Think of it as how weather forecast predicts rain based on past weather patterns. Fraud predictions, we use this in agriculture field too. I'm into automating parking. So under supervised algorithm, there are a lot of algorithms that we will begin tomorrow. Tomorrow, again, as you understand my style, we'll start with regression, then linear regression, logistic, naive bias, KNN, under classification. They all come under classification. So under linear regression, we would be working on multiple linear regression. And before we move on to classification, there are a lot of concepts that we will study, such as, cross-validation, regularization, hyperparameter tuning, sklearn pipelines. So there is a lot more to be explored tomorrow. We will be concentrating on linear regression and its concepts tomorrow, right? And linear regression is now very clear where the output is numerical. Then, like predicting housing pricing, we will use regression. After doing supervised regression in supervised learning, then we will move on to classification algorithm. Under classification, plethora of algorithms that need to be done. Initially, we'll start with logistic regression, naive Bayes, KNN, decision trees, random forest, and support vector machines. So it's a long journey. Tomorrow we'll do linear regression. Next weekend we will be doing classification. And then we will move on to the next stages of ensemble learning. Then it is unsupervised learning, right? So I think so you all are excited about this journey. So it's a long journey. I don't want to burden you today with all the concepts. So let's go slow and steady. That's my rule. Slow and steady wins the race. But I hope you got the crux of today's class, right? So this is 3.1, right? And we'll be beginning with 3.2. We started with the very first session of machine learning, where we understood what machine learning is, what are the different types of learning techniques, what are the different types of machine learning techniques, supervised learning, unsupervised learning, and reinforcement learning. What is supervised learning? Supervised learning means it consists of labeled data, which consists of input and output. We split calculate the errors. The two main algorithms under supervised learning are regression and classification. Then we understood unsupervised learning. Unsupervised learning consists of unlabeled data, where based on the similarity of the data, the groups and clusters are formed. So two main algorithms are clustering and association. And last but not the least is reinforcement learning, that based on the feedback, positive and negative, the machine learns. Are we good to go? Everybody is clear with these concepts of machine learning, the basic concepts? And then we started with the concepts of overfitting, underfitting, and a good fit. Yes, learners, now you will tell me what do we mean by underfitting, fitting in machine learning. Very, very important question. It will definitely be asked if you say that you know the concept of underfitting and overfitting. Yes, learners. Can you tell me what do we mean by underfitting and overfitting? Underfitting is the case where the error is high. What error is high? Bias is high. We are very far from the actual data point, but we talk about simple mathematical function. What is the advantage of simple mathematical function? That it gives us more interpretability of the model. What do we mean by more interpretability? That it gives the relationship between the output. And if we talk about overfitting, again, the error becomes high because the variance goes very high, right? And definitely it makes more and more complex. So we don't want a algorithm to be or model to be underfitted or overfitted. We want a good balance fit. That is, how do we judge that? That the training error and the testing error should be similar, right? So today we will start with the first, learning technique, that is supervised learning technique and the regression model. Are we good to go? So as now you are getting more familiar with my style, first we will try to cover the concepts and then move on to the practical aspect. Because unless and until you clarity of what is happening, how are we going to interpret the model, there is no point moving on to the code. But definitely we'll move on to the code. But let's start with the concept of regression. So here we go with the regression. So what is regression? Now, if I ask you, what is regression? Tell me. So when we're talking about regression, learners, please be clear with this concept that always the target variable or the dependent variable are all numeric values or continuous value. Don't say the term data, right? See, everything is data, but if you're not very specific, technically you go very wrong, right? So you have to understand now data. We're talking about structured data which in tabular form. It consists of input as well as output values, right? whatever are the input or the output value, x over here is referring to your independent variables, right? But whenever we are choosing any model or algorithm, we always and always take into consideration the dependent variable. So it is very important that the dependent variable has to be numerical or continuous, right? So we are trying to find out. So basically, what are we trying to find out? We are trying to find out the relationship between the independent variable based on the output. Clear? So let's try to break the term linear and regression. Linear, we understand from simple mathematics that anything of degree 1, any function which has value 1 is said to be linear. So this means that progressing from one stage to another in a single series of steps, sequential extending along a straight line or nearly a straight line. So we all understand the term linear, right? And as very rightly said by Nanda, regression is a statistical terminology which is used to find out the relationship between one dependent variable. We always have one output. If the output is categorical, we will go in for classification algorithm. And if the outputs are continuous or numerical, we will go in for linear, not linear, but regression algorithms. So moving ahead, thus a linear regression means a linear approach from, so when I combine the two terms, linear regression, it means that the linear approach for modeling the relationship between the dependent and independent quantitative variables, it will plot a straight line because that's the simplest linear approach as a best fit along the data points to predict the target value, right? So what are the different types of linear regression available to us? So a simple linear regression is with one obviously the dependent variable is always one. That's the target or the output. But if the independent variable is one, it is simple linear regression and it is always represented by a straight line. So beta naught is the intercept and this refers to the slope. So this refers to beta naught plus beta 1 x1. Getting my point? And then we have multiple linear regression. That is over here when one independent variable, then this straight line turns into a hyperplane. So line in higher dimension, 2 dimension becomes a plane, and in higher dimension, it becomes a hyperplane. Getting my point? Are you all getting the concept, mathematical equation along with the graphical view and of course with the code? I'm trying to explain you from all aspects. All right. And when I say polynomial, sure, Hardik, I can do that. Right. Over here, we are talking about linear regression. Linear means something of degree 1. So do you see all the variables have, all the coefficients have the degree 1? Do you see this? Right? These are known as the regression. So the term linear regression means we are trying to find out relationship between the independent variables with the dependent variable. So a simple linear regression is beta naught plus beta 1 x1. Clear? That is when we have one input variable and one output variable. Mathematically, it is represented by a straight line where beta naught represents the intercept of the line and the beta naught represents the intercept and beta 1 represents the slope of the line. Clear? Have multiple linear regression. Graphically, a straight line now becomes a hyperplane. That is a multiple linear regression. Of course, generally, practically, we will have more than one independent variables with output variables. And then we have polynomial linear regression. That is y is equal to beta naught beta 1 x1, beta 1 x square, and q. Clear now? So now let's try to understand it from now. The same thing from the machine learning point of view. So in simple terms, it is a method of finding a best straight line fitting the given data set. So in simple terms, find a simple straight line which tries to find the relationship between the independent and the dependent variable. And best linear relationship, how do I decide the term best? Something with minimum error or maximum accuracy, right? Something with minimum error or maximum accuracy is taken in terms of simple terms. And if I talk about technical terms, it is a supervised machine learning algorithm that finds the best fit relationship on the given data set between independent and dependent variable, almost the same thing. But the basic concept or the algorithm it works on it is OLS, the ordinary least square method, also known as the sum of the square residuals. Clear? So to explain these terms graphically, mathematically, I want everybody to concentrate here on the graph or the slide shared. So this is an equation of a straight line. What is beta naught? Beta naught is the intercept. What do I mean by intercept? What is the value of y when x is equal to 0? Are you all getting this point? What does the term intercept mean? That what is the value of y when x is equal to 0? Clear? Is this point getting clear to everyone? And if I talk about beta 1 refers to the slope of line. Is this term getting clear to everybody? Since I have only one input variable or independent variable, it represents a straight line. Clear? Now, once we have understood the equation of the straight line, what do these blue blue dots represent? The actual data points available, right? That the first data point has value 1, y is equal to 3. This is value 4 and value is equal to 6. All right. Now, this is where how we are going to calculate the error. What is the error? The actual value. This you can consider this yi as my actual value, and the red dot on the straight line is the predicted value if I want to fit a straight line on these data points, right? So this is my actual output and this is my predicted output. Clear? The error is clear. How are we calculating the error? Now, what algorithm are we technically using over here? Ordinary least square method or the residual. Residual means the error sum of square error. So what does this mean? It is equal to the sum of the square of error, which is actual minus predicted value. Getting my point? So, and why are we taking the square of the error? There is a story behind that also. Why? Because suppose is plus 2, for example, and this error is minus 2. So the total error is 0. So what I'm trying to say is if the error is plus over here and minus, and if I add them, it will show me 0 error. It is not 0 error. So I will try to take the square of the value. It will become 4 plus 4, that is the error is equal to 8. So always the errors are taken as square of errors and we are looking at minimum square of errors. That is why it is known as the ordinary least square method. We want the sum of the square error to be the least. This is known as the RSS. Getting my point, learners? So this is the total RSS. Why the total? For this particular data point, this is going to be my first error. For this data point, my second error. For the third one, fourth one, fifth one, and if they are infinite points, then infinite data points are calculated. Clear to everybody? So why, okay. Now, because this is my actual y1, and what is my predicted y1? This is my predicted value, right? Because we are using Nanda, this particular function, this is my predicted value, and predicted values are represented as y cap. So for the first one, it will become beta naught minus beta 1 x1, then y2 beta naught beta 1 x2 for each data points. Now clear? This is how, based on this mathematical function, I am going to predict my output for each data points. Clear? So the formal statement of simple linear regression. I'm talking about simple linear regression with one input and one output. Y1 is the value of the response variable. Again, predict, target, predicted, dependent, they all mean the same thing. Do not get confused with the terminologies. In the ith trial, beta naught and beta 1 are the parameters. Xi is the value of the predictor variable in the ith trial, and epsilon I is the random error with mean E. Epsilon I is equal to 0 and variance is equal to square. Clear? Okay. Now this random error, this is very, very important to understand that a random error, we are talking about, are we talking about the whole data set or a part of data set or a sample of data set over here? This is my population, and if I take a part of it for training and as well as testing, do I always consider the whole data set or a part of data set? It's always sample. And is my sample, and we want the sample to be the true representative of the population. But since it is a part of the data, there will be some error also associated with it, which is irreducible, that is represented by epsilon, right? So epsilon I is the random error with mean. This is the random error which is always going to be introduced. It's not reducible like bias and variance or overfitting, but it's part of the whole linear regression where the mean of that error is equal to 0 and the variance is equal to epsilon square. Now clear? So the idea of whole linear regression or significance model is that it is highly interpretable. What is the idea behind this? That it is why the error is 0. We always want the error to be 0. In this case, we are considering that, the average of the error, not the square. The sum of the square or the average of the error is equal to 0, not the square. Okay. So now the significance of linear regression lies in the fact that we can easily interpret and understand the marginal changes with input to the output. So linear regression is a highly interpretable model. How is it interpretable? That if we increase the value of x1 by 1 unit, keeping the other variables constant, then the total increase in the value of y will be beta 1, and the intercept term beta naught is the response when all the predictor terms are set to 0 and are not considered. Right? So how much is my y value change will depend on how much is my beta 1, is it positive or negative, beta 2 and beta n. So now, what are we trying to find out in linear regression? The values of beta naught, beta 1 and beta n, right? Where the error is minimum. Clear? Right? I understand, there are a lot of concepts, a lot of mathematical terms coming. So just hold on till we start moving on to the practical part and, you will see them practically. Just try to grasp as much concepts as you can. So different assumptions which we follow in linear regression is linearity. That is the relationship between the features And the target, homoscedasticity, the error term has, this is where, the linear regression has its assumption or constraint, and the term is known as homoscedasticity, that the error term is constant variance. Throughout the whole data, the error term will be constant. Multicollinearity, there is no multicollinearity between the features. And if we talk about independence, observations are independent of each other. Getting my point? Normality, this is where the point I was saying, that the error residuals follow normal standard distribution, where mean is equal to 0 and the standard deviation is equal to 1. Okay, so multicollinearity means that we can have more than one input. Are they related with each other? No. Every first input should be independent with the second one should be independent with the third. The input should not be dependent on each other. They should all be directly dependent on the output. First, let's try to understand the concept. So how do we go about in the supervised learning process? That we have this full data set, right? And we will, after doing all the pre-processing, so today I told you to revise all your EDA, that we will load the data set using pd.read_csv command, do head and tail, try to find out null values, work on them, do encoding if required, and then split the data into training and testing. First step is getting clear. And of course, training can be, it's generally 7 to 80. If you want to keep it 50-50 also, nobody is stopping you. Or 60-40, that's completely up to you. Okay. And the function which is used in Python in the Scikit-learn preprocessing library is train_test_split. X is the first parameter which represents the features of the input data. So this is how we will create a list or an array which will contain all the input. Y refers to the target or the label vector of the input data. Size of the test data, test_size. And finally, we have random_state. What is this random_state? It is the seed that initializes the pseudo-random number generator. What does that mean? That I will give any fixed number. It could be 42, it could be 3, it could be 0, it could be 500, right? I want to keep this number constant so that the shuffling or the randomization of the data happens in the same way, so that I can check the accuracy and do the comparisons. Clear? Right? So again, remember this point. Whenever data is given to you, you have to identify it in terms or split it in terms first, in number of inputs and the output. Always separate the outputs from the input, and then we will use this function and then we will get 4 outputs. Train_test_split gives 4 output, that is x_train, y_train, x_test and y_test. Clear? Training_test_split is used to split the data, right? We are preparing the data which will be used for training and testing separately. So the parameters of this function are input, output, how much we want to give for testing. It could be 3/4, half, completely up to you, no rules for that. And random_state gives me the seed that initializes or does the shuffling of the data in the same manner. And the output of this function is 4 output. I get input training and output training data and input training and output testing data. Clear? And now if I talk about multiple linear regression, right? In 3-dimensional setting with 2 predictors, 1 response, the least square regression line becomes a plane. So this is a multiple linear regression model. Epsilon is the normalized error. okay, which is irreducible. Nothing can be done much about it. And now we will practically deal with data which has three inputs: the budget of TV, budget of radio, budget of newspaper, and which one of them affects the sales most. So this is the first algorithm that we are going to study. Okay. So this is simple, this is polynomial, and these are the errors. So let's start with the practical work and then get back to the different errors and analysis. Got it? Have you got an idea what linear regression is all about? So I request you all learners to, from the LMS, to open 3.2 Supervised Learning Regression, Linear Regression file. Okay. So now, do you understand the term independent variables, straight line? When we have in two-dimensional, when we have one input, one output, it's a straight line. Blue dots are my data points, and this is a straight line or the line of regression, which I want to fit on the data points. This graph is now very clear to everybody. I'm starting with the file now. The first 3.2 regression, this graph is clear. And where do you think regression is used? It has a huge application in oil and gas industry. Various types of data are collected in oil and gas industry, from surface, subsurface, to understand production, sale processes, how much gas is required, how much liquid, how much is the pressure that needs to be created. So linear, non-linear regression model forecast global oil production. Oh my God, the whole world is fighting on oil, and well, we can use our regression models to forecast the global oil production, right? So the whole world is on a big fight on oil only, right? Marketing linear regression helps to analyze the effectiveness of advertising campaigns, predict sales based on marketing spend, segment customer based on demographic data, right? Then we have retail. Then we have linear regression is utilized in retail for demand forecasting, inventory management, pricing optimization, and customer analytics. Healthcare, linear regression is applied in healthcare for predicting the patient outcomes, analyzing relationship between the different medical variables and their diseases. Getting my point? And finally, we have the real estate, that in the real estate industry, linear regression predicts the property prices based on the factors such as location, size, amenities, and economic indicators. Clear? So now what are the different types of regression? Regression can be classified into two categories: linear and non-linear. Linear regression finds a straight line relationship between the dependent variable and one or more independent variable. Non-linear regression finds a relationship between the dependent variable and independent variable using a curve or more complex shape. Okay, so getting back to linear regression, it is, so technically if somebody asks you what is linear regression, in machine learning, you will say it's a supervised learning algorithm which is used to, please try to understand each and every term, is used to predict a continuous target variable. Please be clear. It's not continuous data, as you all were saying. That's a wrong statement. It helps us to predict continuous output variable by modeling its relationship with one or more independent variables through a linear regression. It predicts a continuous dependent variable based on one or more independent variables. So it predicts the continuous dependent variable. Here it says target, output, dependent, completely anything you can say. It uses the least square criteria to estimate the coefficients of the regression equation. What do we mean by the least square criteria? That the value between the actual and the predicted value, the square of the error of this error, that is RSS, should be minimum. That is the residual sum of squares. Getting my point? And it can be applied if there is linear relationship between the variables. So in case the dependent variable is continuous and independent variables can be continuous or discrete. We are not bothered about our input variables. So for predicting the output, we are always considered about the output. So the relationship between a dependent variable y and one more independent variable x is established using a best fit straight line, which is also known as the regression line. And there are two types of linear regression. One is known as the simple linear regression. Other one is known as the multiple linear regression. All right. So simple linear regression is clear to everybody. We have one independent variable and one dependent variable. Do we understand now the terms beta naught and beta 1? This is the intercept and the slope. Yes, everybody is understanding now what is simple linear regression. And as I told you, a simple linear relationship is given by one of the input, that is TV expenses over here as my input. And in the output, we have that sales. That means in this particular data set, we are trying to establish the relationship that if what is going to be the budget of TV and how it is affecting my sales. So what do you conclude? Do you see the red points? These are the predicted values and the blue points are nothing but my actual data points, and I'm going to calculate. It automatically does the calculation of the error if once I apply the algorithm. Clear? So do you see a kind of positive linear relationship? Can I conclude that this shows a little positive linear relationship? That is, the value of TV expenses increase, the sales is also increasing. It shows a positive relationship between them. Getting my point? And practically, if you look at the real world problems, they will not be simple linear regression problem. They will going to be, multiple linear regression problem. There will be more than one input. From how we know positive and negative? See, positive and negative, Basant, that's shows it very clearly from the graph. If the graph is showing this thing, that as my x is increasing, y is also increasing, it shows a positive relationship. See over here. And if x is decreasing, y is also decreasing. But if my graph is like this, what does it show? That x increases, y decreases. And if x decreases, y increases. Getting my point? So this is a negative relationship. Inverse relationship between input and output shows negative relationship. And direct relationship between input and output shows positive relationship. So as I was telling you, practically, if I talk about, real-time data, we have more than one inputs and output. So multiple linear regression models the relationship between the two and more independent variables, predictors, features, and the dependent variable as a straight line. The equation for multiple linear regression is y is equal to beta naught plus beta 1 x1, beta 2 x2, and beta n xn. That x1, x2, xn are the predictor variables, and beta 1, beta 2, beta n are the coefficients of each predictor. So let's start practically working on this data set. That this becomes now, if I want to try to find out the relationship between TV expenses, radio expenses, and sales. So now my straight line turns into this hyperplane. Do you see the difference? How the straight line has got converted into hyperplane? And of course, there is one constraint that we cannot view more than 2D or 3D graphs, right? We cannot view more than 2D or 3D graphs, right? That correlation covariance is same as, regression, but in regression, it's a linear relationship, but the positive and negative relationship is the concept same as correlation and covariance. That correlation and covariance is founded by Pearson's coefficient of correlation, but here we are talking in terms of linear equation. But if I talk about one input x1 and y, how x1 is related to y, then that is r. That is this +1 -1. That exactly is the same concept. The concept is not very different. Linear regression is using that particular concept. All right. So now let's start practically working on the data set. So what I want everybody to do is on your, go from data set folder, open your Jupyter notebooks and keep the tvmarketing.csv data in the same folder where you have kept this 3.2. Yes, learners, wherever you have kept this 3.2, keep the tvmarketing.csv, copy it from the dataset folder and start uploading this data. Clear? And then run this thing. So basically, this data set consists of 3 input variables. This is my x1, x2, x3, and this is my output. All right. So once I have done my head, what does the head command do? What does the head command do, learners? What does it prints? The top 5 rows by default, and these are my inputs, right? And what does the info function do? Good, Rishi. Good, Anush. What does the info do? It tells me there are no null values in this data set. And of course, unnamed is not required over here. And all other, my inputs are also in numerical value. And what is my output? My output is sales, and that's a numerical value. And that is why regression will be used. Clear? And that is why regression will be used. Getting my point? Okay. So what is the first thing that we are going to do? Since this data does not require pre-processing, it's a clean data, so nothing required to clean or check on the null values, etc., right? So we are considering the data to be clean. So now when I want to fit any model, what is the first step that I will do? I will try to separate the input with the output columns. Agreed? The first step is to extract the features of the data set and output. What is this ILOC in Python code? Index-based filtering. So if I see very closely that 1, 2, 3 are my input index, this is of actually no relevance. This is of no relevance. These are my input values. And this is my output value. Clear? So in this case, ILOC, the first colon represents, it talks about all the rows, but only the columns which are there, it says 1 and 2. So how many inputs are we talking about? Only the first one. Only the first one is TV. And what is the output? Only the sales. This point is getting clear. What are we taking over here? We are talking about TV and sales. So we are trying to implement linear regression, right? We are trying to do simple linear regression. This X and Y is clear. I've only taken a part of it. First, I've taken one input and then I'll take all the 3 inputs. This point is clear, right? And then we have the from Scikit-learn model selection import train underscores test underscore split. And now I am taking my input, that is only the TV input. Y is my sales. Test size, 30% of the data is used for testing, and random underscore state is taken to be 42. 42 is generally considered from a fiction that it's considered to be a a good number for the whole universe. Clear? Okay, so now what are the different steps to now fit the model? Not much of coding. That's why Python is a preferred language, beautiful language. That is from sklearn.linear model import linear regression. That is, first we will import the library. That is, sklearn is the main library and we are importing linear regression from there. So when I imply linear regression, it is lin underscore reg, and this is fitting. That is the training input and output training data. Getting my point? Fit function is used to fit the data or train the data. What do we mean by train the data? Finding the parameters over here, that is beta naught, beta 1, beta 2, beta 3, etc. Clear? Are you all there with me till this code? Anybody who's still facing any difficulty, who's not been able to run this part of the code? Till here, are we good to go? First step is to import the library which contains the linear regression model. And then I will create an instance of this linear regression function, right? That is lin underscore reg. It is a instance. What do you understand by instance? Object of this particular function. And then fit the training input and output data. It is divided by using this train underscore test underscore split. And we get these four outputs. Input training and testing, output training and testing. I explained you train underscore test split, where we get the four outputs. Now let's try to find out the linear relationship between the sales and the TV. So TV and sales. So we want it to be an input. So if you visualize the linear regression model, X label, we don't want it to be, I think so that's a little opposite of it over here. This is TV change, make changes in the code, and output is sales. How do we delineate contributing and constraining factors in model? What do we mean by that? Huyan, delineate, what do we mean by that? Okay. So what does this graph represent? What does this graph represent? This plot shows a positive linear relationship between sales and TV, and where the blue regression line indicates the model's prediction. The green data points are generally close to the line, suggesting the model fits the data reasonably well, though some variability exists. Right? So does it show a positive relationship, Basant? Right? Do we see that there is a positive relationship between TV and sales? No, it's not the trained data. It is the test data. Why test data? Because I'm plotting input as training and predicting the output. The x-axis is the input. The x is input, right? And the output is prediction of the training. Right? So we are trying to plot over here. Plot over here is the straight line. Right? But why am I saying the test data? Because actual data points are my input and output test data. Now clear? We are trying to do a scatter plot over here. Scatter plot is between input and output test data. The actual data points are my testing data points. Okay? And the plot, the straight line is input training and predicting the output. That is why it says the linear regression model for test data set. Now clear? So what do we conclude from this graph? We can conclude that the plot shows a positive linear relationship between sales and TV, where the blue regression line indicates the model's predictions. The green data points are generally close to the line, suggesting the model fits the data reasonably well, though some variability exists. Okay, so this shows a positive relationship. Now, the important point is, how do I understand? Is this model underfitting or overfitting? So, when we are developing machine model, what is the most important point, important concept that needs to be taken into account? The concept of overfitting and underfitting. So when developing machine learning models, achieving the right balance between the complexity and simplicity is crucial. What are the points of overfitting? Let's quickly go through that. Overfitting occurs when the model learns the noise and details in the training data too well, to the extent that it is negatively impacts the performance on unseen data, right? That means when the variance is high, sign high accuracy on the training data, but poor accuracy on the test data. So how do I know that my model has overfitted? That I get a good score for training data, but a bad score for testing data. And why is it? What is the reason? Because the model is too complex. It has got too many parameters. Underfitting happens when the model is too simple to capture the underlying pattern. Poor accuracy on both training and testing data. Underfitting is more easily to detect, but overfitting is a constraining problem. So what are we looking? How do we solve this problem? We want a bias and variance trade-off. Bias error due to overly simplistic assumptions in the learning algorithm, and high bias always causes underfitting. Variance is error due to excessive complexity in the learning algorithm. High variance causes overfitting. Clear? So low bias, high variance, again, it is failing to be a good fit. This refers to overfitting. High bias, low variance, it leads to underfitting. And optimal trade-off, finding a balance between the model performance on both training and test data. So this is what we are actually trying to achieve in the output, right? So just to understand things, you have to understand the machine learning model from the mathematical intuitive behind it. If it is possible to understand it graphically, well and good, because in higher complexity, higher dimensional plane, it becomes difficult to access, to understand it visually. But mathematical intuition, the concept, and how do I interpret the results? Are you understanding? And of course, how we are implementing those functions in Python. That is where, your concentration should be. Mathematical concept, or what is the concept of that particular algorithm? How are we implementing in Python? And how am I interpreting the results? That should be the option. Clear? Is this point getting clear to everybody? And how do I check the error? The checking of the error is going to be through the training and testing error. So if you just look at this, I'll tell you what these errors are. So if you just look at the training, error is more than the testing error. So is it underfitting or overfitting? Definitely underfitting. Consider increasing model complexity. That means linear regression or a straight line fit is not a good fit on this particular data set. Agreed? So now getting back to the concepts of errors, how do I evaluate my regression model? Okay, till here, are we clear? Okay, so one of the simplest error is known as the mean square error. This is nothing but your RSS, the residual sum of square error. Please try to understand. This is nothing. So errors, do you think one error is easy to define linear regression? No. right? There would be several errors. So now let's try to understand different errors available in the linear regression model. Yeah. So if I talk about the mean square error, this is nothing but my RSS, or the residual actual minus predicted value, the whole square. So error, square of the error, and if I take the average of it, it becomes mean square error. Agreed? Are you understanding this error? And when I talk about root mean square error, that is when I take the under root, square root of this particular MSC. But what is the need of taking the root mean? Can anybody tell me? What is the need of taking the root of this mean square error? Anybody who can explain? This is exactly the same question which relates to standard deviation and variance. Anybody who understands the relationship between standard deviation and variance? Anybody who understands the relationship? After square error will increase, so square root will get proper value. No, Nanda, that's wrong answer. Yes, ma'am, rooting variance is standard deviation. Like, but why do we take that under root? That's the question. Why do we take this under root of variance? Why? What is the significance? No, it doesn't mean that squaring will get a proper value. No, square root will. Yeah, because ultimately we have to compare with other values such as average. So average is a simple value. Simple values cannot be compared with a squared value. Mean square value cannot be used for comparison with other values. So to make it at, it's something like, can I compare a centimeter square, the unit of area that is equal to centimeter square, with centimeter? Can I compare a centimeter square or a meter square, a unit of area, with normal meter? No, that goes mathematically wrong. So just by taking the square root of MSC, now it becomes at the same level, and then the comparison can be done. Yes, and if we talk about mean absolute error, that is actual minus the predicted value, and this is I divided by n, I get the mean absolute error. Clear? Now, these are all, we can say absolute terms of error. And if I want to do comparison between different models, now what difference does it make if I'm saying actual minus the predicted, the whole square? And then I say predicted minus actual, the whole square. Is there any difference between that? Is there any difference? No. So mathematically, whatever way they write, the answer will be same. Yeah. Clear now? Now let's understand another factor of comparison, that is R square. Please try to understand R square. Okay. Okay. Now to understand R square, it is a relationship between SSTO. What is this? Total sum of square. These are my actual points. And total sum of square is the difference or the total variation between the actual points and the average. Generally, we want to always find out how far my points are from the average, right? How my points are far from the average, right? So SSTO is getting clear to everybody. So over here, this is my actual data point, and here I'm doing my comparison. Is the total sum of square clear to everybody? What is SSC? Is SSC same as the RSS? Yes. Here we are trying to find out the difference between actual value and its difference with the average. Yi minus y cap b square. Again y square, because I don't want no positive and negative values cancelling each other. Clear? And if I talk about SSC or the error sum of square, this is like RSS, actual minus the predicted value. This is my actual, this is the predicted value. Do you see this? So the uncertainty of the data around Y observations lie around the regression line. If SSC, all observations fall on regression line, larger the SSC, the greater is variation of the Y observation around the regression line. Then we have regression sum of the squares, right? This is actual, the average predicted value with the difference with the average. So the difference between the predicted or the fitted value on the regression line and the mean of the fitted value, that is equal to SSR, the measure of variability of Y's associated with the regression line. Larger the SSR in the relation to SSTO, greater the effect, right? So if we look at now the whole picture, that my total sum of the square is equal to SSC plus SSR. That is the difference, the sum of square values with the actual value minus the average, the whole square is equal to actual minus the predicted, the whole square, and predicted minus the average. Agreed, learners? But what is the use of all these? So now there is this another factor, another unit which helps in comparison of value, that is R squared. That is known as coefficient of determination. That is known as coefficient of determination, which is also known as the R square statistics, proportion of variance explained. The value varies between 0 and 1 and independent of the scale Y, right? So R square is equal to SSTO minus SSE upon SSTO, SSR upon SSTO. So what is the advantage in short? Let's not get into the mathematics. That the R square value will always lie between 0 to 1. So the values which are more close to 1 are better fit as compared to 0. Yeah, mean square error and RMSE relationship is clear, but they are not relative errors. I cannot do comparison between the different models, that this model is better than the other. They are good to tell the errors are less or more comparison between training, but R square is a relative error. Even absolute error is not a relative error. What do I mean by that? What do I mean by that? Let me explain you with an example. For example, you scored 70 marks and I have scored 30 marks. Who scored better? You would say 70 marks, ma'am. You scored better than me. But I scored 30 out of 30. You scored 70 out of 200. Getting my point? So there, how will I find the relative? If I start taking percentage of this, that 30 out of 30 is 100% and 70 out of 200 is somewhere around 40-50%. Then I can do comparisons. Got my point? That is why we are now heading towards ratio between the SSTO, the total sum of squares, with RSS and SSR, taking into all account all the variability of the data points, and that's why I now reach on this R squared term. Now better? Is it better? Sum of square error ranges between 0 to 1, which measures the amount of variability that is left unexplained after performing the regression. And SSTO minus SSC measures the amount of variability that is explained or removed after performing the regression. R squared and the proportion of variability in Y can be explained using X. So R square is trying to take into account all the errors and variability of the data point. So when R square is equal to 1, SSC is 0, that means it's a perfect fit. It's an ideal situation. Will it ever happen? Hardly. I don't think so. It's going to be, but something which is close to 1.99 is a good. And when I get this horizontal line that you all were getting, that means R square is equal to 0. Error is equal to total. That means there is no linear relationship between X and Y. Now clear? right? But R square suffers from one limitation, right? Since R square is also known as if it is greater than 1, it can never be greater than 1. That's Simon, that's not possible mathematics. Can percentage ever come beyond 100%? The formula is such, now because we're taking a ratio out of 100, right, Simon? So mathematically, it can never be true. Got it? Okay. So R square, also known as the coefficient of determination, measures the proportion of the variation in your dependent variable x and explained by your independent variable x for the linear regression model. But the problem that R square also suffers is that it will always remain or increase as we are adding more number of independent variables. So this problem is solved by adjusted R square. What is adjusted R square? That it measures the proportion of the variation, explain only those independent variables that really help. So what do? We divide the error by degree of freedom. Do you understand the term degree of freedom, learners? Might be thinking so many concepts. Degree of freedom is the number of independent variables, right? Suppose if they are 10, if they are 10 input features, then the degree of freedom is n minus 1, that is 9. Clear? How many input features are we depending on, Abhinetri? That is referring to my degree of freedom. It's something like, now let's understand it over here. Now, if I want to predict the price of the car, what are the factors that are determining the price of the car? Safety is a very, very important factor. How many airbags does it have? Does it have a parking sensor or not? The branding. What is the most important factor? The mile, the fuelage consumption, the fuel type in today's world, assistant, infotainment system. Is it a luxury car or not? The color, the kind of, the design, the seats, the wheel, the alloy. There could be several factors. Agreed, learners? But do you think the kind of wheels or the wheel alloys are as important as the engine of the car or the model of the car to determine the price? No, right? So that is what is taken care by adjusted R square, and when we divide it by the number of degree of freedom. Getting my point? See, normally what will happen is if I keep on adding the factors in R square, that I've added the number of alloys, the number of, the seat covers, the color of the car, the R square will keep on improving. It will give me an illusion, oh, my model is giving so much well answers, but that's not true. Maybe, adding the kind of wheel alloy is not that concrete factor to determine the price of the car. See, these numbers of degree of freedom, as I told you, this is some example that they are taken. Degree of freedom depends on the number of input features. So that is why adjusted R square is a better way of determining the results. So if I get back to the file over here, and now look at how I calculate the results. So what am I trying to do? From Scikit-learn metrics, import mean square error, R square error, and then I do the prediction. Prediction is done by the predict function for the training output as well as for the testing output. And then the different metrics can be simply calculated in Python by using the mean square error for training data, for testing data, and R square. And then I can do the comparisons. So if you, do you see the training error is 0.573 and testing error is more than that, that's more closer. So they all refer that the model is underfitting. Now clear? How are we trying to fit the model? How are we trying to fit it, then predict the output, and then calculate the error? So if we talk about linear regression, let's look at it again. That this is my actual output, right? And if I talk about a single variable as my input, and there are two coefficients, beta naught and beta 1, this is the epsilon error. Is this first equation getting clear to everybody? Simple linear regression, single variable is getting clear to everybody. Then we have linear regression, multiple variables, right? We have x1, x2, x3, right? Epsilon over here refers to the random error. And if we talk about a model evaluation, are we clear with these metrics now? The mean absolute error, the mean square error, and the root mean square error, right? So comparisons between the different models is not possible. Therefore, we have R square error, which talks about the ratio, and even better than R square is adjusted R square because it is not affected by the number of inputs in the data. Clear? So basically, we divided by degree of freedom mean model. Clear? And we have also understood different scikit-learn objects. Please try to understand fit function. Fit function helps us to train the input parameters or train the parameters for the data. Transform is transforming the input to output. Fit underscore transform is mixing the function of fit as well as transform. And it is the predict function which is used to predict the output of the training data or of the testing data. To understand it better, types of sklearn objects are based on transformers. Transformers are nothing which transform the data set. Have you learned feature engineering, learners? Do you understand feature engineering? Where we do feature scaling, standardization and normalization, encoding of the data, that we need to transform the data before we actually fit into the model. Let me try explaining you over here. So before the data is actually fed into the model, it needs to be transformed. Why it needs to be transformed? Because if they are missing values that will not fit into the model, if they are categorical features, then we have to involve encoding. Feature scaling is a feature which brings the data into one particular range, and outlier detection. That is why data science is important, because these concepts are covered in detail. How do you deal with data? How do you handle missing values? How do you deal with categorical data? Scaling of the data is all part of the feature engineering process. So in feature engineering, we are not just building models, but we are playing matchmakers for data as well as algorithms. Getting my point, everybody? Okay. So getting back for transforming the data set, right? So fit learns. What does a fit function do? It is an estimator. Please try to understand. Fit is an estimator which estimates the model parameter based on the training data and hyperparameters. And finally, we have the predictors. That is, it predicts the data, makes the data set as input and does the prediction. Score method to measure the quality of the predictions. Getting my point? So here we have the data pre-processing, training, and inference model. Clear? And then we have fit and fit underscore transform, right? What do we do that? When we are trying to train the data. What I'm trying to explain, let me explain it with a slide. That again, please try to understand. Let me rewind things. In supervised learning, we have label data. First of all, what is label data? That we have the input as well as the output. Now, in the story, have you understood two types of output in supervised learning? That we will have the actual output of the label data, and one we will predict the data using the X test. This point is getting clear? What this point, which I'm trying to explain regarding the output, is getting clear, right? So this is output actual as well as predicted. Now we also understand that we divide the training and the testing data, right? So ultimately we are trying to, when we are doing training, it is all on the training data by the fit parameter. So the model, all the training will be done using the fit function in simple terms, right? And the testing and output will be on the predicted. But if I want to transform the data, so I will fit it and then transform it. And can I do the function of fit and transform together? Yes, by using fit underscore transform function. Getting my point? Can I do the function together? Yes, for only training data, I can use fit underscore transform, and for testing data, I will only use the transform function. Now clear? Okay. Okay, so now let's, once we have understood, now let's get back to the code. So now, are we able to also understand how when the model is underfitting and overfitting, that point is also clear? Yes. And if we talk about non-linear regression, polynomial regression is a subset of linear regression that includes polynomial terms. The relationship between the independent variable x and dependent variable y is modeled as an nth degree. So here we are not trying to do it as a straight line, but polynomial regression, which is a subset of linear regression, which includes polynomial terms. The relationship between an independent variable x and dependent variable y is modeled as nth degree polynomial, right? So why polynomial regression is called a special case of multiple linear regression? Some polynomial terms are added to multiple linear regression equation to convert it into polynomial regression. So it is a linear model with some modifications made to increase its accuracy. The data set used in polynomial regression for training is non-linear. So what do we observe? That in this particular graph, this is a straight line, linear regression. And if I change it to a curve, it becomes polynomial linear equation. Do we see that exponential curve over here? Okay. So I have this, simple data, right? In this simple data, this is the project statement, okay? Wait, live. Okay. Yeah, so a certain spare part manufactured company once a month in lots which vary in sizes. Data on lot and size numbers and man hours. That means the input is the lot size of the people and how many man hours are required, right? It's numerical, right? So if I start analyzing the data, actually, it's done through an Excel. It's simple that I do x minus x bar, y minus y bar, and I calculate this. What is this known as? RSS, residual sum of square, actual minus the output the whole square, xi minus xi the whole square. Do you see this? And why am I taking the square value? Because I simply take the difference between y minus y cap. The error is 0, which is actually not. Therefore, we take the square values and I get the answer as 13,660. Okay. So the sample size, the number of rows in this data set is 10. Degree of freedom over here is 9. mean is equal to x bar sigma xi upon n 50. Variance over here is this much. Standard deviation is in this much. So this is where statistics is coming into picture. We have calculated the value. Similarly, we can calculate it for the man hours yi. Okay. And if I try to see the relationship, it's coming out to be straight line, right? Now coming on to the concept of how do we calculate the best fit line, right? So this is the least square concept where we are trying to find out the RSS. So over here, what am I trying to do? Again, yi minus the y cap the whole square, not this one. Okay. Here it is doing hit and trial method, but ultimately the least square estimators can be found out by trial and error method, but that is not the case. We try to calculate it by the normal equation. This is the equation for calculating of beta naught and beta 1. So these are already predefined formulas which run at the back end when I run the linear regression function. So this example shows that whatever values you are getting by solving mathematically or through linear regression model, I get the same values. Okay. So what does polynomial regression on data set work? Again, we are using the tvmarketing.csv features. From the Scikit-learn pre-processing, we are including the polynomial features. Again, first we are splitting the data. So now I am creating an object of polynomial features, right, with degree equal to 2. And now I am using the fit underscore transform function, not the fit function itself, but the transform function because I'm transforming the input values as well as fitting, but I'm only and only transforming the output. Do I want to train the testing data? No. Why don't I want to train the testing data? Because, so if I give you what is going to be, if in your test, if I tell you the questions, is it actually a test? No, that calls for paper leakage. If I tell you what questions are going to come for an exam, that is known as paper leakage. And the same concept is known as data leakage over here. Getting my point, learners? So are you understanding the difference between fit, transform, and transform? The fit underscore transform will only and only work for training data. Transformation will happen for input as well as output. Will happen for training as well as testing. But fit will only happen for training data. When I create an object of linear regression, I get this output. So basically the polynomial features transformer is configured to generate polynomial features up to 4th degree. Then we are only transforming the input to generate a new feature set that includes polynomial features and interaction. Then we transform the test data corrected from fit underscore transform. It is used on x underscore test to apply the same transformation and then train the model. The linear regression model is trained using the transform training data. Clear? And finally, we are going to predict the output and then create a graph, right? Do you see the scatter plot is testing data and plot is X range polynomial predict the output. Now clear? You are getting all the code how the graph is getting created. So what is the observation? And this is exactly, why Jupyter notebooks are hit in the market because we are able to see the graphs over here directly, which VS Code lacks, right? We can see the code as well as I can write my observations also. So as you can see, the regression line is able to fit majority of the data points. You can infer from the above implementation that nonlinear inputs require nonlinear model such as polynomial model. Clear? So, I mean, linear regression also has capability of dealing with
non-linear data up to degree 4, but not very high non-linear data, right? Then we have different variations of the algorithm. And if we talk about performance metrics for analysis, why different metrics? Because it calculates the average of the squares of error, which is differences between the actual and the predicted. Then we have the root mean square error. Oh, I hope you all are clear. Mean absolute error, R square error. Zero value indicates model explains none of the variance in the dependent variable. The independent variables have no exploratory power for the changes in Y, and 1 represents a perfect fit. The model explains all of the variance in the dependent variable. The change in Y are perfectly captured by the changes in the X. Clear? So now we have to start understanding another technique, important technique. Okay. So now let's understand what is cross-validation. And before we understand cross-validation, we need to understand few more concepts. Now in machine learning, there are two terms that you need to understand. One is parameters and other one are hyperparameters. Okay. So now what is the difference between parameter? A lot of learners get confused because they both think they are the same thing. No. Again, I'm telling you, I try to give you exactly, the crisp concepts, differences between them. So when I talk about parameters, they are values learned by the model during the training. So during the training, what the model learns is referred to as parameters, and hyperparameters are defined by the user to control the learning process. Purpose over here is it directly impacts the model predictions. So model automatically learns the parameters, and that is directly impacted in the output. Whereas hyperparameters are controlled by us. For example, how much is going to be the training data and the test data is a hyperparameter, test underscore size or train underscore split. Right? The factors or parameters which are controlled by us during the training process or model fitting process, that are known as hyperparameters. Whereas when the model learns the parameters on its own using the fit function are parameters. Clear? They are estimated during model training. They are generally, estimated before the training begins. Learn from the data using optimization, whereas the hyperparameters are set. They are usually set or tuned using the methods like grid search, random search, or Bayesian optimization. Influence on the model affects the output directly, affects the speed and the quality of the learning. And this is dependent on the data set. These are independent of the data set. So the model parameters are nothing but your coefficients beta naught, beta 1, beta 2, or they can also be represented by weights in general. So generally coefficients become weights. That's the general term used in deep learning. Whereas the test underscore size, the number of iterations, and there are several other factors that will be controlled by us, even random underscore state are all hyperparameters. Is the difference getting clear? Right? So now, what is the need of cross-validation? Do we cross-validate results? Do we like to cross-validate views, reviews of doctors, lawyers? What does that mean, Abhinetri? And why do we want to do that? What does it mean and why do we want to do that? So that, we are more sure of the answer, right? If one of the doctors is saying that, you need to be, maybe, your disease has this and maybe you need to get operated, and even the other doctor says, that means you're more correct that, yes, Or if the other doctor says, no, doesn't need to get operated, you can cure it through these medicines, right? So cross-validation, or also known as rotation estimation or out-of-sample testing, refers to the process of rotating or splitting the data into different subsets. So it helps in in the process of rotating, splitting the data into different subsets. Okay. So one part we are very, very clear that when we take the data set, we divide it into training and test. And definitely we don't want to mix any of their training and testing data sets to avoid any kind of data leakage. That point is also clear, that we want to avoid any kind of data leakage. That point also makes it clear. Now, to make our results better, more confident, more accurate, rather than using only one part of the set, if I use only one part or one sample of the set, if I use multiple samples, I can get better results, right? So this is my mini training data set. So it's always the training data set which gets divided into further training and validation split, right? So what is the idea? That we initially the data is getting split into training set and test set. Train and tune your models using cross-validation. So we will try to find out, okay, we want to make certain changes. This is better, not better, only through the training set. The test set is not involved. Test set we do not touch this until the very end, because ultimately that is going to give us whether the model is robust or not. Is this point clear now? So how do we go about cross-validation? So model evaluation is this: when we fit the model and then we predict the test set. That point is clear, that we have one data set that is divided into training and test set, right? This is normally that we do. We fit it and then we predict the output and do the comparison. But if I want to do model selection between different comparisons, what I will do, now the training data set is going to get divided into train as well as validation data set. What is the use of this model selection? It helps us to explore the hyperparameters grid. Now they are different hyperparameters. How do I know that this is the best hyperparameter for me? I will try to do it through the validation set. Fit on the train, evaluate on the validation, pick the best hyperparameter. Clear? Why are we doing this? Because we want to validate our training and results better. It helps us in finding out the different hyperparameters, right? So as we move along, more algorithms, you will understand it more. It's not part of regression, but part of supervised learning also. So cross-validation, when data set is too small for apply hold out strategy, then cross-validation can be used for evaluation and model selection. So what do we do? Suppose this is my 100 rows in data set, okay? And now I divided into 20 groups. So I have 5 groups, 1, 2, 3, 4, 5. So one of the part is going to be used for validation, other is going to be used for training. Then the next group is going to be used for validation next. So I will iterate it for 5 iteration. Got it? Of course, it is increasing the complexity, but it is giving me a much more validated result. Agreed? So one of the techniques or variants of k-fold is leave. This is known as leave one out cross-validation. Right? So we have 1, 2, 3 and n over here. Right? So if we take one part of the sample and the rest n are taken for training, then the next row is taken, the rest for training. So how many times the loop will be executed? N times. Is it a good idea? No. Taking each sample for validation and others for training is not a good idea because it will increase the number of computation. But if I have k-fold, that is, I divided into number of groups, my number of iterations decrease and I get better results. So how do we go about the performance and the output metrics, right? So what will happen? So the cross validation will automatically create an array. In the first iteration, I will get the first metric. When it takes the second k-fold, I get the second performance metric. When I take the third iteration, I get the third performance metrics. Fourth, the fourth one, and last one, I get the fifth performance metrics. Clear? So to answer that point, everybody please understand the test data is not touched. It is the training data and the different folds which I use, and final evaluation is done on the test data, whether I am getting the correct output. So the concept is same. We are doing comparison between training and testing, and that will give me the results, whether it's overfitting, underfitting, etc. Clear? Yeah. But when we talk about categorical data, what does categorical data means? That the data is in category in terms of males and female. So the folds we have, which have been cross-validated, will be taken up for final testing. Final testing will be on the test data only. Once the parameters have been found out, okay, the number of folds, okay, the number of, k value for this thing is this. So now we will test on this value. Are we getting the minimum results or not? It will help us to calculate the different hyperparameters. Got it? Okay, so when we talk about categorical data, dividing it into male and female. So this is my round one. So stratified k-fold is being used for categorical class, which helps us to keep the ratio of the different categories same. Okay, this we will do it when we do classification. Okay, so what is the difference between k-fold and stratified k-fold? K-fold is random. Stratified k-fold helps us to maintain proportions, may vary across folds, maintains class distribution across folds, imbalanced data set, not ideal, preferred use cases, balance and imbalance. And how do I check the metric that my cross validation is good or wrong? First, my parameters for cross validations are the estimators, input, output, scoring, and CV equal to 5. Estimator is equal to the model object. X is an array of the feature values. Y is an array of the target value. CV, the number of folds. Scoring, the metric, and it returns score, an array of scores at each split. So, the beauty of this particular function is that it returns at score of each iteration. So you are able to see which one is better, but generally we take the average of that. Clear? So now let's get back to the file and do it practically. So this file is quite long. We will be using this file in the next session. Of course, we will not be able to complete all the concepts today. So we are on cross-validation. After cross-validation, then we have regularization. After regularization, then we have hyperparameter tuning, that is model optimization, and then the pipeline. So it's a long journey that definitely we are going to continue. Okay. In this file. Yeah. So cross-validation technique. Everybody is there with me? 3.7.2. So what have you understood? What is cross-validation technique? Tell me, learners. So cross-validation is a machine learning technique that evaluates the model performance on unseen data by dividing the data into multiple folds. In each iteration, one fold is used as a validation set and the remaining as training. That point is clear? Then the process is repeated. So we have to give the number of iterations also. Yes, is repeated so that each fold serves as a validation set once and the results from all iterations are averaged to provide a robust estimate of the model performance. Some of the common cross-validation techniques is k-fold cross-validation. K refers to the number of equally sized folds. That if it is unequal, it will make it equal by adding randomly some of the, randomly the data set only for the last one, right? And there is no harm also in doing it, will not affect it much. So the model is trained on k minus 1 folds and tested on the remaining fold. That point is clear? So if I have 5 folds, then one of the fold will become the validation test and 4 will be tested. This process is repeated k times. So is this k also a hyperparameter? Yes. We decide they are going to be 5-fold, 6-fold, 7-fold, 8-folds, not the system. They are not parameters to the algorithm. It is decided by us, so it's a hyperparameter. And with each fold exactly once as the test data set. The results are averaged to produce a single performance estimate. We generally average them. What is the advantage of k-fold cross-validation? It provides more accurate estimate of the model performance. Yes, that this is the answer. K is the number of folds. Yes, Ajay. And cons, computationally intensive for large data set. Yes, you have to reiterate the training process, but it gives definitely better results. Clear? Then we have stratified k-fold. Similar to k-fold, but ensures that each fold has the same proportion of different classes as the original data set. This is especially useful for imbalanced data set. More reliable performance estimates for imbalanced data set, and still computationally expensive. Third is the holdout method, simple and fast. We divide the data into training and test, and the training data is further divided into training and validation data set. So the model is trained on training set and evaluated on the test set. It is simple and fast. The evaluation may be noisy and variability in the training. So the normal one that we do, we divide it into training and test, is known as the holdout method. And leave one out cross-validation is again a special kind of cross-validation technique used in k-fold. A special case of k-fold cross-validation where k is equal number to the number of data points in the data set. Each observation is used once as a test set. The model is trained on remaining data points. Clear? So this maximizes the amount of training data used. Cons, extremely computationally expensive, especially for the large data set. Clear? 4 variants of cross-validation techniques: k-fold, stratified, hold out, and leave one out cross-validation. Okay. Now can we begin with the code? So I hope everybody is familiar with the Pandas and the Matplotlib library. We are also familiar with the Scikit-learn model selection. These are the different techniques and metrics. Linear regression over here, and this metrics to compare mean square error, absolute, R-square, etc. Clear? So here we are talking about housing.csv. So, yeah, take it as housing. So what are the pre-processing steps? What are the steps involved in EDA? Tell me. How do you perform EDA? You'll do head, tail to view the data, check null values, do info, right? So let's look at info. So if you look at info, it has around 20,640 rows and 8 columns. Do you see this? All are integer values. Do you see this? Yeah. Now the question is, can you tell me what is the output over here? Why it is a regression problem? What are we trying to do in this data set? Can you analyze it through the number of columns? Based on the latitude, longitude, housing, age, total rooms, bedrooms, they all are inputs. I am trying to predict the house value. What will be the value or the price of the house? House price prediction. Now clear? All these are my inputs and one output. House values are numerical continuous value. Therefore, this is known as regression. Clear? Okay, now let's see the observation that price lies between 1.1 million to 2.6 million. Houses are generally 18 to 37 years old. Housing data. Let's check the null values. Yeah, now let's check the null values. So total number of bedrooms, we have 207 values. How do we deal with null values? Either we will replace it by mean, median, or zero. Since null values make up only 1% of the total data, rows and column features with missing values will be removed. So what are we trying to do? We are going to drop now because 207 is hardly 1% of 20,000 rows. So we can drop those data and now my data set is clean, right? And this is the categorical data which we are not using. We don't have that. And now can you tell me what does this mean, X and Y? Now I have dropped the median house value, axis 1, because that's my output. And now this becomes my output. This becomes my input, right? So if I say print X and then print Y. Do you see? Yeah. So now do you see this? So X basically has longitude, latitude, house, median, total bedrooms, etc. And Y is only that. So let's remove Y. Clear? So I keep making changes in the code. Are you understanding? So these are my now the input. And my output is median house value. And then I use the train test underscore split. Clear? Okay. Now let's perform k-fold cross-validation. It implements k-fold, number of splits is 10, divides the data set into 10 folds automatically, random underscore state is 42, shuffle is also equal to. So I have created an object of this k-fold. Now I initialize the model. There with me? And then I evaluate the cross-validation score based on the model. Model was linear regression, training data, and the target variable. Scoring, I'm using negative mean absolute error as the performance metric. So this is where the absolute error comes into the picture. CV cross-validation is KF. Number of jobs is equal to -1. What does this mean? It utilizes all the available processors for parallel computation. Do we understand the concept of threading or the number of core processors, learners? So this parameter takes care of that. Okay. This parameter takes care of that particular one. Clear? So from statistics, import mean, I'll take the mean of the k-fold cross-validation. K-fold scores are not defined. So let me run this. Let me, show you that since the number of folds is 10, so the output of k-fold is an array object. See, do you see? They all are mean negative absolute errors. Negative does not mean that the error is less. It's just the sign. Okay. So we will try to take the average of these, right? There will be 10 outputs since we have given 10 folds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Clear? It's an array. And then I will try to take the absolute average of this. Clear? So we have trained the model and evaluate on the test set. So are we now understanding how are we going about cross-validation score, learners? And now finally, after cross-validation, now we can use the test data. So this is how I have fitted the data, predicted it, through the test, and my MSc, test MSc is here. Similarly, my R square is here, right? So my test MSc and R square scores are here, right? Look at the error, it's so huge, indicating that on average, the squared prediction errors are large. This can be interpreted in context of units of dependent variable, which are likely in order. Since the numbers are very high, that is why the errors is coming out to be large. This can be mitigated by scaling the features. Feature scaling is critical in machine learning to ensure that all features contribute equally. So this is how, and then we demonstrate leave one out also. LOCCV scores, and we get the absolute mean score. Clear? So the mean absolute error is high. To improve the model, more complex model can be considered, which will be discussed in further lessons. So the concept of cross-validation is clear. Let's do a quick knowledge check on that. Okay, a quick knowledge check. First question. Which of the following cross-validation versions may not be suitable for very large data set with hundreds of samples? We just now studied that. I think so we've all seen it practically. Practical has a major impact. We all have just now seen the impact, and it is leave one out cross-validation. Great. Which of the following is a disadvantage of k-fold cross-validation method? Training algorithm has to return from scratch. Do we understand this? Every time it has to restart and do it again. Next question. Suppose you have picked the parameter for model using 10-fold cross-validation. Which of the following is the best way to pick a final model to use and estimate its error? Train a new model on the full data set. Using the parameter you found, use the average cross-validation error as its error estimate. So you can use average cross-validation error as its error. Everybody got this? Why C is not correct? Because we will train the model on the full data set. Okay? So what is the idea? The best way to pick, why is the answer B correct? The best way to pick a final model is to train a new machine learning model on the full data set using the parameter learned to use the average cross-validation error as its error estimate. So please be clear with this particular point. That is why I have added this MCQ. We can compare different models using cross-validation. Cross-validation is mainly used for comparison of different models. For each model, you may get average generalization error on the k-validation sets. Then you will be able to choose the model with the lowest average. Clear? And cross-validation is also used for model checking, not model building, because it allows to repeatedly train and test on a single set of data set. Let us suppose we have a linear regression model and a neural network. To select the best one among these, we can use k-fold cross-validation. So to compare between the models also, we can use cross-validation to select a better performing model. Clear? So when we are now looking at the regression outputs, right, or the regression analysis, some of the outputs are like this. So the output over here that we receive is in these terms of coefficients, that this is my beta naught, this is my beta 1, beta 2, and this is my beta 3. So this is my north, south, east, and constant term. And these are the values, right? So what is it showing? This is the constant value positive. East has positive relationship, but south has more positive relationship with the heat flux. Heat flux is the output, and north has a negative relationship with the output. Are you now understanding it better? How do we get the output and how are we relating it with the the equation of linear regression? So this is nothing but like beta naught plus beta 1 x1, the value of east, plus beta 2 x2 minus. So a lot of you had questioned that how do we understand negative? It will automatically get this. So this is multiple linear regression. Yes, learners. This is multiple linear regression. And there was a lot of confusion regarding, ma'am, what does multi-collinearity mean? Multi means referring to multiple independent variables, multiple inputs with multiple regression. Call means joint or together, referencing to the linear movement or correlation. As I told you, it tries to find out correlation in terms of -1 +1 occurring within the linear equation. And suffix means the idea. So if we look at over here, from statistics, we understand that p-value is a very, very important term, right? That if I have the value lesser than 0.5, then this is accepted. This is accepted. This has a strong evidence, statistically significant. But if this is not lesser than 0.05, that means east is 2.12 is not very statistically proven or confident that the value is this. Clear? And when I talk about VIF, how do I calculate multi-collinearity? It is the variance inflation factor, which is coming out to be 1.21. What does that mean? This is the correlation map, a heat map that you understand. So multi-collinearity is the phenomenon of high correlation between the predictor variables can create instability and bias in regression model. To identify and address multi-collinearity, we use the variance inflation factor. So the VIF is equal to 1 minus 1 upon R square. And if the value is equal to 1, that means all the input values are independent. And if it lies between 1 to 5, it suggests moderate correlation. So over here, we are getting the value between 1 to 5. So there is moderate correlation, or we can say independent also. And if it is greater than 5, then it indicates high correlation. That means then linear regression cannot be can be fitted on that input values. So where VIF should not be used, polynomial equation, dummy variable, or a normal variable. And multi-collinearity reduces the statistical significance of the independent variables. VIF is used to detect these variables. A large variance inflation factor on an independent variable indicates a highly collinear linear relationship to other variables that should be considered or adjusted for structure. Because multi-collinearity is one of the assumptions that we assume when we are trying to build the linear regression model. So that means if the VIF value is greater than 5, then linear regression should not be used. Clear? I hope these points are clear now. First concept that we will learn, data leakage in machine learning. So now we will understand the concepts of pipeline today. Pipeline is a technique for automating different processes. What is the different processes that we do? Whenever the data is loaded, we want to do transformations such as encoding, scaling, right? So we'll try creating a pipeline. And what is our main aim? That we want to avoid data leakage, of course. Why? Because if there is data leakage, the data gets lost. A lot of information is also getting lost. So now if we look at the data from the supervised learning perspective, it is divided into two parts. One is known as the training data and the other one is known as the test data. Agreed? Okay. So a scenario when the ML model already has information of a test data in the training data. Do you think that test data should be present in the training data? If I tell you, okay, in your exam, these questions are going to come, that's going to be very beneficial for you for scoring marks. But do you actually learn out of it? No, that's not a good way of learning, right? That, it can give you good results, but you're not going to be a robust model. That means if any other question is asked from that particular topic, you will absolutely fail, right? But this information would be available at the time of prediction called data leakage. So what is the disadvantage and how can we avoid it? That it causes high performance while training set, but performs poorly in the deployment or the production. Okay. So when there is an, or if I say when there is an overlap of training and test data, then it causes data leakage, right? And basically, data leakage happens due to two reasons. First, we understand train and test contamination or the target leakage. What do we mean by that? Target leakage occurs when the model is trained on the training data that contains target or the feature information. So we don't want that, and that should not be available at the time of prediction. So we have to be very, very careful when we are doing this. The other one is the train test contamination is an event where the test data leaks into the training data and the data pre-processing steps for transformation. For example, scaling, encoding are applied before the splitting the data set. So contamination is when the test data leaks into training there and the pre-processing steps. So that the scaling, encoding should not be applied before the splitting of the data set to avoid data leakage. Got it? Basically, if there is mixing of training data in the test data set, or rather test data in the training data set, then this causes data leakage. And we have to avoid it in every case. That is, we should not apply any transformation, that is scaling or encoding, before the splitting of the data set. Now clear? Now, another very important concept of regularization. There are two types of regularization available under regression, that is ridge and lasso. Preventing overlearning, yes. Normalizing the data, yes, we can say that. So regularizing thing in a normal way, right? We want to prevent it from overfitting, overlearning, right? So regularization is a technique in machine learning which prevents overfitting of the model. And how do I know that the model has overfitted? How do I know that the model has overfitted? Test error much higher than the training error. And why is it that the model is trained so complex than requires high variance? It covers every possible train outcome, making it complex. Yeah, so the complexity of the model increase. It tries to train on each and every data point and fails on the final test data due to noise, due to learning of noise in the training data. So to avoid it, so as I've been telling you that in machine learning, do we suffer more from underfitting or overfitting? Overfitting, right? So we need methods so that our model does not overfit, and we need certain control parameters to achieve that. So there are two, algorithms under this, that is ridge and lasso. So lasso is known as L1 regularization technique. Can anybody tell me what does this term mean? Anybody? It is summation of the actual value or the true output minus the predicted output, the whole square. What is this term known as? It's an error. I want the typical name of this error. It is the residual sum of square error. But rather than only taking this error actual minus the predicted value, the whole square, I take into account the another hyperparameter lambda, which I will use to control or regulate the training process. So do we have a regulator? Do we have a regulator to control the speed of the fan? Similarly, lambda, we will use the regulator. And similarly, summation of beta. Can anybody tell me what is this beta over here? What does the term beta mean? It is the coefficients. It could be a single, it could be many multiple variables. So this is known as the regression coefficients. Right? Not the intercept or slope. That is only in two-dimensional case, like beta naught plus beta 1 x1. I agree. Both of you are correct on those perspective. But in general, betas are known as regression coefficients or the weights parameter. So what is the advantage that we are getting through this L1 regularization? That in the error term, in the RSS term, now we have added the penalty lambda, which is controlled by us and which controls the value of these regression coefficients. Getting my point? And in ridge regression, that is known as L2 regularization. So this is now also, known as my error, or it is also known as the cost function. Try to understand. In deep learning, the error with which we are calculating becomes my cost function. In this case, it is represented as L over here. It represents it as my loss function. There is slight difference, but actually in machine learning, they all mean the same thing. Okay? So here we have the RSS W. Now what is this W over here? Is it the same as beta? Is it the same as beta? Yes. It's the regression coefficient. Is the lambda same? Yes. The lambda in Python is known as alpha. And then we have sum of the square of the weights. And what is this? Actual value, predicted value. Now are you understanding whether it's W or beta? They mean the same. And this is the lambda parameter with the square of the coefficients. Okay. So what are the advantages and disadvantages? And now then we will practically jump onto the file and start learning from there. So L1 regularization performs feature selection. What do we mean by features? Independent variables or the inputs. Yes, the inputs. So now we are trying to control. So now what is the use of overfitting? We understand that overfitting generally leads to high variance, agreed learners, and complex models. Agreed? Do we understand this concept, everybody? So to reduce the complexity, now I will try to control my coefficients, regression coefficients, beta naught, B1, and beta n, or in general, I can also call them as weights. Now getting my point. Do not get confused with the terminologies. Somewhere it would be written as weight, somewhere as beta, somewhere as independent variable, somewhere as features. So you should be able to understand the concept of it. Clear? So the beauty of L1 regularization is that it performs feature selection by shrinking the less important features weights to 0. So if I have a multivariable data set from beta 1 to beta naught to beta 7, it will shrink few of the features. That means some of the features or the weights will become 0. That means they have no significance relationship with the output. For example, if we want to, just try to listen and absorb as much as you can. That suppose, we want to predict the price of the car. Okay. So there are several factors from fuel to design to color of the car to the alloy of the wheels to the security systems to the infotainment system to the sunroof. There can be several features, but maybe the alloy of the car or the wheel of the car might not be important, so it can be reduced to 0. That will help us to reduce the complexity, and that will try to reduce the overfitting of the model. So, very, very important concept. L1 is used to reduce or shrink the less important features weights to 0. So, it helps us in feature selection, right? And it can also be used for high dimensional data set with many number of columns such as 20, 30, 50, 100 with many irrelevant features. And the disadvantage is it is not effective for data set with many important features. Now you might say, ma'am, how can we remove a feature? My every feature is important for the output. Then we use L2 regularization, okay? Where the where the value of the coefficients of the weights will not become 0. It provides a smooth solution and improves the generalization performance of the model. So, ma'am, Ridge is going to doing the opposite. Instead of 0, it is reducing the weight. Ridge is trying, or it is trying to see, the first one is making it 0 and the L2 will try to reduce the value. L1 is lasso and the ridge one is making the value of the coefficient small, not huge or big, but small. So therefore, the biggest advantage is that it can handle data sets with many important features. Okay, so now moving ahead to great, Abhinitra. Now let's get back to the file. Everybody has the file? Everybody is ready in the Jupyter notebooks? Okay. So regularization in regression. In linear regression, regularization encompasses a set of techniques employed to address the issue of overfitting. So what is regularization? Regularization is the method, techniques to achieve the objective by introducing a penalty term. Please try to understand. Again, it's a very, very important question from the point of interview. Introducing penalty term lambda to model's objective function to prevent it from overfitting. This objective function, typically measured by mean square error, is minimized during the training process. So generally, the error of the mean square error, or the RSS to be precise, is minimized during the training process. What is the advantage of that penalty term or the lambda? The penalty term discourages the model from attaining excessive complexity by penalizing the size of the model coefficients. So, model coefficients, regression coefficients, beta naught, beta 1, beta 2, or the W1, W2, Wn, thereby mitigating the overfitting process. Got it, learners? All right. So now if we talk about the regularization term, alpha, it can be known as alpha as well as lambda. Okay. They all mean the same thing. It's written as lambda or sometimes as alpha. So do not get confused. Okay. So there is a little terminology mishap happening. So everyone uses their own technique, but try to grasp the concept. Okay. So alpha is the hyperparameter that scales the penalty term. It controls the strength of regularization. Higher the alpha, it imposes stronger penalty on the coefficients. That means they tend to become 0, leading to greater regularization. This tends to produce a simpler model that may underfit the training data, but often generalizes better to unseen data. If we talk about lower alpha, It imposes a weaker penalty, leading to a model that is less restricted by regularization and more complex, potentially capturing more details in the data, but at the risk of overfitting. So what are we looking at? We are definitely looking at a value which is not very high and very low. So again, minimum mid value to find out. Got it? How do we find it? What are the best methods that we will understand today? That is known as hyperparameter tuning. That's part of this today's session also. Okay. Now, what are the benefits of regularization? It enhances the generalizability of the model. By mitigating the overfitting factor, regularization fosters model that can perform well on unseen data, reduce model complexity, it promotes interpretability, and potentially reduces computational cost associated with training complex models. And the two common regularization techniques are L1 and L2. L1 is lasso. Lasso is the full form of least absolute shrinkage and selection operator, right? So absolute term is there as the penalty. So Simon, is there any standard to label it as high, alpha or low? Yeah, we'll understand. Of course, low is my zero values or negative values, and high values are in thousands and lakhs. Let's do it practically to understand that point better. Okay. So is the full form of lasso clear to everybody? So which is the penalty term? Of course, it is the alpha or the the lambda. But what are we trying to add? The absolute value of the regression coefficient. So the least absolute shrinkage and selection operator regression relies upon the linear regression model, but additionally performs a so-called L1 regularization, which is a process of introducing additional information in order to prevent overfitting. As a consequence, we can fit a model containing all possible predictors. What are predictors? I'm purposely reading. You might feel ma'am just reads the data, but I'm purposely reading it to make you understand line by line. So what is containing all possible predictors? Predicted value is an output. Predictors are input. So we can fit a model containing all possible predictors and use lasso to perform a variable selection by using a technique that regularizes the coefficient. So what is that lambda parameter doing? It is having control on the value of the lambda or the alpha has where it's controlling or regulating the values of the coefficients. The regression coefficients. That's up to you how you want to represent it as betas or weights, right? So it performs variable selection or feature selection. It forces some of the coefficient estimates to be exactly equal to 0 with the help of large tuning parameter. So more the value of the lambda, some of the features coefficient value will turn out to be 0. And that is why this is a technique which is also used in dimensionality reduction. What is dimensionality reduction? Reducing the number of features in the data set so that it reduces the complexity. So L1 again plays a major role in that. It helps to reduce learning of more complex data and overfitting. It decreases the variance of the model without increase in the bias. All right. So in minimization, objective does not include RSS like the OLS regression, but also the absolute value term. So this RSS now is clear. This is the residual sum of square. And this is how we can expand it and write it. This point is also clear. What is yi? This is the actual output. And what is this output? This is the predicted output. Are you all understanding it mathematically, conceptually? But in lasso, where does the difference come? The RSS is the same, but we have added the penalty term alpha or lambda along with the absolute value of the summation of the coefficients. Now clear? If the alpha is equal to 0, then there is no regularization that will happen because the error term will be same as the RSS. If it is equal to infinity, all the coefficients will become 0. And if the alpha is greater than 0, lesser than infinity, coefficients are between 0, that of least square linear regression. Got it? Is the theory part clear? Now let's move on to the practical part. Start with a new data set. So let me share it with you, hitters.csv. Okay, here we go. Please download this data set and be ready. I hope different libraries are also clear. The NumPy Pandas, then linear model lasso, the matrix mean square error, R square. All these are there. Okay. So basically now let's understand the description of the data set. So I have provided a link over here. So this is for we have now IPL matches. So here we are trying to predict the salary of the player based on at-bat, number of times he batted in 1986, hits, the number of hits, the number of home runs, the number of runs, the number of runs batted, walks, number of times a bat during his career. So lots and lots of parameters to decide the salary of the player. That is 1987 annual salary on opening day in thousands of dollars. Got it? And then we have another important column that is new league, a factor with A and N indicating the players league at the beginning of 1997. So what is the first step? We've loaded the libraries, we load the data set and the view of the data set with df.head. Okay, what are the other functions that we would perform? Info. So this data set is quite huge in the sense that it has the number of rows are only 322, but the number of columns are many. So this is an object data type. At-bat, everything is integer, but we have league, division as categorical data. And then we have salary over here as the output and new league. So what are the different steps that need to be performed? Can we directly apply the model onto this data set? So these are my columns. So I have used df.drop unnamed equal to 0. Encoding, if any. Do you think encoding is required? Encoding is definitely required for league division for all the columns which are of object data type. Please remember this point, learners. Encoding is definitely required for object data type. Without that, you will not load it into the model. Duplicate values, if they are, then we need to check that. Okay. We are removing unnamed column because that is not required. We are specifying the access. What does in place equal to true mean? Permanent removal of that column from the data set. So now if I see my first column gets removed, so the first processing that I have done. Now let me check the null value. Are there any null values over here? Only the null value is in the output, in the salary field, right? Which is my output field. Agreed, learners? Do I need to separate my X and Y also? Yes. So the number of missing value in salary is 59. So 59 out of 322 observation with null values correspond to columns salary. Since we will use the lasso algorithm from the Scikit, we need to encode our categorical also. Okay. Now, how do we deal with categorical data? What is the use of value underscore counts function? It gives the category along with the frequency, along with the count, right? That's incomplete. It gives the category along with the count. So in league, there is A and N with these categories. In division, there is W and E, Western and Eastern. And again in new league, we have A and N, the American League or the National League. So if I separate this into a data frame, do you see this data frame rather? This code is getting clear to everybody. Are we here? Till here? Okay. So what are the different ways of encoding data? One is one-hot encoding, other one one-hot encoding, other one label encoding. What is the difference between the two? One-hot encoding adds column and then gives the binary output. If that column value is there, then it has 1, else all values are 0. Yes. And label and assign integers to each of the category. Yes. And label encoding is used when we have a ordinal data. One-hot encoding is used when we have nominal data. That means there is no order. So over here, we are using which function, learners? Yes, it is now one-hot encoding, that now it will have, instead of 3, 6 columns with 0 and 1 value. Right? So do you see this? League A, League N, Division E. Do you see now? So wherever we have value of league, get underscore dummies is one-hot encoding and label encoder, that is the function. So is the output of dummies dot head is also clear? That now if these are the 6, the 3 categorical value can get converted into 6, and wherever the value was there, this is 1 or this is 0, and this is 1. Clear? Okay, so what are we doing? We have separated the output. X numerical value, we are dropping the output, the league, the division, and the new league because they all are categorical data, and everything gets converted into float type. So the numerical columns are now clear. The input X numerical and the output Y salary. Good, Chakrapani. Good. Now, do we need to concatenate these columns with the original data? So we'll just take one of them. Since it has binary category, please try to understand. Since all of them have binary category, therefore it can be used for league underscore N, division underscore W, and new league underscore N. Getting my point? So now you see all my inputs have become integer values, numerical values, and that is what is required before you feed any data into the model. Now, once my data is ready, now we go in for testing and splitting of my input and output. Test size is 25%, rest is training, and I get my 4 outputs, right? So Lasso, performs best when all the numerical features are centered around 0 and have variance in the same order. Homoscedasticity needs to be maintained. And if a feature has a variance that is orders of magnitude larger than others, it might dominate the objective function and make the estimator unable to learn from others. So it should not be that, one of the columns have very high values and the other one low. This means it is important to standardize our features. We do this by subtracting the mean from our observations and then dividing by standardization. What is this concept known as? Of feature engineering. Okay, I've given you one hint. This is the concept involved in feature scaling, and this refers to standardization, that is scaling the factors with mean equal to 0 and standard deviation equal to 1. Clear? To avoid data leakage, standardization of numerical features should always be performed after data splitting only for the training data. Please try to understand. To avoid data leakage, we will only and only use it after the splitting of the data. We saw that. So what is data leakage? We understood what is data leakage. that it occurs when the information from the outside, the training data set, is used to create the model. This can happen if the data would not be available at the time of prediction, is included in the training process. So data leakage can lead to optimistic performance estimates and models that fail to generalize well to new as well as unseen data. Clear? So, which is the Python function? Which is the Python function to perform standardization, standard scaler, which creates an instance of the object. Fit trains the X-train numerical data, that is, training means to find out the parameter to compute the mean and the standard deviation for each feature in X-train list underscore numerical. X underscore train is your for each data set, and the list numerical is the list of column names corresponding to the numerical features. Got it? What is the use of transform? It applies to the standardization of the training data, which transforms each feature in the training data set to have mean 0 and standard deviation 1, right? And then we only use the transform function on the test data. Now clear? Okay. Standard scaler is clear. It's the function to perform standardization. Standardization is one of the feature scaling technique where we take mean equal to 0 and standard deviation equal to 1, Anush. That point is getting clear. Fit is always performed on the training data, that is numerical data. Till here also this point is getting clear. That this refers to the list of numerical data, and transform we are doing it on the trained data. That is how we are going to avoid data leakage. Now clear? Got it? But when we talk about testing data, are we going to apply fit function on it? No, we are only going to transform it. So it applies the same standardization parameters, mean and standard deviation computed from the training data to test data. And this ensures that the test data is scaled in the same data as training. Now clear? Okay, right? So practically, how do we go about it? So we have imported the standard scaler from the Scikit-learn library, and then we perform this function. So the explanation is given above. Right? So what are we trying to do? We are fitting the standard scaler to numerical features so that there is no biasness in the data set. Now, you'll see positive, negative value because the sum of all these values should be 0. The mean of all them should be 0. Clear to everybody? So the training data has 241 rows and 19 columns. Clear? Similarly, test 1 will only have 81 rows because of the 25% data and 19 columns. Clear? Now they were missing values in the output data. How do we go about it? How do we go about it? Let's see. Yeah. So what are we doing over here? Yes. What are we doing? We are taking the training model as well, training data as well as the testing data, and filling it with the median value. Wherever there is null value, it will fill it up with median. Not mode over here. Dr. Henry, we see it practically that it's getting filled with median. What is the difference between mean and median? Besides that, which one is affected by the outliers? Where do we use median? When we do not want to get affected by the outliers. So now let's move ahead and understand the lasso model. So whenever we have to create, how do we begin with the hyperparameters? If I want to start any of the models, how do we begin with hyperparameters? we will randomly assign any value and then start training on it. And to find out the actual value, we do hyperparameter tuning. So we apply lasso regression on the training set with regularization parameter, that is alpha equal to 1. So we begin with a very simple value, alpha equal to 1. This value is commonly used as default and provides a good balance between maintaining model complexity and reducing overfitting. Okay. So by default, whenever we have to do things, you can randomly assign any value to the hyperparameter. Alpha is equal to 1, maximum iteration is equal to 10,000. And now we are fitting the training data. And this is now my new intercept coefficients, the regression coefficients, beta naught, and the other coefficients. Because since they are how many parameters? Can you tell me how many parameters are there in this particular question? How many are there? 19, all the numerical values, right? So we would have 19 coefficients. And do you see after applying lasso, some of them have become 0? This one, this one, this one, and this one. Getting my point? So if I see the output, these are my coefficients and some of my coefficients have become 0. Do you see? Then you might say, ma'am, what is negative 0? It just puts the sign. There is nothing, no term in mathematics as negative 0. Clear? So what do we conclude? This is the intercept term of your lasso regression model. It represents the expected mean value of the independent variable when all the independent variables are set to 0. In practical terms, it is the baseline prediction when no other information from the variables is provided. So the lasso coefficients represent the relationship between the variable. Positive coefficients. Now, what do we interpret out of it? Let's see that. A positive coefficient indicates that as independent variable increases, the dependent variable also increases. That's the positive relationship. A negative coefficient indicates that an independent variable increases, the dependent variable decreases. The magnitude of the coefficient shows the strength of the impact. Now clear? So the magnitude of the coefficient shows the strength of the impact. A larger absolute value indicates a stronger defect. Lasso regression is known for its ability to perform feature selection. So ultimately, the values have become 0. So now my 19 features have reduced to, so I have reduced these two. Then I have also reduced 2 above and 1 in the last. So 3 features get reduced. So 19 gets reduced to 16, right? When we have taken lambda equal to 1. All right? Right? But in this model, however, it seems that none of the coefficients are exactly 0, suggesting that all included variables have some impact on the models though some impacts are very, very small. So basically 4 features. Yeah, okay, 4 features. So now how do I evaluate it? I'll calculate my mean square error for the training data and then for the testing data. This code is also getting clear. That helps me to decide whether it's overfitting or underfitting. So now you tell me, is it an overfitting model or an underfitting model? Testing error is more than the training. So is it underfitting, overfitting? It's overfitting. And if I do the R square over here, so the value is very, very less. So to better understand the role of alpha, the regularization parameter. So what is alpha known as? The regularization parameter. Plot the lasso coefficients as a function of alpha. Maximum iterate are the maximum number of iterations. So here we have np.linspace function. What does the np numpy linspace function do? That now the values of alpha will range between 1 to 5 and with 10 equidistance value. So now what are we trying to create? Linspace function, do we understand of NumPy? So now if I say now I will start understanding the range of the values from 0.01, right, to 500, and the value is still 100, right? So over here, these are the values or the array created of alpha. The maximum iterations are 10,000. And now I will try to run or fit on each of these alphas. And then look at this beautiful graph. Simon, specially for you. So the value of the alpha goes from 0.01 to 100 and 1000. And we see as the value of the alpha is increasing, some of the coefficients actually become 0. You see this? So that is why L1 regularization is also known as feature selection. Agreed? Okay. So have you understood this graph now? So we create now the best value of alpha. How do we find out the value of alpha? That now we will use cross validation to find out the best value for alpha. Lasso regression comes with built-in cross validation. So beauty of lasso is that you can combine lasso with cross validation. Alpha again ranges between 0 to 1000, CV is equal to 10, maximum iteration 10,000, and n underscore jobs is equal to -1. Can you, anybody tell me what is the use of this parameter? Okay, I need to repeat that. Okay, Simon, I'll do that. In the meanwhile, tell me what is the use of n underscore jobs, learners? See, once we have checked on the training and the testing process, and we found out that it is an overfitting model, the test error was too high than the others. So now we have to find out the, the best value of alpha. Okay. Right, so use the maximum course, and which is the, best alpha value which has come out. Over here, 6 comes out to be the best regularization. So get the best alpha regularization strength selected by the cross validation. Clear? So it was not, the value of alpha was not 1, but it will come out to be 6. And now I will create and fit the lasso model, taking this value. Now I will fit it and now check on my training and testing errors. So have they improved? Well, the test error is still higher than the training, right? But it shows a better performance on the tuned parameters. So zero coefficients such as runs, RBI, CAT, and all these new leagues have several coefficients shrunk to 0. This indicates the lasso has deemed these features less important, irrelevant for the data set, and the non-zero coefficients give us the detailed relationship. Clear? Moving on to ridge regression. Ridge regression is another technique for handling overfitting of the data. That's known as L2 regularization. Here, none of the features will become 0. Rather, values will become less, right? So, where it is used, when to use that and when to use the other one. Get the best alpha selection validation. Now, what is this? Added below library. Okay, so when is ridge to be used? It is useful for handling multi-collinear data where two predictors, independent variables, are highly correlated to each other. Right? And the second important reason, Ajay, you are absolutely correct. Ajay Kana, you're absolutely correct. But the second reason where we use ridge regression is that it is useful for handling multi-collinear data where two predictors, independent variables, are highly correlated to each other. Now getting my point? Collinearity refers to a situation where two or more predictor variables in multiple regression model are highly correlated, meaning they have a linear relationship, and this makes it difficult to determine the individual effect of each predictor on the target variable. Right? So that's why the penalty term is added, the regularization terms are added. Getting my point? So now let's see ridge. Again, we have a ridge CV function which can do. So on the same data, we will first apply the alpha fit function and get the intercept value. Yes, ridge needed to use if we want to keep all the important features. So I have not been running the code, so I will get error. So sorry for that. I'm not running the whole code, going back and running it. So now let's move and then evaluate the model. Again, testing error is more than the training. So overfitting is there. And do we see the coefficients now? None of them become 0. Now we can use cross validation again to find out the best value. These are the values. I have used rich cross validation, and in this case, the value comes out to be 204. Right? Then we train on it, and these are my new coefficients. These are my new coefficients, right? All values have reduced. If you compare with the original, all values have reduced now. So the negative error relationship is with errors, division W, they show the negative relationship. So the coefficients with highest value suggest cumulative career statistics, total runs, the total hits are most important and showing a positive relationship with salary. Division underscore W, the only feature which is notably high negative coefficient, which indicates that being in Western division is associated with negative effect on the target variable. So do not be in the Western division. Years assist and new league and these features are smaller. So are you understanding? This is how you're practically supposed to run the code and write down the observations over here. And if we see it graphically, that in this case, the values will not become 0, but near to 0. Clear? So have you understood the concept of regularization? How it helps in preventing overfitting, whereas L1 helps in feature selection and ridge helps in reducing the values if all are important. And of course, this analysis helps in understanding the relative importance and influence of different aspects of a baseball player statistics on the predicted target. Clear? Now moving on to the next concepts, that is optimization, right? Model optimization. Now, what does the term optimization mean? What is the meaning of model optimization? Optimizing resources. We want minimum number of code, less number of time to giving the best. Yes, how the model performs efficiently. Absolutely. So if we talk about the journey of data science or analysis, see everything, if you are doing a normal Excel, maximum, minimum, drawing graph, that's also analysis. And even when we are doing machine learning, that's also analysis. But where is the difference? Are you able to get this graph that I'm showing? Where is the difference? Can you tell me? If we already have a data set, so this is the side for that. We are going to describe, about the historical data that we have. That is simple finding out hindsight in the data. When we try to find out why that happened, that becomes diagnostic analysis, that is insight. And if we move further, what is going to be predicted? Sorry. Or what will be the output? That becomes predictive analytics. And similarly, why that we are predicting that output, whether that is going to be good or bad, that is known as prescriptive analytics. So this is where we start from insight, and now we want to move to the foresight. How does it happen? When we start optimization of the model. Are you understanding this point? Very, very important graph. From one analysis to another. To explain you in more layman language, suppose you have cold and cough, right? And you go to the doctor. Doctor sees, okay, your nose is running, you have cold and cough. He says, you take this normal medicine and, do a lot of steaming and take this medicine, you'll be fine. But that was his, analysis which he done to just by seeing you. So then you come back, you are not fine. Then you go back after a week to him. You say, no, I have fever also, I have other thing. Then he thinks that the fever, he is not getting well. So maybe he has some kind of an infection. Then he prescribes you certain blood tests. So based on the blood test, he would give you certain medicine. But you are still not fine. Your further analysis is needed. Maybe you have a chest infection now or something, and maybe you want to go in for an MRI. So that's how the level of analysis increases. All right. So basically, what do we want to do and what do we want to optimize in this whole machine learning process? That if we have this input data, that is the training data, including the target output. Of course, if it is supervised learning, we would also have the target output. This is my model, right? And output prediction calculated by model. So when we try to compare the predicted output with the actual output, therefore we are able to calculate the error and the loss function. Are you all there with me? Then we are able to calculate the error and the loss function. And using this error and or loss function, we can use optimization method to, further reduce the values. How we can further reduce its value. Getting my point? Right? So that's how we are trying to improve on the error part of it. And then another way to optimize the model is through hyperparameter tuning versus model training. What is hyperparameter tuning? That to find the best hyperparameters which give us the most efficient results. And this is a very, very important slide because it gives the whole crux of the data, of all the points that we have studied till now. Please look here. This is my data set. Feature engineering is performed before. What are the different aspects of feature engineering? And why is feature engineering required? Tell me. What are the different aspects of feature engineering and why is it required? To prepare the data to feed into the model, not tune, we will say to prepare the data, pre-process the data to feed into the model. And what are the different types of feature engineering? So what are the different processes? Encoding, scaling, transformations, right? Dealing with the outliers, they all come under feature engineering. First step is clear. Then what is happening in this particular step? Can anybody tell me? What is this step known as? Splitting, but what are we splitting and why are we splitting? It is splitting of the data set. Why are we splitting it into 3 parts? Normally it is training and testing. This step is known as cross-validation, that it divides the training data into training and validation and a separate test data. Second step is splitting of the data, yes, but we generally keep using it for cross-validation By taking multiple samples. Got it? By taking multiple samples. Now, this is an iterative process. This keeps on getting repeated. So the training data, we build models, train the results, right? And finally, once the training is done, then on the validation thing, we do the training results, do hyperparameter tuning, and keep on repeating this iterative process. Finally, the best model which is selected is then used for testing the output and compare the results. Do not get confused. See, every concept that we study has its own role and concept, right? So where will the regularization fit over here? If I compare the result, my testing result is much higher than the training result, then it is an overfitting model, right? We always start with the basic mega. Then we will use the model over here as ridge or lasso and then do the comparison. Now getting my point, everybody? All right. And the two types of hypertuning methods are grid search and random search. Grid search is the one in which it's an exhaustive search technique where we have different hyperparameters, one such as A, B, and C. It's not necessary that, we have understood that regularization has one hyperparameter. We have other models like decision tree, which have many hyperparameters. Hyperparameter to XYZ value, and then we try to take all the combinations and then see which one works best for a model. Disadvantage of this method is it's an exhaustive method. Computationally and time-wise, it is expensive. Clear? And random search, that randomly we will select any hyperparameters and do training on it. Clear now? And we have seen, so cross-validation is a very, very important technique. Why? Because it helps to split the data into training, validation, and test set. Please make this point clear. Cross-validation technique will almost be used in supervised learning because it will divide the data set into three parts. That is training, validation, and testing set. Useful if you want to have a metric on how well your model is performing. Clear? So once the grid CV search returns with tuned parameters, build the model using this set with the tuned parameters and test the new model with the test set. Clear? And this is another, slide which I always show it to my learners even in my feature engineering class. Now, are you able to interpret this particular slide, everybody? Yes. Right, so we again have a data set, retrieve the data set, perform pre-processing, wrangling, feature extraction, feature engineering, train the model, then model evaluation, hyperparameter tuning, and reiterate the process. But this slide gives a much better picture of each step. Got it, learners? So getting back to the file. So this file is pretty long, Last week also we have done, and I think so this session also we would be using. So model optimization means hyperparameter tuning is the process of finding the best settings for the parameters in the machine learning model. Hyperparameters are settings that are not learned during the training, but are set before the training process begins. Hyperparameter tuning involves trying different combinations of the hyperparameters and evaluating the model's performance using validation techniques. So the two techniques that we can use is grid search. So how does it work? How do we do the grid search? It systematically works through the multiple combinations of hyperparameters. It performs an exhaustive search on a specified parameter grid. So how do we go about it? Please try to understand the different steps. The first step is we define a parameter grid that is defined with the help of dictionaries, because there can be more than one hyperparameters in the model. Combination evaluation. The algorithm evaluates all possible combinations of these hyperparameters. Model training. For each combination, the model is trained, evaluated using cross-validation. And then we have the optimal parameters combining, yielding the best performance. Highest accuracy is chosen as the optimal set. All right. And how does the random search work? It defines the parameter distribution, specify the distributions and ranges of the hyperparameter. Random sampling, random sample combinations of hyperparameters from these distributions. Model training for each sample combination, and optimal parameters. All right, so now on the same hitters.cv, we are running the code. I might get a lot of error. It will. Let me run the x_train. Okay, so this is the grid search cross-validation. Here we are creating a cross-validation object with repeated k-fold function. Number of splits is equal to 10. Number of repeats is 3. Random state is equal to 1. Are you now there with me? Everybody, other code, else code is running. Then we create a grid or a dictionary and then try to find out the values. So still it's giving error. Is it running for everybody else? Oh, well, I've tried to do a shortcut, but shortcuts never work in life. Value y input consists of nan. Okay. Yeah, are you getting it? I'm not running the code. So this point is clear. So the best parameter grid of alpha, now it's coming out to be 0.9. Is it the same with everybody? So then we create and fit the ridge regression model to avoid training data with the optimal alpha. So here we have the ridge function results into best parameters alpha, fit them through the training input as well as output, and find the mean square value that comes out to be 341. And R square comes out to be 0.38, which suggests a moderate fit. The model captures some of the variability in the data, but not a large portion. And now if I see the coefficient, this is how the coefficient values are. Now let's move on to the next concept, last concept, by creating pipelines. So Scikit-learn pipelines are nothing but an automation of the model fitting and data transformation steps for training and data set. So what are we doing at the moment? When we upload the data, we separately use fit and transform, do encoding, do scalar standardization. Now we will try to implement it with the help of a single pipeline. So what do? If we have test data, test labels, we would perform feature scaling, standard scalar initially. Then if feature selection or extraction, dimensionality reduction is required, that can also be done. And then the model data can be fed to the different models. So how do we go about it? We are very clear in supervised learning. We have a training set and a test set with class label, right? So in the first step, we will try to fit the training data that is missing in the test set, because we do want to avoid data leakage, right? The fit function will never ever work for the test data, right? And therefore we have the fit transform function over here. This is the pipeline, right? So over here, we do the transformation such as for scaling, dimensionality reduction, and then do the predictive model. And over here, it is fit and transform for the training data, but for the test data, it is only the transform function. Clear? And the predict will only be for the test data. Now let's see how do we practically implement it. So why Sklearn pipelines? Pipelines provide an organized approach to managing your data, pre-processing, modeling the code. They combine the pre-processing and the modeling steps into a single streamlined process. Cleaner code pipelines eliminate the need to manually manage training and validation data at each pre-processing step, reducing the clutter and the complexity. Fewer bugs by bundling steps together. So bugs are few. It gives a much more cleaner code and easier to productionize. That is, they simplify the transition from a prototype to a model to a scalable, deployable solution. Clear? So we have Sklearn is a beautiful library. We just need to, create a class, or we do import the pipeline function, and we will create an object of pipeline class, whatever steps that we want to perform. Do we want to use any kind of memory or verbose? Clear? So a pipeline is a sequence of data transformers that can include a final predictor also, final output also. It lets you apply pre-processing steps to your data in order and optionally end with a predictor for modeling. Each intermediate step in the pipeline must have fit and transform methods, while final step only needs the fit function. Memory stands that you can use cache memory for these transformations to make the processing fast using the memory argument. The pipeline main goal is to combine multiple steps that can be cross-validated together and have their parameters adjusted. You can set parameters for any step by using it name followed by a underscore. So you can set any of the parameters by default followed by a underscore name and the parameter name. And you can replace any steps estimator with another estimator or remove transformer by setting it or pass through or none. So now over here, they are using a different data set. That is the one with ocean proximity, that is housing one. I think so I gave you for testing also. So it is little different from original because one of the parameter is categorical ocean underscore object. So how do I check that? What are the different categories of this particular function? How do I check that? So we have this categorical data. So what are the different encoding techniques? Either we use one-hot encoding. That is better because there is no order in this. So we'll not use label encoding. We'll use get underscore dummies function to perform it. Value underscore counts function is a function in Python which gives the categories along with their frequency count. Very, very important function. What is happening in this particular code of line number 46? Come on, learners. Y is getting the output value and then we are separating the X. Yes, we are defining input and out. What is happening in the next step? Line number 48, what is happening in the next step? Splitting of the data, very, very important. And then we see the info and sum over here, right? So where are the null values? Where are the null values? Total bedrooms has 162 null values. Data is huge, 14,448, right? So definitely cleaning is required. Removing of the null values, encoding is required, right? So rather than now performing each of these steps separately, can I use the concept of Sklearn pipelines? First, I will feed in for training data, perform feature scaling, feature extraction, and ML algorithms, and then work on the test data. Getting my point, learners? Okay. So what are the steps that we want to perform before building the model? Feature engineering steps. So feature engineering part is used as Sklearn. Even the other parts can be combined as pipeline. First, missing value treatment, imputation, 162 missing values in the total bedrooms, numeric data column. Then we have the dummy variable creation for categorical data. And finally, standardization of the numerical value. So how do we go about it? These are my different libraries that I will import, and most importantly is the pipeline library. Getting my point? A very important concept in Scikit-learn is the column transformer. That importing column transformer class to apply different pre-processing steps to different subsets of the feature. So column transformer has the capability that encoding is applied only on categorical data, not on numerical data. Getting my point? So it will only be applied on categorical. So let me explain this. Okay, so this is how the fit transformation happens. But if these are my features, which is a combination, obviously, of numerical, categorical, and others. So column transformer has the beauty that for numerical columns, only scaling will happen. For categorical, one hot encoding, and maybe others can simply pass through. It's not necessary that some operation needs to be performed on it. And finally, we can get a transform data in very one go, and it can be combined together. Got it? Column transformer concept is clear to everybody? So here we go about implementing it. So now when you read about column transformer, you will understand that it allows you to apply different pre-processing steps to different subsets of the features in your data set. This is particularly useful when you have a mix of numerical and categorical data that require different types of pre-processing. Column transformer ensures that each column or group of columns gets appropriate transformation before combining the results for further processing or modeling. Okay, so now step 1. Let's store the names of the numeric and object type variables differently. So how are we going to do? And now we have splitted the training and the testing data, and we are exclusively selecting the data types: include object, exclude object, and result. Are you understanding this code, learners? So housing underscore cat will only have one, since this data set has only one categorical data, that is ocean underscore proximity, and the rest are all numerical in nature. Clear? Now, the next step says to set up Scikit-learn pipelines for numeric variables, we need to perform missing value imputation and then standardization. So how do we go about it? Now we will create a pipeline object using this pipeline function, num underscore pipeline. So for numerical data, we will import, do the missing value imputation and standard scaling. Is this point getting clear? Simon, are you there? Are you understanding this code now of creating pipelines? Yes, learners. What is imputation and what are we trying to achieve over here? Imputation is the concept of missing value, and here we are filling the missing value with the median value. Good, Megha. Very clearly it says that, right? And standardization is that we are trying to create the mean of the data 0 and standard deviation equal to 1. Then unified data processing with pipelines and column transformer. Now, we need to create another pipeline. No. So we've created a numeric pipeline. Now we create a column transformer, the numeric pipeline, and the other one categorical. For categorical data, we only need to perform only and only one function that is known as the one hot encoder function. Clear? So this ensures both numerical and categorical data are pre-processed approximately within single unified work. Now got it? The beauty of column transformer that we have combined the numerical as well as categorical values. Okay, then we do pre-processing fit underscore transform x underscore train. We're going to fit and transform and now check the data set for training. Clear? Now do you see? It has already done this. So, right. So now we fit and transform and now check the training data. This is my training data. And now if I check the scaling has already happened, negative values are there, as well as the null values have been removed. Got it? Pipelines, are you understanding? So what is our observation? Good to see all missing values are treated, numeric values are standardized, ocean proximity is converted. Now, the other way of creating model is again, you can create a final pipeline for pre-processing and model ridge. Over here, we are creating ridge regression model straight away and then moving ahead. So have you printed that also, the final pipeline also? Yeah, so final pipeline gives you this, that after applying the basic thing, we are applying the ridge model, right? And then we define the grid of hyperparameters. To search, you can set parameters for any step. So over here, this is my ridge alpha, the hyperparameter, which will range from 0.1 to 2.1. And then I use my grid search CV along with cross validation. Estimator is my final pipeline. These are my grids that I have passed onto it. Scoring, I'm using negative mean absolute error. Number of jobs is equal to -1 and we fit and get the output. Clear? So the mean absolute error is 49,000 and the alpha value is coming out to be 0.1. Then I check my test result. The test result is slightly higher, so it's almost a good fit of the value. Now clear? How, and even in classification model, we would be using a lot of pipelines to get the result. Getting my point? So finally, today, after Scikit-learn, we come to the end of regression analysis, which is, part of supervised learning, predicting numerical value. Regression analysis is an essential method for estimating, examining, and predicting variable relationships. In this lesson, we type, as we had discussed initially, types of regression, then the different error matrices, the cross-validation technique, the regularization technique, hyperparameter tuning, and then finally the pipelines. Are we all now clear with this particular file 3.2? Finally, we are ending with regression today. First question, what is the primary goal of regularization in machine learning model? Why do we want to do regularization? Yes, if we want to prevent overfitting. Which of the following is a characteristic of L2 regularization? Squaring of the value. Which answer is correct? A, B, C, D. Quick learners. It is both B and C because it adds the squared magnitude. It's rich of coefficient and it reduces overfitting by reducing the model complexity. Next question. What effect does increasing the alpha parameter in lasso regression have on the model? Lasso, do we want to increase model complexity or decrease? Obviously, when alpha increases, the model complexity. What is the primary difference between L1 and L2 regularization in terms of the effect on the model coefficients? Remember, L2 means squaring of the value, L1 is absolute. So it's simple. L1 encourages sparsity. What is sparsity? Having value 0. So it makes most of the features equal to 0. Well, while L2 regularization does not encourages sparsity. Now clear? How does regularization help in improving the generalization ability of a machine learning model? Do you want to reduce the variance or the bias? Overfitting. Overfitting gets reduced by variance. What is the risk with tuning hyperparameters using test data set? What will happen if we tune hyperparameters? What is the risk with tuning hyperparameters using test data set? The model will overfit the test set and data leakage can happen. Which of the following is not the purpose of optimizers? They try to avoid overfitting because that's the work of regularization. If searching among large number of hyperparameter, you should try values in a grid rather than random value so that you can carry out the search more systematically and not rely on chance. True or false? We should carry out more systematic searches or random searches when searching a large number of hyperparameters. Right? False. You should try values in a grid rather than random values. Why? Because then it would become an exhaustive search, right? We should always try random values. I hope this knowledge check was helpful for everybody.
Start with another part of supervised learning, that is classification. Now tell me, how will you define classification? It says supervised learning used when the output is categorical, right? Yeah. So this is supervised learning technique when the output is categorical. So these are the independent input variable and the model classifies them as animals and fruits. So are you aware about different classification techniques, learners? Do you understand different classification techniques? Do we understand the concept of binary classification? What can you interpret from this particular diagram? That the model will classify the input or not input, sorry, the outputs into two categories. For example, if a mail is there, it will either put it into the spam folder or the inbox. So when there are two categories as output, that is known as binary classification. Getting my point, learners? Can we have more than two classes as output? Can we have more than two classes as output? Yes, we can have, when we want to label different vegetables such as capsicum, carrots, tomato, radish, turnip, it could be endless number of classes, and that is known as multi-class classification. Are you all getting this point, learners? That is known as multi-class classification, learners. What is this? Suppose I have an image and in the image there can be multiple labels. This image consists of a truck, boat, dog, as well as a plane. So if we have more than one, it's not multi-class, but a same, image or a same input. For example, a movie can be romantic, thriller, horror also, right? Or comedy, thriller, horror. So the same item can have multiple labels. That is known as multi-label classification. What do you observe over here? If the classes are not balanced, right? The images of trucks are around 60% plain, only 25% boats, 15. Then there is a different techniques to deal with imbalanced class data set. All right, so this basic concept of different classes is clear. Now let's straight away dive into how we will analyze the classification output, right? Or what are the different metrics to analyze the classification output? So what do you think? How will I check whether my model is classifying the mails and the spam mails correctly? The metrics which is used or the major role that is being played is done by the confusion matrix. Please try to understand. For example, I'm taking a very simple example. There is a bag of balls of red and green balls. Now, if I tell you to classify them, it is good that in the red ball bag, you put all the red balls, and in the green ball bag, you put all the green balls, right? So that is true positive and true negative. So the green balls which belong to the green bag are in the green bag, and the red balls which belong to the red bag are in the red bag. But is there a possibility that a red ball can be in a green bag or a green ball can be in a red bag? Is that possibility? Yes, machine can create those errors, and that kind of errors are known as false negative and false positive, right? When the machine does not predict the correct output. So what is our aim as a model? We always want to increase the true negative and true positive to create the best results, right? And we always want to decrease the errors, that is the false negative as well as the false positive. Getting my point, right? So a confusion matrix, please remember again, it is very, very important point when we always talk about classification, that a confusion matrix is an n by n matrix used for evaluating the performance. And that is why statistics is said to be the strong foundation for machine learning concepts. Bang on, Mega. Appreciate this. Yeah. So confusion matrix is an n by n matrix used for evaluating the performance of a classification model where n is the number of target classes. So it will always be a square matrix. A good model, as we have understood, will have high true positive and true negative rates, and whereas a low or a bad model will have high low true positive and true negative rates. So what do we do when we have imbalanced data set? That means the ratio of the classes is not same or equal. It's always better to use confusion matrix as your evaluation criteria for your machine learning model. So this is how you will get the output in terms of your Python code. It will create this kind of a matrix and display for you. And I hope the terms true positive and true negative, false negative are clear. True positive is predicted positive, which are actually positive. False positive, predicted positive, but are actually negative. Getting my point? And this is exactly the same example I always use in my hypothesis testing class also. I use the same example. All right. So this is a very, very interesting example. We have the images of cat and dog, right? So we have about 20 images of cat and dog, right? So for cat, they were only 7 images, and dog, they are around 13 images, right? So I, ran this particular images on the model. So 6 images, which were actually cat, were predicted positive by the model. So that becomes my true positive. 11 images, which were not cat, were actually predicted that they are not cat. They come under the true negative category. So very good. But the errors were that the image was of the cat, but it says that you are a dog. So one error over here of false negative. And similarly, the image was of the dog, but it says that you are a cat. So this is false positive. So the false negative errors are known as type 2 errors also, and the false positive are known as type 1 error, or also known as alpha and beta. If you remember from hypothesis testing, same concepts. absolutely same concepts are being used. Are you understanding this? So they are different metrics that can be evaluated from this confusion matrix: accuracy, precision, recall, F1 score, FPR, and FNR all can be calculated. So if I talk about accuracy, accuracy simply measures how often the classifier makes the correct prediction. It's the ratio between the number of correct predictions and the total number of predictions. So what does accuracy mean? I'll take my true positive, true negative divided by the total number of output. That gives me accuracy. But what is the illusion over here? The illusion over here is that it is not valid for imbalanced data set. Anu says, why type 1 and type 2? Why type 1 and type 2? Is there a possibility that the classes might not be classified correctly? So type 2 and type 1 actually arise because I am considering one of the statement as positive. Positive means that the image is of the cat, and negative statement means that you are not a cat, right? So false positive error means that actually it is not a image of a cat, but still says you are a cat. That is why false positive, that it is not a cat, and false negative because it is not a dog. The same game we play between null, but we'll be resolving it into different metrics. So one of them is accuracy, the other one is precision. So the precision is defined as the ratio of the total number of correctly classified positive classes divided by the total number of one predicted. So precision is useful when, please try to understand, precision is a useful metric in cases where the false positive is a higher concern than false negative. What do we mean by that? That false positive is a higher concern in precision. So what is more deterring? Whether, the mail is not a spam, but the model predicted as spam. Is that more important than a mail which was spam and model predicted as not spam? Getting my point? So if our important mail is considered as spam, then that is a serious issue. Therefore, the precision needs to be high. So what is precision? It is true positive upon the true positive plus false positive. Getting my point? All right. So the other metric that we can use is recall. Recall is classified as the ratio of the total number of correctly classified positive classes divided by the total number of positive classes. Or out of all the positive classes, how much we predicted correctly. So recall should be high and ideally 1. And again, where is the recall function mostly used? It is useful metric in cases where false negative trumps false positive. Getting my point? So what would be the case where false negative is important than false positive? For example, medical cases where it does not matter if we raise a false alarm, but actual positive cases should not go undetected. Got my point? So this is the formula for recall: the true positive divided by the true positive plus false negative. Clear? Ma'am, do we need to calculate all these formulas? No, you just need to understand the mathematical intuition. The Python programming will do it all for you. Right? So some might say, ma'am, sometimes, the false negative error as well as the false positive error, both are important, right? Then how do we go about? Then the metric which is used to balance it out is known as the F1 score. So the F1 score is a number between 0 and 1, and it is the harmonic mean of precision and recall. So the definition already has the formula. Okay, harmonic mean, We use harmonic mean because it is not sensitive to the extreme values. So F1 score is valid when we have imbalanced data set because it maintains a balance between the precision and recall for your classifier. If your precision is low, the F1 is low and the recall is low again, and F1 score is low. So what do I mean by that? This is the harmonic mean and this is the formula. So F1 score is the harmonic mean and it should be ideally equal to 1. So there will be cases where there is no clear distinction whether to use precision or recall, then we can use the F1 score. Got it? So again, a quick recap. Accuracy is used when true positive and true negatives are more important. Accuracy is better metric for balanced data. False positive is much more important. Use precision. Whenever false negative is much more important, then use recall. F1 score is used when the false negative and false positives are important. Now clear? This gives you more clarity when to use what and where. And how do we create this confusion matrix in Python? By simply importing Scikit-learn matrix import confusion matrix and running the confusion underscore matrix function. So this is my Y test, Y predicted, and this is how I get the output in form of two-dimensional array, right? But the best part about it, that simply by using Scikit-learn matrix import classification report, we can get all the metrics in one particular output. This is what we actually use. Is it good? 85% accuracy. See, if you're not, see, Simon, it's a very, very relative question, right, Simon? Obviously, 100% is perfect. But depending on the model, the kind of problem that you are facing, if you're not getting accuracy more than that, then this is the best. But if you can get accuracy up to 92, 95, or 97%, then of course, 85% is not acceptable. You are the one who's going to decide whether to accept or to reject the project. Or you want to make further improvements or optimizations onto it. All right. So this is a very, very beautiful, code that, for classification, that we will have this classification report in which we get all the output, precision, recall, F1 score in one tabular form. All right. And this is what we are going to actually use for, comparing the results. Getting my point? So again, a quick recap: accuracy, precision, recall, F1 score, specificity, and different metrics can be calculated. But as I told you, we do not use different metrics. We will straight away import classification underscore report and get the output. Now, another very, very important factor, how graphically we can judge the output. So in classification problem, we have AUC and ROC curve. What does AUC stand for? AUC stands for area under the curve and ROC stands for receiver operating characteristics. This material is not there in the Simplilearn file. This is my material. I'll be sharing it. Even the regression material, classification material, right? So another very important factor to understand classification is the graph AUC and ROC curve. AUC stands for area under the curve and ROC stands for receiver operating characteristics. So AUC ROC curve is a performance measurement for the classification problems at various threshold settings. Now, what do we mean by various threshold settings? That we will try to change the that whether the classes have been classified correctly. The threshold value always ranges between 0 to 1. So it's like a meter rating. Okay. Now this is a point or this is the boundary. Yes, these two classes have been classified correctly, or the other two, right? ROC is the probability curve. Please try to understand. ROC is nothing but a probability curve, and AUC represents the degree or the measure of separability between the classes. So here we are trying to measure how well the two classes have been classified correctly based on the threshold value. It tells how much the model is capable of distinguishing between the classes. Higher the area under the curve, the better the model is at predicting 0 classes as 0 and 1 classes as 1. Now getting my point? What do we mean by AUC? It represents the degree or the measure of separability. The higher the area under the curve, the better the model is at distinguishing between patients with diseases or no diseases. So how does it work basically? So this graph is drawn between the false positive rate on the x-axis and true positive rate on the right-hand axis, right? And this graph is, and this is area under the curve, and this is the ROC, the receiving operative. Sorry. So this is receiver operating characteristics. And these are the different formulas that we have just now seen. So sensitivity and specificity are inversely proportional to each other, whereas TPR and FPR are proportional. Okay. So sensitivity and specificity. Okay. Recall the name. Recall, have we understood recall? Recall is nothing but the ratio between true positive and the true positive and false negative. Okay. The recall is also known as the true positive rate, and the other name is sensitivity. Now clear? Specificity is opposite of this. This is true negativity divided by true negative plus false positive. So ROC curve is the plot between the true positive rate and the false positive rate. That point is clear. Across the all possible thresholds. So what is this threshold? The threshold value is always between 0 to 1. And in between, it tells how well the two classes have been classified. Right? And AOC is very clear that it is the area under the curve. So the more the area under the curve, which is equal to 1, the better is the classification. Now clear, Anush? So ROC AOC curve is the area under the curve. It sums up how well a model can produce a relative scores to discriminate between the positive and the negative instances across all classification threshold. And the values will always lie between 0 to 1. So AUC is desirable for the following. That why do we want to understand the area? Why do we want to use this area under the curve? Let me go through it, and still you have errors. I'll explain them. First, let's get the crux of it. I understand a lot of points are there. First, let's get the crux of it. Area under the curve is scale invariant. It measures how well predictions are ranked rather than the absolute value, right? So it's scale invariant. It tells how well the predictions were ranked. It's not absolute value. It helps in comparison. Secondly, it is classification threshold invariant, measures the quality of the model's predictions, irrespective of what classification threshold is chosen. So this is what I mean by my threshold. Generally, it should be like 50-50%. Generally, 50-50%. That my true negatives have been classified as true negative. Green balls in green bag, red balls in red bag. And the total area under the curve is 1. So this is one of the ideal situations. This is one of the ideal situation that there is no overlap. Area under the curve is 1 and the model has ideal measure of separability. Now moving on to the next point. If we see it practically, even if my threshold is 0.5, there would be some, errors that, the red ball going into the green bag and the green ball going into the red bag. But these should be less. And if my area under the curve is close to 1, around 0.9, 0.8 or 0.7, then also it is said to be a good classification problem. So AUC 0.7 means that there are 70% chances that the model will be able to discriminate between negative and positive classes. Now getting my point, is everybody? Now are you understanding the meaning of threshold? Now if I decrease the threshold, suppose if I make it to 0.2, what will happen? My false negative error will become less, but my false positive error will become more. So the threshold, we have to try to always create a balance to get the minimum errors. Okay. Now look at over here. This is the case where the model was not able to differentiate between negative and positive classes. One of the worst cases, that area under the curve is 0.5. So we don't want the area under the curve to be equal to 0.5. So this is a worst situation where area under the curve is approximately 0.5. The model has no discrimination capacity to distinguish between the positive classes and the negative class. Now better. And what could be the even worse situation? That the true negatives have been classified as true positive and true negatives, positives as negative, and the area under the curve is 0. So when AUC is approximately equal to 0, the model is actually reciprocating the classes. It means the model is predicting a negative class as positive class. And do we want this situation? Never. We don't want this situation. Area under the curve to be 0, area under the curve to be close to 0.5, but close to 1 is a good option. That means the classes are able to distinguish each other clearly. What is the role of threshold? Classification threshold in machine learning is a boundary. At what boundary, as I told you, we will cut the two classes or cutoff point used to assign a specific predicted class for each object. Any machine learning algorithm for classification gives output in probability format. That point is also clear. So in the morning also I was teaching the LLM. So LLM chat GPT is, predicts the next word. They all come under the category of classification problems and they all give the output in terms of probability. Okay, so a little bit of Gen AI and LLM models. So LLM chat GPT, your Copilot, all the different models, they are all come under the category of classification problem and generate the word based on probability. Okay, so that's the tip of the day today. So in order to assign a class to an instance for binary classification, we compare the probability value to the threshold, and if the value is greater than that, then the probability it belongs to class 1. If it is less than that, it belongs to 0. So the story of threshold is like this, that what is the cutoff point that we can achieve to get the best distinguished classes? That if you increase the threshold, you move left on the curve, and if you decrease, you move right to the curve. Okay. Let's get back to the file. So now we are on lesson number 4. You can go ahead with 4.1. So there are a lot of algorithms that we would be covering in this classification: logistic regression, naive-Bayes classifier, KNN, decision tree, support vector machines. So today we will be touching on to the classification algorithms. Let's see how many are we able to do. Let's logistic, naive Bayes and KNN. Definitely we are doing 3. Let's see if we are able to begin with decision tree also. Let's see. So now if I ask what is the definition of classification, how will you define it? Tell me, what is the definition of classification? Yes, learners. I am purposely asking you these questions so that you have the, clarity of the concepts, and then you are also well prepared for the interviews. Supervised machine learning algorithm using categorical data. Always say it is part of which learning technique, and where the model is trained to predict the class label. The output is important. When I say label the output of the given input data, so it is important that the output is categorical. Getting my point? Please try to cover all the points in the definition. If you're going to just put 3-4 words, it will never give you a complete answer. Getting my point? Okay. So classification is a supervised machine learning technique used to predict the category of class of n observations based on the training data. So I think so this definition is quite correct. So classification algorithms categorize data into different categories. So do you think that in classification there is a role of this, straight line or linear regression? Do you think that can we use a straight line to separate two classes? Let's see. Since linear regression is a simple function, let's see, can it be used? But before that, classification, examples of classification in healthcare, whether you are diabetic or not, or your medical condition is there, all come under the healthcare category. Finance, banks, financial institutions are classification algorithm, whether you are eligible for loan or not. Marketing, classification aids in customer segmentation and target marketing. It helps business identify potential customers and tailor marketing strategies by categorizing customers based on their behavior. Retail, in retail, classification algorithms are crucial for managing inventory, forecasting demand, and manufacturing. Classification is essential for quality control, fault detection. So there is no domain where classification problems cannot be used. I hope you all are getting this point in retail, marketing, manufacturing, HR, everywhere. Right, learners? Now, what are the different types of classification that we have understood? Can you tell me? This is what you are going to try to solve, Roshan. Can we use regression in classification problem? This is we are just about to solve it. We're just about to solve it. Just be patient. Okay? Okay. So what are the different types of classification? What is binary classification? So when the model is able to classify only two classes, for example, whether the mail is fraud or not fraud, or spam or not spam, comes under binary classification. Already predefined, yeah, to classify into predefined multiple classes, whether it is a tomato or whether it is a vegetable, it is a fruit, or it is an animal, or is it a domestic animal or pet. So many classes can be used. One to many? No, Chakrapani, that's not the correct way to answer. The model is capable of predicting more than one classes of the input. That's the way to answer it. Multi-label. Multi-label classification. Be careful while answering this, that each data point can be assigned multiple labels simultaneously rather than just one. Yes, simultaneously, like in an image, it can have an image of a dog, cat, rat, a chair, etc. Okay. And the last part is imbalanced classification. What is imbalanced classification? When the classes are there, they can be two classes or more than two classes, but they are not equally balanced, right? One class, like 70% of males are there and 30% of females. When the classes are do not have the same frequency count, or we can say when one class has higher significantly more than other observations, right? When one becomes a majority class, other one becomes a minority class. Okay. So binary classification, under binary classification, some popular algorithms are used. So please try to understand. Binary classification can be achieved by logistic regression, naive Bayes, KNN, decision trees, and support vector machine. We are supposed to, do all of these. So while these methods excel in binary, capable of handling multi-class. So, except logistic regression or other are capable of handling multi-classification task also. This versatility allows them to be used in wider range of applications such as recognizing multiple categories of objects in images or predicting several types of behavior. So now we'll start with logistic regression. Before that, let me also let's do a recap. Now, what are the different metrics involved in classification? How do I judge that my classification problem is correct or not correct? Confusion matrix. Yes, so what are the different components of a confusion matrix? Accuracy, precision, recall. These are the different metrics, but components of confusion matrix I said components. True positive, true negative, false positive, false negative. Absolutely correct. And based on these components, we calculate different metrics which can be used to analyze the classification model. So if this is my data and I divide the data, because classification also comes under supervised learning technique. So if this is my data and I divide it into training and test set, and the training set over here, we have, right, from the training, we develop the model. Test set is used for model evaluation. And we understand for classification problem, the different metrics used are accuracy, precision, and recall, right? So it's a quick revision again. So this is my end-to-end matrix. If I have two classes, what are true positive and true negative? So when the output is also true, the predicted value is also true. When the output is false, when the predicted value is also false. But what are the two types of errors? What are the two types of error that we analyze in confusion matrix? Type 1 error is also known as alpha, or the false positive error, right? The type 1 is also known as the false positive or the alpha error. And type 2 error is also known as the beta errors. Clear? Then which metric is to be used when? We have accuracy, when out of the prediction model has been made what the percentage is. If it is an imbalanced class, is accuracy a good metric to be used, right? If we have more of positives, right, true positive, right, out of all the yes, how many them were correct, then we use the precision. Recall and sensitivity are the same. When we want to answer the question how good the model was predicting at real yes events. Recall and specificity. So there is always this confusion about recall. So recall is associated with specificity also and sensitivity also. The question can accuracy. So F1 score. So F1 score is a more matured score which can be used, which is not biased towards the precision or recall. And it is used when dealing with imbalanced data set, meaning that they are more of one class label than they are of the other. It corresponds to the harmonic mean of precision and recall, right? And what is the graph that we understood, which helps us to identify whether the two classes have been classified correctly or not. If you remember that graph, learners, the AUC, it's AUC and ROC curve. ROC stands for receiver operating characteristics. AUC stands for area under the curve, right? So what was that graph telling me? This graph generates probability value instead of binary 0 and 1. It should be used when your data is set roughly balanced. The ROC is imbalanced data set leads to incorrect interpretation. So ROC curves provide good overview of trade-off between the true positive and the false positive rate for binary classifier using different probability threshold. So the value, if the value is below 0.5, it's a poor classifier. 0.5 random classifier, but if it is 0.7 or greater than 1, we can set that it is a good classifier. Now clear? So this is how we understand the ROC and the AOC curve is between the false positive rate and the true positive rate, right? And if we look at the more closer look at the AUC and the ROC curve, this is my X, this is my Y axis. This is my optimal threshold. Practically, we are going to draw this graph also and the selected threshold. The ROC curves gives a quick visual understanding of the classifier's accuracy. The closer to the right angle curve, the more accurate the model is. So more closer it is to the right. Classification threshold that turns the upper left corner of the curve, minimizing the difference between the true positive rate, false positive rate is the optimal threshold. Clear? Okay, so now let's go ahead and understand the first algorithm for classification, logistic regression, that is transform linear regression, which gives output between 0 and 1. So there was this query of you all, can straight line be used for classification problem, right? That was the query. So when I say, binary classification, how do you think that binary classification would appear? Yeah. So I'm asking you, how do you think that binary classification points would actually look in the graph? Tell me. Yeah. Maybe not a straight line always. Absolutely correct. Right? There can be on the either side of the straight line, right? So if I say it's a typical good binary classification data, it's a typical binary classification data that either the output will be 0 or the output, this is an ideal situation. Agreed? Either the Y will be 0 or the Y will be 1. Do you all agree? So now tell me, is a straight line a good fit on these data points? Or is it covering, is it consistent, or is it underfitting? No, this is not a good fit. And moreover, the values are also getting lesser than 0, some of the values, and some of the values are greater than 1 that we don't want. Because in binary classification, the output will either be 0 or be 1 in ideal case. Agreed? So now I need to modify this straight line into a sigmoidal curve or an S-shaped curve. Is it helpful for me? First of all, the values will always be within the range between 0 to 1. Is this point getting clear to everybody? And suppose if I want to find out that my threshold value over here is 0.5. So if my value is 0.2, it is very clear that it belongs to this class. And if the value is 0.7, it belongs to this class. Only the confusion would arise at 0.5. So it is up to me. The 0.5, I want to keep it on this class or that class. Clear? Yes, linear regression, that question that regression are incapable of solving binary classification problem. Why? because the straight line gives underfit to all data points. The values can exceed greater than 1 or 0, right? So are all these points getting clear to everybody? Right? So how do we go about mathematically? So we understand this sigmoidal function equation is written like this, right? P is the probability 1 upon 1 plus e to the power minus y, where y is nothing but the, why can you tell me? It's like the linear polynomial, not even polynomial, multiple linear regression equation. Agreed, learners? So this is your linear regression. This is your sigmoidal function. So now if I start taking log on both the sides, so now on the left hand side, this is the equation that log to the power p. P is nothing but the probability. We want the answer in terms of probability that the values will lie between 0 to 1, that is p upon 1 minus p, beta naught, beta 1 x1, beta 2 x2. So again, ma'am, are we need to solving the coefficients over here? Yes. Logistic regression is a modification of linear regression, but here also we are trying to find out these regression coefficients. Got my point? Is this point getting clear to everybody? So taking this point further, log px upon minus px is known as the log it function. Now getting my point? Where does the term logistic term comes from? Because of this equation, and simple px 1 minus px is known as odds of p. That's the technical term. So now you are clear that the straight line or linear regression is not capable of solving the logistic regression problem. So the straight line gets converted into the sigmoidal S curve because the predicted y lies within the range 0 and 1. I hope this is clear to everybody. So, ma'am, in probability, P is the success, 1 minus P is the failure of the probability, right? Same we are using. Absolutely, the concept remains the same. Yes. Okay. So, if I say what is supervised learning, what is logistic regression, please try to understand and try to answer all the points. This is what the interviewer will catch. How many concepts you have grasped. Okay. So logistic regression is a supervised machine learning technique primarily used for binary classification. In this method, we apply the sigmoidal function to the linear combination of independent variables and predictors. Now clear? Always say that it is a part of supervised learning classification problem used for binary classification. And here we are applying the sigmoidal function to predict using the linear combination of independent variables, predictors of features. What does this mean? What does that mean? Independent variable predictors of features. This refers to the input part of it, right? Absolutely correct. Great. So this produces probability value between 0 and 1, and this probability represents the likelihood of a data point belonging to a specific class, positive or negative outcome. Clear? Now, the mathematical concept of logistic regression, it uses the sigmoidal function. The core is the sigmoidal function, sigma ZS. So over here, logistic regression is also known as sigmoidal function. This is how it will always range between 0 to 1, 1 plus e to the power minus z, where z is nothing but the linear combination of input. Multiple variable linear regression, and the output is in terms of probability ranging between 0 to 1. Are these points 1, 2, 3 getting clear to everybody? So now you're getting the crux of machine learning. You have to first understand the mathematical intuition of that algorithm or model. Then how do we implement it in Python? Understand it from three perspectives. As I always tell in my data science class also, first try to understand the concept, the mathematical intuition behind it. Second, how do we implement it in Python? And third, how are we going to interpret the output? All these things need to be taken into account. Got it? What is the cost function? What is cost function? The error function. How are we calculating the error function in logistic regression? That is calculated with the help of binary cross entropy. Please try to understand. The cost function used in logistic regression is binary cross entropy, which measures the differences between the predicted probability and the actual class label, where M is the number of the training samples, Y is the true label, Y cap is the predicted probability. Clear? What is the term optimization now mean, learners? Do we need to optimize our models also? See the concept, same concepts will be applied. So what is optimization? Why do we need to optimize the model? Tell me. Nobody understands. Why do we need to optimize? What is optimization? Extracting the best, right? Getting the best. So the goal is to find weights W and bias B that minimize the cost function. That is, this is typically done using gradient descent. So we'll try doing the gradient descent algorithm as we move ahead with further algorithm. Mostly in ensemble learning I've covered. Yeah, so basically we want the best output from the model. So now we are going to use the breast cancer data set. Do I need to share this with you all? Okay. Please download this and be ready. So this breast cancer Wisconsin diagnostic data set is widely used data set in the field of machine learning, particularly in classification problems related to medical diagnosis. This data sets consist of breast cancer cases derived from a group of patients who underwent surgery and had their breast mass tissue sampled, whether they are cancerous or not. And basically, there are two types of cancer. One is malignant and the other one is benign. Malignant, I don't know how I really pronounce it correct or not. And the other one is benign, right? And this data set contains 569 instances, each representing an individual sample of the breast tissue. Number of attributes, they are 30 numeric attributes computed from the digitized images of the tissue sample. These measurements of the cell nuclei present in the images. So based on that, we are there. So what are the different attributes or inputs in this data set? Radius, mean of the distance from the center to point. So it's not an image, just they have taken different parameters, which will help us to decide whether it's cancerous or not. Textured standard deviation of the grayscale, perimeter, area, smoothness, compactness, concavity, concave point, symmetry, fractal dimension. The target variable diagnosis indicates the cancer type, which can be malignant or benign. So what is the output? Diagnosis. And what are the two outputs of the diagnosis? Whether the cancer is malignant or benign. Now clear? is the objective. Please always try to give time on the data set. Without that, you will not be able to understand the analysis, what you're trying to do and what you are trying to achieve. So we will use this data set to explore and compare various binary classification algorithm, examining how their performance varies depending on the type, implementation of each algorithm, accompanied by the mathematical explanations. Yes, learners, are we good to go? Why do we do regularization? First, let's understand that. If regularization is required, then only we will do. Anush, why do we do regularization? Tell me. Yes, if observed overfitting, if the model will overfit, then we will. Okay, Anush? Yes. Now clear? So now let's start implementing. So what are the steps in Python? Come on, tell me quickly, learners. What are the steps in Python that we need to perform? Tell me quickly. Importing of the libraries. I hope the basic libraries are clear to everybody. Then these are for the pre-processing model scaler. Pipelines. Have we understood the concept of pipelines? Can we implement it in classification? Yes. What is the concept of pipelines? EDA? What does EDA mean over here? No. We don't. Yeah, we start with EDA, but first is import of libraries. I'm starting from very basic, Simon. So what is the use of pipelines? Tell me, learners. Yesterday we did Scikit-learn pipelines. Deployment after package. What do you mean by that? Organized workflow. Yeah, it's an automating workflow for building ML models. Good, Ajay. That's a better way. It's automating because we would do all the pre-processing in one workflow. That's the correct way of answering it. Okay. And sklearn linear model, logistic regression and accuracy. My sklearn version is 1.5.1. What about you, learners? Have we been able to load the breast cancer data set, everybody? With ID, diagnosis, radius mean, texture mean. Oh, so Subra, yours is higher than mine, right? So what do we observe in the info of this data set? Tell me. What do we observe in the info of this data set? Tell me. Where is my output? This is my output. And of course, it has to be categorical as malignant or benign. And all others are numerical values. You see, all others are numerical value. So do we need to convert the output categorical value into numerical? Do we need to encode the output? No. Ajay, we don't need to encode the output. Is encoding required? Yes, we definitely need to. Because computer will not understand benign or malignant. All the categorical value need to get converted into numerical value. Okay? So df.describe, okay? So this is the ID, this is the radius mean, texture mean, the perimeter mean. Do you see this? The count, the average value, standard deviation, minimum and maximum. So you have to, observe whether the values are lying within the range or are they too deviated, right? Right. So this is if I do df.describe.t, then I get the values for all other parameters. So unnamed, do we see there are, complete null values? So can we drop off this column? So df dot drop nr, right? Access equal to 1, it is for the column. In place equal to true, we understand that means it will make the changes original in the data set. So now we will remove this column because it is of no relevance. Got it? So now my data set is ready or not? So when I do a df dot shape, it has got this particular data set has got 569 rows and 32 columns. Agreed? So this particular data set has 569 rows and 32 columns. And what is the best way to check categorical data? By using unique function, which gives me the different categories. N unique gives me the number of categories, but I always prefer value underscore counts function. That means it gives me the frequency along with the category. So they are 357 benign, cancerous patients and malignant 212 malignant patients. Got it, learners? And if I draw a bar graph or count plot of it, I get this type. Everybody is getting this point, learners? Are you all there with me, learners? Even in your project or in real world, always try to create graphs, write down the observation, what the graph is doing. Right? Then again, which ID has been dropped? Which column has been dropped? The ID column has been dropped, and this is my original data frame. Got it now? Trying to plot a correlation heat map to understand the relationship between the features. The heat map visualizes the correlation between differences in the data set. So what does the heat map do, or what is correlation? Yesterday, we discussed about this. We've discussed this point. What are the values of correlation? What does the correlation do? What is the range of values of correlation? Tell me what is correlation, Pearson's relationship, which will always range between -1 to +1. Did I share that with you or not? So what are the values of correlation? -1 to +1. Positive correlation, yes. Negative correlation and no correlation. Yes, good, good. So you all remember, other learners? Great. So heat map is the map which gives me relationship between the various dimensions. So what do we observe? That there is high correlation value between radius mean, perimeter mean, and area mean. Whereas when we talk about other observations, feature groups, features related to worst, largest value of these features for being each image, mean and error, standard error calculations are grouped over here. Now tell me what is happening in the next stage. What is happening over here? That from Scikit-learn preprocessing import label encoder. Right, label encoder is one type categorical encoding. Please try to understand the correct word. This is categorically encoding, and we are using label encoder, right? And only one column is categorical, that is diagnosis. And here I am trying to fit and transform only the diagnosis column. So now my benign and malignant values change into 0 and 1. Clear? Is this point getting clear? So now when I see my df dotted, I see now no M and B. Earlier, please look at the output, the column of says it is in terms of M and B. Now I can see it in terms of 0. Can we define what is 1 and what is 0? How else? Yeah. So when 1 is malignant and 0 is benign. Yes, we can. Now what is happening over here? Yeah, so basically we are trying to separate the input and output and then split the training and the testing data, right? And after the splitting only, then we move to Scikit-learn pipeline, dot pipeline to streamline the pre-processing and the training process. Why do we do this? Why do we do this after splitting the training and the testing data? That the features in the training and the test sets are standardized to have a mean of 0 and standard deviation of 1. A logistic regression model is trained using standardized training data to avoid data leakage. We don't want our testing data to be part of the training data, otherwise there would no point be of the prediction. Got it? Right? So do we understand this pipeline function? What are the two things that we are doing in this pipeline function, learners? We are creating a pipeline. First step we are doing, what is standard underscore scalar do? Come on, learners, tell me, it's not that difficult. We've all done the EDA part of it. What is standard scalar do? Feature scaling, yes, standardization. And then we are applying model selection, logistic regression, which will be iterated 10,000 times and randomly the data 42 is getting selected. So till here, are we clear? We have splitted the data, right, into training and testing. Now, after training and testing split, and even the categorical encoding has been done, I am doing standard scalar function. What is standard scalar function? That all my data points will be standardized with mean equal to standard deviation equal to 1. Right? They will all be having that value, mean equal to 0 and standard deviation equal to 1. And next step, we will apply logistic regression on the data. Now better, Simon? Now clear? And finally, we go in for the pipeline dot fit. What does pipeline dot fit do? It will try to find out the parameters or the training data happens on input as well as output training data. Till here, so now when I do fit, it will automatically first do standardization of all the input points and then fit the model. And then we will predict the output using training and testing data. Clear? But since it is a binary classification problem, we will do not use simple predict function. We use predict underscore probability A. What does that mean? Probable outputs are needed that will range between 0 to 1. So this is my output, obtain the predicted output after training the model. Got it, learners? So now, how do I actually test? This is my actual label. This is my predicted label, and this is the probability associated with it. Are you understanding the three aspects of it? So when I do the probable A, it gives me the values in binary. Yeah, the values will be 0 and 1. The values will be 0 and 1. But will it be 0 or 1 will depend on the probability value. Got it, Ajay? This is what I was saying when I say about the LLM models, right? The probability decides what is going to be the output. And then we can calculate the accuracy score and the training score. So in this case, both of them are coming out to be quite same. So we can say it's overall coming out to be a good fit. But which are the metrics which are actually used for classification problem? Which are the metrics which are actually used for classification problem? The confusion matrix. Because it's a little imbalanced, not highly imbalanced, because if two classes were absolutely equal, then it would have been balanced data, 50-50. But it is somewhere around 60-40, I would say. Okay, Puneet? Value underscore counts on this graph is telling me it's imbalanced. Right? So the training and the testing accuracy is there. But ultimately, who is the judge? The confusion matrix. The components of confusion matrix are true positive, true negative, false positive, false negative. I hope these points are very much clear to you. So the provided confusion matrix provides a summary of the effectiveness of COVID-19 tests that identify individuals with the virus and those without it. So we have understood this concepts that the case correctly classified as positive and predicted also as positive. These terms are very clear. We've discussed it in detail yesterday and I had done a recap. So now significance of confusion matrix is in terms of these metrics such as accuracy, precision, recall, which is sensitivity, true positive rate, specificity, and the F1 score. Right, learners? And do we understand the formula? That's also we've gone in detail. So lots and lots of revision for you. Then we also understand the ROC curve or the AUC curve, which is used as a graphical representation of a classification model's performance across different classification thresholds. It plots the true positive rate against the false positive rate at various threshold settings. So true positive rate or recall at these settings. Clear? So what is our main aim in, plotting the AUC or the ROC curve? That the default threshold for many classification algorithm is 0.5, meaning that if the predicted probability is greater than 0.5, the instance is classified as positive. However, this threshold might not always be optimal, especially in the cases of skewed classes. Do we understand the term skewed? What do we mean by skewed class distribution, learners? If the data is not normally balanced, it is known to be skewed data. Okay. So the methods of finding optimal threshold, there are two ways. One is maximizing your Jordan's J statistics. In this, we will find out the value of J by subtracting the true positive rate with the false positive rate. The optimal threshold is where the statistics is maximized. This method balances the TPR and the FPR, aiming to maximize the true positive while minimizing the false positive. Closest point to 0, 1. Another method is to point on ROC curve that is closest to the top left corner, representing ideal classifier. Clear? An area under the curve also we are clear. Now getting back to the Python code. So again, confusion matrix, classification report, ROC underscore curve, all these are part of which library? They are part of which library, learners? Learn metrics. Be very clear. sklearn dot metrics. Even the RSS, MSc, they were all under these curves. Clear? So the confusion matrix is created simply by calling the confusion matrix by passing the actual value, predicted value output, and based on that, I get this display. What do I observe? 70 are my true positive, 41 are my true negative. And if I talk about type 1 and type 2 error, it's quite less. So logistic regression has done well. It gives me 2 and 1 errors. Clear? And then the best way to go about is creating a logistic regression report. So over here, the precision is 97, 98 for 0 and 1. Recall, F1 score is 98 and 96. And if I look at the Overall accuracy is also coming out to be 97%. So overall, this particular logistic regression has come out to be a good classifier for this particular data set. Clear? So over here, they've given in detail class 0, negative class. Precision is 0.97, 97% of instances predicted as class 0 are actually 0. 99% of actual class 0 instances are correctly predicted as class 0. And here we move ahead. Right? All of the detail is given over here. Okay. And finally, how do I do the judgment that I need to do plotting of the ROC AUC curve, which shows the trade-off between the positive rate and the false positive rate at various threshold settings. The AUC value indicates the model's ability to discriminate between the positive and the negative classes. So parameters used in plotting are these many parameters. That first of all, ROC underscore curve is the function which gives me the different values of FPR, TPR, and threshold, right? And based on that, I'm going to calculate my Jordan's J and find out my optimal threshold value. So what do I observe? That optimal threshold value is coming out to be 0.4848 and ROC or the area under the curve as 1. So is it a good classifier? Area under the curve is nearing, it's almost 1. It is 1, not even almost 1. So it is a very good classifier. Getting my point, learners? So the ROC curve in the image reaches the top left corner, TPR equal to 1, FPR equal to 0, which indicates a perfect classification performance. The model perfectly distinguishes between positive and negative classes at various threshold settings. And the ROC curve for logistic regression model has AUC1. This model has perfect discriminatory power, and AUC of 1 means model correctly classifies all positive and negative instances without error. And the optimal threshold of 0.4867 defines the decision boundary for the classifier. Probabilities above this value indicate stronger belief that an instance belongs to the positive class, whereas the probability below this value indicate stronger belief that it belongs to the negative class. Clear? You know, this practical example has made all the points clear. So over here, are we doing any kind of sigmoidal function, anything? That's already part of the implementation. So again, I'm repeating this point. First, try to understand the mathematical intuition behind the algorithm or the model. Secondly, how we will implement in Python. And thirdly, how do we interpret the results? Is it a good model or not? Clear? Ajay says, ma'am, one doubt. Despite I seen that this model is perfect in matrix itself, what is the main purpose of seeing ROC curve also? See, ROC curve tells me whether the two classes have been classified. Are they well separated from each other or not? That is the idea. Is this more overlapping or not? So just to reconfirm things, it's not by just doing one test. You know, if you are suffering from some problem, the doctor wants to reconfirm from different tests, maybe the blood test, MRI report, and X-rays or other things, something like. So it's something which is more visually appealing, tells us has more impact. Yes, this is a good model. The confusion matrix also tells us, the different classification report also tells us, and AUC ROC curves also tells us. So there shouldn't be any doubt left, you know, when we are doing our analysis. All the analysis should give the same result, right? So now do we understand this graph? Let's see. So now this is also one of the reasons the threshold is used. That if I take it as 0.5, any value coming above it, as I told you, would belong to this class, you know. So distinctly, there is no overlapping. It distinctly classifies all the points, and any value which is lesser than 0.5 belongs to this class, right? So can we go in for a quick knowledge check about logistic regression? and classification. So question number 1, which of the following metrics are used to evaluate classification models? Confusion matrix, ROC, and F1 score is calculated using confusion. What is a classifier? So when we talk about classifier, the output has to be categorical. So which one gives the output as category? It's both A and B? No. Output as a single discrete value or output as a single discrete value. So both A and B. Input can be anything, continuous or discrete. Yes, the answer is C. Next, false negative. What does false negative represent? Which option is correct? It's A, predictive negatives that are actually positives. Yes. In binary logistic regression, definitely it is C. The dependent variable consists of categories. Next question. Why is linear regression model output a poor predictor of probability? Why? Because D is the correct answer. It can give, it cannot, the range can be beyond 0 and 1. Next, the output in logistic regression problem is yes, equivalent to 1 or true. What is its possible value? So of course it is B. It would depend on the threshold value. Okay. So now we have naive Bayes classifier. Okay, now moving on to the next algorithm. The next algorithm is completely based on probability. So what is probability, learners? Chances of occurring of an event. And what is the formula? Mathematical formula of probability. The number of successful outcomes upon the total number of outcomes, right? What is the probability of getting a head when I throw a coin? It's 1 upon 2.5. When I throw a coin, what is the probability of getting head? What is the probability of getting 1 when I throw a dice? That is 1 by 6. But there is another concept which is associated, which is known as the conditional probability. Do we understand? What is the probability of event A given probability of event B? Do we understand conditional probability? This particular algorithm is based on that. Bayesian theorem. That's why data science is important. So learners who have done data science should be clear about the Bayesian theorem. Conditional probability or the posterior probability is equal to the likelihood function, that's opposite. What is the probability of event B given A into the prior probability A divided by the marginal probability? Do you remember this point or not? No? Posterior probability is directly proportional to the likelihood function. You understand this or not? Into prior probability. Okay. So the naive Bayes classifier, this is the formula that if I have these random figures or, shapes, the classifier is capable of classifying them into different shapes or groups, right? And the basic formula lies in that the posterior probability is directly proportional to the likelihood function into the class prior probability divided by the predictor prior probability, right? So how is this, posterior probability actually calculated? It is nothing but the product of the likelihood function. Do you see this? X1, my first input given C, Px2 given C, Pxn given C into the class prior probability. So the products are generally written, the summation, not the summation, but the products are written in terms of pi and summations are written like this. Clear? So how is this particular, algorithm useful? Let's understand it practically with the help of an example. So suppose this is my categorical data where I have my inputs also as categorical: outlook, temperature, humidity, windy. And based on these factors, I will decide whether I will go for play or not. Play over here, again, it's a binary classification problem because I will go to play or otherwise I will no. So the outputs are yes and no. See, what is C over here? That my output probability whether I will go to play or not. Clear? Right? Now, if this is my input, okay, these are my input values: output, temperature, humidity, and wind. This is represented as my X1, X2, X4. Got it, learners? So, what could be the values of the outlook? Outlook has three outputs, whether it could be sunny, whether it could be overcast, or it could be rainy. Are you understanding the three categories of outlook column? Then the temperature can be hot, cool, or mild, again 3. Humidity can be high and normal. I don't think so there is any other category. And windy, again 2, true and false. Clear? So how do we go about calculating whether we will go to play or not? So what is my C1? Yes, I will go to play. Suppose I want to calculate, yes, I will go to play, given the humidity, the outlook, the wind situation, and the other one was temperature, right? So this becomes my formula. And once I separate them, as I told you, they become the individual products of probability. This formula is getting clear to everybody. We just now understood based on Bayesian theorem, mathematics behind this particular theorem. Okay. So how do we go about it? What is the probability of going to play when it is sunny? That is the situation I want to check. Hot, high, and windy. So from here, I can calculate the probabilities of sunny, hot, high, false, and no. Then the other one is sunny, hot, high, true, and no, overcast. So based on the given data, I can calculate the individual probabilities and put into the formula and finally get the output. Now clear, learners? How are we going to predict whether you will go for, and this is the algorithm which is practically used to determine whether the email is a spam or not. Email is a spam or not is used, actually the naive-based classifier is used for that. Getting my point? So the advantages of naive Bayes is simplicity and speed. Naive Bayes is computationally efficient, very good algorithm. This algorithm is simple and also gives good result. So naive Bayes is computationally efficient and straightforward to implement and making it suitable for large data set and real-time applications. And it is also effective with small data, performs well on small data sets when the number of features is high relative to the number of samples. Got it? But every algorithm in machine learning will have its pros and cons also. What do we mean by pros and cons? That then we have to decide, okay, on this data set, this algorithm is giving good result, or this data set with looking at its advantages and disadvantages. So the assumptions of independence assumes that the features are independent given the class label, which is often not the case in the real world data, leading to potential performance issues. So what does it, assume? So naive actually means that all the inputs are independent of each other. Poor performance with correlated features can perform poorly if the features are highly correlated, as the independence assumption does not hold good. Getting my point? So the naive-based classifier is clear that why statistics, why probability are heroes in machine learning. Okay. So what is naive bayes? Naive Bayes, it's not naive, somebody says naive Bayes. So naive Bayes is a probabilistic classifier, completely based on probability. Even the previous one was based on probability, right? And it is based on Bayesian theorem. Naive Bayes is called naive because, why the word naive? Because it assumes that the input variables are independent of each other. This is what it means. And this is a strong assumption and unrealistic for real data. It is particularly suited for large data set, widely used for binary and multi-class classification tasks. It is widely used for text as well as sentimental analysis. Lot of practical use of this. As I told you, even you can check on mail, the spam filtering is based on this particular theorem. So what is the mathematical concept? It's based on Bayesian theorem that the posterior probability is directly proportional to the likelihood function into the prior probability. Clear? The mathematically, with an example, I made the point clear. Let's do it practically. So we are running the same data set, breast cancer data set. So what are we doing over here? Who's going to explain me the code? Line by line. Yes. What is the first step? Come on, let's see. Who is the smart one, attentive one, and quick to answer in the batch? Let's see. What is the first point? What does the first line of code do? Importing library from Scikit-learn. Now we want to create naive Bayes classifier or Gaussian NB. Second, what are we doing in the second step? What are we doing in the second step? Defining pipeline. Very good. And what are we trying to do in this pipeline? Two-step pipeline. What are we trying to do? Feature scaling and not model selection, do model creation. We are trying to build the model, not model selection, but model creation. The last step, what are we trying to do or achieve over here? Training the model, fitting the data, both are correct. Okay. Now tell me what is happening over here. Predicting the Y output, predicting the test output, training as well as the testing output. Agreed? Predicting both the training, input training and testing. Based on that, I'm getting my output training and output testing. Accuracy score, we require output training and predicted, output testing and output predicted, and calculate the training and the testing score and then check the prediction of the probability. So if we compare it with logistic regression, is it better than that or not better than that? Tell me. Compare it with logistic regression, the training and the testing accuracy. It's slightly towards overfitting, right? Slightly. But logistic regression was better, or is this model better? Now this was better or that? Here the training was 98 and testing was little less than that. But they were almost equal. But in naive Bayes, it's 93 and 96. Of course, logistic regression has given better results than naive Bayes classifier. Now clear, Abhinetri? And that is how judge or test. Okay, now this algorithm is better than that. How is this overfitting? Testing accuracy is better than training. Isn't it? This one. In this case, check this one. When the training error, see, actually the training error is less and the testing error is very high. Or when is overfitting? When the training error is less and the testing error is high. So in that case, that is the situation. Check the naive Bayes result. All right. So the training accuracy is 93.63%. Testing accuracy is this much, are relatively close to each other. This suggests that the model is not overfitting to the training data. Agreed, Puneet. Good. As the performance on the training set is slightly higher and comparable to the training set. Good, Puneet. So you corrected that particular point. Yes, it's not overfitting. Good, Puneet. Right? So this is how we get the predicted probabilities and the actual probabilities, do the comparison. So the naive-Bayes classifier computes the probability of the class given the input features by multiplying the individual conditional probabilities of each feature, as I've told you. Internally, many naive Bayes implementation use logarithms to prevent numerical underflow when multiplying many small probabilities. The extreme values observed might be result of the conversion back from log space to probability space. So here internally, a lot of conversions take place. That is why it is e to the power minus 0.9 and plus 9, because a lot of conversions take place from logarithmic space to probability space. Got it? But the ultimate decision maker is the confusion matrix, right? So here, this is my true positive, true negative, but my error is 3 and 1. Have my, the type 1 and type 2 errors also increased. Type 1 and type 2 errors also increased. Have my type 1 and type 2 errors also increased? Then logistic regression, do the comparison and let me know. And is my overall accuracy F1 score better? Yes, the errors have increased. Has the accuracy decreased? Yes. F1 score only for 0 is 97%, other is 95, 96%. Got it? And if I look at my AUC ROC curve, so this is again 1 and my optimal threshold is 0.0126. Getting my point, learners? Clear? So what do we observe by the ROC AUC curve? The ROC, I'm sure, most of you have still not understood what does it tell. The ROC curve for the naive Bayes classifier demonstrates outstanding performance with area under the curve of 1.0, indicating perfect classification ability on, like it's perfect. That means there is no overlapping. Whichever data belong to the benign, they fall under benign, they have been predicted as benign, and whichever which fall under malignant cancer, they have been put into malignant database. So this simplifies the model, is highly effective in distinguishing between benign and malignant cases with no errors. Optimal threshold is 0.0126. Some models such as naive Bayes often produce uncalibrated probabilities that tend to be extreme. This result in needing a very low threshold to balance sensitivity, specificity explicitly. Now clear? Is this point getting clear to everybody? Good to go? All right. So KNN. KNN stands for K nearest neighbor, and it is simply based on the concept or logic, birds of feather flock together. What does that mean? The data points which are near to you, you are likely to be like them. Agreed, learners? Agreed? And how do I calculate my neighbors? With the help of distance, how close they are to me. How do I check the proximity of the data points? So the data points who are near to me, I'm likely to be like them. So the calculation of distance between the 2 points. So mathematically, what are the different ways to calculate distance between 2 points? Tell me, what are the different ways? Euclidean distance, Manhattan distance. Yes, these are the methods in which we calculate. Now, please look at over here. Now, suppose see, again, machine learning is all about prediction. So there are different ways. Every algorithm is using different way to predict what a particular data point is. right? So if this is the question mark, we want to predict what this question mark is. How do we go about it? I'll try to analyze the neighbors around it. So suppose if I try to calculate 4 neighbors, how will I predict that what this question point is? Maybe the lines which are more near, I will predict that. But if we talk about probability, there are 3 over as stars and 3 as triangles. So we never take the number of neighbors equal to the number of neighbors k equal to even values. Getting my point? We never want to take them as even values, right? So generally the k is taken as odd, that is taking 3 closest data points, and based on this there is 1 star and 2 triangle points. So chances are that this question mark is a triangle, right? Whichever ones are with maximum probability. Simple algorithm. Yeah. So here we are going to predict a data point based on our neighbors. Okay, Abhinetri. So if I take even number of neighbors like 3 stars and 3 odds, right? How will I actually predict this data point? So the probability of number of stars is a 3, and this is also 3. So again, I will not be able to decide correctly what this data point is. So generally, K stands for number of neighbors. We want to keep it as odd value. So now when I predict based on these three data points, the question mark, so the triangle has more probability than the star. So the question mark we will predict as triangle. Now clear? Simple logic, right? So again, let's put it over here. If I take k is equal to 1, the nearest data point is red. So I can simply say that this particular question mark is red. But if I take k equal to 3, then, since there is 1 red and 2 blue values, it becomes blue. And if I take k equal to 4, the number of neighbors as even, then the classification is not properly defined. Now clear? So that is what I want to say, that k is never taken equal to even values. We always want to keep it as odd. Now clear to everyone? And the different types of distant functions. So when we are defining the KNN model itself, how are we defining the KNN model? First, we will import its library, call its function. So whenever we are defining the KNN model, we can define the type of distance we are using to calculate. So whether it is a Euclidean distance, Manhattan distance, or Minkowski distance, that we need to take into account. So different formulas are there mathematically. Clear? So now what are the different steps that are performed in KNN algorithm? The first step is choose the number of k neighbors. How do we choose the number of k neighbors? Randomly. Start with randomly assigning the k numbers, or there can be another technique which we have studied in regression to find out this value of k. Anybody who can tell me? Any other technique that we have studied in regression which can help us? Absolutely correct. Cross validation can again be used to find out this technique. Very good, Ajay. Then we calculate the Euclidean distance of k, the number of neighbors. Get the k nearest neighbors according to the calculated Euclidean distance. Out of these k neighbors, determine the number of data points in every category. 5, give the new data points to the category that has maximum number of neighbors. And finally, the model is ready. Getting my point, learners? So what is the effect of K? What is the effect of K in KNN algorithm? How do we decide when the model is underfitting or overfitting over here? right? So it is this K which significantly impacts the model performance by influencing the bias and variance. So whenever the K is small, it will always lead to overfitting. And whenever the number of neighbors K is equal to large, it will lead to underfitting. And as very correctly said by Ajay, finding the optimal K requires balancing these effects, often using the techniques like cross-validation. So this will make your concepts even better because things keep on getting repeated and concepts keep getting more clearer. Got my point, learners? So what happens when the boundary K is equal to 1? Do you see I get a very complicated curve? It is like overfitting, but still they are still misclassification. And if I keep a large value, it's like a straight line, but it's like an underfitting. So how do we go about finding the K? Wherever there would be minimum bias and variance, that particular value of K will be taken. Agreed? Getting my point, learners? So the advantages are simplicity. It is easy to understand and implement. Non-parametric. What is, so this is a non-parametric algorithm. Do we understand this term? Very, very important. Non-parametric algorithm means that it makes no assumptions about the data, making it versatile. If I talk about adaptability, it performs well with noisy data and complex distribution. Disadvantage, I've tried to cover advantages and disadvantages of all the algorithm, that it is computationally expensive. That is, the entire training set must be stored as compared, which can be inefficient. Choice of the K would be challenging because it significantly affects the performance, and sensitivity to irrelevant data, that each feature contributes to the distance, so irrelevant features can distort the results. Getting my point? All right. So can we get back to its practical implementation? Back to the file again. Distance computation should be done for each feature or combination of them. Each feature. Data point, it will automatically calculate for the predicted value and the feature beneath. Each feature. All right. So the KNN algorithm is a popular machine algorithm used for classification, and it relies on the idea that similar data points tend to have similar values or label. During the training phase, the KNN algorithm retains the entire training data set as reference. For predictions, it computes the distance between the input data and all the training examples using a selected distance metric, such as Euclidean distance or any other diagram. Now clear? So the steps are also clear. We will load the data, choose the value randomly, then find the optimal value of K on the specific data set using cross-validation. So for every point in the test data, what does it do? That's the question asked by Puneet Reddy. That it calculates the distance between the test data point and each point in the training data set using distance metric, right? Sort the calculated distance in ascending order. Select the top K closest data points, smallest distances from the sorted list. Assign the most frequent class among these K nearest neighbors to test the data point. Clear? Is this point getting clear to everybody? So what are the first steps that we will be using for implementing on KNN? That we would, what we would do, we would import the libraries KNN, define the pipeline for standardization and model, right? And now where is the difference? Please look here. What are we explicitly defining over here when I'm creating the KNN model? Yes. So when we are creating the model we have to first initialize the neighbors count. So here we are taking 3 neighbors randomly, then fitting the data and then predicting the value. Clear? Creating any object, and if you want to find anything about it, it's very clear that you can just put a question mark, introspection. By default, the number of neighbors, if you're not specifying, it will take it as 5. And the metric parameters, by default, the distance metric it uses is Minkowski. Clear, learners? Okay, so now if we look at the accuracy, the training accuracy is again here, but the testing accuracy should be even higher than the training, right? That is going to be a good model, but it is lesser than that. Agreed? So the error over here of the testing error is more than the training, right? Now I'm answering, saying it correctly. Now is it correct? The testing accuracy should be higher than the training. No, that was a good point, because I was interpreting it in that way. So accuracy. So is it a good model or a bad model? Not very good, because the testing accuracy should definitely be more than the training, right? If it has to be a really good fit. So not a very good fit. Testing accuracy is higher than training. So it's a little overfit. We can say now it's a little overfit. Agreed, learners? So let's see, what does the observation have to say? So this is how it's predicting the output. This is my confusion matrix. Oh, so what do we observe? What do we observe? And we are not getting the accuracy also very good, because the testing accuracy has reduced. And what do I observe in the confusion matrix? Now you tell me. What do I observe in my confusion matrix? The errors have increased, both type 1 and type 2 error. And it very clearly shows on my classification report that my precision, my recall all have reduced, and overall average has also reduced from 97-98% to 95-94%. Right, learners? And let's look at the ROC AUC curve. And the ROC AUC curve is not giving me full 1. It has reduced to 98% with optimal threshold value equal to 0.33. So now you will be able to iterate algorithm and see which algorithm is best. So it's an iterative process. Okay, let me apply this algorithm, that algorithm to finalize it. So the ROC curve has a steep ascent to high true positive with low positive, false positive rate, indicating the classifier is affecting and distinguishing between positive and negative classes. Now, hyperparameter tuning in KNN. So what is the best way to find out the value of K? By using hyperparameter tuning along with cross-validation. So the concepts that we have studied are all applied in supervised learning. Getting my point, learners? Yes or no? So the number of neighbors is a crucial hyperparameter in the KNN algorithm. It specifies how many nearest neighbors this algorithm should consider when making prediction. The selection of K impacts the model's ability to generalize effectively. A smaller K can make model sensitive to noisy data, that is overfitting, and high value of K can cause underfitting. So how are we going to do grid search and cross-validation? So Scikit-learn model selection part has grid search CV function also. Now, how do I define my parameter grid? Did we study this yesterday? So whenever we are doing grid search, we have to define the grid with the help of dictionary. Since there is only one hyperparameter, I will define the KNN ranging between 221. Since my data set is like that, so I can range between 1 to 21. Or if more you want to do, you can range it between 1 to 50, 1 to 100, not more than that, right? Then I create my pipeline, and now I create a grid search CV object, pass the model pipeline, grid parameter grid, cross validation, the k-fold cross validation value equal to 10. And finally, I'm going to do judgment on the basis of accuracy, fit the data, and finally, this after fitting it, I will get the optimal k. So in grid search, if I use the parameter, best parameters, best score, CV results, I am able to distinguish between them. So the optimal number of neighbors is coming out to be 7, and the best cross-validated accuracy for that is coming out to be 97%. That is why it was not giving good result. Why? Why it was not giving me good result? Because what was the value of k which I had taken? What was the value of k initially? 3. Now clear to everybody? So how is hyperparameter tuning and cross-validation helpful to us? And if I see it graphically also, so wherever is my maximum accuracy, it is somewhere coming out to be over here. It was 7. Let me do the opposite way. So this is my maximum value. This is my around 7. Clear? So now you can again transfer this value to k and then check the accuracy results and score, and you will see definitely better improvements in the results. Here, so there is a lot more to study in decision trees and then support vector machines. So now let's start with decision trees. So lots of concepts that needs to be covered in decision trees. So what are decision trees? Like a tree, as we understand, has root, branches, and leaf. And a decision tree that is in computer science also has a root, branches, and leaves. But what does they technically mean? Anybody who has an idea? What do they technically mean over here? Now, root is always the starting node, right? A decision tree will always start. So a real tree follows a bottom up approach, but a tree starts from top to bottom approach. So root always starts at the beginning. Then we start splitting the nodes, internal nodes. That is the decision node on which whether, your age is greater than 30, your salary is greater than 30,000. And based on that, we will, have the leaf nodes, whether you are eligible for the loan or not, right? Getting my point? Again, I'm repeating, technically a decision tree consists of 3 main parts. One is a root node, internal node, as well as the leaf node. Root node is always the starting node. Internal nodes are the nodes in between which help to take decision, follow a graph or follow the rules. And then we have the terminal node, also known as the leaf node, which will be my output or the concluding factor. Clear? Is this point getting clear to everybody? So decision trees are a family of non-parametric supervised learning models. I explained to you today what does the term non-parametric mean. Please try to understand. Take help from Google or Companion, do search and tell me what do we mean by non-parametric models. Supervised, we understand that they would be training and testing and splitting. What does the term non-parametric mean? No assumption about the data or function that it is following a linear function or, sigmoidal function. There is no assumption. We start with the root node. There's no mathematical function involved. And which are the algorithms assume a function. Can you name few parametric learning, supervised learning models which assume a function that it is a linear, it is polynomial? Regression is all parametric supervised learning. Even logistic regression where we are assuming the function to be sigmoidal. KNN was parametric or non-parametric? Did we assume any function in KNN? It was non-parametric. There was no assumption about any function. It was all about K. K was the ruler which was deciding the number of neighbors and the output. Getting my point? All right. Another important concept. So there are a lot of concepts in decision tree. That is why, practically it is being asked a lot and a lot to be explored in decision tree. Okay. Then the terms, which are over here, we don't use the concept of confusion matrix to determine the output of classification. Here we talk about purity in classification tree. What do we mean by purity? That if the classes are distinctly classified, like the AOC ROC curve, that means if there is no mixture between the different classes, they are said to be pure nodes or with minimum impurity. So do not get confused like me between accuracy. So are they talking about purity or impurity? Try to just comprehend logically. So we want less impure nodes or highly pure nodes which are able to classify data points in each classes. Getting my point? Is this point getting clear to everybody? The to split at each node is made according to the metric called purity. So when we decide a decision node, how the split is going to happen, that's how a tree will be generated with help of these purity score, right? So when I say it is 100% impure, that is node split evenly 50-50. And if I say 100% pure, when all the data belongs to the single class, so then it becomes a leaf node, right? When it has perfectly defined a class, then it becomes the leaf node. Getting my point? So in order to optimize our model, we need to reach the maximum purity, impurity. Are these terms getting clear to everybody, learners? See, it is all about red and green. If the red and green balls are mixed together, then it is said to be an impure class. It is very, very impure. But if I am able to separate the red and green classes or balls easily into two different classes, then they are supposed to be minimum impure classes. Are you understanding the term very impure and minimum impure? Minimum impurity means pure nodes. We are looking at 100% pure nodes, 100% purity in the classes. And there are different metrics available in decision trees to calculate the impurity. The most important impurity measures are entropy. Do we understand the term entropy? The randomness. When we have studied physics, the randomness, the heat part in data entropy, which is again based on probability. As I've told you, probability is a hero in machine learning for all classification problems. So it is minus of P class I total. What kind of probability it is? Conditional probability. So this refers to the conditional probability. Log to the base 2, P class I equal to total. Getting my point, learners? Other way to measure the impurity is the Gini index, which is again 1 minus summation of P class I total square. This is again based on conditional probability, or it could be the misclassification error, right? And it could be based on misclassification error, that is 1 minus max of probability class I given total. Then you would try to understand, ma'am, what is the difference? See, it is very clear that the entropy value will lie between 0 to 1, whereas the value of Gini index and misclassification lies between 0 to 1.5. Right? Now, when I say probability, what is the entropy at probability 0 and 1? What is the value of entropy, Gini index, or misclassification error at probability 0 or 1? 0. Why? Because when the probability is 0, are we sure that that event will not happen? Do we have certain certainty in that? There is surety. Similarly, the entropy becomes 0 when we are certain, okay, there is no, red ball or green ball at that particular point. And are we also certain when probability is equal to 1? We are very sure that the event will happen. Yes or no? And we are very sure that the event will happen. Yes. So the entropy curves looks like this. You can use any one of them, but it gives you the same answer. But the maximum entropy or Gini index or misclassification error will be at probability equal to 0.5. So all the three show same behavior. So any of one of the methods or metrics can be used for classification. Okay. Yeah. So basically, what does entropy mean? It is a measure of the randomness in the information being processed. Higher the entropy, the harder it is to draw any conclusions from the information. For example, flipping a coin is an example and action that the probability provides is random. So entropy, we understand this is Hx represents entropy, lies between 0 to 1. It is highest as at 0.5 and lowest as 0 and 1. And that is why we get this inverted U shape. This is the formula to calculate entropy, which is summation of minus pi log to the base 2 pi. So if you want to play golf, and now I want to check the probability. What is pi? The probability of an event I of state S or percentage of class I in the node of state S. So how do we go about it? Entropy is 5, 9. What is 5, 9? What is the probability of getting no? It is 5 upon 14. Agreed, learners? 9 plus 5. And what is the probability of getting yes? 9 upon 14. Agreed? Is this point getting clear to everyone now? And if I substitute this in this formula for yes and no, I get the total entropy for playing golf. What is the present current state? We are trying to find out whether we want to play golf. So there are two, internal states involved in it, yes or no. Mathematically, are you able to understand this concept or not, learners? What is going to be the entropy for multiple attributes? Ultimately, we have to look at the multiple attributes. So when I have to decide, we have to play golf. When the outlook could be sunny, overcast, or rainy. So how do I say what is my entropy for that I'm playing golf and with the outlook as an input, taking one input at a time. So what is the probability of being sunny? Sunny is 3, 2 because of playing golf is yes and no. Probability of overcast is 4 and 0. And probability of rainy entropy is 2, 3. So now we understand how to calculate these. Probability of sunny with this, probability of overcast and probability of rainy that we are calculating over here. Clear, learners? So we get this entropy. So if you look at this particular example, right? Entropy before. Can anybody tell me how am I getting 7 and 6? How many data points, circle and plus symbols are there? How many plus and circle, blue circle symbols are there? Total 13. How many are blue circles? Circle is equal to 6. So the circle is 6 and the plus sign is 7 upon 13, right? Ideally, this should be complete, all should be plus sign. Ideally, this should be, all should be circles. But practically, we get this entropy. There are 5 plus signs and 1 circle, 2 plus signs and 5 circles. Now clear? So now this particular slide is also clear. Can you explain this slide? Can you interpret this slide? That what is the at probability 0, look at the states of the classes. They are so distinctly classified. And the maximum randomness is at probability equal to 0.5. Right? Okay. Yeah. So now we have understood the different ways to calculate the impurity or the purity of a decision tree is Gini index, misclassification errors, and entropy. But it is ultimately the information gain. Please try to understand. Ultimately, it is the information gain or IG, a statistical property that measures how well a given attribute separates the training examples according to their target classification. So now it is the information gain. That means the maximum the information gain, that particular attribute will be chosen for splitting the data set. Clear? Then constructing a decision tree is all about finding an attribute that returns the highest information gain and the smallest entropy. So what are we always interested? We are interested in entropy before. What do we mean by entropy before? This. When the split has not happened, and then we calculate the entropy after the split has happened. Clear? So the information gain Tx is equal to entropy of the T, that is the parent, minus entropy of the Tx. So if I want to check the information gain of the previous example, that is play golf and Outlook, it is equal to entropy of play golf minus that. So the information comes out to be 0.247. Getting my point? So do we want low information gain or high information gain? High information. High information gain, more purer nodes or impurer nodes? High information. What is the purity of the nodes in high information gain? More purer nodes. And similarly, Gini index is a cost function used to evaluate the splits in the data set. It is calculated by subtracting the sum of the squared probabilities of each class from 1. It favors larger partitions, easy to implement, whereas information gain favors smaller partitions with distinct values. So how do we create a classification tree? It's quite different from other model. That is why it is favorite questions among the interviewer. Now getting my point? And the recent algorithms are also based on decision trees. Okay? Yes. So classification tree, we calculate the purity of the node. First, how do we calculate the purity of the node? What are the different metrics? Entropy, it could be Gini index, any one of them, or misclassification error, right? Select the candidate for the split, calculate the purity of the data after the split, then calculate after the split also, then repeat for all variables. So we'll keep on repeating for all variables before and after Choose the variable with greatest increase in purity or information gain. Got it? Again, it's an iterative process that we keep on doing on our input features. And repeat for each split until stop criteria is met. So let me explain it with an example. This is a very famous example in the domain of data science, the Titanic cruise. I don't know whether you've done it before or not, but it talks about the luxury cruise ship driven by demographic features. And here we've just taken a very small example part of it, that 10 people survived and 15 people died, and the total is 25. This point is clear? So what were the criterias of survival in Titanic? If you remember, what were the criterias? Whether you are a male or a female, female and children were saved more. Not named Jack getting lifeboat. No, the criteria, the boats were given more to the females and kids, less to the males, depending on the class, not much on the age, but the class of the people, like did they belong to the luxury business class or the lower class? Yes or no? If you have sibling or not, all these concepts and criteria were taken into account, right? So if we look at the survival probability, it is 10 upon 25. Died is 15 upon 25. That's the criteria. So this is the Gini index for this. This is the entropy and this is the misclassification error. So I'm trying to give you comparison of all the three. So now when I substitute these values, the Gini index will always lie between 0, 1, it will lie between 0 to 0.5. And if we talk about entropy, it is 0.97. Clear? All three metrics are getting clear. So this is before the split. Agreed, learners? The survival and the death. Now let's understand the split based on gender. So the data that was given to us was that males, only 2 survived and died 13. And if we talk about female, I don't know where there's the survival gone. No, survived 8 and died 2. Here it is. Do you see this? Gender was a major criteria in the Titanic ship. Maybe you don't remember the movie clearly. I mean, whatever was shown in the movie, right? So based on gender, now I have to calculate each of the impurity nodes for the male node and the female node. So if I look at the probability over here, that how many survived is 2 by 15. It is 13 by 15 in case of males. And in case of female, it is survived is 8 by 10 and died is 2 by 10. Agreed, learners? Right, so these are my male nodes, these are my female nodes calculation. Got it now? But ultimately, what do we have to calculate? What do we have to calculate? We have to do it for other attributes also. And then now we will calculate. Oh, Gini gender can also be calculated. Then entropy gender can also be calculated. And ultimately, we have to calculate the information gain based on this. So the information gain based on gender comes out to be this much. Then we can calculate the number of siblings on board. And do you belong to the first class, second class, or third class? So this is the table of comparison. We don't create any table. This is just to understand how the decision tree is working at the back end. Clear? With this example, I'm trying to make the point clearer to you. So based on the male and the female, this is how we get the information gain from entropy, information gain for sibling, information gain for 0.6. So which node should be selected? Which node should be selected based on gender, sibling, or class? Tell me. Based on gender. Right. So this is the maximum information gain. Got it? We're always looking at maximum information gain. So first split should occur on the gender, then on the basis of class, and finally on the basis of sibling. Getting my point? So a lot of concepts and decision trees. Agreed? Should I go ahead with more? That what are the different hyperparameters in tree? While creating a tree, we have to keep in mind the depth of the tree. This is said to be level 0, level 1. So that is why depth is equal to 1. This is 0, this is 1, this is 2, this is depth 2, this is 0, this is 1, this is 2, and this is 3, this is depth 3. Got it? So we should have maximum depth or minimum depth? Tell me. How do we decide the depth of the tree? What effect will it have? We should keep it maximum depth. If the depth is 100, we have to traverse 100 levels. Is it a good way, Abhinetri? Not really. No. 100 level will make it very, very complicated system. So hyperparameter means not very less, not very large. We have to decide where we are getting the good results. So even, it doesn't mean that more depth will give you good answers. More depth will make the system more complicated also. Yeah, we should go up to maximum purity or 100% purity, but there might be cases when we have reached, a lot of levels and still we are not getting that purity. There has to be a criteria of stoppage of the depth of the tree. Okay, especially for complicated algorithms. And decision trees can also be used for regression problems as well as for classification problem. Be clear with that. It is used for both the technique. That is why it is a super hit in the market. The next, criteria is minimum number of samples to split, right? If the samples are less than 11, we will not do the splitting of the node. So one is the depth of the tree is a hyperparameter. What is a hyperparameter? We decide before training the algorithm. Second is minimum to 11, right? And the minimum number of samples to split. Yeah, if it is more than 11, then we will split. Now clear? Two criteria are clear. Third criteria is minimum samples per leaf. We will decide the per leaf criteria. So even if there is one sample per leaf, I am accepting it as a class. Now, getting my point? Is this point getting clear to everyone? Still a lot more concepts to be done and go. But in the meanwhile, let's go back and start working on it practically, and then we will cover it up. So we are on classification 2 PDF. I need to upload that. And what are the best ways to find the hyperparameters, learners? What is the best way to find hyperparameters? How did we find out the K in KNN? Grid search cross-validation. Hyperparameter tuning combined with cross-validation is the best technique to find out hyperparameters. So now let's get back to the code. So today, we are still on 4.1. We'll keep continuing 4.1 till we reach the end of it. Okay, so where is the decision tree? Okay. So what are decision tree? So when we look at the decision tree, it is a non-parametric. Now the term non-parametric is clear. Please try to understand. It is a non-parametric supervised learning algorithm used for classification and regression. And the term which is generally used for decision tree is CART. That is, it is classification and regression trees. So CART stands for classification regression trees. It is a hierarchical tree structure. What are the three components of a decision tree? The root node, the branches, the internal nodes, and the leaf node. What do we mean by root node? That's always we only have one root node, that is the starting node. Then we have the branches, the different internal nodes to take decisions, like we saw in Titanic example, based on gender, based on the number of siblings, based on the class, we are going to take the decision. And what is a leaf node? What is a leaf node, learners? The ending one. Actually, the output or the classes. So decision trees can be used for classification, regression tasks, providing easy to understand. This is clear. The root node part is clear. Decision node, the root node, the leaf node. Now that part is clear. So let's understand it with an example. Suppose if you want to buy a car, if the car of the color is red, then you will check the model is greater than 2015. If it is yes, then I will buy. Otherwise, I will check the mileage. If it is not, then I will buy. Otherwise, don't buy. So what is this decision tree doing? Is it a classification problem or a regression problem? It's a classification. Which kind of classification? Multi-class binary classification. Binary, because we are taking a decision whether we will buy the car or not buy the car. Exactly. And if the color is white, then we will check if the car is equal to Harrier, then we will buy it, else we will not buy. So how does the decision tree work? Please read this. How does a decision tree work? Creating decision tree involves a series of steps aimed at systematically breaking down the data set. So what are important? First, selecting the best attribute, and that is completely based on information gain. How do we select the root node or the best attribute? With those attributes are selected with maximum information gain. Agreed? Is this point getting clear to everybody? Then splitting the data set. The data set is then divided into subsets based on the value of the selected attribute. And then we repeat the process. The process is repeated recursively for each subset, creating new internal nodes or leaf nodes until a stopping criteria is met, or till the depth is decided and the different hyperparameters are decided. So the metrics which are used for splitting, do we understand what are the metrics used in decision trees? Tell me, learners, what are the different metrics used in decision trees? It is the Gini impurity. It is the measure of impurity or disorder in a set of elements commonly used in decision tree algorithms. This metric measures the likelihood of incorrectly classifying a randomly chosen element if they labeled according to the class distribution. And what is the range of Gini impurity? It will lie between 0 to 0.5. Entropy, it quantifies the amount of uncertainty or impurity in the data set. The values lie between 0 to 1. And information gain is the metric measures that reduction in entropy or Gini impurity after the data set is split on a given attribute. Clear? Is this point getting clear to everyone? All right. Now, what are the advantages and disadvantages of the tree that you have understood? Our trees are good example if they follow non-parameterized approach. That means no assumption about the function. Okay. It's interpretable. Is our trees easily interpretable? I can easily find out why I'm not buying the car or why I want to buy the car. Are they easily interpretable? Yes. So they are simple and interpretable, versatile, because the trees can be used for regression as well as classification problem. No feature scaling is required, right? In decision trees, we do not use standard scalar or normalization method on the data, and it handles non-linear relationships also. So they are capable of capturing and modeling complex non-linear relationship between features and the target variable. Got my point? Moving ahead with disadvantages of decision tree. The biggest disadvantages, yes, that's why looking huge. The biggest disadvantage of decision tree is overfitting. What does overfitting mean in decision trees? That they are able to learn the noisy data also, particularly if they grow very deep with many nodes. Instability, small changes in the training data can result in significant differences in the structure of the tree. Bias towards features with more levels. Attributes with greater number of levels can disproportionately influence the tree structure, potentially leading to biased results. As I tell you, every algorithm will have its advantages and disadvantages. It is completely you as a user who will decide the hyperparameters and the results, whether you will accept the results or reject it. Getting my point? So the errors are even more than the other. That's why decision tree looks huge, right, Ajay? Okay. Still lot more to be done in decision trees. Yes. Huge topic. Yeah. Now let's get back to the next part of it. That is pruning. Yeah. So we are getting huge big trees, and the huge big trees will take are complex. They are difficult to handle. So can we cut off the extra branches? Yes. And cutting off the extra branches in the tree so that it's not so complicated, it's not so huge. That concept is known as tree prune. Getting my point, learners? So are you understanding how the tree is getting bigger and bigger? Yes. So an overfitted tree captures noise and it becomes very, very complex. And a prune tree, that means cutting off the extra branches, cutting off the extra information, is much more simplified and generalized better. Getting my point? This point is getting clear. Do you see the difference? We always start from the root node, and all these points have been pruned or cut off so that we are able to get a more simpler and a better generalized tree. Right? Clear, learners? So there are two types of pruning, pre-pruning and post-pruning. What is pre-pruning? Before we build the whole tree, we will pre-prune it. We have decided the depth that we will not go beyond the 10th depth or 10th level depth of the tree. Post-pruning is build the whole tree and then cut off the extra branches. Getting my point? Understanding pre and post. Let me see. So tree pruning example. This is post pruning. This is an unpruned decision tree that is fully created. But after creating the tree, we cut off this particular branch and then this becomes my pruned decision tree. Getting my point? Pre-pruning. A pre-pruning tree is a decision to stop growing the tree early. We stop the tree, beforehand, and it's not necessary that it should be a fully grown tree. Right, Puneet, Atul, Anush, it answers your query, right? It's not necessary. We will always go till the end of the node and keep on creating more depths or branches. So how do we post pruning? See, this is pre-pruning. A decision stops growing the tree early. We have decided the criteria to stop it. And post pruning is build the tree and then use your criteria to cut it off. So how do you prune a decision tree? Pre-pruning, of course, which are the parameters which will help us? The hyper parameter will help us in the tree, or the pre-pruning is also known as early stopping of the tree. Which are the different hyperparameters in decision tree? What is going to be my maximum depth, the minimum samples per leaf, the minimum samples per split? All these things will be my hyperparameter. So there's no one parameter, three parameters: maximum depth, how many number of samples per split, and minimum samples per leaf. Got my point? So these are same parameters and can also be used to get a robust model. However, you should be cautious as early stopping can lead to underfitting also. So we again always have to keep in mind that the model should not be underfitted. Also, it should not be overfitted. Agreed, learners? So post pruning does the opposite of pre pruning and allows the decision tree model to grow to its full depth. So once the model grows to its full depth, tree branches are removed to prevent the model from overfitting. So if we are pre-pruning, doing early stopping, the model can suffer from underfitting. And in post-pruning, the model can suffer from overfitting, and that is why we prune the. Got it, Dr. Henry, Roshan, Kalpana, Atul, Anush? And the parameter, one more hyperparameter to go. The hyperparameter that can be tuned for post pruning and prevent overfitting is CCP alpha. CCP stands for cost complexity pruning. So we have to always take into account the cost which is going to be there to perform the action. That can be used as another option to control the size of the tree. A higher value of CCP alpha will lead to an increase in the number of nodes pruned. So essentially, pruning recursively finds the node with the weakest link. What do we want to delete? How are we going to decide the cutoff criteria? Nobody asked me that. When we are doing post pruning, of course, and that was early stopping, how do we decide the criteria for pruning? We have to calculate the weakest link. That means the node which has least effect on the whole decision tree. The weakest link is by effective alpha, where the nodes with smallest effective alpha are first. So mathematically, the cost complexity measure for the tree is given by R alpha t, that is RT plus alpha into slash t, right? So RT is the total training error of the leaf node. That's how the cost complexity for pruning is calculated, and T is the number of leaf nodes. Now clear? So this is an example I've given you, tried to explain as how regression trees work. So this is an original decision tree, and we are calculating the Guinea, the number of samples and value. So as we move ahead, there is no class as such, but numerical value which are there. And prune decision tree after alpha pruning, that some of the branches of this branch, you see this branch has been pruned. Got it? Is this point getting clear to everybody? Got it, learners? Have you understood decision tree? You've still not practically implemented. Let's get back to the file. Yeah. Till here, are we clear? What are the advantages and disadvantages of the tree? Yes, learners, are you there with me? So now let's quickly run through the practical part of it. So what is pruning? If I ask you what is pruning, it's like regularization in prevent overfitting. Decision trees can be pruned. It's like regularization of linear regression. Over here, we can call it as pruning. Okay? Right, learners? So pruning involves removing parts of the tree that do not provide significant power in classifying instances. This can be done in two main ways. Pre-pruning, that is early stopping, which halts the growth of the tree early based on stopping criteria such as the maximum depth or the minimum number of samples required to a split. And post-pruning, now we are clear that the first, it grows the full tree and then removes the data. That adds little predictive power to reduce complexity and improve generalization. Clear? Are we clear with these points, learners? Okay. So using the same breast cancer detection criteria, first step, we import the Scikit-learn decision tree classifier, and then that scalar actually is not required, but since we are doing it in the pipeline, we do it over here. We fit it and then predict the output and accuracy score. So is the accuracy score good? What do you observe? Training accuracy is perfect. Testing accuracy is less. So is it underfitting or overfitting? Training accuracy equal to 1 definitely means it's overfitting. That how can a model learn perfectly, but it is learning perfectly over here. And when we see the predicted probabilities, we are almost getting the correct answer. So the please try to understand. There's a lot of significance in getting that one. Training accuracy indicates the decision model perfectly classifies the training data. This is a strong indicator of overfitting. Please be clear, Puneet Reddy, on this particular point. Where the model is too complex and it captures in the noise in the training data, resulting in perfect accuracy. Now clear? See, while still high is lower than the training. The testing accuracy is not low, but it is lesser than the training accuracy. And this difference indicates the model does not generalize well to the unseen data. Again, it is reinforcing that the model has overfitted. Clear? So if it is overfitted, does it require regularization? Yes. And how will we perform regularization here? Does it require pruning? Does it require pruning? So when there is a significant difference between training and testing accuracy, as seen in the training data at 1.0 and testing accuracy at 92%, it suggests the model might be overfitting to the training data. Cross-validation helps confirm this by showing how the model performs on different subsets of the data. The primary goal of cross-validation is to assess how well the model generalizes to the independent sets. A model performs well on cross-validated data is more likely to generalize well to new or unseen data. So how do we use the cross-validation? From Scikit-learn model selection cross-validation, I will use the pipeline, the training data and cross-validation equal to 5. And what is the score coming out to be? Why is it required to use cross-validation over here? Because the model was overfitting there, right? I got the training accuracy equal to 1. So what is this cross-validation score suggesting? That this is 91%. Please try to understand this concept, learners. It's very, very important and it will be repeated again. So this cross-validation scores are relatively consistent, that even after splitting or changing the different parts of the data, validating data with accuracies ranging from approximately 91.21% to 94.51%, this consistency indicates that the model is robust, performs well on across different subsets of the data. This confirms that it is not overfitting, that it is robust and it can perform well on the different subsets. Getting my point? The mean cross-validation score of approximately 92.31 suggests that the model generalizes well to the unseen data, providing a reliable measure of performance. And using cross-validation helps to ensure that the performance estimate is not overly optimistic or pessimistic, giving a balanced view of the model's effectiveness. Is confusion matrix also going to be a metric which will help us? Yes. So the errors are more. So decision tree has still not given good results for this particular, algorithm. And if you look at the F1 score, it's reduced further, 94% for 0, 91% for 1. And overall accuracy is also coming out to be 93%. Clear, learners? Are you there with me? Is this point getting clear to everyone? And ma'am, do we need AUC ROC curve? Yes. AUC ROC curve is giving me 93% of areas. In others, we were getting full 1%. So of course, it's not performing well as logistic regression or K-naves or naive Bayes algorithm, but it is 93% and the optimal threshold has come out to be 1. Okay. So since this model has been overfitting, can we apply pruning? Let's apply pruning also. Are you there with me, learners? Can we move ahead with the pruning of the decision tree? So by pruning a decision tree, we aim to improve generalization of the model, thereby avoiding overfitting. Let's apply pruning to the decision tree and then evaluate the model's performance. So we have CCP alpha is a parameter when we are creating the decision tree classifier. Accuracy came out to be 92%. Great, Anush. Which 92%? Which one came out to be 92%? This one. This in classification report. Classification report. It's okay. So the decision tree classifier, we have taken the CCP alpha equal to 0.01 with random state equal to 42. And then we have using the cross validation score also when I have seen the pipeline pruned. Now my pipeline has changed. Why? Because I have set the the cost complexity pruning factor equal to 0.01, giving the training data with CV equal to 5. So now when I check my pruned accuracy, mean CV is 92%, and now the training accuracy is 98%. So definitely overfitting has reduced. Agreed? Now it's not overfitting, right, learners? Do we see that? Yes, learners. Are we able to observe that this is the prune decision tree is giving better results? And now if I see the confusion matrix, the overall results have also improved. Classification report. Everybody is able to observe this. And now look at my ROC AUC curve. The area from 93% has improved now to 94%. Agreed, learners? So pruning the decision tree has successfully reduced overfitting, and that is what we wanted, as indicated by the reduced training accuracy and improved testing accuracy. The prune model shows more consistent cross-validation performance, indicating better stability and generalization. The overall classification metrics remain high, demonstrating that the prune model maintains strong performance while avoiding the pitfalls of overfitting. And we have also understood the hyperparameters tuning in decision tree. What are the main hyperparameters? And what is the importance of hyperparameters? That they are crucial in improving the performance of the model, right? So maximum depth, what length or depth we want the tree to be. Minimum number of sample splits, second. Minimum sample leaves, and maximum features, the number of features consider when looking for best. CCP alpha for pruning is also a hyperparameter, and the criteria, the function to measure the quality of a split is also a criteria. So 6 hyperparameters to be considered when we are, creating decision trees. Getting my point, learners? Are the 6 parameters clear to everybody? Parameter tuning technique, as we have seen. Grid search is an exhaustive search technique. Well, there are too many parameters over here. Along with cross-validation can be used, or a random search over a specified parameter grid. So if we look at the parameter grid, do you understand what is a grid? We always define the grid in terms of dictionary. So this is the maximum depth that I want to keep for my tree, none, 10, 20, 30. The maximum depth of decision tree, if none, the nodes are expanded until all leaves are pure. Full expansion of the tree until all leaves contain minimum split samples. Specific values 10, 20, 30 limit the depth of the tree control to its complexity and preventing overfitting. Minimum sample splits 2, 5, and 10. Again, higher values prevent model from learning over overly specific patterns by requiring more samples for a split. And minimum number of leaves, the maximum features, the alpha value. So if we look at over here, now I've imported grid CV cross validation, created a pipeline of it, and now I define my dictionary of different parameters. How much could be my maximum depth, the sample number of splits, the minimum samples per leaf, the maximum features, square root, or log 2. What do we mean by maximum features? The number of features to consider when looking for the best fit? Is it consider all features, take the square root of it, or log base 2 of it? Okay. And then we do the grid CV search, fit it, and then find out the best parameters. So the best parameters, alpha comes out to be 0. That means no pruning is required. Maximum depth is none. The maximum features is log 2. Minimum number of leaves is 1. And minimum number of sample split is 2. So the best cross-validation score is 94% and accuracy is 95%. So it is higher, so it is giving you much better results, and there is no overfitting of this decision tree. Right? Point getting clear to everybody. So we are not able to do the support vector machine. It again requires a little more thing, but I think so the decision tree, was long explanation. A decision tree consists of a root node, internal nodes, and the leaves and the branches. We always start from the root node, move towards the internal nodes, and then we have the leaves, right? And what is the important metric? We need to calculate the purity of the nodes, how well the classes have been classified, right? The purity. So what are the different ways? What are the calculation metrics used for purity? Entropy, it's not entropy, Roshan. It's entropy. So entropy, Gini index are the two. And ultimately based on the information gain. So whichever node has maximum information gain, that metric is used to create the decision tree. How do we avoid overfitting in decision trees? Yeah, it is tree pruning. The two types of pruning are pre-pruning and post-pruning. That means we cut the tree before the tree is not grown in its full length. It is depending on the depth of the tree, right? And the other one is post-pruning, where we create a complete tree and then try to cut it down. Clear? So what are the different hyperparameters of a tree? I think so we discussed that, but quickly we'll start discussing that. And today we have to do support vector machines and do multi-classification algorithms also. Yeah. Imbalanced classes if possible. Yeah. Yeah. It is the depth of the tree. Then the other one is the number of leaves per split, right? The number of split that we can calculate in per class. So how do we calculate hyperparameters? Hyperparameters are those parameters which are user defined. We define their value. So what is the best way to find the hyperparameters? Hyperparameter tuning. What are the two methods of hyperparameter tuning? Grid search, CV, or the random search. What is the difference between grid search and random search? Grid search performs all the combinations of parameters and randoms rules selects randomly. So grid search is an exhaustive search algorithm, right? So grid search is one of the hyperparameter tuning technique in which different hyperparameters are taken, and then we decide which model, which combination of the hyperparameter model gives us the best result. Getting my point? Right? So what does this particular diagram represent? What does it mean? Let the tiny circles represent different hyperparameters, and we begin with one value of hyperparameters to train the model. So, right, when we start training, we take one set of hyperparameters and train the model. Then we use different hyperparameters to train the model. We tend to continue the method until we have exhausted the various parameter values. So continuously, whatever permutation combinations can be formed, this is what we always try to do. Got it?
Every model produces an error. We pick the hyperparameter that minimizes the error. So that's the whole trick of machine learning, that we will always choose those parameters, hyperparameters that will minimize our error. To pick hyperparameter, we split our data set into 3 parts. What is this concept known as when we split the data set into 3 parts? The training, the validation set, and the test set. Cross-validation. So we tend to train the model for the different hyperparameters, and we use the error component for each model. We select the hyperparameter that minimizes the error or maximizes the score on the validation set. After that model has been picked or hyperparameter has been finalized, in the end, test our model performance using our test data. Clear? Right? So if we talk about decision trees, this is the parameter, please try to understand in grid search, we always write the parameter in terms of dictionary. Okay, so this is the criteria, this is the range. First is, which criteria are we using to finalize the internal node? Are we using the Gini or the entropy method? Maximum depth, we want to range it between 1 to 10 level, right? Or 1 to 9 level. Minimum number of sample split is 1 to 10. And minimum number of sample split is also range from 1 to 5. This point is clear? So the grid search CV over here, grid search cross-validation is always carried out, in which the data set is divided into training, validation, and testing. Training and validation is used to find out the best hyperparameters. Is this point getting clear to everybody? So the colorful balls are representing these hyperparameter. This is the function in which we are doing a grid search on the decision tree. Parametric grid, this is the grid we are passing. Cross-validation, we are using 10 times, verbose 1. N underscore jobs equal to -1 helps us to, utilize all the cores which are there in the hardware. And grid.fit trains the data. Clear? So how do I know the best parameters? By using grid.best underscore params underscore. Criteria is grid. Maximum depth is 9. Minimum sample leaf is 3. After doing or running the algorithm, cross-validating it, these are the best result that we get. And it is Gini index 9, 3, and minimum sample split is 7. And the best estimator is this, with maximum depth with this much, minimum number of sample leaves this much, minimum sample split 7. So the best score which has come out after applying these hyperparameter is 82.94%. Clear? And what is the effect of hyperparameters? The maximum depth limits the number of levels in the tree, preventing it from becoming overly complex. So this prevents overfitting. Low depth may lead to underfitting, where the model fails to capture the complex pattern. Maximum depth, or I would say large values of depth, high depth can lead to overfitting, where the model learns the training data too well, including noise, and performs poorly on the unseen data. Example, maximum depth is equal to 5. This would restrict the tree to a maximum of 5 levels. Minimum number of samples split specifies the minimum number of data points a node must have before a split is attempted. It impacts the complexity of the tree by preventing splits in nodes with very few samples. All right. And then we have minimum samples per leaf, specifies the minimum number of data points a leaf node terminal node must have. Why it is important? Because it helps to prevent the overfitting by ensuring the leaf nodes are not too small based on limited number of samples. Clear? The impact is also there. And then we have the maximum leaf nodes purpose limits the number of leaf nodes in the tree. Similar to the maximum depth, it helps to control the complexity of the model. For example, if maximum leaf node is equal to 10, limits the tree to maximum 10 leaf nodes. Clear? Are the hyperparameters clear? So we are very clear with decision trees now. Okay, now let's quickly do the knowledge check. First question, what is the assumption of naive Bayesian classifier? So a quick revision of different algorithms. First question, what is the assumptions of naive Bayesian classifier? Yes, it is C that all the input attributes are considered independent of each other and the model is considered to be generated. Second question, which one of the following application is not an example of naive Bayesian algorithm? Tell me. Naive Bayesian algorithm is used for classification, not for regression. Yes, it is stock market forecasting. Which of the following statement is false about k nearest neighbor algorithm? Again, the answer is C. Yes, the answer I think is C. It cannot. It can be used for regression. Next, consider the figure if a person A starts driving at 8:30 a.m. and there is no other vehicle on the road. The another person B starts driving at 10 a.m. and there is an accident on the road. What will be the commute time of A and B respectively? Yes, the answer is again C. So all answers are C. What is the entropy in context of decision trees? That answer is A. It measures the disorder or impurity in a node. Absolutely correct. In a decision tree, what is the purpose of the leaf nodes? Yes, it helps us to represent the class label or class value. Next question, which of the following is a disadvantage of using decision trees for classification tasks? It is B that decision trees are prone to overfitting. If they're computationally expensive, then you have to avoid the depth, right? So B is the better answer, not D. All right. Next question. Given entropy for a split, E split is equal to 0.39 and entropy before the split, E before is equal to 1. What is the information gain for the split? So information gain is equal to before minus after. So 1 minus 0.39 is C. Clear? So here we go in with support vector machine. It is also one of the very, very important algorithm which helps in handling non-linear data, right? So again, it leads to the problem of classification if two classes are really far apart from each other. Example which I generally take is, I don't know how much relevant it is in today's world. The boys' hostel and the girls' hostel in a university are well separated from each other, right? So now the question is, which linear straight line, divides the two classes in a pretty well? Is this the line I should consider? Or this is the line? And it's not about line. It is all about hyperplane. What is the difference between a line and a hyperplane, learners? What is the difference between line and hyperplane? Absolutely correct, Megha. Here we are talking about not one dimension. Hyperplane is in multi-dimension, right? Not always in three. It can be more than three also, Kamal. Okay. So what is the best way to solve? No, not necessary. Plane is in 2D. Hyperplane is in higher dimension, Kalpana. You're wrong. Hyperplane is never in 2D. Planes are in 2D. Line in 1D, plane in 2D, and in higher dimension, it becomes a hyperplane. Okay, please be clear with that concept. So, taking the first two data points of this particular class, which are known as my vectors. Okay. Similarly, I'll take one vector this, one vector this, and try to pass a straight line. So two hyperplanes are being, created. One of them is known as a negative hyperplane, and the other one is known as a positive hyperplane. Are you understanding this equation also? This is nothing again, this represent your linear regression. Why linear regression? It is your weights W0 X0 plus W1 X1 plus W2 X2. Getting my point? So this is WTX is equal to minus 1. This is the negative side. And the positive side is WTX is equal to 1. Right? And this is known as the center one is known as the decision boundary, which is equal to 0. So any points lying on this side belongs to this class. Any points lying on this side belongs to this class. And the margin is the difference between the positive and the negative, hyperplane. And what is our aim? Our aim to maximize this margin. That means we should be very clear and distinct that this class belongs to the positive hyperplane and data points lying to this side belongs to the negative hyperplane. Clear? So why it is known as a support vector machine? Because over here we are using this concept of support vectors to draw the margins to deal them in higher dimension plane. Now clear? So again, I'm telling you in two-dimensional, one-dimensional, a single line is represented with this equation. And when in higher dimension, the equation becomes WT. You would say, ma'am, what is this WT transpose? This is how I write my multiplication, or it is a vector of weights with dot product of these values, x1, x2, x3, xn. Now clear? Both represent the same linear equation. So again, we are clear. Here we want to maximize our margin. This is my decision boundary where it is equal to 0. And then we have the plane on this side. This is known as the negative hyperplane. On this side, this is known as the positive hyperplane. Getting my point? But in the real world scenario, do we have very strict margins that all the data points are going to lie on the on the left side of the negative hyperplane and all the data points are going to lie on the positive side? No. In the real world scenario, there is always mixture of data points. There can be a situation that some data points lie on the other side of the margin also. And on the other class can belong to the other class also, like the red data point. Right, learners? Is that possible? All right. So what is the hyperparameter over here? The hyperparameter over here is what should be the distance or the width of this particular margin. Ultimately, our aim is to maximize it. So the larger value of the C parameter makes this margin slower, or it leads to overfitting of the data, and small value of C gives maximum margin, that means well separated. Clear? What if there is data on the line of the decision boundary? Yes, we are coming. Oh, on this particular point. So it is completely up to us whether we want to put it on this class or this class. That's going to be our logic. That's completely depends on what logic are we going to implement in our algorithm. Okay. Okay. So Megha, I'll repeat. See, ultimately, we want to maximize this particular width, right? So there is this regularization parameter C, which will help. The larger value of C means the margins have reduced, and smaller value of C means the margins have expanded. What I'm trying to say is, how do we go about? So what does C become? C becomes my hyperparameter. Agreed? Which is going to decide the width of this margin. So if the value is lesser, this is maximum width. But is it showing a good margin? No, there is a lot of mixture of data points. Now, when I make C equal to 1, this is better. You know that there are certain misclassification, but it can be handled. When I make C equal to 10, it becomes even more smaller, and C equal to 100, it makes even more smaller margins. So C is known as the regularization parameter of the support vector machine, which manages the width of the margin, right? But another C seems like length. Yes, we can say that, we're trying to, adjust the width. But when we try to finalize the width of the margin, we also have to understand the different data points, right? How far are they, far are they from the different, the distance, the margins they are. So this is another hyperparameter of support vector machine, which is known as the slack variable. What is this known? This is known as the slack variable. Yes, C is a hyperparameter as well as this epsilon, also known as the slack variable. Right. So if we look at this, if we look at it, again, what is value of epsilon? If a particular data point belongs to the correct side of the margin, that means the epsilon is considered to be equal to 0. Right? If it is on this side, it is again considered to be 0. If it is on this side, it is considered to be correct. Right? And what is the case? If the epsilon is greater than 1, what does that mean? If it is greater than 1, that means a data point belonging to one class is now shifted to another class. So that means a data point is not classified correctly or is in the other class. Right, learners? And if it lies between 0 to 1, that means it is within the margin. Clear? Let's understand it in a better way. So the slack variable. So please try to understand in support vector machine, there are two hyperparameter. One is known as the epsilon, the slack variable, and the tuning parameter C. Okay. Slack variable epsilon tells us the location of the ith observation relative to the hyperplane and the margin. So what does it tell? The distance, location of the ith observation relative to the hyperplane and the margin. If epsilon I is equal to 0, then the ith observation is at the correct side of the margin. Clear? That means if epsilon is 0, there is nothing to worry. But if it is greater than 0, then the ith observation is on the wrong side of the margin and ith observation has violated the margin. If epsilon is greater than 1, then it is on the wrong side of the hyperplane. Then it is on the wrong side of the hyperplane. Now, these three parameters are clear. So the tuning parameter C bounds the sum of the epsilon that can violate the margin as well as the hyperplane. So if C is equal to 0, no violations would be allowed. So tuning parameter C bounds it, the sum of epsilons that can violate the margin and the hyperplane. So if C is equal to 0, no violations are allowed. That means all the epsilons are equal to 0. But if C is greater than 0, no more than C observations can be on the wrong side of the margin. Clear, learners? And the other case is that if we have studied, if in an example is on the wrong side of the hyperplane, then epsilon greater than 1, then the optimization problem requires that epsilon should be lesser than equal to C. So there has to be tuning of the slack variable and the C in such a way that if C is greater than more, obviously C will be having some margin, not more than C observations can be on the wrong side. And if epsilon is greater than 1, then epsilon should be lesser than equal to the regularization parameter. So what does this mean? As we increase the value of C, a greater number of violations of the margins will be allowed and the margin will widen. That's true. As we decrease C, we will allow lesser number of violations to the margin. The margin is narrow. So how do we treat this? We treat C as the tuning parameter, which is chosen as cross-validation. So over here, something like this only. When C is very small, the margins are very, very high. And as the value of C is increasing, the margins gets reduced. But ultimately, it is through cross-validation, we find out the correct value of C based on the value of epsilon. How many wrong, classifications have been there? Is this example making things clear? Right? So there is this one violation happening over here and maybe one over here. That's it. Basically, what we are trying to do is we always want to find out the values of hyperparameter in decision trees, like it was the number of leaves per node and the samples per leaf, the depth, right? Here there are two parameters, C and epsilon. So over here, we want to find out that value of C where the number of misclassifications are less. Clear? So when the C value is less, this is the most widened hyperparameter. Right? So this is of course not a good choice. As the value of C is increasing, the margin is getting lower. And maybe at this particular position, we see it is at best with only two misclassifications in this particular case. Now clear? Now better? Another very, very important feature of support vector machines, for which, support vector machines are mostly used, that's for non-linear equation. Now look at over here. This is a non-linear function which separates the two classes, the red balls as well as the blue balls. Is this polynomial function correct? Is it a simple function or a complicated function? Is it a simple function or a complicated function? Are we interested in complicated functions? No. Now, by increasing, and this is in two-dimensional plane. This is a two-dimensional plane. Now, if I increase the dimension, I am converting this two-dimensional data points to three-dimensional data points. But do you see the advantage? This complicated function now gets into a simple hyperplane, and then I am able to separate my red and blue points successfully. But ma'am, why are we increasing the dimension? We are increasing the dimension only in that case, only in one condition, when my function, mathematical function, is becoming simpler. It's not complicated anymore, right? So if these are my data points, right, and we understand this is my nonlinear decision boundary and we will apply the kernel, right? I have now increased it into 3-dimensional space by applying some polynomial curve, radial bias curve, and now the beauty is that by using a simple hyperplane, I am able to separate the two data points. Are you liking the beauty of support vector machines? See, every algorithm is different because every data is also different. Every, every algorithm cannot be fitted on the same data. Getting my point? So what are the different types of kernel? So kernel again becomes my hyperparameter. Can I say that? Kernel again becomes my hyperparameter. Clear? So what is the idea? When we have non-linear decision boundaries, the two steps for generating non-linear decision boundaries are transform the original training input data into high-dimensional data using non-linear mapping. Once the data is transformed into new, higher dimension, find the linear separating hyperplane in the new space. So if I have two variables, two dimensions, variable x1, x2, then this is the polynomial transformation terms, that is x1, x2, x1 square, x2 square, x1, x2. Clear? Clear to everybody? So now do you see this hyperplane? Yes, learners, do you see the hyperplane equation now? How are we converting it? Because now the x1, x2 have changed into these many variables. So what is the advantage? From this equation, we will get a non-linear decision boundary in the original feature space. And it is used up to second terms. Two features are expanded to 5 of degree term, third degree term, and 3 features are expanded to 9. Okay. So what is the advantage? So we can use the support vector classifier in the expanded space to solve the problems in lower dimension space. So what is the idea? That kernel functions are used to handle the nonlinear transformations of input data into higher dimensional. Yes, the disadvantage is that it may be computationally heavy. Kernel functions were introduced to avoid some of these problems. So therefore, support vector machine is an extension to support vector classifier, which results in transformation of input of data in a specific way using kernels. The main idea behind the support vector machine is to enlarge our input data so that we can accommodate non-linear decision boundary between the classes. So support vector machines are very good algorithm which help in resolving non-linear classification data. And the different types of kernels used are linear kernel, RBF kernel, the radial basis kernel. This is the iris data set, if you remember, right? So this is how it is. And then we have this polynomial kernel and sigmoidal kernel. Getting my point? So now let's quickly get back to the file. I think so. We were on which file in classification? Lesson number 4. First 4.1 only. We are still on 4.1. I think so we are still on 4.1. Right, learners? Please start loading the data. So this is the breast cancer data set, right? Then we drop this app data and do the df.info. We have to do it till the split thing does. Then we drop the ID also. This is the heat map. Yeah, then the label encoder. What is the use of label encoding? The output diagnosis, because two types of cancer are there, benign and malignant. And this is the splitting thing. And then we create the pipeline. Pipeline, we will create the support vector. Yes, learners, are you there with me? I have loaded my data set till there. Hopefully it should run. So it is the supervised machine learning algorithm used for both classification and regression challenges. Another beauty of support vector machine is that it can be used for both classification and regression both algorithms. It is mainly used for classification in support vector machine. The required straight line is to fit the data is called a hyperplane. The goal of support vector machine algorithm is to find a hyperplane in an n-dimensional space that distinctly classifies the data points. The closest data points to the hyperplane on the either side are called the support vectors, and the support vectors influence the position, orientation of the hyperplane, aiding in the construction of the support vector machine. So are we clear? There are two types of support vector machines. Linear support vector machines and non-linear. Linear separates the data in a linear pipeline, and if the data is separated into using two straight line, it is linearly separable. When it is non-linear, then we use the kernel function in higher dimensions to make it easily separable. Agreed? So sklearn.svm import svc. From sklearn.pipeline import pipeline, right? So pipeline, what is the use of pipeline, learners? Automating the process. We are trying to use two processes simultaneously, that is standard scaler and the support vector classifier. Training accuracy is 98.90 and testing accuracy is 98.24%. So can you tell me, is it a good fit, underfit, or an overfit? Very good fit, Almost the training accuracy and testing accuracy are coming out to be the same. Good, good. So you all understand this. So this is the predicted output we are getting. So support vector machines also perform well. And if we look at the confusion matrix, one of the errors have reduced to 0, other one is 2. So it will give us good classification report. Do we understand classification report? Yes. Almost all the scores, micro, macro, everything is coming out to be 98%. So support vector classifier or machine has performed very well on this data set. Agreed? And if I talk about the ROC AUC curve over here, it's coming out again to be 1. Right? And if I talk about different hyperparameters in support vector machines, tell me, what are the different hyperparameters in support vector machine? The kernel type, the regularization parameter, and the slack variable, the gamma. So in support vector machines, hyperparameters play a crucial role in determining the model's performance. Here are some key parameters typically adjusted in SVM. Kernel type. The kernel function transforms the input data into higher dimensional space where a hyperplane can be used to separate classes that are not non-linearly separable in original space, right? And the different kernel types are linear, polynomial, RBF, sigmoidal, right? C regularization parameter, Kalpana, are you now clear? The parameter trades off for correct classification of training examples against maximization of the decision's margin. A higher C tries to classify all training examples correctly. That means low bias, high variance. What is low bias and high variance? What is this condition of low bias and high variance known as? While lower C allows more misclassifications but pushes for larger margin, the larger margin leads to high bias, low variance. That means underfitting. Good. Gamma, this hyperparameter is used with certain types of kernels like the RBF, where it defines how far the influence of a single training example reaches. Low value means far, high value means close. The gamma parameter can be crucial in avoiding overfitting or underfitting in the SVM model. Clear? Low bias, low variance, good fit. Yes, Ajay, right. So now clear? We have understood major algorithms of classification. We started with logistic regression, naive-bayes, KNN, decision trees, support vector machine, and each method was explored through theoretical discussion and practical example. And we have taken one example, that is the breast cancer data set, so that the comparison between all the algorithms can be done. Clear? Yes. So what is multi-class classification? See, nothing over here. We will do the same algorithm, naive-bayes, KNN, decision tree, and random forest for multi-class, but we will be using on different data set. That is online gaming behavior data set, right? So what is multi-class classification? When the target variable has more than two classes, that is known as multi-class classification. So now let's look at this online gaming behavior. So multi-class classification is a type of classification task that involves classifying instances into two or more classes. Unlike binary classification, which deals with two classes, multi-class can handle problem where an instance can belong to multiple categories. Getting my point? Is this point getting clear to everyone? So a tree can be classified as a banyan tree, palm tree, or pine tree. So this is a class of multi-class? Of course. So what are the algorithms which come? Except logistic regression. Logistic regression is the only algorithm which is used for binary classification. All other algorithms can be used for multi-class like naive-bayes, KNN, decision trees, and random forest. Clear? So now let's take this data set example with online gaming behavior. This particular data set on Kaggle is designed to analyze and predict players' behaviors in online gaming. It includes data on various aspects such as player identification, session duration in game, actions and purchases. The data set comprises several features that capture player activities and interaction within the game environment, providing a rich source of information for developing predictive models. So the number of instances is these many. 40,034 rows are there, and it has 13 columns or features. So we have this player ID, age, gender, location, game genre, playtime hours, in-game purchases, game difficulty, sessions per week, average session duration per minute, player level, achievements unlocked. But why is it a multi-class algorithm, multi-class algorithm, or under the category of multi-class classification, because the output variable or the target variable can be categorized into reflecting the three types of player. That is, if you belong to the medium category, high or low. Getting my point? It's more than two classes. A player can be engaged in three different types of category, that is low, high, and medium. Getting my point? All right. So let's start with its implementation. Yes. So are you getting scared looking at these many libraries? The first four libraries, now you are very familiar. Then ultimately it is Scikit-learn, but with model selection, I'm using train underscore testplate. For pre-processing, I'm using these function, and the naive base, KNN, pre, ensemble. I'm doing all the importing of the files for different algorithm in the very first command only, along with the metrics. Now clear? I hope these many, libraries are not scaring you, or is it? Are these many libraries scaring you? All right. So let's load this data set. Yes. Good, Ajay. Have you been able to load the data successfully? Are you there with me with 4.2 learners? Okay. So we have 13 attributes: player ID, age, gender, location, game genre, playtime hours, etc. So that point we are very clear. These many rows, 40,034 rows, 13 columns. And if you look at the detail of the column, these are the details. So what are my categorical data? And which is my target variable? Which is my output variable? Of course, it has to be categorical in nature. So the engagement level of the player is divided into three categories: low, medium, high. Clear? What are we doing with this particular command? What are we doing with this particular command? Checking the null value. So does this data set has any null values? No. Let's do the describe function. So this is the ID, this is the age, around 30, 31 is the age, average age. Minimum is 15 years, maximum even 50 years old. Play games. Do you all play online games? I mean, just asking. So these are the number of hours which get invested. Some invest 0, and even some even invest one full day, around 24 hours a day. Okay. In-game purchases, session, play, etc. So I hope you are now familiar with how to analyze this data set. Everybody understands how to analyze the output of the command, since we have been doing in data science and as well as in machine learning. Now, this is important. This is the different classes along with their frequency, right? So this is the median, high, and the low value. Clear? This is the engagement level, value underscore counts. Getting my point, learners? Okay. Now tell me, what are we trying to do over here? I always ask this question to you. Earlier, defining the X and Y. Only separating the input and the output. Splitting is into training and testing data. So when I do dot gender, it is the males who are playing more than the female. Is it like that? Males play more online games than female according to this data, at least. Location, people from USA play the most, then Europe, then Asia and others. I think so Indians should be the more, no? We Indians play a lot of games, no? So based on this data, it's more of the people in USA. And if I talk about game genre, what kind of games do you like to play more? Then we have the different game genres. The game difficulty level, easy, medium, hard, that needs to be counted. I hope you are appreciating this value underscore counts function. Yes, learners, I hope you are appreciating that. That it is generally used for categorical data where we have different categories along with the frequency count, right? Right. Now, what are we trying to do in this particular code? Now, you tell me. Well, all the comments are there, but what do we understand? This is a categorical columns list I have created, and then I'm using the label encoder. What is the use of label encoder? Converting categorical data to numerical value. So, what is the concept of label encoders? Is it ordered data or nominal data? Ordered, like low we can give least rank and high we can give high rank. So this is how we, get the label encoders. And then what are we trying to do over here? What does x_core do? Good or, what does x.core function do? Relationship between the features, also multicollinearity, that how strongly they are related. We can say, but multicollinearity is generally calculated with VIF, variance inflation factor, Puneet Reddy. But correlation helps to find out the strength of the relationship. That is what we are trying to say. So now when I do the correlation matrix, how do I interpret? How do I interpret? The darker color means negative relationship, lighter color means strong relationship. So where is the lighter color? Between the game genre. So this is a good score. Game genre, and this is also a good score, right? The game genre is this, and the play time hours is this much. Clear? And now finally, what is happening in this particular code? Here we are splitting the data for training. Now clear? First we were separating all the input and output, and it is the train underscore test underscore split function which is used to split the data. All right. What is that known as? Preparing the data set, or another technical word, pre-processing. Okay, good. Another technical word. Another technical word. Feature engineering. Can we call that feature engineering? Yes, Atul. Good. So preparing the data to be fed into the model. So what are we doing in this last step? Can anybody tell me why did I apply standard scalar after the split? Why did I apply standardization after the split? First of all, what is standardization? Tell me that. No fit for the test data, right? But we are transforming only the test data. But why after the split, Puneet Reddy? Test data we are only transforming. For input, we are doing the fit. Why? To prevent data leakage. And what is standard scalar? What does the standard scalar function do? It standardizes the data, right? Mean equal to 0, deviation equal to 1. Excellent, Puneet. Feature scaling. And why do we do feature scaling? Yes, a large value will not decide or skew the result, so that our model is not biased. Now, what is the first model that we are trying to do? So now our, data is well prepared to be fed into the model. Now it is up to me, I want to use the pipeline or not. So first step for implementing model, importing the library, creating an object of the data and fitting the model. What does the fit function do? What does the fit function do? It trains the input as well as the output data, and then we get the predicted output results. Clear? Is this code and point getting clear to everybody? Then we are trying to find out the class order over here and then check the results output. So what is the class order? Basically, high has the high, then we have low and medium. This is the actual label, predicted label, along with the probabilities. Why do you think the medium is the output? Because medium has highest probability in all the cases. Clear? Concept of probability is getting clear. In classification problems, we will always get the output in terms of probability. And as I've told you, in LLM models, V is a classification problem. So therefore, it also gives the output in terms of probability. Right, Ajay? This is what we learned. And now if I look at the naive-based classifier accuracy, what do you conclude from this? I mean, it's not very good, but the training and the testing accuracy again are coming out to be almost the same. Ajay says, ma'am, why logistic regression not in multi-class? We can't extend logistic regression? No, we cannot, because the sigmoidal function gives only two outputs, that is 0 and 1. That is why it is only valid for two classes, practically. It doesn't give. So either you will get the output as 0 or 1. That's it. So therefore, for multi-class classification, you need 0, 1, and 2, which is not possible in logistic regression. Sigmoidal function does not do that. Now tell me, what is the result of naive-based classifier? Is it a good fit, underfit, overfit? It's again a very good fit. Less accurate, but it's a good fit. Yes. If you look at the confusion matrix, now do you see the confusion matrix? It's a 3 by 3 confusion matrix. Difference you are understanding? Earlier it was only 2 because we were talking about 2 classes, and now class confusion matrix with labels. So high and high, no error, low. So these are the perfect classified classes, and these are the errors associated with each term. Got it, learners? So high, the class is relatively high number of the true positive, that is 3,234, but also considerable amount of false negatives, indicating that some instances misclassified as low and medium. So I think so the best way to do it is check the classification report. Right, so it's quite giving us 85% for high, 78% for low, and medium it is 87%. And this is how I'm getting my accuracy. Clear, learners? So look at the beauty. If there would have been 4 classes, it would have been 4 by 4 matrix, and the classification report would have 4 classes output. Then we have label underscore binarize. It is a function from Scikit-learn that is used to convert class labels into binary format. Right? Here we are using one more function, which is part of the Scikit-learn library, which converts class labels into binary format suitable for certain type of classifiers as well as the evaluation metrics. Particularly, why do we need to convert it into binary format? Because there are 3 classes. Useful when you need to handle multi-class problems with methods that are inherently designed for binary classification, such as ROC and AUC curves. So even the ROC or AUC curves are inherently designed to deal with classification or binary classification problem. So to draw the ROC curve for multi-class setting, this is how we would get my results. that it would check, label, binarize. It would check, make the output in terms of binary value 0, 1, y test classes is equal to nb underscore model dot classes. Getting my point? So n underscore classes is equal to y test binarized is equal to shape 1. And this is my predicted probability, right? Do we understand predicted probability? Function that is used is predict underscore prob a, not normal predict function that we use in linear regression. And with the help of these binary value, I get my 3 curves, ROC curve of class 0, class 1, and class 2. So they all are almost performing well, around 94, 91, 90%. So what do we see? That class 0 represents high class. The model performs very well in classifying instances of class 0 because the area under the curve is 94, indicates that there is 94% chance that the model will correctly distinguish between the randomly chosen positive instance and randomly chosen negative instance for class 0. Getting my point? What is the significance of diagonal black line? The diagonal line represents random guessing with AUC of 0.5. So always the area under the curve should be more than 0.5. If it is 0.5 or lesser than that, that means it's not a good classification model. So any ROC curve below this line indicates worse than random performance, while curves above this line indicate better than random performance. Now clear? So we can see that naive Bayes performs exceptionally well for all classes as the area under the curve are all in 90s. The model is best at classifying instances of class 0, high class closed by class 1, class 2. Now clear? What is the significance of ROC AUC curve? That the class 0 or the high class game players have been classified very well as compared to class 1 and class 2. Clear? Now moving ahead to k nearest neighbors algorithm. What is the concept of k nearest neighbors algorithm? Tell me. How does the KNN work? The output is based on nearer data points, right? The neighbors of predicting it, right? And generally the number of neighbors are kept even or odd. Yeah, looking at the k closest data point, always odd, so that, we can conclude, at least one. Even data points can always lead to clashes, right? So from Scikit-learn neighbors, import k neighbors classifier. KNN model is k neighbors classifier with three neighbors, and KNN model dot fit is equal to training. SC, what is this X underscore train SC? What is SC? Scaled X. Yeah, standardized input training data. Yes. Try to understand learners code. Okay. Good. Scaled or standardized X. Right. And that's what then we are going to, fit the model and then predict the output. So we see the medium, high, low values are getting predicted along with the probability values. Then we can get the class order and see the actual and the predicted outputs. Clear? So KNN has not given us good answers. This is wrong. It should be medium. This is also wrong. So KNN has not performed that well as naive Bayes. I don't know. Naive Bayes has, somehow it performs pretty well than other algorithms, right? Getting my point? And then what is the training and testing accuracy? What will you conclude? Is it an underfit or an overfit, Puneet? You're talking about accuracy. I think so. You brought out this point. The testing error is more than the training error, right? Is it underfit? Is it overfit? Yeah, it is overfit. The training error is definitely more than the testing error. Sorry, testing error is much more than the training error, right? So it's overfitting the. Got it, everybody? So now, if I see the classification report, it's not as good as we saw it in the naive-Bayes classifier. And if we check the ROC AUC curve, the area, the area under the curve has also reduced from 92, 93% to 89, 83, 79%. Right? So cyan line is class 0 area under the curve. The model performs well in classifying instances of class 0 medium. Area under the curve is 89%, that it has 89% chance that the model will correctly distinguish between the randomly chosen positive instance and randomly chosen negatively instance for class 0. So what are our observations? The KNN classifier performs reasonably well for all classes, but not as good as it was a naive-Bayes classifier, with AUC values ranging from 0.79 to 0.89. If the data set has imbalanced classes, some classes have significantly more instances than others. So this could affect the model's performance. And the ROC curve, it is essential to consider under class distribution when interpreting these results. Right? So the next step that we are going to learn after classification is ensemble learning. That is where we combine the outputs of different algorithms and to improve the overall result. That can also be one of the methods. Data is variable, data is uncertain, data is changing constantly. Right? So no one algorithm is fixed, no rule is fixed on data. Okay? So when we talk about real world data, it's constantly changing. All right. So here we are starting the multi-class and the multi-label classification problem. Binary classification, we are clear. Only logistic regression is that algorithm that, helps in binary classification of the things, right? Then we have multi-class classification where, outputs can be more than one, as we are already doing one of the real-time data sets. That's for online gaming data set, which is classifying the players into low, medium, and high level of players, right? And then we have multi-label classification where we have the dog, cat, bird, same image getting done. So multi-class and multi-label classifiers. Multi-class classification can be judged on the basis of one versus rest classifier, one versus one, or multi-label classifiers can be, checked based on multi-output classifier, right? Then we have also understood the label underscore binarized function in Scikit-learn is designed to handle multi-class labels by converting them into binary matrix format using one versus all. What is one versus all or one hot encoding scheme? Why is it important to do label underscore binarize? Right? Then it is able to, do the comparison between the different classes. Getting my point? Right? Format using one versus all or one hot encoding. The function takes original labels and a defined list of all possible classes, then outputs a 2D array where each row represents a sample, each column corresponds to a class. A1 indicates the sample belongs to the class, 0 indicates it does not belong to the class. Getting my point? What is one hot encoding? What is one hot encoding? One hot encoding is when the data is categorical data is not ordinal, it's nominal. This process is effectively one hot encoding for multi-class data. Then we have the class order. The order of the columns in the output matrix y underscore bin matches the order of the classes you provide to the function. Then we have binary versus multi-label. It's important not to confuse this with multi-label classification, where a single sample can belong to multiple classes simultaneously. Multi-label, you are very clear? So for true multi-label problems, you would use the multi-label binarizer class, not the neighbor normal label underscore binarizer class. Alternate, the Scikit-learn preprocessing label binarizer class provides the same functionality but with fit underscore transform method for use within the Scikit-learn pipeline. Clear? So this is binary classification and this is multi-class. And what do I mean by binary comparison? Since there are three classes over here, first the red one will be compared with the black one, then the red one with the blue one, and then the black and blue ones are compared. Got it? But the approach which is used, that was it talking about one versus all in binarize, label underscore binarize is that if I want to do the comparison of green with other classes, I will take them as the green and all other belonging to one class. Clear? Then I'll take another class square and all other belonging to one class. Is the approach getting clear? The difference between one versus all and one versus rest with one versus one classifier? Is the difference between the two clear to everybody? And then we have the multi-label classification, multi-output classifier over here, and multi-output regression. Getting my point? So till now we have implemented two algorithms, naive-Bayes classifier and KNN. Naive-Bayes classifier performed better than KNN, but very good point was pointed out that if we could hypertune the parameter, we did not hypertune the K parameter, then the results would have been better. Right? Agreed? Can we move forward again on 4.2 file? Yeah. Now let's apply decision tree classifier again on the same online training data. So what is this code doing? Importing the library. Second is creating the object of the model. Calling the function or creating the object of decision tree classifier. Third step, training the model with input as well as the output training data. Then we are predicting on the testing set. Clear? So now let's check the class order. So it says that x underscore train sc is not defined. So I'm not running the previous code. It is nothing but the standardized input, right? You all remember? So now do you see how well this has performed? This is fine, but this is the wrong conclusion, right? And the probability is coming out to be perfect for median, but here it is high. This one is wrong. Rest everything it is, classifying correctly, right? So what are we observing as the output in decision tree classifier? What output can we observe in the decision tree classifier? The model is overfitting. Why, Atul? Why is it overfitting? So how can we check the overfitting in a decision tree? Right? So how can we, cross-check this training accuracy or improve this overfitting model in decision trees? By doing cross-validation. By doing cross-validation, can we do that? So the training accuracy combined with So when we have a training accuracy combined with slightly lower testing accuracy, typically points towards the overfitting scenario that we all are understanding. In practice, this might mean that the decision tree has complex branches that perfectly classifies the training data but slightly misses when predicting new or unseen data. Adjustments such as pruning the tree, like dealing with hyperparameters, setting a maximum depth, increasing minimum samples required for a node, split might help in reducing overfitting and improving models generalization. So, does cross validation also help in checking the model just memorizes the training data or if it generalizes well overall unseen data? Is cross validation also a better way to check? Yes, it is. Please try to understand. Cross validation is also one of the ways to check. So when I take the mean of cross validation, it is coming out to be almost same as the accuracy of testing, 82.8%. And this is also coming out to be 82.8. So that means it is not learned the data. The data is like that it has learned it very well during the training. It is not just memorize the training data or if it generalizes well over the unseen data. Clear? So the cross-validation scores vary slightly but generally remain high with a mean cross-validation score of 0.82%. This indicates good model performance and stability. Getting my point? So if I look at the classification report, it is 80%, 83 to 82%. So the confusion matrix and classification report show that while the model performs well overall, there are some misclassifications. Agreed, learners? Right? So which was one of the best results? Naive-Bayes bias classifier was giving you one of the best results. Agreed? Now we will understand one more important concept of decision trees, that is random forest. What does the term forest mean? It is a group of trees, right? What does that mean? That rather than using a single tree for predicting the output, we will use a group of trees to judge the output. Getting my point? Right? So now with this approach, let me explain you tomorrow's foundation. We would be moving on to ensemble learning method. That is, rather than taking output from 1D, we will combine the output of many trees. And will it, do you think, it's going to overall improve the results? Yes, of course. So how do we go about it? That if this is my data set, I will randomly divide it into different features randomly divided into different samples. The original, let me put it again. The original data set gets divided into different samples, random samples. From the first sample, I create a tree one, check its output. Then from the second sample, I create another tree and I can create n number of trees. And then getting the output of everybody and then take the average or the majority voting to predict the final class. Clear? Are you understanding the concept of random forest now? So to address the limitations observed with the decision tree, we can transition to using a random forest model. Random forest is an ensemble method, right? So there is one more topic in classification that is still left. How do we deal with imbalanced class? We'll just start after we finish this particular file. After finishing that ensemble model, maybe we will not be able to complete it fully, that we will take it up tomorrow also. After that, Tomorrow we will take up ensemble learning method. Very, very important. It covers certain concepts of deep learning also. So I request you to be present to follow the class, because tomorrow we would be touching up into calculus, a little higher concepts that will be required in deep learning also. Clear? So we can transition to using random forest model. Random forest is an ensemble method, builds multiple. What is the concept? It builds multiple decision trees and combines their predictions to improve performance and reduce overfitting. So what are the benefits of random forest? It reduces overfitting. Averaging the results of multiple decision trees reduces the risk of overfitting seen with a single decision tree. It improves generalization. The combinations, predictions from the multiple trees enhance the model's ability to generalize to new unseen data. More robust predictions, random forest is more robust to noise, variability in the training data. Clear? So how do we go about it? It's not difficult. Simply, we will, like we did the decision tree classifier, we will create the object or the model of random forest classifier and then fit it and then predict the output. Great. So my code has run. And now if I see it, again, I get only one wrong answer over here. And now what do you observe? The testing accuracy has improved, but is it overfitting? Again, we can cross-check. It's not overfitting. It's due to cross-validation. So this is 90%, 91%. Overall, giving you better accuracy than the decision tree. Agreed? Okay. So the random forest model shows perfect accuracy on both the training as well as testing sets, indicating that it has classified all instances correctly. The confusion matrix for the random forest model shows perfect classification for all classes with less misclassifications. The decision tree had a few misclassifications, particularly one misclassified instance in medium and low. Given the perfect performance of the random forest model on this data set, further hyperparameter tuning might not be necessary. I hope, Ajay, you got the answer. Given a perfect performance on random forest model on the data set, further hyperparameter tuning is not required. However, for more complex data set, hyperparameter tuning could further optimize the model performance. So, if you feel that the data set is more complex, you can, work on the depth, work on the number of splits, then it could even give better results or better performance. Got it, learners? So over here now, multi-class. So what difference did you find out? Was there any difference in the code? Whether we were applying, KNN algorithm on binary or multi-class? No, there was no difference. The same logic, same libraries were imported, same this thing, but classification report and confusion matrix were giving me based on the 3 outputs. If they are 4, then it would give me 4 by 4 confusion matrix. Right? Now let's understand multi-label classification. This particular classification is, comes under the category of deep learning, right? Because it generally talks of images, generally talks of text categorization, movies. So multi-label classification is not covered under machine learning. It's generally covered as part of deep learning. All right, learners. So multi-label classification allows us to classify additional knowledge. What does that mean, Ajay? Deep learning is required, which is a separate course where you cover multi-label classification, not under this course. Okay, Ajay? I'll just make the point more clear. So it allows us to classify data sets with more than one target variable. There are several labels for the output of a given prediction, and making predictions. A given input may belong to more than one label. So example is text categorization, new article classification. A new article might belong to multiple categories such as politics, economy, and health. So when I talk about the concept of text categorization, it does not come under the domain of machine learning algorithms, right? It comes under the category of NLP. Getting my point? So NLP is only after deep learning. So multi-label, the classifier can tag each song because text has to be understood. Tagging question answers in QA platform, again, it is based on text, so NLP. So a single question might relate to multiple topics such as Python, data science, machine learning. So a multi-label classifier can automatically assign all relevant tags to each question posted on the platform. Got it? And below, additional resources are there like deep learning for multi-label learning, comprehensive comparative study of multi-label classification methods, and multi-label classification with transformer. So they all come under the category, right? But multi-class classification and binary classification, almost same methods are being used, whether you are using the same algorithm. No difference in the steps. Got it, learners? 4.2 file is clear. So classification techniques are integral to understanding and predicting categorical outcomes based on features, right? In this comprehensive exploration, you have delved deep into the realms of multi-class and multi-label classification, employing data sets such as online gaming behavior, data set to anchor your learning in the real-world context. You have become familiar with essential classification algorithms, including naive Bayes, KNN, decision trees, and random forest, observing the applications across different scenarios. So can I do a quick knowledge check with you all? First question, what is the goal of decision tree algorithm during training? Yes, we want to minimize the impurity. C will be the correct answer. Well, all are correct, but I think so more relevant term to trees is impurity. The goal of support vector machine is to find the optimal separating hyperplane which minimizes the margin of the training data. True or false? Minimize or maximize? Of course, we want to maximize the margin. The term kernel in SVM refers to, is it a hyperparameter? Yes, it is, but it is generally known as what? Transformation function. It is a hyperparameter, but kernels are also known as transformation function. Getting my point? Which of the following statement is not true about hyperplane in SVM? That if we select a hyperplane which is close to the data point of one class, then it generalizes. All others are true. A hyperplane is very close to data point, its margin will be small. Okay. If the hyperplane is far, the margin will be large. Optimal hyperplane will be the one with the biggest margin. Got it? In supervised learning, the training data set consists of input as well as output labels. What is the main objective of classification algorithm in supervised learning? It is C, assign input data to the predefined categories or classes. What is logistic regression used for? Due to the sigmoidal curve output. Which classification algorithm assumes independence among features and calculates the probability of a sample belonging to a certain class using Bayes theorem or Bayes theorem? It is B. Which machine learning technique is primarily used for classification tasks and involves dividing the data into distinct categories. So we've done only one of them. So you know already it is decision tree only. Rest regression is only for numerical data. It cannot be for categorical data, right? KNN classifier assigns the majority class of k nearest data points, right? What is the process of scaling features so that they have mean equal to 0 and standard deviation equal to 1? That's known as standardization. Which supervised learning algorithm uses hyperplanes to separate the classes? Yes, it is SVM. Okay. All right, I think so. That was quick revision. Okay, now let's start understanding handling of imbalanced data set. What do we mean by imbalanced classes? What do you observe in this particular slide? Yes, learners. Yeah, 1 hour more to go to finally. Let's complete this topic as much as we can. So what do you mean by imbalanced data set or imbalanced data in classification? We see that the orange class has more of the majority points as compared to the cyan point. So this is known as the major class. Yes, the samples or the classes are of different sizes, not the sample. Sample is the part of the data. Here we will say the classes are of different size. The class with maximum data point is known as a majority class, and a class with minimum number of point is known as a minority class. So again, an imbalanced data set have many more instances of certain classes, not samples, okay, than of others. Getting my point? Right? So now do you see this? So how do you try to make, imbalance classes, majority, minority classes the same? How do you go about it? One of the ways, either reduce the majority class to minority or convert the minority classes to majority, right? This is one of the ways we can do. Yes, or I add more weightage to this particular class as compared to the majority one. Adding weightage to classes also makes the balance equal. Right, so few terminologies that needs to be understood. So the points which are less in number are known as minority data points. Points which are large in number are majority data points. If the minority data point is present in majority, that becomes the noise sample. Safe edges samples are those which are clearly, belonging to the minority class or the majority class, and safe inner samples which belong to the inner points of the class, and some belong to the borderline sample, right? So why? What is the problem dealing with imbalanced data set? That is the question. What is the problem in dealing with imbalanced data set? Yes, learners. Model will predict an output only by majority, not from the true learning. Yes, it can get biased towards the majority class, right? So it is up to us as a data scientist, machine learning expert to create that balance. The output should not be biased. Okay. So the conventional model evaluation methods do not accurately measure the model performance when faced with imbalanced data set. So which of the metric of confusion matrix should not be used in imbalanced data set? Which of the metric should not be used in imbalanced data set? So the standard classifier algorithms like the decision tree or the logistic regression have a bias towards classes which have more number of instances. They tend to only predict the majority class data. The features of the minority classes are treated as noise and are often ignored. Thus, there is a high probability of misclassification of the minority class as compared to the majority class. Right? So, what are there are three challenges, three problems faced when we talk about imbalanced data set. First is the bias models. Machine learning models optimize balanced metrics or functions by default. Hence, imbalanced data can lead to biased training models that tend to predict the majority class more accurately while neglecting the minority class. So what is the other issue? This can result in high false negative rate while minority class is misclassified as a majority class. Got it? Second issue is skewed class distribution. Imbalanced data shows a skewed class distribution where the majority class dominates the data set, and this can lead to lack of diversity in the data and make it difficult for model to learn the underlying patterns of the minority class. Getting my point? And the third is the differing cost of misclassification errors. Another challenge with imbalanced data is that misclassification errors can have varying costs depending on the application. For example, a false negative can be life-threatening in medical diagnosis, while false positive may cause inconvenience. Got it, learners? So imbalanced data set is clear. It can be due to oversampling, due to adding more features, use class weights, undersampling are the different methods to deal with imbalanced data set. So an imbalanced data set is a data set where each output class or target class is represented by different number of input samples or data points. Okay. Oversampling is one of the technique to solve it. What is oversampling? Increase the number of samples of the smallest class up to high size of the biggest class. How this can be done? This can be done by generating synthetic samples. SMOT is one of the technique that we will understand. Undersampling is another technique that we would be using. We decrease the number of samples of the biggest class down to the size of the smallest class. Remove some samplers from the biggest class. Other way is class weights, assign weights to each class so that the weights of the two classes or this thing can be balanced. Then we have the decision threshold. If a predicted value is greater than the threshold, it is set to 1, otherwise it is set to 0. Getting my point? So what is resampling? You can change the data set that you use to build your predictive model to have more balanced data. This change is called sampling your data set when there are two main methods you can use to even up the classes. One is oversampling. Oversampling consists of creating synthetic data for the underrepresented, right? Or formally sampling with replacement. Do you understand? So what does sampling with replacement mean? That suppose there are 10 red balls and green mixed balls. So what do? You take a sample of 3 balls, then you keep it back, then you take another 3 samples of ball, another 3 samples of ball. So whatever sample you are taking, you put it back and then take it out another, right? And what is undersampling? You can delete the instances from overrepresented class called undersampling. Yeah, that's exactly like probability questions you might have done, right? So undersampling, what are the issues with undersampling? Can you tell me? When the majority class is made of the same size as minority, what are the issues with undersampling, learners? Yes, they can be loss of information. What could be the problem? They can be loss of information in the data. And when I talk about oversampling, what is the issue with oversampling? Noisy data, unnecessary data can also get added in the while we are creating the synthetic data, right? Agreed, learners? Synthetic data will not represent the real world data. We may have bloated information. Could be, yes. But still we use these techniques, right? Because we want to ultimately make the data set balanced. So when we are talking about oversampling, we use the SMOTE technique, that is synthetic minority oversampling technique, right? So SMOTE refers to synthetic minority oversampling technique. SMOTE consists of synthesizing elements for the minority class based on those that already exist. It works randomly picking a point from the minority class and computing. So it works little bit on the concept of k nearest neighbors for this particular point. The synthetic points are added between the chosen point and its neighbors. Clear? So how do we go about it? Suppose these are my two classes and I want to make the classes balanced. So now based on the nearest neighbors, I will create the synthetic data points. The green data points are being created. So the algorithm which runs at the back end is that if this is my data, S is the minority class, N is the total number of synthetic samples to be generated, K, how many neighbors to consider. So it is again based on K and N. So synthetic data is S synthetic, considered to be null. We will run from 1 to N, randomly select a sample from S, randomly select one of its neighbor, and then put it onto the synthetic data. Now you are understanding why sampling with replacement. So you take the sample, you put it back into the data again, try to take out another new sample, right? So how do we go about it? Let's see by an example. If 2, 1 is my original sample and the neighbor is 4, 3. So how can I create a new sample or a synthetic data? Maybe in between these two samples. So 2 minus 2, 1 minus 0 0.4 into 2, 1 minus 4, 3. Why are we using this 0.4? S plus U, Z minus S. U is the uniform random value that we choose from 0 to 1. Are you understanding this particular formula? We are using exactly this. This is my original, this is the neighbor. U is a uniform random value chosen between 0 to 1. So over here I have chosen 0.4, 2, 1 minus 4.3. So this is the value I get, and my new sample, synthetic sample value comes out to be this. So it will not be exactly like 2, 2. No, we will generate it randomly, right? Because randomness is one of the very important features of data. Is this point getting clear? Are you understanding the algorithm? How the synthetic data is getting generated? Right? So we are trying to take an example case of k equal to 4. Where generally, we do not take k is equal to 4 because it's an even number. But okay, this is my x1 1 point, x1 2 point, x1 3 point, and x1 4 point. And I'm trying to find out the difference or the radius between this x1. So r1 is equal to x1 plus gap into the difference. Same formula, but done it in the different way. Same formula. Are you understanding how the synthesized data gets generated? So what is the advantage of oversampling? It improves performance, balances the data set. It's not limited to specific machine learning algorithm, easy implementation. But when we talk about disadvantage, it increases computational complexity, not suitable for all data sets, incompatible with regression problem. It can lose the subtitles of the original data also. And if I talk about undersampling, undersampling is randomly removing the imbalanced data set. Okay, so this is my imbalanced data set. Green points represent my majority class Red triangle represent my minority class. And finally, I get a random undersampler data set. So now let's get back to the code part of it. So the final file, that is 4.3. So handling of the imbalanced data set is crucial because it leads to skewed databases, incorrect results, and can lead to favorite majority classes, leading to poor performance in identifying the minority class. Therefore, we need to deal with imbalanced data set. Now, in real time, in real life problem, do you think imbalanced data set should exist? Try to understand the example given. Imbalanced data set should exist, especially if I'm talking about, the ratio of a country, city with healthy and non-healthy people. Do I want that ratio to be balanced? No, not at all. I want healthy people to be maximum and non-healthy people to be in the minority group. This is what actually we want in the data set or not. People who are smoking to non-smoking. We want non-smokers more than the smoking category of the people. Sometimes we want that imbalanced data set. Getting my point? Healthy versus junk food. We want more people to eat healthy food as compared to junk food. Getting my point? Yes or no? Or do we feel that all data should be absolutely balanced? This is what we were thinking till now. Or every data should be 50-50. Yes or no? Yes, in male-female ratio, yes, it should be 50-50. Neither the male should be more nor the female should be more. But in some cases, we want the distribution to be imbalanced. Right, learners? So what are the applications of handling imbalanced data set? Medical diagnosis system. Of course, we want healthy more than unhealthy. Fraud, less fraud as compared to normal. Spam detection to be much lesser than the original data. Right? Are we understanding these example, learners? Medical diagnosis, fraud detection, spam detection. So before diving techniques into handling imbalanced data, it is important to first understand how to determine if your data is balanced or imbalanced. So which graph will give me balanced and imbalanced data set? Well, this is a pie chart, scatter plot. I think so. Lot more graphs can give you that it is a balanced or an imbalanced data set. Getting my point? All right, so now we are talking about a data set about credit card transaction, right? This data set consists of credit cards by a European company in September 2013. It contains only numerical input variables where each results are of PCA transformation. Unfortunately, due to confidentiality issues, original features and more background information about the data is not available. So features V1, V2, V8 are the principal components obtained with PCA. The only features which have not been transformed with PCA are time and amount. So other data are being hidden due to confidentiality, but time, amount, and class, that is the target variable, is not hidden, right? So what do you think? The fraud transaction should be much lesser than the all non-fraudulent transactions, right? Okay. So first thing that you need to do is please import this, run this particular command, pip installed imb balance learn. This particular library is required to learn for imbalanced data set. So now if we look at this particular data set, it consists of 2000 rows. So it consists of 2000 rows and about quite a lot of columns, 31 columns, where class is my output, amount is again my input, all others are like they have been hidden due to confidentiality. Okay. Simple, data set is simple to understand. And if I look, is it imbalanced? Is it an imbalanced data set? Yes. Non-fraudulent transactions are 1974 and fraudulent transactions are only 26, less than even 1%, around 1% of it. What is 1% of 2000? 1% of 2000 is 200. So it's like even less than that, 0.1%. Right? And if I look at through two graphs, one is the count plot or the bar graph. I see a major difference. Two graphs are also getting clear. First, I am using the distribution plot bar graph with different colors. And in the other one, I am using the pie plot. Do you see the imbalance in the data set? What do we observe? So the data set is highly imbalanced with nearly 2000 non-fraudulent transactions, only around 25 fraudulent ones. Significant imbalance needs to be addressed to avoid bias models and ensure fair and accurate predictions. Using this data set for classification has following disadvantage that it can be biased towards non-fraudulent data and can also give you misleading results. That we are very clear. Now let's understand the techniques to handle imbalanced data set. One is oversampling technique that we will use the SMOT. Undersampling technique, randomly removing the data. Are we also clear in these two techniques? How are we going to handle imbalanced data set? In my field, we mostly deal with these kinds of data set. And another technique that we will use is ensemble methods for imbalanced data is balanced random forest. Condition for use effective when leveraging an ensemble approach. As I've told you, tomorrow we'll start with ensemble approach to maintain robustness and generalizability while addressing the class imbalance. Clear? For oversampling, the condition for use is ideal when minority classes severely underrepresented, as in this case. Undersampling, useful when data set is large enough, and removing instances won't result in significant loss of information. So that concepts, I think so, we all are very much clear. Oversampling is a technique to balance the class distribution by increasing the number of minority class sample. This can be done by duplicating existing samples or creating synthetic ones. Okay. So now let's understand the SMOT, synthetic minority oversampling technique. More advanced method that generates new synthetic samples from minority class. First, it selects random minority class sample. Depending on the random k nearest neighbors, depending on that, it generates the formula. Advantage of SMOT is that definitely it prevents overfitting of the data. Unlike simple duplication, SMOT generates new sample while helps in creating more generalizable model. Balances the data set by creating new samples. SMOT helps balance the class distribution, improving the model's ability to learn from minority class sample. So here we go with the practical implementation. So which library is new for us? imblearn is a new library in which we are importing the SMOT technique. Otherwise, all others are the same, right? Upload the data set, separate the input and the output features. That's it's done. Then the split can be done and standardization. And now let's first plot the imbalanced data set. So just imagine, the orange, the yellow ones are your fraudulent data and purple ones are your non-fraudulent data. Agreed, learners? Do you see this? Are you all able to observe this imbalanced data set? We are using the scatter plot now. So the color of each data point indicates the class it belongs to. The color scale on the right shows the gradient from purple to yellow, where each color represents a class label. They are predominantly purple points indicating a majority of data points belong to class 0, yellow points indicating they belong to close to class 1, which are fewer in comparison. So now when I apply the smooth technique, learners, are you there? Simply you have to call the smooth function and create a smooth object, and then ultimately fit resample on the training input and output data to get your more smooth examples, right? So now do you see we had X trains smooth. So earlier they were 2000 samples. Now we have 2364 samples and 1200 in the output training data also. Is this point getting clear to everybody? Right? So earlier my class distribution was this much. Now it is 2364 versus 1200. So now if I see the output, do you think it's more balanced? Definitely the yellow points are almost similar to the purple points now. Agreed? So what we can see clearly that the data is more balanced after applying the smooth technique. Then we train and evaluate and predict on the training data set. So what do you observe? What do you observe on the training and the test accuracy? Almost same. Almost same. Can we say that? It has classified it correctly now? Yeah. Close to, yeah, good fit. It's close to good fit, right? So the decision tree classifier, when trained on smooth, balanced data set, achieved high accuracy on both training, 99.4%, testing 98% sets, indicating strong model performance. However, the slight drop in text accuracy compared to train accuracy suggests some overfitting. The model generalizes well but may still benefit from further tuning or validation techniques. Agreed, learners? And now if I look at the confusion matrix, one of the error is 0, another one is high. One error is high. Right? The methods, methodologies, everything remain the same. What kind of model you are going to apply remains the same. Only that before, applying the data points, you will use the smooth technique so that you balance out the data. Clear? This is where you will do. And what do you observe in the classification report? So it clearly shows that 0 is giving you more higher accuracy, and the synthetic data which has been generated is only giving you 57%. Clear distinction is you can see in the F1 score as well as in the overall macro as well as weighted average. And now if I create the ROC AUC curve, let's see how much area. Oh, it's giving me perfect 1. That means the two classes of, even after creating synthetic data, the two classes are being classified very, very correctly as fraudulent and non-fraudulent classes. Right, learners? Can we move on to the undersampling technique, learners? Here, there is no algorithm or any other technique. We will just randomly remove the data from the majority classes. Got it? So undersampling is an opposite of oversampling. It involves reducing the number of samples in majority class to balance the data set. This can be done by randomly removing samples or using more sophisticated techniques. So here we will be using grid. So random undersampling is one of the simplest undersampling techniques. How random undersampling works? First, it identifies the majority and the minority classes. First, identify which class is overrepresented, majority class, which one is underrepresented. Randomly select and remove samples from the majority class until the samples in each class is balanced or same. So if you have 1,000 samples in the majority class and 100 in minority, you might randomly remove 100 samples from majority class. Resulting data set, the resulting data set will have more balanced distribution of class with a reduced number of samples from the majority class. Got it? So what are the advantages? Simple and easy to implement, reduces training time. Disadvantage, we are also very clear, loss of information or can lead to overfitting. Clear? So now we will use the same data set and train test split for applying these data balancing techniques and fitting the classification model. Then again, let's import the undersampling random undersampler for the IMB-learn library. Done. I hope everybody's code is running now, especially the imbalanced dataset library. And which is the function that we are using? Random undersampler. What is the use of this random underscore state 42? Yeah, controls the same randomness and splitting. And then I am doing an undersampler.fit resample and passing the scaled data points. And now when I plot it, my majority class gets reduced to minority class. Now do you see the purple points have reduced to yellow points? Right? So we can see the data is more balanced after applying random undersampling, but the data points are less. So now we can again initialize and train the decision tree classifier on the undersampled training data, predict on the training data and the testing set and calculates its accuracy. So now what do you observe? Good fit, underfit, overfit. So it seems like overfitting, training accuracy equal to 1. So how do we? It seems like, Ajay, we have to cross check it. So the training accuracy of 1 indicates that the model has perfectly learned or memorized the training data set. It can correctly predict the outcome of every sample it was trained on. This could be the sign of overfitting, not always overfitting, but could be sign of overfitting. But how do I check this? Using technique like k-fold cross-validation to assess model performance. Please be clear with this particular point. This can be a question of asked in your interviews that when you get the train accuracy equal to 1, does it actually mean it is overfitting? No, not necessary. It is a sign of overfitting, but it can be cross-checked with the help of cross-validation technique. So this helps to ensure that the model's performance is robust across different subsets. So now, can I also use the IMB pipeline technique? Why IMB pipeline technique? What is the use of pipeline? It is specifically designed to handle imbalanced data set by integrating resampling methods directly into the pipeline. So the imbalanced library also has this pipeline function, then model selection. Now, say why are we using stratified k-fold over here? Maybe it looks overfitting only in that particular split. CV and shows. Yes. What is the concept of what is stratified k-fold? Cross-validation technique. Yes, learners. It's used for classification problems. So what does it do? That if I have an imbalanced distribution, it tries to split each group into that same proportion. Yes, we try to split in different, folds the same ratio. We try to keep it the same ratio for males and females. So this is round 1, round 2, round 3. So keeps the distribution of the classes in each fold the same. So now we are using the pipeline method. Pipeline where we want to first do the standardization. Then I want to use a random undersampler. And then finally the decision tree classifier. Okay. And once my pipeline has been created, then I will use the stratified k-fold because it's a classification problem. Number of splits as 5, shuffle is equal to true, random state is 42. And now if I check the cross validation accuracy, it is 87%. So it was here 80, cross validation is giving you 87%. And now do you see, look at the difference in the output. A clear distinction in the F1 score is there. You see that, learners? Because the ratio is very different. Similarly, I'm not even getting this as 50. So what we can conclude? What are the observations? In situations where the data set is highly imbalanced, the ROC curve can give an overly optimistic assessment of the model, since it is still highly imbalanced. This optimism bias arises because the ROC curve false positive rate can become very small when the number of actual negatives is large. As a result, even a larger number of false positive would lead to a small false positive rate. So how do we overcome to this problem? Rather than using ROC AUC curve, can you tell me in ROC AUC curve, what is there on the X and Y axis? Can you all tell me in ROC AUC curve, what is there on the X and Y axis? Yeah, true positive rate and the two, it was TPR. But for imbalanced data set, we will try to create an AUC ROC AUC curve between precision and recall. That is why it is known as AUC PR curve, because it is between precision and recall, which is especially useful when positive classes is rarer and more relevant. Getting my point? Why are we now not using the AUC, the XY true positive rate and the false positive rate? So now from the Scikit-learn metrics, when I import precision and recall curve, average precision score, and now predict the output, and instead of the ROC AUC curve, I will use the precision recall curve to get the value and then see the curve. You see this? So the area under the curve is coming out to be how much? 4.938%. Getting my point? So the curve starts with high precision value of 1 and the recall is near 0. This indicates that a very low threshold setting where the model predicts only the most confidentially positive samples are positive, it does so correctly. As recall increases slightly, the precision drops sharply to a low value close to 0.2 and remains nearly constant across the rest of the recall range. This is a characteristic of a model that after a certain point begins to classify more and more negative samples. So ultimately, this nearly flat and low precision across most of the recall range suggests that the model suggests to discriminate between positive and negative classes effectively as it attempts to increase the recall. Okay. And last but not the least is the ensemble method, where we try to create a balanced forest data set.
In this session, we will cover all the important supervised and unsupervised learning algorithms that are widely used with hands-on demonstrations in Python. Our instructors with rich experience in machine learning will take us through this course. But before we begin, make sure to subscribe to the Simplilearn channel and hit the bell icon to never miss an update. So we will start by understanding the basics of machine learning from a short animated video, followed by the difference between supervised and unsupervised learning. We will then jump into learning the various algorithms from scratch. So we will understand linear regression, logistic regression, decision tree, and random forest. We'll then look at support vector machines and k-nearest neighbor algorithm with a hands-on demonstration in Python. Finally, we'll get an idea about unsupervised learning algorithms such as k-means clustering and principal component analysis. We will conclude this session with regularization in machine learning. So let's get started.
We know humans learn from their past experiences, and machines follow instructions given by humans. But what if humans can train the machines to learn from their past data and do what humans can do and much faster? Well, that's called machine learning. But it's a lot more than just learning. It's also about understanding and reasoning. So today, we will learn about the basics of machine learning. So that's Paul. He loves listening to new songs. He either likes them or dislikes them. Paul decides this on the basis of the song's tempo, genre, intensity, and the gender of voice. For simplicity, let's just use tempo and intensity for now. So here, tempo is on the x-axis, ranging from relaxed to fast, whereas intensity is on the y-axis, ranging from light to soaring. We see that Paul likes the song with fast tempo and soaring intensity, while he dislikes the song with relaxed tempo and light intensity. So now we know Paul's choices. Let's say Paul listens to a new song. Let's name it as Song A. Song A has fast tempo and a soaring intensity, so it lies somewhere here. Looking at the data, can you guess whether Paul will like the song or not? Correct. So Paul likes this song. By looking at Paul's past choices, we were able to classify the unknown song very easily, right? Let's say now Paul listens to a new song. Let's label it as Song B. So Song B lies somewhere here with medium tempo and medium intensity. Neither relaxed nor fast, neither light nor soaring. Now can you guess whether Paul likes it or not? Not able to guess whether Paul will like it or dislike it? Are the choices unclear? Correct. We could easily classify Song A. But when the choice became complicated, as in the case of Song B, yes, and that's where machine learning comes in. Let's see how. In the same example, for Song B, if we draw a circle around the Song B, we see that there are 4 votes for like, whereas 1 vote for dislike. If we go for the majority votes, we can say that Paul will definitely like the song. That's all. This was a basic machine learning algorithm also. It's called k-nearest neighbors. So this is just a small example in one of the many machine learning algorithms. Quite easy, right? Believe me, it is. But what happens when the choices become complicated, as in the case of Song B? That's when machine learning comes in. It learns the data, builds the prediction model, and when the new data point comes in, it can easily predict for it. More the data, better the model, higher will be the accuracy. There are many ways in which the machine learns. It could be either supervised learning, unsupervised learning, or reinforcement learning. Let's first quickly understand supervised learning. Suppose your friend gives you 1 million coins of 3 different currencies, say 1 rupee, 1 euro and 1 dirham. Each coin has different weights. For example, a coin of 1 rupee weighs 3 grams, 1 euro weighs 7 grams and 1 dirham weighs 4 grams. Your model will predict the currency of the coin. Here, your weight becomes the feature of coins, while currency becomes their label. When you feed this data to the machine learning model, it learns which feature is associated with which label. For example, it will learn that if a coin is of 3 grams, it will be a 1 rupee coin. Let's give a new coin to the machine. On the basis of the weight of the new coin, your model will predict the currency. Hence, supervised learning uses labeled data to train the model. Here the machine knew the features of the object and also the labels associated with those features. On this note, let's move to unsupervised learning and see the difference. Suppose you have cricket dataset of various players with their respective scores and the wickets taken. When we feed this dataset to the machine identifies the pattern of player performance. So it plots this data with the respective wickets on the x-axis while runs on the y-axis. While looking at the data, you will clearly see that there are 2 clusters. The one cluster are the players who scored high runs and took less wickets, while the other cluster is of the players who scored less runs but took many wickets. So here we interpret these 2 clusters as batsmen and bowlers. The important point to note here is that there were no labels of batsmen and bowlers. Hence, the learning with unlabeled data is unsupervised learning. So we saw supervised learning where the data was labeled and the unsupervised learning where the data was unlabeled. And then there is reinforcement learning, which is reward-based learning, or we can say that it works on the principle of feedback. Here, let's say you provide the system with an image of a dog and ask it to identify it. The system identifies it as a cat. So you give a negative feedback to the machine saying that it's a dog's image. The machine will learn from the feedback, and finally if it comes across any other image of a dog, it will be able to classify it correctly. That is reinforcement learning. To generalize machine learning model, let's see a flowchart. Input is given to a machine learning model, which then gives the output according to the algorithm applied. If it's right, we take the output as a final result. Else, we provide feedback to the training model and ask it to predict until it learns. I hope you've understood supervised and unsupervised learning. So let's have a quick quiz. You have to determine whether the given scenarios uses supervised or unsupervised learning. Simple, right? Scenario 1. Facebook recognizes your friend in a picture from an album of tagged photographs. Scenario 2. Netflix recommends new movies based on someone's past movie choices. Scenario 3. Analyzing bank data for suspicious transactions and flagging the fraud transactions. Think wisely and comment below your answers. Moving on, don't you sometimes wonder, how is machine learning possible in today's era? Well, that's because today we have humongous data available. Everybody is online, either making a transaction or just surfing the internet, and that's generating a huge amount of data every minute. And that data, my friend, is the key to analysis. Also, the memory handling capabilities of computers have largely increased, which helps them to process such a huge amount of data at hand without any delay. And yes, computers now have great computational powers. So there are a lot of applications of machine learning out there. To name a few, machine learning is used in healthcare, where diagnostics are predicted for doctors' review. The sentiment analysis that the tech giants are doing on social media is another interesting application of machine learning. Fraud detection in the finance sector, and also to predict customer churn in the e-commerce sector. While booking a cab, you must have encountered surge pricing often, where it says the fare of your trip has been updated. Continue booking? Yes, please, I'm getting late for office. Well, that's an interesting machine learning model which is used by global taxi giant Uber and others, where they have differential pricing in real time based on demand, the number of cars available, bad weather, rush hour, etc. So they use the surge pricing model to ensure that those who need a cab can get one. Also, it uses predictive modeling to predict where the demand will be high, with the goal that drivers can take care of the demand and surge pricing can be minimized. Great! Hey Siri, can you remind me to book a cab at 6 p.m. today?
Okay, I'll remind you.
Thanks.
No problem.
Comment below some interesting everyday examples around you where machines are learning and doing amazing jobs. Hi guys, this is Apeksha from Simplilearn, and we are going to talk about the two types of machine learning, supervised and unsupervised learning, their types and applications. But before we talk about them, let's quickly understand what is machine learning. These days, applications use artificial intelligence in machine learning to optimize speech recognition. I usually ask Siri things I want to know, like, hey Siri, how far is the nearest subway? So whenever we ask something to Siri, a powerful speech recognition kicks off and converts the audio into its corresponding textual form, which is then sent to the Apple servers for further processing. Then, neural language processing algorithms are run to understand the user's intent. And then finally, Siri tells you the answer. Well, this is what machine learning is all about. Making the machines learn and act like humans by feeding them with data and information without being explicitly programmed. As we saw in the previous example, when the data comes in, machines immediately starts analyzing the data and eventually gets trained on it and learns it. Now, when a new data point comes in, machine accurately makes prediction and decisions based on the past data. Now that you know what is machine learning, let's talk about supervised and unsupervised learning. Supervised learning, as the name suggests, works under supervision. That is, it's a learning in which machine is trained with data which is well labeled, and then it predicts with the help of the labeled dataset. But what is a labeled dataset? Data for which you already know the target answer is called a labeled data. Like I show you an image and tell you that it's a dog, then it's a labeled data. While if I show you an image without telling you what exactly it is, then it's an unlabeled data. Now let's say we have images which are labeled as spoon or knife. We then feed it to the machine which analyzes and learns the association of these images with its labels based on its features such as shape, size, sharpness, etc. Now, when a new image is fed to the machine without any label, with the help of the past data, the machine is able to predict accurately and tell that it's a spoon. Hence, in supervised machine learning, the algorithm teaches the model to learn from the labeled example that we provide. So supervised learning can be further divided into classification and regression. It is a classification problem when the output variable is categorical, such as red or blue, disease or no disease, male or female, whereas it's a regression problem when the output variable is a real or continuous value. For example, salary based on work experience, weight based on height, so it creates a predictive model showing trends and data. So now if I say, will I get a salary raise or not? That's classification. But if I say, how much salary raise will I get? That is regression. Now let's understand classification with the help of an example. In order to predict whether an email is a spam or not, first we need to teach our machine what a spam mail looks like. This is done based on a lot of spam filters, like firstly reviewing the content of the email, then review the email header and search if it contains any falsified information. This is done based on some keywords like free, lottery, price claim, etc. Then general blacklist filters to stop emails that come from already blacklisted known spammers, and etc. So all these filters scores the email, which is known as spam score. The lower the total spam score of the email, it is more likely that the email will land in subscribers' inboxes. So based on the content, labels, and spam score of the new incoming mail, the algorithm decides whether it should land in inbox or the spam folder. Now let's quickly understand regression. So let's say we have two variables, that is temperature and humidity, where temperature is the independent variable and humidity is the dependent variable, such that as the temperature increases, humidity decreases. Hence, they are correlated. When we feed this data to a regression model, it will understand the relationship between these two variables and how one variable depends on the other. After the machine is trained, it can easily predict the humidity based on the given temperature. Well, that was about regression. Now, let's see some real-life applications where supervised learning is used. So, supervised learning is used in risk assessment to assess risk in financial services or in insurance domain to minimize the risk portfolio of the companies. Image classification. Facebook recognizes your friend in a picture from an album of tagged photos. So, image classification is one of the key use cases of demonstrating supervised machine learning algorithms. Obviously, a lot more goes into all these, like convolutional neural networks, etc. Fraud detection, whether the transactions made by the user are authentic or not, and visual recognition, the ability of a machine learning model to identify objects, places, people, and actions in images. Now, let's quickly talk about unsupervised learning. In unsupervised learning, there is no supervision, that is, no training will be given to the machine, allowing it to act on the data which is not labeled. Hence, machine tries to identify patterns and gives the response. Let's take a similar example as before, but this time we do not tell the machine whether it's a spoon or a knife. The machine identifies patterns from the given set and groups them based on their patterns, similarities, etc. Again, unsupervised learning can be further grouped into clustering and association. Clustering is basically where the machine forms groups based on the behavior of the data. Secondly, association. It is a rule-based machine learning to discover interesting relation between variables in large datasets. For example, which customer made similar product purchases is clustering, whereas association is which products were purchased together. Now, let's understand clustering with the help of an example. To reduce their churn rate, a telecom company studies the behavior of the customers based on average call duration and internet usage, and observes that while some customers' call duration is quite high, others have heavy internet usage. The customers are grouped based on their observed behavior, and a strategy is adopted to minimize churn rate and maximize profit via suitable promotions and campaigns. As you can see in the chart on the right hand side, customers in Group A uses more data and also have high call duration. Group B customers are heavy internet users, while Group C customers have high call duration. So Group B will be given more data benefit plans, while Group C will be given cheaper call rates to buy their loyalty. So this was the example of clustering. Now let's understand association with another example. Let's say customer 1 goes to a supermarket and buys these products, say bread, milk, fruits, wheat. Then customer 2 goes and buys bread, milk, rice and butter. Now, when customer 3 goes and buys bread, it is highly likely that he will also buy milk. Hence, relationship is established based on customer behavior and recommendations are made. Now, let's look at some real-life applications of unsupervised learning. Market basket analysis is a machine learning model based on the algorithm that if you buy a certain group of items, you are less or more likely to buy another group of items. Semantic clustering. Semantically similar words share similar contexts. People post their queries on websites in their own ways. Semantic clustering groups all responses in a cluster with same meaning to ensure that the customer finds the information they want quickly and easily. It plays an important role in information retrieval, good browsing experience, and comprehension. Delivery store optimization. Machine learning models are used to predict the demand and keep up with the supply. Also, to open stores where demand is more and optimizing routes for more efficient deliveries according to past data and behavior. We can also use unsupervised machine learning models to identify accident-prone areas based on the intensity of those accidents and the area in order to introduce safety measures. By now, I hope you've understood supervised and unsupervised learning. For a quick recap, let's see a few differences between the two. The most fundamental difference is that supervised learning uses known and labeled data, and unsupervised learning uses unlabeled data as their input. Secondly, supervised learning follows a feedback mechanism, while unsupervised learning does not. Also, the most commonly used algorithms in supervised learning are decision tree, logistic regression, support vector machine, etc. And in unsupervised learning, they're k-means clustering, hierarchical clustering, a priori algorithm, and many more.
Welcome to Linear Regression. My name is Richard Kirshner. I'm with Simplilearn. Let's look at an example of a common use for linear regression: profit estimation of a company. If I was going to invest in a company, I would like to know how much money I could expect to make. So we'll take a look at a venture capitalist firm and try to understand which companies they should invest in. So we'll take the idea that we need to decide the companies to invest in. We need to predict the profit the company makes, and we're going to do it based on the company's expenses, and even just a specific expense. In this case, we have our company, we have the different expenses, so we have our R&D, which is your research and development, we have our marketing, we might have the location, we might have what kind of administration it's going through. Based on all this different information, we would like to calculate the profit. Now, in actuality, there's usually about 23 to 27 different markers that they look at if they're a heavy-duty investor. We're only going to take a look at one basic one. We're going to come in, and for simplicity, let's consider a single variable R&D and find out which companies to invest in based on that. So when we take our R&D and we're plotting the profit based on the R&D expenditure, how much money they put into the research and development, and then we look at the profit that goes with that. We can predict a line to estimate the profit. So we can draw a line right through the data. And when you look at that, you can see how much they invest in the R&D is a good marker as to how much profit they're going to have. We can also note that companies spending more on R&D make good profit. So let's invest in the ones that spend a higher rate in their R&D. What's in it for you? First, we'll have an introduction to machine learning, followed by machine learning algorithms. These will be specific to linear regression and where it fits into the larger model. Then we'll take a look at applications of linear regression, understanding linear regression, and multiple linear regression. Finally, we'll roll up our sleeves and do a little programming in use case profit estimation of companies. Let's go ahead and jump in. Let's start with our introduction to machine learning, along with some machine learning algorithms and where that fits in with linear regression. Let's look at another example of machine learning. Based on the amount of rainfall, how much would be the crop yield? So here we have our crops, we have our rainfall, and we want to know how much we're going to get from our crops this year. So we're going to introduce two variables, independent and dependent. The independent variable is a variable whose value does not change by the effect of other variables and is used to manipulate the dependent variable. It is often denoted as x. In our example, rainfall is the independent variable. This is a wonderful example because you can easily see that we can't control the rain, but the rain does control the crop. So when we talk about the independent variable controlling the dependent variable, let's define dependent variable as a variable whose value change when there is any manipulation in the values of the independent variables. It is often denoted as y. And you can see here our crop yield is dependent variable, and it is dependent on the amount of rainfall received. Now that we've taken a look at a real-life example, let's go a little bit into the theory and some definitions on machine learning and see how that fits together with linear regression. Numerical and categorical values. Let's take our data coming in, and this is kind of random data from any kind of project. We want to divide it up into numerical and categorical. So numerical is numbers, age, salary, height, where categorical would be a description, the color, a dog's breed, gender. Categorical is limited to very specific items, where numerical is a range of information. Now that you've seen the difference between numerical and categorical data, let's take a look at some different machine learning definitions. When we look at our different machine learning algorithms, we can divide them into three areas: supervised, unsupervised, reinforcement. We're only going to look at supervised today. Unsupervised means we don't have the answers and we're just grouping things. Reinforcement is where we give positive and negative feedback to our algorithm to program it, and it doesn't have the information until after the fact. But today we're just looking at supervised because that's where linear regression fits in. In supervised data, we have our data already there and our answers for a group, and then we use that to program our model and come up with an answer. The two most common uses for that is through the regression and classification. Now we're doing linear regression, so we're just going to focus on the regression side. And in the regression, we have simple linear regression, we have multiple linear regression, and we have polynomial linear regression. Now on these three, simple linear regression is the examples we've looked at so far, where we have a lot of data and we draw a straight line through it. Multiple linear regression means we have multiple variables. Remember where we had the rainfall and the crops? We might add additional variables in there, like how much food do we give our crops? When do we harvest them? Those would be additional information add into our model. And that's why it'd be multiple linear regression. And finally, we have polynomial linear regression. That is, instead of drawing a line, we can draw a curved line through it. Now that you see where a regression model fits into the machine learning algorithms, and we're specifically looking at linear regression, let's go ahead and take a look at applications for linear regression. Let's look at a few applications of linear regression. Economic growth, used to determine the economic growth of a country or a state in the coming quarter, can also be used to predict the GDP of a country. Product price can be used to predict what would be the price of a product in the future. We can guess whether it's going to go up or down, or should I buy today. Housing sales, to estimate the number of houses a builder would sell and what price in the coming months. Score predictions, cricket fever, to predict the number of runs a player would score in the coming matches based on the previous performance. I'm sure you can figure out other applications you could use linear regression for. So let's jump in and let's understand linear regression and dig into the theory. Understanding linear regression. Linear regression is the statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, remember that from before, and x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield. which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that, we put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle, a good estimate. Here we're going to dig deeper into the math behind the regression line. Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half, you can see where we've broken that down into pieces. And as it goes through the first 2 points, it computes the squared value of x, the squared value of y, and x times y. And then it takes all of x and adds them up, all of y adds them up, all of x squared adds them up, and so on and so on. And you can see we have the sum of equal to 15, the sum is equal to 20, all the way up to x times y, where the sum equals 66. This all comes from our formula for calculating a straight line, where y equals the slope times x plus the coefficient c. So we go down below, and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute, and where that information comes from is called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part, if you read through the brackets, you have the number of data points times the sum of x times y, which we computed one line at a time there, and that's just the 66. And take all that and you subtract it from the sum of x times the sum of y. And those have both been computed. So you have 15 times 20. And on the bottom, we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your c coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1, plus 2.2 equals 2.8, so on and so on. And here, the blue points represent the actual y values, and the brown points represent the predicted y values, based on the model we created. The distance between the actual and predicted values is known as residuals or errors. The best fit line should have the least sum of squares of these errors, also known as e-square. If we put these into a nice chart where you can see x and you can see y, what the actual values were, and you can see y predicted, you can easily see where we take y minus y predicted and we get an answer. What is the difference between those two? And if we square that, y minus y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1, all the way down until we have a summation equals 2.4. So, the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least e-square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, x and y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic, multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have y equals m1 times x1 plus m2 times x2, so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that and we're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import NumPy as NP. And then I want you to skip one line and look at import Pandas as PD. These are very common tools that you need with most of your linear regression. The NumPy, which stands for NumPy, is usually denoted as NP, and you have to almost have that for your Scikit-learn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your Scikit-learn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the Pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT, and then Seaborn as SNS. Seaborn works with the matplot library, so you have to always import matplot library, and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplot library inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplilearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/Simplilearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row, that's what the first colon is, comma, except for the last column. That's what the second part is, where we have a :-1, and we want the values set into there. So X is no longer a data set, a Pandas data set, but we can easily extract the data from our Pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the Pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what Pandas, one of the things Pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the Pandas. You could also open this up in an Excel and it would separate it since it is a comma-separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is Pandas. As you can see, we imported the matplotlibary.pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplotlibary inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine, the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any two of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in two steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the Scikit-learn preprocessing, where we're going to import the label encoder and the one hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. We have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the third row. And in there we're going to take the label coder and we're going to fit and transform the X, also the third row. So we're going to take that third row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally we need to do a one hot encoder, which equals one hot encoder categorical features equals 3. And then we take the X and we go ahead and do that equal to one hot encoder fit transform X to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print X and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have X equals X colon comma 1 colon. All this is doing is removing that one extra column we put in there when we did our one hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now, whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise, we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or two so it all fits on one line. So from the Scikit-learn module selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit, because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train, test, split, we take X and we take Y. We've already created those. X has the columns with the data in it, and Y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to just put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the Scikit-learn .linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom and we were doing all this summization? And then we also looked at setting it up with the different lines, and then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case, we do X train and Y train, because we're using the training data, X being the data in and Y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy X equals true, fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a yPredict variable, and we're going to put in the X test. And let's see what that looks like. Scroll up a little bit, paste that in here, predicting the test set results. So here we have yPredict equals regressor.predict X test going in, and this gives us yPredict. Now because I'm in Jupyter inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print yPredict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print yPredict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. And we can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m into the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works, and understand how good it works. So, calculating the R-squared value. That's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the R-squared value. And we're looking at the error. So, in the R2 score, we take our y-test versus our y-predict. Y-test is the actual values we're testing. That was the one that was given to us, so we know are true. The Y-predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if R-squared value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression.
What is logistic regression? Let's say we have to build a predictive model or a machine learning model to predict whether the passengers of the Titanic ship have survived or not, the shipwreck. So how do we do that? So we use logistic regression to build a model for this. How do we use logistic regression? So we have the information about the passengers, their ID, whether they have survived or not, their class and name and so on and so forth. And we use this information where we already know whether the person has survived or not. That is the labeled information. And we help the system to train based on this information, based on this labeled data. This is known as labeled data. And during the process of building the model, we probably will remove some of the non-essential parameters or attributes here. We only take those attributes which are really required to make these predictions. And once we train the model, we run new data through it, whereby the model will predict whether the passenger has survived or not. Alright, what is logistic regression? As I mentioned earlier, logistic regression is an algorithm for performing binary classification. So let's take an example and see how this works. Let's say your car has not been serviced for quite a few years, and now you want to find out if it is going to break down in the near future. So this is like a classification problem. Find out whether your car will break down or not. So how are we going to perform this classification? So here's how it looks. If we plot the information along the x and y axis. X is the number of years since the last service was performed, and y is the probability of your car breaking down. And let's say this data was collected from several car users. It's not just your car, but several car users. So that is our labeled data. So the data has been collected, and for the number of years and when the car broke down and what was the probability, and that has been plotted along x and y axis. So this provides an idea, or from this graph we can find out whether your car will break down or not. We'll see how. So first of all, the probability can go from 0 to 1. As you all are aware, probability can be between 0 and 1. And as we can imagine, it is intuitive as well. As the number of years are on the lower side, maybe 1 year, 2 years, or 3 years till after the service, the chances of your car breaking down are very limited, right? So for example, chances of your car breaking down, or the probability of your car breaking down within 2 years of your last service are 0.1 probability. Similarly, 3 years is maybe 0.3 and so on. But as the number of years increases, let's say if it was 6 or 7 years, there is almost a certainty that your car is going to break down. That is what this graph shows. So this is an example of an application of the classification algorithm. And we will see in little details how exactly logistic regression is applied here. One more thing needs to be added here is that the dependent variables outcome is discrete. So if we are talking about whether the car is going to break down or not, so that is a discrete value, the y that we are talking about, the dependent variable that we are talking about. What we are looking at is whether the car is going to break down or not, yes or no. That is what we are talking about. So here the outcome is discrete and not a continuous value. So this is how the logistic regression curve looks. Let me explain a little bit what exactly and how exactly we are going to determine the class, the outcome rather. So for a logistic regression curve, a threshold has to be set saying that because this is a probability calculation. Remember, this is a probability calculation and the probability itself will not be 0 or 1. But based on the probability, we need to decide what the outcome should be. So there has to be a threshold. Like for example, 0.5 can be the threshold, let's say in this case. So any value of the probability below 0.5 is considered to be 0 and any value above 0.5 is considered to be 1. So an output of let's say 0.8 will mean that the car will break down. So that is considered as an output of 1, and let's say an output of 0.29 is considered as 0, which means that the car will not break down. So that's the way logistic regression works. Now let's do a quick comparison between logistic regression and linear regression because they both have the term regression in them, so that can cause confusion. So let's try to remove that confusion. So what is linear regression? Linear regression is a process, is once again an algorithm for supervised learning. However, here you're going to find a continuous value. You're going to determine a continuous value. It could be the price of a real estate property. It could be your hike, how much hike you're going to get, or it could be a stock price. These are all continuous values. These are not discrete compared to a yes or a no kind of a response that we are looking for in logistic regression. So this is one example of a linear regression. Let's say the HR team of a company tries to find out what should be the salary hike of an employee. So they collect all the details of their existing employees, their ratings and their salary hikes, what has been given, and that is the labeled information that is available, and the system learns from this. It is trained and it learns from this labeled information so that when a new employee's information is fed based on the rating, it will determine what should be the hike. So this is a linear regression problem and a linear regression example. Now, salary is a continuous value. You can get 5,000, 5,500, 5,600. It is not discrete like a cat or a dog or an apple or a banana. These are discrete, or a yes or a no. These are discrete values, right? So this where you're trying to find continuous values is where we use linear regression. So let's say, just to extend on this scenario, we now want to find out whether this employee is going to get a promotion or not. So we want to find out, that is a discrete problem, right? A yes or no kind of a problem. In this case, we actually cannot use linear regression, even though we may have labeled data. So this is the labeled data. So based on the employee rating, these are the ratings, and then some people got the promotion, and this is the ratings for which people did not get promotion. That is a no. And this is the rating for which people got promotion. We just plotted the data about whether a person has got, an employee has got promotion or not, yes, no, right? So there is nothing in between. And what is the employee's rating? Okay, and ratings can be continuous, that is not an issue. But the output is discrete in this case, whether employee got promotion, yes, no. Okay, so if we try to plot that and we try to find a straight line, this is how it would look. And as you can see, it doesn't look very right because it looks like there will be a lot of errors. The root mean square error, if you remember, for linear regression would be very, very high. And also the values cannot go beyond 0 or beyond 1. So the graph should probably look somewhat like this, clipped at 0 and 1. But still, this straight line doesn't look right. Therefore, instead of using a linear equation, we need to come up with something different. And therefore, the logistic regression model looks somewhat like this. So we calculate the probability, and if we plot that probability not in the form of a straight line, but we need to use some other equation, we will see very soon what that equation is, then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process, and this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening. And this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0. And when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this. And the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line, which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression, it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function, and the shape of the curve is S. It's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values, like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to be rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? Is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images. We can display using matplotlib some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix, the heat map, and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. Alright, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting, right? So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 93-94%, because the diagonals should have the maximum numbers, and the others other than diagonals, the cells other than the diagonals, should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0, and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and one has been predicted as number 8, and another one has been predicted as number 9. So these are two misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's a gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has, there are, I think, 37 plus 5, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7, and 2 of them have been predicted as number 8, and so on and so forth. Okay, all right, so with that, let's go into Jupyter Notebook and see how the code looks.
So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like NumPy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code, and so that it becomes easy to understand. So these are about 5 images, sample images that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number, what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test, so that the training data set is used to train the system. So we pass this probably multiple times, and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of the entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x underscore train and y underscore train for the training data set. And what is x underscore train? These are the features, right, which is like the independent variable, and y underscore train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x underscore train, and since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2, so that this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this, right? So this is the label. So the same way, x underscore train, y underscore train is for the training data set, x underscore test, y underscore test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of these. So x underscore train, the shape is 1383 by 64, and y underscore train has 1383 because there is nothing like the second part is not required here. And then x underscore test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of Scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that, so that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these 2 lines. So the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right? This is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this, in this case the data is not large, but by and large the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose we use the fit method. There is a method called fit, which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method, and we pass this particular image, and we see that the shape is, or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So this confusion underscore matrix method takes two parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set, and then out of that, the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations. That will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So let me run this piece of code, and this is how the heat map looks. And as you can see here, the diagonals again are all the values are here, most of the values. So which means this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. All right, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value, and also the predicted value. Both are 4. This is an image of 0. So the predicted value is also 0. Actual value is of course 0. Then this is the image of 9. So this has also been predicted correctly, 9, and actual value is 9. And this is the image of 1. And again, this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. problems that decision tree can solve. So let's look at the two different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between three types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with a gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like and how do we split the data. We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is a measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I would be the percentage of that animal times the log base 2 of the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as a condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need is something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here. We have to make a couple changes as we go through this first part of the import. The first thing we bring in is NumPy as NP. That's very standard. When we're dealing with mathematics, especially with very complicated machine learning tools, you almost always see the NumPy come in for your numbers. It's called NumPy. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use Pandas as PD. That's also a standard. The Pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the Pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the Scikit-learn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the Scikit-learn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this and it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and there's this very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the Scikit-learn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is. And very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 1, 2, 3, 4, 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balanced data from the Panda read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance underscore data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the Pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a Pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, and let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or open Office Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into 2 groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our X and Y. Where do X and Y come from? Well, X is going to be our data, and Y is going to be the answer or the target. You can look at it source and target. In this case, we're using X and Y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in X equals the balance of the data dot values. The first brackets means that we're going to select all the lines in the database. So it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, we always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for Y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into 2 different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have X going in, where we're going to train it, and we have to know the answer to train it with. And then we have X test, where we're going to test that data. And we have to know in the end what the Y was supposed to be. And that's where this train test split comes in, that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these Scikit-learn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So it'll have at least 3 splits, it'll have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it, let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what's it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created. And then you'll see .predict. And that's very common in the Scikit-learn modules, that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X test data in here. Now, if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredictEn to print it. I could just as easily have put the print and put brackets around yPredictEn to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our yPredict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since Scikit-learn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y test, that's the one we ran the predict on. And then we put in our yPredictEn, that's the answers we got. And we're just going to multiply that by 100, because this is just going to give us an answer as a decimal. And we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We may not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not. We're going to be looking at random forest, one of the many powerful tools in the machine learning library. Before we dive into the topic, let's start by looking at a few of the uses for random forest. Currently today it's used in remote sensing. For example, they're used in the ETM devices. If you're a space buff, that's the enhanced thematic mapper they use on satellites. which see far outside the human spectrum for looking at land masses. And they acquire images of the Earth's surface. The accuracy is higher and training time is less than many other machine learning tools out there. Also, object detection, multi-class object detection is done using random forest algorithms. A good example is traffic, where you're trying to sort out the different cars, buses, and things. And it provides a better detection in complicated environments. It's very complicated up there. And then we have another example, Connect. And let's take a little closer look at Connect. Connect, they use a random forest as part of the game console. And what it does is it tracks the body movements and it recreates it in the game. And let's see what that looks like. We have a user who performs a step. In this case, it looks like Elvis Presley going there. That is then recorded, so the Connect registers the movement, and then it marks the user based on accuracy. And it looks like we have Prince going on this one, from Elvis Presley to Prince. It's great. So it marks the user based on the accuracy. If we look at that a little closer, we have a training set to identify body parts. Where are the hands? Where are the feet? What's going on with the body? That then goes into a random forest classifier that learns from it. Once we've trained the classifier, it then identifies the body parts while the person's dancing. And it's able to represent that in a computer format, and then based on that, it scores the game and how accurate you are as being Elvis Presley or Prince in your dancing. So why random forest? It's always important to understand why we use this tool over the other ones. What are the benefits here? And so with the random forest, the first one is there's no overfitting. If you use of multiple trees, reduce the risk of overfitting. Training time is less. Overfitting means that we have fit the data so close to what we have as our sample that we pick up on all the weird parts. And instead of predicting the overall data, you're predicting the weird stuff, which you don't want. High accuracy. Runs efficiently on large database. For large data, it produces highly accurate predictions. In today's world of big data, this is really important. And this is probably where it really shines. This is where why random forest really comes in. It estimates missing data. Data in today's world is very messy. So when you have a random forest, it can maintain the accuracy when a large proportion of the data is missing. What that means is if you have data that comes in from 5 or 6 different areas, and maybe they took one set of statistics in one area, and they took a slightly different set of statistics in the other, so they have some of the same shared data, but one is missing like the number of children in the house if you're doing something over demographics, and the other one is missing the size of the house. It will look at both of those separately and build 2 different trees, and then it can do a very good job of guessing which one fits better even though it's missing that data. Let us dig deep into the theory of exactly how it works. And let's look at what is random forest. Random forest, or random decision forest, is a method that operates by constructing multiple decision trees. The decision of the majority of the trees is chosen by the random forest as the final decision. And let's we have some nice graphics here. We have a decision tree, and they actually use a real tree to denote the decision tree, which I love. And given a random, some kind of picture of a fruit, this decision tree decides that the output is it's an apple. And we have a decision tree 2, where we have that picture of the fruit goes in, and this one decides that it's a lemon. And the decision 3 tree gets another image, and it decides it's an apple. And then this all comes together in what they call the random forest. And this random forest then looks at it and says, okay, I got 2 votes for apple, 1 vote for lemon. The majority is apples, so the final decision is apples. To understand how the random forest works, we first need to dig a little deeper and take a look at the random forest and the actual decision tree and how it builds that decision tree. In looking closer at how the individual decision trees work, we'll go ahead and continue to use the fruit example, since we're talking about trees and forests. A decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So in here we have a bowl of fruit, and if you look at that, it looks like they switched from lemons to oranges. So we have oranges, cherries, and apples. And the first decision of the decision tree might be, is the diameter greater than or equal to 3? And if it says false, it knows that they're cherries because everything else is bigger than that. So all the cherries fall into that decision. So we have all that data we're training. We can look at that. We know that that's what's going to come up. Is the color orange? Well, it goes, orange or red? Well, if it's true, then it comes out as the orange. and if it's false, that leaves apples. So in this example, it sorts out the fruit in the bowl, or the images of the fruit. A decision tree, these are very important terms to know because these are very central to understanding the decision tree and when working with them. The first is entropy. Everything on the decision tree and how it makes a decision is based on entropy. Entropy is a measure of randomness or unpredictability in the data set. Then they also have information gain, the leaf node, the decision node, and the root node. We'll cover these other 4 terms as we go down the tree, but let's start with entropy. So starting with entropy, we have here a high amount of randomness. What that means is that whatever's coming out of this decision, if it was going to guess based on this data, it wouldn't be able to tell you whether it's a lemon or an apple. It would just say it's a fruit. So the first thing we want to do is we want to split this apart. And we take the initial data set, and we're going to create a data set 1 and a data set 2. We just split it in 2. And if you look at these new data sets, after splitting them, the entropy of each of those sets is much less. So for the first one, whatever comes in there, it's going to sort that data and it's going to say, okay, if this data goes this direction, it's probably an apple. And if it goes into the other direction, it's probably a lemon. So that brings us up to information gain. It is the measure of decrease in the entropy after the data set is split. What that means in here is that we've gone from one set, which has a very high entropy, to 2 lower sets of entropy. And we've added in the values of E1 for the first one and E2 for the second 2, which are much lower. And so that information gain is increased greatly in this example. And so you can find that the information gain simply equals decision E1 minus E2. As we're going down our list of definitions, we'll look at the leaf node. And the leaf node carries the classification or the decision. So we look down here to the leaf node. We finally get to our set 1 or our set 2. When it comes down there and it says, okay, this object's gone into set 1, if it's gone into set 1, it's going to be split by some means, and we'll either end up with apples on the leaf node or a lemon on the leaf node, and on the right it'll either be an apple or lemons. Those leaf nodes, or those final decisions or classifications, that's the definition of leaf node in here. If we're going to have a final leaf where we make the decision, we should have a name for the nodes above it, and they call those decision nodes. A decision node has 2 or more branches. And you can see here where we have the 5 apples and 1 lemon, and in the other case the 5 lemons and 1 apple. They have to make a choice of which tree it goes down based on some kind of measurement or information given to the tree. And that brings us to our last definition. The root node, the topmost decision node, is known as the root node. And this is where you have all of your data and you have your first decision it has to make, or the first split in information. So far we've looked at a very general image with the fruit being split. Let's look and see exactly what that means to split the data and how do we make those decisions on there. Let's go in there and find out how does a decision tree work. So let's try to understand this, and let's use a simple example, and we'll stay with the fruit. We have a bowl of fruit, and so let's create a problem statement, and the problem is we want to classify the different types of fruits in the bowl based on different features. The data set in the bowl is looking quite messy, and the entropy is high in this case. So if this bowl was our decision maker, it wouldn't know what choice to make. It has so many choices. Which one do you pick? Apple, grapes, or lemons? And so we look in here. We're going to start with a training set. So this is our data that we're training our data with. And we have a number of options here. We have the color, and under the color we have red, yellow, purple. We have a diameter, 331, 331, and we have a label, apple, lemon, grapes, apple, lemon, grapes. And how do we split the data? We have to frame the conditions to split the data in such a way that the information gain is the highest. And it's very key to note that we're looking for the best gain. We don't want to just start sorting out the smallest piece in there. We want to split it the biggest way we can. And so we measure this decrease in entropy, that's what they call it, entropy, there's our entropy, after splitting. And now we'll try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking the gain that we get out of them. The conditions that give us the highest gain will be used to make the first split. So let's take a look at these different conditions. We have color, we have diameter, and if we look underneath that, we have a couple different values. We have diameter equals 3, color equals yellow, red, diameter equals 1. And when we look at that, you'll see over here we have 1, 2, 3, 4 threes. That's a pretty high selection. So let's say the condition gives us a maximum gain of 3. So we have the most pieces fall into that range. So our first split from our decision node is we split the data based on the diameter. Is it greater than or equal to 3? If it's not, that's false, it goes into the grape bowl. And if it's true, it goes into a bowl full of lemon and apples. The entropy after splitting has decreased considerably. So now we can make two decisions. If you look at, they're very much less chaos going on there. This node has already attained an entropy value of 0, as you can see. There's only one kind of label left for this branch. So no further splitting is required for this node. However, this node on the right still requires a split to decrease the entropy further. So we split the right node further based on color. If you look at this, if I split it on color, that pretty much cuts it right down the middle, and it's the only thing we have left in our choices of color and diameter too. And if the color is yellow, it's going to go to the right bowl, and if it's false, it's going to go to the left bowl. So the entropy in this case is now 0. So now we have 3 bowls with 0 entropy. There's only one type of data in each one of those bowls. So we can predict a lemon with 100% accuracy. And we can predict the apple also with 100% accuracy, along with our grapes up there. So we've looked at kind of a basic tree in our forest, but what we really want to know is how does a random forest work as a whole? So to begin our random forest classifier, let's say we already have built 3 trees. And we're going to start with the first tree that looks like this. Just like we did in the example, this tree looks at the diameter. If it's greater than or equal to 3, it's true, otherwise it's false. So one side goes to the smaller diameter, one side goes to larger diameter. And if the color is orange, it's going to go to the right, true. We're using oranges now instead of lemons. And if it's red, it's going to go to the left, false. We build a second tree very similar, but it's split differently. Instead of the first one being split by diameter, this one, when they created it, if you look at that first bowl, it has a lot of red objects. So it says, is the color red? Because that's going to bring our entropy down the fastest. And so, of course, if it's true, it goes to the left. If it's false, it goes to the right. And then it looks at the shape, false or true, and so on and so on. And tree 3 is the diameter equal to 1. And it came up with this because there's a lot of cherries in this bowl. So that would be the biggest split on there is the diameter equal to 1. That's going to drop the entropy the quickest. And as you can see, it splits it into true. If it goes false, and they've added another category, does it grow in the summer? And if it's false, it goes off to the left. If it's true, it goes off to the right. Let's go ahead and bring these 3 trees so you can see them all in one image. So this would be 3 completely different trees categorizing a fruit. And let's take a fruit. Now let's try this. And this fruit, if you look at it, we've blackened it out. You can't see the color on it, so it's missing data. Remember, one of the things we talked about earlier is that a random forest works really good if you're missing data, if you're missing pieces. So this fruit has an image, but maybe the person had a black and white camera when they took the picture. And we're going to take a look at this, and it's going to have, they put the color in there, so ignore the color down there. But the diameter equals 3. We find out it grows in the summer equals yes, and the shape is a circle. And if you go to the right, you can look at what one of the decision trees did. This is the third one. Is the diameter greater than or equal to 3? Is the color orange? Well, it doesn't really know on this one, but if you look at the value, it'd say true, and it'd go to the right. Tree 2 classifies it as cherries. Is the color equal red? Is the shape a circle? True, it is a circle. So this would look at it and say, oh, that's a cherry. And then we go to the other classifier, and it says, is the diameter equal 1? Well, that's false. Does it grow in the summer? True. So it goes down and looks at as oranges. So how does this random forest work? The first one says it's an orange. The second one said it was a cherry. And the third one says, it's an orange. And you can guess that if you have 2 oranges and one says it's a cherry, when you add that all together, the majority of the vote says orange. So the answer is, it's classified as an orange, even though we didn't know the color and we're missing data on it. I don't know about you, but I'm getting tired of fruit. So let's switch, and I did promise you we'd start looking at a case example and get into some Python coding. Today we're going to use the case, the iris flower analysis. Ooh, this is the exciting part as we roll up our sleeves and actually look at some Python coding. Before we start the Python coding, we need to go ahead and create a problem statement. Wonder what species of iris do these flowers belong to? Let's try to predict the species of the flowers using machine learning in Python. Let's see how it can be done. So here we begin to go ahead and implement our Python code. And you'll find that the first half of our implementation is all about organizing and exploring the data coming in. Let's go ahead and take this first step, which is loading the different modules into Python, and let's go ahead and put that in our favorite editor, whatever your favorite editor is. In this case, I'm going to be using the Anaconda Jupyter Notebook, which is one of my favorites. Certainly there's Notepad++ and Eclipse and dozens of others, or just even using the Python terminal window. Any of those will work just fine to go ahead and explore this Python coding. So here we go. Let's go ahead and flip over to our Jupyter Notebook. And I've already opened up a new page for Python 3 code, and I'm just going to paste this right in there. And let's take a look and see what we're bringing into our Python. The first thing we're going to do is from the sklearn.datasets import load iris. Now this isn't the actual data, this is just the module that allows us to bring in the data, the load iris. And the iris is so popular, it's been around since 1936 when Ronald Fisher published a paper on it, and they're measuring the different parts of the flower, and based on those measurements predicting what kind of flower it is. And then if we're going to do a random forest classifier, we need to go ahead and import a random forest classifier from the sklearn module. So sklearn.ensemble import random forest classifier. And then we want to bring in two more modules. And these are probably the most commonly used modules in Python and data science with any of the other modules that we bring in. And one is going to be Pandas. So we're going to import Pandas as PD. PD is the common term used for Pandas. And Pandas is basically creates a data format for us where when you create a Pandas data frame, it looks like an Excel spreadsheet. And you'll see that in a minute when we start digging deeper into the code. Pandas is just wonderful because it plays nice with all the other modules in there. And then we have NumPy, which is our numbers Python. And the numbers Python allows us to do different mathematical sets on here. We'll see right off the bat, we're going to take our NP and we're going to go ahead and seed the randomness with it with 0. So np.random.seed is seeding that as 0. This code doesn't actually show anything. We're going to go ahead and run it because I need to make sure I have all those loaded. And then let's take a look at the next module on here. The next 6 slides, including this one, are all about exploring the data. Remember I told you half of this is about looking at the data and getting it all set. So let's go ahead and take this code right here, the script, and let's get that over into our Jupyter Notebook. And here we go. We've gone ahead and run the imports. And I'm going to paste the code down here. And let's take a look and see what's going on. The first thing we're doing is we're actually loading the iris data. And if you remember up here, we loaded the module that tells it how to get the iris data. Now we're actually assigning that data to the variable iris. And then we're going to go ahead and use the df to define data frame. And that's going to equal PD. And if you remember, that's pandas as PD. So that's our pandas. And panda data frame. And then we're looking at iris data. And columns equals iris feature names. And we're going to do the df head. And let's run this so you can understand what's going on here. The first thing you want to notice is that our df has created what looks like an Excel spreadsheet. And in this Excel spreadsheet, we have set the columns. So up on the top, you can see the 4 different columns. And then we have the data, iris.data, down below. It's a little confusing without knowing where this data is coming from. So let's look at the bigger picture. And I'm going to go print. I'm just going to change this for a moment. And we're going to print all of iris and see what that looks like. So when I print all of iris, I get this long list of information. And you can scroll through here and see all the different titles on there. What's important to notice is that first off, there's a brackets at the beginning. So this is a Python dictionary. And in a Python dictionary, you'll have a key or a label. And this label pulls up whatever information comes after it. So feature names, which we actually used over here under columns, is equal to an array of sepal length, sepal width, petal width. These are the different names they have for the 4 different columns. And if you scroll down far enough, you'll also see data down here. Oh goodness, it came up right towards the top. And data is equal to the different data we're looking at. Now there's a lot of other things in here like target. We're going to be pulling that up in a minute. And there's also the names, the target names, which is further down. And we'll show you that also in a minute. Let's go ahead and set that back to the head. And this is one of the neat features of Pandas and Panda data frames, is when you do df.head or the Panda data frame.head, it'll print the first 5 lines of the data set in there, along with the headers if you have it. In this case, we have the column headers set to iris features. And in here, you'll see that we have 0, 1, 2, 3, 4. In Python, most arrays always start at 0. So when you look at the first 5, it's going to be 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So now we've got our iris data imported into a data frame. Let's take a look at the next piece of code in here. And so in this section here of the code, we're going to take a look at the target. And let's go ahead and get this into our notebook, this piece of code, so we can discuss it a little bit more in detail. So here we are in our Jupyter notebook. I'm going to put the code in here. And before I run it, I want to look at a couple things going on. So we have df species. And this is interesting because right here you'll see where I have df species in brackets, which is the key code for creating another column. And here we have iris.target. Now these are both in the Pandas setup on here. So in Pandas we can do either one. I could have just as easily done iris and then in brackets target, depending on what I'm working on. Both are acceptable. Let's go ahead and run this code and see how this changes. And what we've done is we've added the target from the iris data set as another column on the end. Now what species is, this is what we're trying to predict. So we have our data, which tells us the answer for all these different pieces. And then we've added a column with the answer. That way when we do our final setup, we'll have the ability to program our neural network to look for this different data and know what a setosa is, or a varicolor, which we'll see in just a minute, or virginica. Those are the 3 that are in there. And now we're going to add one more column. I know, we're organizing all this data over and over again. It's kind of fun. There's a lot of ways to organize it. What's nice about putting everything onto one data frame is I can then do a printout and it shows me exactly what I'm looking at. And I'll show you where that's different, where you can alter that and do it slightly differently. But let's go ahead and put this into our script up to date now. And here we go. We're going to put that down here. And we're going to run that. And let's talk a little bit about what we're doing. Now, we're exploring data, and one of the challenges is knowing how good your model is. Did your model work? And to do this, we need to split the data up. And we split it into 2 different parts. They usually call it the training and the testing. And so in here, we're going to go ahead and put that in our database so you can see it clearly. And we've set it df. And remember, you can put brackets. This is creating another column. Is train, so we're going to use part of it for training. And this equals np, remember that stands for numpy, .random.uniform. So we're generating a random number between 0 and 1. And we're going to do it for each of the rows. That's where the length df comes from. So each row gets a generated number. And if it's less than 0.75, it's true. And if it's greater than 0.75, it's false. This means we're going to take 75% of the data, roughly, because there's a randomness involved, and we're going to use that to train it. And then the other 25%, we're going to hold off to the side and use that to test it later on. So let's flip back on over and see what the next step is. So now that we've labeled our database for which is training and which is testing, let's go ahead and sort that into 2 different variables, train and test. And let's take this code and let's bring it into our project. And here we go, let's paste it on down here. And before I run this, let's just take a quick look at what's going on here. Is we have up above, we created, remember there's our def.head, which prints the first 5 rows. And we've added a column is train at the end. And so we're going to take that, we're going to create 2 variables. We're going to create 2 new data frames. One's called train. One's called test, 75% in train, 25% in test. And then to sort that out, we're going to do that by doing df our main original data frame with the iris data in it. And if df is train equals true, that's going to go in the train, and if df is train equals false, it goes in the test. And so when I run this, we're going to print out the number in each one. Let's see what that looks like. And you'll see that it puts 118 in the training module, and it puts 32 in the testing module, which lets us know that there was 150 lines of data in here. So if you went and looked at the original data, you could see that there's 150 lines. And that's roughly 75% in one and 25% for us to test our model on afterward. So let's jump back to our code and see where this goes. In the next two steps, we want to do one more thing with our data, and that's make it readable to humans. I don't know about you, but I hate looking at zeros and ones. So let's start with the features, and let's go ahead and take those and make those readable to humans. And let's put that in our code. Let's see, here we go, paste it in. And you'll see here we've done a couple very basic things. We know that the columns in our data frame, again this is a Panda thing, the df columns, and we know the first four of them, 0, 1, 2, 3, that'd be the first four, are going to be the features or the titles of those columns. And so when I run this, you'll see down here that it creates an index, SEPA length, SEPA width, petal length, and petal width. And this should be familiar because if you look up here, here's our column titles going across, and here's the first four. One thing I want you to notice here is that when you're in a command line, whether it's Jupyter Notebook or you're running command line in the terminal window, if you just put the name of it, it'll print it out. This is the same as doing print features. And the shorthand is you just put features in here. If you're actually writing a code and saving the script and running it by remote, you really need to put the print in there. But for this, when I run it, you'll see it gives me the same thing. But for this, we want to go ahead and we'll just leave it as features because it doesn't really matter. And this is one of the fun thing about Jupyter Notebooks is I'm just building the code as we go. And then we need to go ahead and create the labels for the other part. So let's take a look and see what that. For our final step in prepping our data, before we actually start running the training and the testing, is we're going to go ahead and convert the species on here into something the computer understands. So let's put this code into our script and see where that takes us. Alright, here we go. We've set y equal to pd.factorize train species of 0. So let's break this down just a little bit. We have our pandas right here, pd. Factorize. What is factorize doing? I'm going to come back to that in just a second. Let's look at what train species is and why we're looking at the group 0 on there. And let's go up here, and here is our species. Remember this that we created this whole column here for species? And then it has Setosa, 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 and if you scroll down enough, you'd also see Virginica and Varicolor. We need to convert that into something the computer understands, zeros and ones. So the trained species of 0, because this is in the format of an array of arrays, so you have to have the 0 on the end. And then species is just that column. Factorize goes in there and looks at the fact that there's only 3 of them. So when I run this, you'll see that y generates an array that's equal to, in this case it's the training set, and it's 0s, 1s, and 2s representing the 3 different kinds of flowers we have. So now we have something the computer understands, and we have a nice table that we can read and understand. And now, finally, we get to actually start doing the predicting. So here we go. We have 2 lines of code. Oh my goodness, that was a lot of work to get to 2 lines of code. But there is a lot in these 2 lines of code. So let's take a look and see what's going on here and put this into our full script that we're running. And let's paste this in here. And let's take a look and see what this is. We're creating a variable CLF, and we're going to set this equal to the random forest classifier. And we're passing 2 variables in here, and there's a lot of variables you can play with. As far as these 2 are concerned, they're very standard. In jobs, all that does is to prioritize it. Not something to really worry about. Usually when you're doing this on your own computer, you do in jobs equals 2. If you're working in a larger or big data and you need to prioritize it differently, this is what that number does, is it changes your priorities and how it's going to run across the system and things like that. And then the random state is just how it starts. 0 is fine for here. But let's go ahead and run this. We also have clf.fit train features, y. And before we run it, let's talk about this a little bit more. clf.fit. So we're fitting, we're training it. We are actually creating our random forest classifier right here. This is the code that does everything. And we're going to take our training set. Remember, we kept our test off to the side. And we're going to take our training set with the features, and then we're going to go ahead and put that in, and here's our target, the y. So the y is 0, 1, and 2 that we just created, and the features is the actual data going in that we put into the training set. And let's go ahead and run that. And this is kind of an interesting thing because it printed out the random forest classifier and everything around it. And so when you're running this in your terminal window or in a script like this, this automatically treats this like just like when we were up here and I typed in y and it printed out y instead of print y. This does the same thing. It treats this as a variable and prints it out. But if you were actually running your code, that wouldn't be the case. And what is printed out is it shows us all the different variables we can change. And if we go down here, you can actually see injobs equals 2. You can see the random state equals 0. Those are the two that we sent in there. You would really have to dig deep to find out all these different meanings of all these different settings on here. Some of them are self-explanatory if you kind of think about it a little bit, like max features is auto. So all the features that we're putting in there is just going to automatically take all 4 of them. Whatever we send it, it'll take. Some of them might have so many features because you're processing words. There might be like 1.4 million features in there because you're doing legal documents, and that's how many different words are in there. At that point, you probably want to limit the maximum features that you're going to process. And leaf nodes, that's the end nodes. Remember we had the fruit and we're talking about the leaf nodes. Like I said, there's a lot in this. We're looking at a lot of stuff here. So you might have, in this case, there's probably only 3 leaf nodes, maybe 4. You might have thousands of leaf nodes, at which point you do need to put a cap on that and say, okay, you can only go so far, and then we're going to use all of our resources on processing this. And that really is what most of these are about, is limiting the process and making sure we don't overwhelm a system. And there's some other settings in here. Again, we're not going to go over all of them. Warm start equals false. Warm start is if you're programming it one piece at a time externally. Since we're not going to have, we're not going to continually to train this particular learning tree. And again, like I said, there's a lot of things in here that you'll want to look up more detail from the Scikit-learn. And if you're digging in deep and running a major project on here. For today though, all we need to do is fit or train our features and our target y. So now we have our training model. What's next? If we're going to create a model, we now need to test it. Remember, we set aside the test feature, test group, 25% of the data. So let's go ahead and take this code and let's put it into our script and see what that looks like. Okay, here we go. And we're going to run this, and it's going to come out with a bunch of 0s, 1s, and 2s, which represents the 3 types of flowers, the setosa, the virginica, and the versicolor. And what we're putting into our predict is the test features, and I always kind of like to know what it is I am looking at. So real quick, we're going to do test features. And remember, features is an array of sepal length, sepal width, petal width. So when we put it in this way, it actually loads all these different columns that we loaded into features. So if we did just features, let me just do features in here so you can see what features looks like. This is just playing with Pandas data frames. You'll see that it's an index. So when you put an index in like this into test features, into test, it then takes those columns and creates a Panda data frames from those columns. And in this case, we're going to go ahead and put those into our predict. So we're going to put each one of these lines of data, the 5.0, 3.4, 1.5, 0.2, and we're going to put those in and we're going to predict what our new forest classifier is going to come up with. And this is what it predicts. It predicts 0, 0, 0, 1, 2, 1, 1, 2, 2, 2. And again, this is the flower type, setosa, virginica, and versicolor. So now that we've taken our test features, let's explore that. Let's see exactly what that data means to us. So the first thing we can do with our predicts is we can actually generate a different prediction model. When I say different, we're going to view it differently. It's not that the data itself is different. So let's take this next piece of code and put it into our script. So we're pasting it in here, and you'll see that we're doing predict, and we've added underscore proba for probability. So there's our clf.predict probability. So we're running it just like we ran it up here, but this time with this we're going to get a slightly different result, and we're only going to look at the first 10. So you'll see down here, instead of looking at all of them, which was 27, you'll see right down here that this generates a much larger field on the probability. And let's take a look and see what that looks like and what that means. So when we do the predict underscore proba for probability, it generates 3 numbers. So we had 3 leaf nodes at the end. And if you remember from all the theory we did, this is the predictors. The first one is predicting a 1 for Setosa. It predicts a 0 for Virginica, and it predicts a 0 for Versicolor, and so on and so on and so on. And let's, you know what, I'm going to change this just a little bit. Let's look at 10 to 20, just because we can. And we start to get in a little different of data, and you'll see right down here, it gets to this one, this line right here. And this line has 0, 0.5, 0.5. And so if we're going to vote, and we have 2 equal votes, it's going to go with the first one. So it says Setosa gets 0 votes, Virginica gets 0.5 votes, Versicolor gets 0.5 votes, but let's just go with the Virginica since these 2 are equal, and so on down the list. You can see how they vary on here. So now we've looked at both how to do a basic predict of the features, and we've looked at the predict probability. Let's see what's next on here. So now we want to go ahead and start mapping names for the plants. We want to attach names so that it makes a little more sense for us. And that's what we're going to do in these next 2 steps. We're going to start by setting up our predictions and mapping them to the names. So let's see what that looks like. And let's go ahead and paste that code in here and run it. And this goes along with the next piece of code. So we'll skip through this quickly and then come back to it a little bit. So here's iris.targetNames. And if you remember correctly, this was the names that we've been talking about this whole time, the Setosa, Virginica, Versicolor. And then we're going to go ahead and do the prediction again. We could have just set a variable equal to this instead of rerunning it each time. But we're going to go ahead and run it again, clf.predict test features. Remember that returns the 0s, the 1s, and the 2s. And then we're going to set that equal to predictions. So this time we're actually putting it in a variable. And when I run this, it distributes, it comes out as an array, and the array is Setosa, 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 Setosa. We're only looking at the first 5. We could actually do, let's do the first 25, just so we can see a little bit more on there. And you'll see that it starts mapping it to all the different flower types, the Versicolor and the Virginica in there. And let's see how this goes with the next one. So let's take a look at the top part of our species in here, and we'll take this code and put it in our script. And let's put that down here and paste it. There we go. And we'll go ahead and run it. And let's talk about both these sections of code here and how they go together. The first one is our predictions. And I went ahead and did predictions through 25. Let's just do 5. And so we have Setosa, 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 Setosa. That's what we're predicting from our test model. And then we come down here and we look at test species. I remember I could have just done test.species.head, and you'll see it says Setosa, 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 and they match. So the first one is what our forest is doing, and the second one is what the actual data is. Now, we need to combine these so that we can understand what that means. We need to know how good our forest is, how good it is at predicting the features. So that's where we come up to the next step, which is lots of fun. We're going to use a single line of code to combine our predictions and our actuals so we have a nice chart to look at. And let's go ahead and put that in our script in our Jupyter notebook here. Let's see, let's go ahead and paste that in, and then because I'm on the Jupyter notebook, I can do a control minus so you can see the whole line there. There we go, resize it. And let's take a look and see what's going on here. We're going to create in Pandas, remember PD stands for Pandas, and we're doing a crosstab. This function takes 2 sets of data and creates a chart out of them. So when I run it, you'll get a nice chart down here. And we have the predicted species, So across the top you'll see the Setosa versicolor virginica and the actual species, Setosa versicolor virginica. And so the way to read this chart, and let's go ahead and take a look on how to read this chart here. When you read this chart, you have Setosa where they meet, you have versicolor where they meet, and you have virginica where they meet. And they're meeting where the actual and the predicted agree. So this is the number of accurate predictions. So in this case it equals 30. If you add 13 plus 5 plus 12, you get 30. And then we notice here where it says virginica, but it was supposed to be versicolor. This is inaccurate. So now we have two inaccurate predictions and 30 accurate predictions. So we'll say that the model accuracy is 93. That's just 30 divided by 32. And if we multiply it by 100, we can say that it is 93% accurate. So we have a 93% accuracy with our model. I did want to add one more quick thing in here on our scripting before we wrap it up. So let's flip back on over to my script. In here, we're going to take this line of code from up above. I don't know if you remember it, but predicts equals the iris.target underscore names. So we're going to map it to the names. And we're going to run the prediction, and we read it on test features. But we're not just testing it, we want to actually deploy it. So at this point, I would go ahead and change this. And this is an array of arrays. This is really important when you're running these to know that. So you need the double brackets, and I could actually create data. Maybe let's just do 2 flowers. So maybe I'm processing more data coming in, and we'll put 2 flowers in here. And then I actually want to see what the answer is. So let's go ahead and type in preds and print that out. And when I run this, you'll see that I've now predicted 2 flowers that maybe I measured in my front yard as versicolor and versicolor. Not surprising since I put the same data in for each one. This would be the actual end product going out to be used on data that you don't know the answer for. So that's going to conclude our scripting part of this. Introducing Naive Bayes Classifier. Have you ever wondered how your mail provider implements spam filtering, or how online news channels perform news text classification, or how companies perform sentimental analysis of their audience on social media? All of this and more is done through a machine learning algorithm called Naive Bayes Classifier. Welcome to Naive Bayes Tutorial. My name is Richard Kirshner. I'm with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. What's in it for you? We'll start with what is Naive Bayes, a basic overview of how it works. We'll get into Naive Bayes and machine learning, where it fits in with our other machine learning tools. Why do we need Naive Bayes? And understanding Naive Bayes Classifier, a much more in-depth of how the math works in the background. Finally, we'll get into the advantages of the Naive Bayes Classifier in the machine learning setup. And then we'll roll up our sleeves and do my favorite part. We'll actually do some Python coding and do some text classification using the Naive Bayes. What is Naive Bayes? Let's start with a basic introduction to the Bayes theorem, named after Thomas Bayes from the 1700s, who first coined this in the Western literature. Naive Bayes classifier works on the principle of conditional probability as given by the Bayes theorem. Before we move ahead, let us go through some of the simple concepts in the probability that we will be using. Let us consider the following example of tossing 2 coins. Here we have 2 quarters, and if we look at all the different possibilities of what they can come up as, we get that they could come up as head-heads, they can come up as head-tail, tail-head, and tail-tail. When doing the math on probability, we usually denote probability as a P, a capital P. So the probability of getting 2 heads equals 1/4. You can see on our data set we have 2 heads, and this occurs once out of the 4 possibilities. And then the probability of at least 1 tail occurs 3/4 of the time. You'll see on 3 of the coin tosses we have tails in them, and out of 4 that's 3/4. And then the probability of the second coin being head given the first coin is tail is 1/2, and the probability of getting 2 heads given the first coin is a head is 1/2. We'll demonstrate that in just a minute and show you how that math works. Now when we're doing it with 2 coins it's easy to see, but when you have something more complex you can see where these formulas really come in and work. So the Bayes theorem gives us the conditional probability of an event A given another event B has occurred. In this case, the first coin toss will be B and the second coin toss A. This could be confusing because we've actually reversed the order of them and go from B to A instead of A to B. You'll see this a lot when you work in probabilities. The reason is we're looking for event A. We want to know what that is. So we're going to label that A since that's our focus. And then given another event B has occurred. In the Bayes theorem, as you can see on the left, the probability of A occurring given B has occurred equals the probability of B occurring given A has occurred times the probability of A over the probability of B. This simple formula can be moved around just like any algebra formula. And we could do the probability of A after a given B times probability of B equals the probability of B given A times probability of A. You can easily move that around and multiply it and divide it out. Let us apply Bayes' theorem to our example. Here we have our 2 quarters, and we'll notice that the first 2 probabilities of getting 2 heads and at least 1 tail we compute directly off the data. So you can easily see that we have one example, HH, out of 4, 1/4, and we have 3 with tails in them, giving us 3/4, or 3/4, 75%. The second condition, the second set, 3 and 4, we're going to explore a little bit more in detail. Now we stick to a simple example with 2 coins because you can easily understand the math. The probability of throwing a tail doesn't matter what comes before it, and the same with the heads. So it's still going to be 50% or 1/2. But when that probability gets more complicated, let's say you have a D6 dice or some other instance, then this formula really comes in handy. But let's stick to the simple example for now. In this sample space, let A be the event that the second coin is head and B be the event that the first coin is tails. Again, we reversed it because we want to know what the second event's going to be, so we're going to be focusing on A. And we write that out as the probability of A given B. And we know this from our formula that equals the probability of B given A times the probability of A over the probability of B. And when we plug that in, we plug in the probability of the first coin being tails given the second coin is heads, and the probability of the second coin being heads given the first coin being over the probability of the first coin being tails. When we plug that data in, and we have the probability of the first coin being tails given the second coin is heads times the probability of the second coin being heads over the probability of the first coin being tails. You can see it's a simple formula to calculate. We have 1/2 times 1/2 over 1/2, or 1/2 equals 0.5, or 1/4. So the Bayes theorem basically calculates the conditional probability of the occurrence of an event based on prior knowledge of conditions that might be related to the event. We will explore this in detail when we take up an example of online shopping further in this tutorial. Understanding naive Bayes and machine learning. Like with any of our other machine learning tools, it's important to understand where the naive Bayes fits in the hierarchy. So under the machine learning, we have supervised learning, and there is other things like unsupervised learning. There's also reward system. This falls under the supervised learning. And then under the supervised learning, there's classification. There's also regression, but we're going to be in the classification side. And then under classification is your naive Bayes. Let's go ahead and glance into where is naive Bayes used. Let's look at some of the use scenarios for it. As a classifier, we use it in face recognition. Is this Cindy or is it not Cindy or whoever? Or it might be used to identify parts of the face that they then feed into another part of the face recognition program. This is the eye, this is the nose, this is the mouth. Weather prediction, is it going to be rainy or sunny? Medical recognition, news prediction. It's also used in medical diagnosis. We might diagnose somebody as either as high risk or not as high risk for cancer or heart disease or other ailments. And news classification. When you look at the Google News and it says, well, is this political or is this world news? Or a lot of that's all done with the naive Bayes. Understanding naive Bayes classifier. Now, we already went through a basic understanding with the coins and the 2 heads and 2 tails and head tail, tail heads, etc. We're going to do just a quick review on that and remind you that the naive Bayes classifier is based on the Bayes theorem, which gives a conditional probability of event A given event B. And that's where the probability of A given B equals the probability of B given A times probability of A over probability of B. Remember, this is an algebraic function, so we can move these different entities around. We can multiply by the probability of B, so it goes to the left-hand side, and then we could divide by the probability of A given B, and just as easily come up with a new formula for the probability of B. To me, staring at these algebraic functions kind of gives me a slight headache. It's a lot better to see if we can actually understand how this data fits together in a table. And let's go ahead and start applying it to some actual data so you can see what that looks like. So we're going to start with the shopping demo. problem statement. And remember, we're going to solve this first in table form so you can see what the math looks like, and then we're going to solve it in Python. And in here we want to predict whether the person will purchase a product. Are they going to buy or don't buy? Very important if you're running a business, you want to know how to maximize your profits, or at least maximize the purchase of the people coming into your store. And we're going to look at a specific combination of different variables. In this case, we're going to look at the day, the discount, and the free delivery. And you can see here under the day, we want to know whether it's on the weekday. You know, somebody's working, they come in after work, or maybe they don't work. Weekend, you can see the bright colors coming down there, celebrating not being in work, or holiday. And did we offer a discount that day? Yes or no? Did we offer free delivery that day? Yes or no? And from this, we want to know whether the person's going to buy based on these traits so we can maximize them and find out the best system for getting somebody to come in and purchase our goods and products from our store. Now, having a nice visual is great, but we do need to dig into the data. So let's go ahead and take a look at the data set. We have a small sample data set of 30 rows. We're showing you the first 15 of those rows for this demo. Now, the actual data file you can request. Just type in below under the comments on the YouTube video, and we'll send you some more information and send you that file. As you can see here, the file is very simple, columns and rows. We have the day, the discount, the free delivery, and did the person purchase or not. And then we have under the day whether it was a weekday, a holiday, was it the weekend. This is a pretty simple set of data, and long before computers, people used to look at this data and calculate this all by hand. So let's go ahead and walk through this and see what that looks like when we put that into tables. Also note, in today's world, we're not usually looking at 3 different variables in 30 rows. Nowadays, because we're able to collect data so much, we're usually looking at 27, 30 variables across hundreds of rows. The first thing we want to do is we're going to take this data and based on the data set containing our 3 inputs, day, discount, and free delivery, we're going to go ahead and populate that to frequency tables for each attribute. So we want to know if they had a discount, how many people buy and did not buy. Did they have a discount, yes or no? Do we have a free delivery, yes or no? On those days, how many people made a purchase and how many people didn't? And the same with the 3 days of the week. Was it a weekday, a weekend, a holiday? And did they buy, yes or no? As we dig in deeper to this table for our Bayes theorem, let the event buy be A. Now remember, when we looked at the coins, I said we really want to know what the outcome is. Did the person buy or not? And that's usually event A is what you're looking for. And the independent variables, discount, free delivery, and day, be B. So we'll call that probability of B. Now let us calculate the likelihood table for one of the variables. Let's start with day, which includes weekday, weekend, and holiday. And let us start by summing all of our rows. So we have the weekday row, and out of the weekdays there's 9 plus 2, so it's 11 weekdays. There's 8 weekend days and 11 holidays. Wow, that's a lot of holidays. And then we want to sum up the total number of days. So we're looking at a total of 30 days. Let's start pulling some information from our chart and see where that takes us. And when we fill in the chart on the right, you can see that 9 out of 24 purchases are made on the weekday, 7 out of 24 purchases on the weekend, and 8 out of 24 purchases on a holiday. And out of all the people who come in, 24 out of 30 purchase. You can also see how many people do not purchase. On the weekday, it's 2 out of 6 didn't purchase, and so on and so on. We can also look at the totals, and you'll see on the right we put together some of the formulas. The probability of making a purchase on the weekend comes out at 11 out of 30. So out of the 30 people who came into the store throughout the weekend, weekday, and holiday, 11 of those purchases were made on the weekday. And then you can also see the probability of them not making a purchase. And this is done for, doesn't matter which day of the week. So we call that probability of no buy. It would be 6 over 30 or 0.2. So there's a 20% chance that they're not going to make a purchase no matter what day of the week it is. And finally, we look at the probability of B if A. In this case, we're going to look at the probability of the weekday and not buying. 2 of the no buys were done out of the weekend out of the 6 people who did not make purchases. So when we look at that, probability of the weekday without a purchase is going to be 0.33 or 33%. Let's take a look at this at different probabilities, and based on this likelihood table, let's go ahead and calculate conditional probabilities as below. The first 3 we just did. The probability of making a purchase on the weekday is 11 out of 30, or roughly 36 or 37%, 0.367. The probability of not making a purchase at all, doesn't matter what day of the week, is roughly 0.2 or 20%. And the probability of a weekday no purchase is roughly 2 out of 6. So 2 out of 6 of our no purchases were made on the weekday. And then finally we take our P of AB, If you look, we've kept the symbols up there. We got P of probability of B, probability of A, probability of B if A. We should remember that the probability of A if B is equal to the first one times the probability of no buys over the probability of the weekday. So we could calculate it both off the table we created. We can also calculate this by the formula, and we get the 0.367, which equals, or 0.33 times 0.2 over 0.367, which equals 0.179, or roughly 17 to 18%. And that'd be the probability of no purchase done on the weekday. And this is important because we can look at this and say, as the probability of buying on the weekday is more than the probability of not buying on the weekday, we can conclude that customers will most likely buy the product on a weekday. Now, we've kept our chart simple and we're only looking at one aspect. So you should be able to look at the table and come up with the same information or the same conclusion. That should be kind of intuitive at this point. Next, we can take the same setup. We have the frequency tables of all three independent variables. Now we can construct the likelihood tables for all three of the variables we're working with. We can take our day like we did before. We have weekday, weekend, and holiday. We filled in this table. And then we can come in and also do that for the discount, yes or no. Did they buy, yes or no? And we fill in that full table. So now we have our probabilities for a discount and whether the discount leads to a purchase or not, and the probability for free delivery. Does that lead to a purchase or not? And this is where it starts getting really exciting. Let us use these three likelihood tables to calculate whether a customer will purchase a product on a specific combination of day, discount, and free delivery, or not purchase. Here, let us take a combination of these factors. Day equals holiday, discount equals yes, free delivery equals yes. Let's dig deeper into the math and actually see what this looks like. And we're going to start with looking for the probability of them not purchasing on the following combinations of days. We are actually looking for the probability of A equal no buy, no purchase. And our probability of B we're going to set equal to, is it a holiday? Did they get a discount? Yes. And was it a free delivery? Yes. Before we go further, let's look at the original equation. The probability of A if B equals the probability of B given the condition A and the probability times the probability of A over the probability of B occurring. Now this is basic algebra, so we can multiply this information together. So when you see the probability of A given B, in this case the condition is B, C, and D, or the three different variables we're looking at. And when you see the probability of B, that would be the conditions. We're actually going to multiply those three separate conditions out. Probability of, you'll see that in just a second in the formula, times the full probability of A over the full probability of B. So here we are back to this, and we're going to have let A equal no purchase, and we're looking for the probability of B on the condition A, where A sets for three different things. Remember that equals the probability of A given the condition B. And in this case, we just multiply those three different variables together. So we have the probability of the discount times the probability of free delivery times the probability is the day equal a holiday. Those are our three variables of the probability of A if B. And then that is going to be multiplied by the probability of them not making a purchase. And then we want to divide that by the total probabilities, and they're multiplied together. So we have the probability of a discount, the probability of a free delivery, and the probability of it being on a holiday. When we plug those numbers in, we see that 1 out of 6 were no purchase on a discounted day, 2 out of 6 were a no purchase on a free delivery day, and 3 out of 6 were a no purchase on a holiday. Those are our three probabilities of A if B multiplied out. And then that has to be multiplied by the probability of a no purchase. And remember, the probability of a no buy is across all the data. So that's where we get the 6 out of 30. We divide that out by the probability of each category over the total number. So we get the 20 out of 30 had a discount, 23 out of 30 had a yes for free delivery, and 11 out of 30 were on a holiday. We plug all those numbers in, we get 0.178. So in our probability math, we have a 0.178 if it's a no buy for a holiday, a discount, and a free delivery. Let's turn that around and see what that looks like if we have a purchase. I promise this is the last page of math before we dig into the Python script. So here we're calculating the probability of the purchase using the same math we did to find out if they didn't buy. Now we want to know if they did buy. And again, we're going to go by the day equals a holiday, discount equals yes, free delivery equals yes, and let A equal buy. Now right about now you might be asking, why are we doing both calculations? Why would we want to know the no buys and buys for the same data going in? Well, we're going to show you that in just a moment, but we have to have both of those pieces of information so that we can figure it out as a percentage as opposed to a probability equation. And we'll get to that normalization here in just a moment. Let's go ahead and walk through this calculation. And as you can see here, the probability of A on the condition of B being all three categories. Did we have a discount with a purchase? Did we have a free delivery with a purchase? And is a day equal to holiday? And when we plug this all into that formula and multiply it all out, we get our probability of a discount, probability of a free delivery, probability of the day being a holiday, times the overall probability of it being a purchase, divided by, again multiplying the three variables out, the full probability of there being a discount, the full probability of being a free delivery, and the full probability of there being a day equal holiday. And that's where we get this 19 over 24 times 21 over 24 times 8 over 24 times the P of A, 24 over 30, divided by the probability of the discount, the free delivery times the day, or 20 over 30, 23 over 30 times 11 over 30, and that gives us our 0.986. So, what are we going to do with these two pieces of data we just generated? Well, let's go ahead and go over them. We have a probability of purchase equals 0.986. We have a probability of no purchase equals 0.178. So, finally, we have a conditional probabilities of purchase on this day. Let us take that, we're going to normalize it, and we're going to take these probabilities and turn them into percentages. This is simply done by taking the sum of probabilities, which equals 0.986 plus 0.178, and that equals the 1.164. If we divide each probability by the sum, we get the percentage. And so the likelihood of a purchase is 84.71%, and the likelihood of no purchase is 15.29%, given these three different variables. So if it's on a holiday, if it's with a discount and has free delivery, then there's an 84.71% chance that the customer is going to come in and make a purchase. Hooray! They purchased our stuff. We're making money. If you're owning a shop, that's is the bottom line, is you want to make some money so that you can keep your shop open and have a living. Now, I promised you that we were going to be finishing up the math here with a few pages. So we're going to move on and we're going to do two steps. The first step is I want you to understand why you want to use the naive Bayes. What are the advantages of naive Bayes? And then once we understand those advantages, we'll just look at that briefly, then we're going to dive in and do some Python coding. Advantages of naive Bayes classifier. So let's take a look at the 6 advantages of the naive Bayes classifier, and we're going to walk around this lovely wheel. It looks like an origami folded paper. The first one is very simple and easy to implement. Certainly you could walk through the tables and do this by hand. You got to be a little careful because the notations can get confusing. You have all these different probabilities, and I certainly mess those up as I put them on, is it on the top or the bottom? You got to really pay close attention to that. When you put it into Python, it's really nice because you don't have to worry about any of that. You let the Python handle that, the Python module. But understanding it, you can put it on a table and you can easily see how it works, and it's a simple algebraic function. It needs less training data, so if you have smaller amounts of data, this is a great, powerful tool for that. Handles both continuous and discrete data. It's highly scalable with number of predictors and data points. So as you can see, you can just keep multiplying different probabilities in there, and you can cover not just 3 different variables or sets. You can now expand this to even more categories. Number 5, it's fast. It can be used in real-time predictions. This is so important. This is why it's used in a lot of our predictions on online shopping carts, referrals, spam filters, is because there's no time delay as it has to go through and figure out a neural network or one of the other many setups where you're doing classification. And certainly there's a lot of other tools out there in the machine learning that can handle these, but most of them are not as fast as the naive Bayes. And then finally, it's not sensitive to irrelevant features. So it picks up on your different probabilities, and if you're short on data on one probability, you can it automatically adjust for that. Those formulas are very automatic, And so you can still get a very solid predictability even if you're missing data or you have overlapping data for two completely different areas. We see that a lot in doing census and studying of people and habits, where they might have one study that covers one aspect and another one that overlaps, and because the two overlap, they can then predict the unknowns for the group that they haven't done the second study on, or vice versa. So it's very powerful in that it is not sensitive to the irrelevant features, and in fact you can use it to help predict features that aren't even in there. So now we're down to my favorite part. We're going to roll up our sleeves and do some actual programming. We're going to do the use case text classification. Now, I would challenge you to go back and send us a note on the notes below underneath the video and request the data for the shopping cart. So you can plug that into Python code and do that on your own time so you can walk through it, since we walk through all the information on it. But we're going to do a Python code doing text classification, very popular for doing the naive Bayes. So we're going to use our new tool to perform a text classification of news headlines and classify news into different topics for a news website. As you can see here, we have a nice image of the Google News, and then related on the right, subgroups. I'm not sure where they actually pulled the actual data we're going to use from. It's one of the standard sets. But certainly this can be used on any of our news headlines in classification. So let's see how it can be done using the naive Bayes classifier. Now we're at my favorite part. We're actually going to write some Python script. Roll up our sleeves. And we're going to start by doing our imports. These are very basic imports, including our news group. And we'll take a quick glance at the target names. Then we're going to go ahead and start training our data set and putting it together. We'll put together a nice graph, because it's always good to have a graph to show what's going on. And once we've trained it and we've shown you a graph of what's going on, then we're going to explore how to use it and see what that looks like. Now, I'm going to open up my favorite editor, inline editor for Python. You don't have to use this. You can use whatever your editor that you like, whatever interface IDE you want. This just happens to be the Anaconda Jupyter Notebook. And I'm going to paste that first piece of code in here so we can walk through it. Let's make it a little bigger on the screen so you have a nice view of what's going on. And we're using Python 3, in this case 3.5. So this would work in any of your 3x. If you have it set up correctly, it should also work in a lot of the 2x. You just have to make sure all of the versions of the modules match your Python version. And in here, you'll notice the first line is your percentage matplot library in line. Now, 3 of these lines of code are all about plotting the graph. This one lets the notebook know, since it's an inline setup, that we want the graphs to show up on this page. Without it in a notebook like this, which is an Explorer interface, it won't show up. Now, a lot of IDEs don't require that. A lot of them, like if I'm working on one of my other setups, it just has a pop-up and the graph pops up on there. So you have that setup also. But for this, we want the matplot library inline. And then we're going to import NumPy as NP. That's NumPy, which has a lot of different formulas in it that we use for both of our Scikit-learn module. And we also use it for any of the upper math functions in Python. And it's very common to see that as NP, NumPy as NP. The next 2 lines are all about our graphing. Remember I said 3 of these were about graphing? Well, we need our matplot library.pyplot as PLT, and you'll see that PLT is a very common setup, as is the SNS and just like the NP. And we're going to import Seaborn as SNS, and we're going to do the SNS.set. Now, Seaborn sits on top of pyplot, and it just makes a really nice heat map. It's really good for heat maps. And if you're not familiar with heat maps, that just means we give it a color scale. The term comes from the brighter red it is, the hotter it is in some form of data, and you can set it to whatever you want. And we'll see that later on. So you'll see that those 3 lines of code here are just importing the graph function so we can graph it. And as a data scientist, you always want to graph your data and have some kind of visual. It's really hard just to shove numbers in front of people and they look at it and it doesn't mean anything. And then from the sklearn.datasets, we're going to import the fetch 20 news groups. Very common one for analyzing, tokenizing words and setting them up and exploring how the words work and how do you categorize different things when you're dealing with documents. And then we set our data equal to fetch 20 news groups. So our data variable will have the data in it. And we're going to go ahead and just print the target names, data.target names. And let's see what that looks like. And you'll see here we have alt atheism, comp graphics, comp OS, MS, Windows.miscellaneous. And it goes all the way down to talkpolitics.miscellaneous, talkreligion.miscellaneous. These are the categories they've already assigned to this news group. And it's called fetch 20 because you'll see I believe there's 20 different topics in here, or 20 different categories as we scroll down. Now, we've gone through the 20 different categories, and we're going to go ahead and start defining all the categories and set up our data. So we're actually going to go ahead and get the data all set up and take a look at our data. And let's move this over to our Jupyter Notebook, and let's see what this code does. First, we're going to set our categories. Now, if you noticed up here, I could have just as easily set this equal to data.target_names, because it's the same thing. But we want to kind of spell it out for you so you can see the different categories. It kind of makes it more visual so you can see what your data is looking like in the background. Once we've created the categories, we're going to open up a train set. So this training set of data is going to go into fetch 20 news groups, and it's a subset in there called train, and categories equals categories. So we're pulling out those categories that match. And then if you have a train set, you should also have the testing set. We have test equals fetch 20 news groups, subset equals test, and categories equals categories. Let's go down one size so it all fits on my screen. There we go. And just so we can really see what's going on, let's see what happens when we print out one part of that data. So it creates train, and under train it creates train.data, and we're just going to look at data piece number 5. And let's go ahead and run that and see what that looks like. And you can see when I print train.data number 5 under train, it prints out one of the articles. This is article number 5. You can go through and read it on there. And we can also go in here and change this to test, which should look identical because it's splitting the data up into different groups, train and test. And we'll see test number 5 is a different article, but it's another article in here. And maybe you're curious and you want to see just how many articles are in here. We could do length of train.data. And if we run that, you'll see that the training data has 11,314 articles. So we're not going to go through all those articles. That's a lot of articles. But we can look at one of them just so you can see what kind of information is coming out of it and what we're looking at. And we'll just look at number 5 for today. And here we have it. Rewording the Second Amendment IDs, VTT, lines 58, in article, etc. And you can scroll all the way down and see all the different parts to there. Now, we've looked at it, and that's pretty complicated when you look at one of these articles to try to figure out how do you weight this. If you look down here, we have different words, and maybe the word from. Well, from is probably in all the articles, so it's not going to have a lot of meaning as far as trying to figure out whether this article fits one of the categories or not. So trying to figure out which category it fits in based on these words is where the challenge comes in. Now that we've viewed our data, we're going to dive in and do the actual predictions. This is the actual naive Bayes. And we're going to throw another model at you, or another module at you here in just a second. We can't go into too much detail, but it deals specifically working with words and text and what they call tokenizing those words. So let's take this code and let's skip on over to our Jupyter Notebook and walk through it. And here we are in our Jupyter Notebook. Let's paste that in there. And I can run this code right off the bat. It's not actually going to display anything yet, but it has a lot going on in here. So at the top, we had the print module from the earlier one. I didn't know why that was in there. So we're going to start by importing our necessary packages. And from the Scikit-learn features extraction.txt, we're going to import tf-idf vectorizer. I told you we're going to throw a module at you. We can't go too much into the math behind this or how it works. You can look it up. The notation for the math is usually tf.idf. And that's just a way of weighing the words. And it weighs the words based on how many times they're used in a document, how many times or how many documents they're used in. And it's a well-used formula. It's been around for a while. It's a little confusing to put this in here, but let's let it know that it just goes in there and weights the different words in the document for us. That way we don't have to wait. And if you put a weight on it, if you remember I was talking about that up here earlier, if these are all emails, they probably all have the word from in them. From probably has a very low weight. It has very little value in telling you what this document's about. Same with words like in article, in articles, in, cost of, un, maybe cost might, or where words like criminal, weapons, destruction, these might have a heavier weight because they describe a little bit more what the article's doing. Well, how do you figure out all those weights in the different articles? That's what this module does. That's what the tf-idf vectorizer is going to do for us. And then we're going to import our Scikit-learn.naive Bayes, and that's our multinomial NB. Multinomial naive Bayes. Pretty easy to understand that, where that comes from. And then finally we have the Scikit-learn pipeline import make pipeline. Now, the make pipeline is just a cool piece of code because we're going to take the information we get from the TF-IDF vectorizer and we're going to pump that into the multinomial NB. So a pipeline is just a way of organizing how things flow. It's used commonly. You probably already guessed what it is if you've done any businesses. They talk about the sales pipeline. If you're on a work crew or a project manager, you have your pipeline of information that's going through, or your projects and what has to be done in what order. That's all this pipeline is. We're going to take the TF-ID vectorizer and then we're going to push that into the multinomial NB. Now, we've designated that as the variable model. We have our pipeline model. And we're going to take that model, and this is just so elegant. This is done in just a couple lines of code. Model.fit. And we're going to fit the data, and first the train data, and then the train target. Now, the train data has the different articles in it. You can see the one we were just looking at. And the train.target is what category they already categorized that particular article as. And what's happening here is the train data is going into the TF-ID vectorizer. So when you have one of these articles, it goes in there, it weights all the words in there. So there's thousands of words with different weights on them. I remember once running a model on this and I literally had 2.4 million tokens go into this. So when you're dealing like large document bases, you can have a huge number of different words. It then takes those words, gives them a weight, and then based on that weight, based on the words and the weights, and then puts that into the multinomial NB. And once we go into our naive Bayes, we want to put the train target in there. So the train data that's been mapped to the TF-ID vectorizer is now going through the multinomial NB, and then we're telling it, well, these are the answers. These are the answers to the different documents. So this document that has all these words with these different weights from the first part is going to be whatever category it comes out of. Maybe it's the talk show or the article on religion, miscellaneous. Once we fit that model, we can then take labels and we're going to set that equal to model.predict. Most of the Scikit-learn use the term .predict to let us know that we've now trained the model and now we want to get some answers. And we're going to put our test data in there because our test data is the stuff we held off to the side. We didn't train it on there and we don't know what's going to come up out of it, and we just want to find out how good our labels are. Do they match what they should be? Now, I've already run this through. There's no actual output to it to show. This is just setting it all up. This is just training our model, creating the labels so we can see how good it is, and then we move on to the next step to find out what happened. To do this, we're going to go ahead and create a confusion matrix and a heat map. So the confusion matrix, which is confusing just by its very name, is basically going to ask how confused is our answer. Did it get it correct, or did it miss some things in there or have some missed labels? And then we're going to put that on a heat map so we'll have some nice colors to look at to see how that plots out. Let's go ahead and take this code and see how that, take a walk through it and see what that looks like. So back to our Jupyter notebook, I'm going to put the code in there, and let's go ahead and run that code. Take it just a moment. And remember, we had the inline, that way my graph shows up on the inline here. And let's walk through the code and then we'll look at this and see what that means. So, make it a little bit bigger. There we go. No reason not to use the whole screen. Too big. So we have here, from Scikit-learn metrics, import confusion matrix. And that's just going to generate a set of data that says the prediction was such, the actual truth was either agreed with it or is something different. And it's going to add up those numbers so we can take a look and just see how well it worked. And we're going to set a variable mat equal to confusion matrix. And we have our test target, our test data that was not part of the training. Very important in data science, we always keep our test data separate. Otherwise, it's not a valid model if we can't properly test it with new data. And this is the labels we created from that test data. These are the ones that we predict it's going to be. So we go in and we create our SN heat map. The SNS is our seaborn, which sits on top of the pie plot. So when we create a SNS.heatmap, we take our confusion matrix, and it's going to be mat.t. And do we have other variables that go into the SNS.heatmap? We're not going to go into detail what all the variables mean. The annotation equals true. That's what tells it to put the numbers here. So you have the 166, the 1, the 0001. Format D and C bar equals false have to do with the format. If If you take those out, you'll see that some things disappear. And then the X tick labels and the Y tick labels, those are our target names. And you can see right here, that's the alt atheism, comp graphics, comp OS, MS, Windows, miscellaneous. And then finally, we have our plt.x label. Remember, the SNS or the Seaborn sits on top of our matplot library, our PLT. And so we want to just tell it x label equals a true is true. The labels are true, and then the y label is prediction label. So when we say a true, this is what it actually is, and the prediction is what we predicted. And let's look at this graph, because that's probably a little confusing the way I rattled through it. And what I'm going to do is I'm going to go ahead and flip back to the slides, because they have a black background they put in there that helps it shine a little bit better, so you can see the graph a little bit easier. So in reading this graph, what we want to look at is how the color scheme has come out. And you'll see a line right down the middle, diagonally, from upper left to bottom right. What that is if you look at the labels, we have our predicted label on the left and our true label on the right. Those are the numbers where the prediction and the true come together. And this is what we want to see, is we want to see those lit up. That's what that heat map does, is you can see that it did a good job of finding those data. And you'll notice that there's a couple of red spots on there where it missed. You know, it's a little confused when we talk about talk religion miscellaneous versus talk politics miscellaneous, social religion Christian versus alt atheism. It mislabeled some of those. And those are very similar topics, so you could understand why it might mislabel them. But overall, it did a pretty good job. If we're going to create these models, we want to go ahead and be able to use them. So let's see what that looks like. To do this, let's go ahead and create a definition, a function to run. And we're going to call this function, let me just expand that just a notch here. There we go. I like mine in big letters. Predict categories. We want to predict the category. We're going to send it S, a string. And then we're sending it train equals train. We have our training model. And then we had our pipeline, model equals model. This way we don't have to resend these variables each time. The definition knows that because I said train equals train, and I put the equal for model. And then we're going to set the prediction equal to the model.predictS. So it's going to send whatever string we send to it. It's going to push that string through the pipeline, the model pipeline. It's going to go through and tokenize it and put it through the TF, IDF, convert that into numbers and weights for all the different documents and words, and then it'll put that through our naive Bayes. And from it, we'll go ahead and get our prediction. We're going to predict what value it is. And so we're going to return train.targetNamesPredict of 0. And remember that the train.targetNames, that's just categories. I could have just as easily put categories in there .predict of 0. So we're taking the prediction, which is a number, and we're converting it to an actual category. We're converting it from, I don't know what the actual numbers are, but let's say 0 equals alt atheism. So we're going to convert that 0 to the word, or 1, maybe it equals comp graphics. So we're going to convert number 1 into comp graphics. That's all that is. And then we got to go ahead and then we need to go ahead and run this. So I load that up. And then once I run that, we can start doing some predictions. I'm going to go ahead and type in predict category. And let's just do predict category Jesus Christ. And it comes back and says it's social, religion, Christian. That's pretty good. Now, note I didn't put print on this. One of the nice things about the Jupyter Notebook Editor and a lot of inline editors is if you just put the name of the variable out as returning the variable train.target_names, it'll automatically print that for you. In your own IDE, you might have to put in print. Let's see where else we can take this. And maybe you're a space science buff. So how about sending load to International Space Station? And if we run that, we get science space. Or maybe you're a automobile buff. And let's do, they were going to tell me Audi is better than BMW, but I'm going to do BMW is better than an Audi. So maybe you're a car buff. And we run that, and you'll see it says recreational. I'm assuming that's what REC stands for. Autos. So I did a pretty good job labeling that one. How about if we have something like a caption running through there? President of India. And if we run that, it comes up and says talk, politics, miscellaneous. So when we take our definition or our function and we run all these things through, kudos, we made it. We were able to correctly classify texts into different groups based on which category they belong to using the naive Bayes classifier. Now, we did throw in the pipeline, the TF IDF vectorizer. We threw in the graphs. Those are all things that you don't necessarily have to know to understand the naive Bayes setup or classifier, but they're important to know. One of the main uses for the naive Bayes is with the TF IDF tokenizer or vectorizer, where it tokenizes the word and adds labels. And we use the pipeline because you need to push all that data through, and it makes it really easy and fast. You don't have to know those to understand naive Bayes, but they certainly help for understanding the industry and data science. And we can see our categorizer, our naive Bayes classifier. We were able to predict the category religion, space, motorcycles, autos, politics, and properly classify all these different things we pushed into our prediction and our trained model. Before we dive into the SVM, let's take a look at applications of the support vector machine, at least some general ones that are commonly used with it. Face detection, text and hypertext categorization, classification of images, and bioinformatics. These are only but a few of those that are used with this SVM. As we go through this lesson, see if you can figure out what other ones you could apply it to, and also what you would want to use some other tools for. So in this example, last week, my son and I visited a fruit shop. Dad, is that an apple or a strawberry? So the question comes up, what fruit did I just pick up from the fruit stand? After a couple of seconds, you could figure out that it was a strawberry. So let's take this model a step further, and let's, why not build a model which can predict an unknown data? And in this, we're going to be looking at some sweet strawberries or crispy apples. We want it to be able to label those two and decide what the fruit is. And we do that by having data already put in. So we already have a bunch of strawberries, we know are strawberries, and they're already labeled as such. We already have a bunch of apples, we know are apples and are labeled as such. Then once we train our model, that model then can be given the new data, and the new data is this image. In this case, you can see a question mark on it, and it comes through and goes, it's a strawberry. In this case, we're using the support vector machine model. SVM is a supervised learning method that looks at data and sorts it into one of two categories. And in this case, we're sorting the strawberry into the strawberry side. At this point, you should be asking the question, how does the prediction work? Before we dig into an example with numbers, let's apply this to our fruit scenario. We have our support vector machine. We've taken it and we've taken a labeled sample of data, strawberries and apples, and we draw on a line down the middle between the two groups. This split now allows us to take new data, in this case an apple and a strawberry, and place them in the appropriate group based on which side of the line they fall in. And that way we can predict the unknown. As colorful and tasty as the fruit example is, let's take a look at another example with some numbers involved, and we can take a closer look at how the math works. In this example, we're going to be classifying men and women, and we're going to start with a set of people with a different height and a different weight. And to make this work, we'll have to have a sample data set of female, where you have their height and weight, 174, 65, 174, 88, and so on. And we'll need a sample data set of the male. They have a height 179, 90, 180 to 80, and so on. Let's go ahead and put this on a graph so we have a nice visual. So you can see here we have two groups based on the height versus the weight. And on the left side, we're going to have the women. On the right side, we're going to have the men. Now, if we're going to create a classifier, let's add a new data point and figure out if it's male or female. So before we can do that, we need to split our data first. We can split our data by choosing any of these lines. In this case, we've drawn two lines through the data in the middle that separates the men from the women. But to predict the gender of a new data point, we should split the data in the best possible way. And we say the best possible way because this line has a maximum space that separates the two classes. Here you can see there's a clear split between the two different classes, and in this one there's not so much a clear split. This doesn't have the maximum space that separates the two. That is why this line best splits the data. We don't want to just do this by eyeballing it. And before we go further, we need to add some technical terms to this. We can also say that the distance between the points in the line should be as far as possible. In technical terms, we can say the distance between the support vector and the hyperplane should be as far as possible. And this is where the support vectors are the extreme points in the data set. And if you look at this data set, they have circled 2 points which seem to be right on the outskirts of the women and one on the outskirts of the men. And hyperplane has a maximum distance to the support vectors of any class. Now you'll see the line down the middle, and we call this the hyperplane because when you're dealing with multiple dimensions, it's really not just a line but a plane of intersections. And you can see here where the support vectors have been drawn in dashed lines. The math behind this is very simple. We take d plus, the shortest distance to the closest positive point, which would be on the men's side, and d minus is the shortest distance to the closest negative point, which is on the women's side. The sum of d plus and d minus is called the distance margin, or the distance between the two support vectors that are shown in the dashed lines. And then, by finding the largest distance margin, we can get the optimal hyperplane. Once we've created an optimal hyperplane, we can easily see which side the new data fits in. And based on the hyperplane, we can say the new data point belongs to the male gender. Hopefully that's clear how that works on a visual level. As a data scientist, you should also be asking what happens if the hyperplane is not optimal. If we select a hyperplane having low margin, then there is a high chance of misclassification. This particular SVM model, the one we discussed so far, is also called or referred to as the LSVM. So far so clear, but a question should be coming up. We have our sample data set, but instead of looking like this, what if it looked like this, where we have two sets of data, but one of them occurs in the middle of another set? You can see here where we have the blue and the yellow, and then blue again on the other side of our data line. In this data set, we can't use a hyperplane. So when you see data like this, it's necessary to move away from a 1D view of the data to a two-dimensional view of the data. And for the transformation, we use what's called a kernel function. The kernel function will take the 1D input and transfer it to a two-dimensional output. As you can see in this picture here, the 1D when transferred to a two-dimensional makes it very easy to draw a line between the two data sets. What if we make it even more complicated? How do we perform an SVM for this type of data set? Here you can see we have a two-dimensional data set where the data is in the middle surrounded by the green data on the outside. In this case, we're going to segregate the two classes. We have our sample data set, and if you draw a line through it, it's obviously not an optimal hyperplane in there. So to do that, we need to transfer the 2D to a 3D array. And when you translate it into a three-dimensional array using the kernel, you can see where you can place a hyperplane right through it and easily split the data. Before we start looking at a programming example and dive into the script, let's look at the advantage of the support vector machine. We'll start with high-dimensional input space, or sometimes referred to as the curse of dimensionality. We looked at earlier 1 dimension, 2 dimension, 3 dimension. When you get to 1,000 dimensions, a lot of problems start occurring with most algorithms that have to be adjusted for. The SVM automatically does that in high dimensional space. One high dimensional space that we work on is sparse document vectors. This is where we tokenize the words in documents so we can run our machine learning algorithms over them. I've seen ones get as high as 2.4 million different tokens. That's a lot of vectors to look at. And finally, we have regularization parameter. The regularization parameter, or lambda, is a parameter that helps figure out whether we're going to have a bias or overfitting of the data. Whether it's going to be overfitted to a very specific instance or it's going to be biased to a high or low value. With the SVM, it naturally avoids the overfitting and bias problems that we see in many other algorithms. These three advantages of the support vector machine make it a very powerful tool to add to your repertoire of machine learning tools. Now, we did promise you a use case study where we're actually going to dive into some Python programming. And so we're going to go into a problem statement and start off with the zoo. So in the zoo example, we have family members going to the zoo and we have the young child going, "Dad, is that a group of crocodiles or alligators?" Well, that's hard to differentiate. And zoos are a great place to start looking at science and understanding how things work, especially as a young child. And so we can see the parents sitting here thinking, well, what is the difference between a crocodile and an alligator? Well, one, crocodiles are larger in size, alligators are smaller in size. Snout width, the crocodiles have a narrow snout and alligators have a wider snout. And of course, in the modern day and age, the father's sitting here thinking, how can I turn this into a lesson for my son? And he goes, let a support vector machine segregate the two groups. I don't know if my dad ever told me that, but that would be funny. Now, in this example, we're not going to use actual measurements and data. We're just using that for imagery. And that's very common in a lot of machine learning algorithms and setting them up. But let's roll up our sleeves and we'll talk about that more in just a moment as we break into our Python script. So here we arrive in our actual coding. And I'm going to move this into a Python editor in just a moment. But let's talk a little bit about what we're going to cover. First, we're going to cover in the code the setup, how to actually create our SVM. And you're going to find that there's only 2 lines of code that actually create it, and the rest of it is done so quick and fast that it's all here on the first page. And we'll show you what that looks like as far as our data, because we're going to create some data. I talked about creating data just a minute ago. And so we'll get into the creating data here, and you'll see this nice correction of our 2 blobs, and we'll go through that in just a second. And then the second part is we're going to take this and we're going to bump it up a notch. We're going to show you what it looks like behind the scenes. But let's start with actually creating our setup. I like to use the Anaconda Jupyter Notebook because it's very easy to use, but you can use any of your favorite Python editors or setups and go in there. But let's go ahead and switch over there and see what that looks like. So here we are in the Anaconda Python Notebook, or Anaconda Jupyter Notebook with Python. We're using Python 3. I believe this is 3.5, but it should be work in any of your 3x versions. And you'd have to look at the Scikit-learn and make sure if you're using a 2x version or an earlier version. And let's go ahead and put our code in there. And one of the things I like about the Jupyter Notebook is I can go up to View, and I'm going to go ahead and toggle the line numbers on to make it a little bit easier to talk about. And we can even increase the size because this is edited in this case I'm using Google Chrome Explorer, and that's how it opens up for the editor. Although like I said, any editor will work. Now the first step is going to be our imports. And we're going to import 4 different parts. The first 2 I want you to look at are line 1 and line 2 are NumPy as NP and matplotlibary.pyplot as PLT. Now these are very standardized imports when you're doing work. The first one is the numbers Python. We need that because part of the platform we're using uses that for the NumPy array. And I'll talk about that in a minute so you can understand why we want to use a NumPy array versus the standard Python array. And normally it's pretty standard setup to use NP for NumPy. The matplot library is how we're going to view our data. So this has, you do need the NP for the Scikit-learn module, but the matplot library is purely for our use for visualization. And so you really don't need that for the SVM, but we're going to put it there so you have a nice visual aid and we can show you what it looks like. That's really important at the end when you finish everything, so you have a nice display for everybody to look at. And then finally, I'm going to jump one ahead to line number 4. That's the sklearn.datasets.samples generator import and make blobs. And I told you that we were going to make up data. And this is a tool that's in the Scikit-learn to make up data. I personally don't want to go to the zoo, get in trouble for jumping over the fence, and probably get eaten by the crocodiles or alligators as I work on measuring their snouts and width and length. Instead, we're just going to make up some data. And that's what that make blobs is. It's a wonderful tool if you're ready to test your setup and you're not sure about what data you're going to put in there. You can create this blob and it makes it real easy to use. And finally, we have our actual SVM, the Scikit-learn import SVM on line 3. So that covers all our imports. We're going to create, remember I used the make blobs to create data. And we're going to create a capital X and a lowercase y equals make blobs in samples equals 40. So we're going to make 40 lines of data. It's going to have 2 centers with a random state equals 20. So each group's going to have 20 different pieces of data in it. And the way that looks is that we'll have under X an XY plane. So I'll have 2 numbers under X, and Y will be 0 or 1. That's the 2 different centers. So we have yes or no, in this case alligator or crocodile. That's what that represents. And then I told you that the actual Scikit-learn or the SVM is in 2 lines of code. And we see it right here with CLF equals SVM.SVC kernel equals linear, and I set C equal to 1. Although in this example, since we are not regularizing the data, because we want it to be very clear and easy to see, I went ahead, you can set it to 1,000 a lot of times when you're not doing that. But for this thing, linear, because it's a very simple linear example, we only have the 2 dimensions, and it'll be a nice linear hyperplane. It'll be a nice linear line instead of a full plane. So we're not dealing with a huge amount of data. And then all we have to do is do CLF.fit x, y. And that's it. CLF has been created, and then we're going to go ahead and display it. And I'm going to talk about this display here in just a second, but let me go ahead and run this code. And this is what we've done, is we've created 2 blobs. You'll see the blue on the side and then kind of an orangish on the other side. That's our 2 sets of data. They represent, one represents crocodiles and one represents alligators. And then we have our measurements. In this case, we have like the width and length of the snout. And I did say I was going to come up here and talk just a little bit about our plot. And you'll see PLT, that's what we imported. We're going to do a scatter plot. That means we're just putting dots on there. And then look at this notation. I have the capital X, and then in brackets I have a colon, comma, 0. That's from NumPy. If you did that in a regular array, you'll get an error in a Python array. You have to have that in a NumPy array. It turns out that our make blobs returns a NumPy array. And this notation is great because what it means is the first part is the colon. It means we're going to do all the rows. That's all the data in our blob we created under capital X. And then the second part has a comma 0. We're only going to take the first value. And then if you notice, we do the same thing, but we're going to take the second value. Remember, we always start with 0 and then 1. So we have column 0 and column 1. And you can look at this as our XY plots. The first one is the X plot, and the second one is the Y plot. So the first one is on the bottom, 0, 2, 4, 6, 8, and 10. And then the second one, X of the 1, is the 4, 5, 6, 7, 8, 9, 10 going up the left-hand side. S equals 30 is just the size of the dots, so we can see them instead of real tiny dots. And then CMap equals plt.cm.paired. And you'll also see the C equals Y. That's the color. We're using two colors, 0, 1, and that's why we get the nice blue and the two different colors for the alligator and the crocodile. Now you can see here that we did this, the actual fit was done in 2 lines of code. A lot of times there'll be a third line where we regularize the data. We set it between like -1 and 1, and we reshape it. But for this, it's not necessary, and it's also kind of nice because you can actually see what's going on. And then if we wanted to actually run a prediction. Let's take a look and see what that looks like. And to predict some new data, and we'll show this again as we get towards the end of digging in deep, you can simply assign your new data. In this case, I am giving it a width and length 3, 4 and a width and length 5, 6. And note that I put the data as a set of brackets and then I have the brackets inside. And the reason I do that is because when we're looking at data, it's designed to process a large amount of data coming in. We don't want to just process one line at a time. And so in this case, I'm processing 2 lines. And then I'm just going to print, and you'll see clf.predict new data. So the clf and the .predict part is going to give us an answer, and let's see what that looks like. And you'll see 0, 1. So predicted the first one, the 3, 4, is going to be on the one side, and the 5, 6 is going to be on the other side. So one came out as an alligator, and one came out as a crocodile. Now that's a pretty short explanation for the setup, but really we want to dig in and see what's going on behind the scenes. And let's see what that looks like. So the next step is to dig in deep and find out what's going on behind the scenes. And also put that in a nice pretty graph. We're going to spend more work on this than we did actually generating the original model. And you'll see here that we go through a few steps, and I'll move this over to our editor in just a second. We come in, we create our original data. It's exactly identical to the first part, and I'll explain why we redid that and show you how not to redo that. And then we're going to go in there and add in those lines. We're going to see what those lines look like and how to set those up. And finally, we're going to plot all that on here and show it. And you'll get a nice graph with what we saw earlier when we were going through the theory behind this, where it shows the support vectors and the hyperplane. And those are done where you can see the support vectors as the dashed lines and the solid line, which is the hyperplane. Let's get that into our Jupyter notebook. Before I scroll down to a new line, I want you to notice line 13. It has plot show. And we're going to talk about that here in just a second, but let's scroll down to a new line down here. And I'm going to paste that code in. And you'll see that the plot show has moved down below. Let's scroll up a little bit. And if you look at the top here of our new section, 1, 2, 3, and 4 is the same code we had before. And let's go back up here and take a look at that. We're going to fit the values on our SVM, and then we're going to plot scatter it, and then we're going to do a plot show. So you should be asking, why are we redoing the same code? Well, when you do the plot show, that blanks out what's in the plot. So once I've done this plot show, I have to reload that data. Now we could do this simply by removing it up here, rerunning it, and then coming down here, and then we wouldn't have to rerun these first 4 lines of code. Now in this, it doesn't matter too much, and you'll see the plot show is down here and then removed, right there on line 5. I'll go ahead and just delete that out of there, because we don't want to blank out our screen. We want to move on to the next setup. So we can go ahead and just skip the first 4 lines, because we did that before. And let's take a look at the AX equals plt.gca. Now right now, we're actually spending a lot of time just graphing. That's all we're doing here. Okay, so this is how we display a nice graph with our results and our data. AX is very standard used variable when you talk about PLT, and it's just setting it to that axis, the last axis in the PLT. It can get very confusing if you're working with many different layers of data on the same graph, and this makes it very easy to reference the AX. So this reference is looking at the PLT that we created and we already mapped out our two blobs on. And then we want to know the limits. So we want to know how big the graph is. We can find out the x limit and the y limit simply with the get x limit and get y limit commands, which is part of our matplot library. And then we're going to create a grid. And you'll see down here we've set the variable xx equal to np.linespace, x limit 0, x limit 1, 30. And we've done the same thing for the y space. And then we're going to go in here and we create a mesh grid. And this is a NumPy command. So we're back to our numbers Python. Let's go through what these NumPy commands mean with the line space and the mesh grid. We've taken xx, small xx equals np line space, and we have our x limit 0 and our x limit 1, and we're going to create 30 points on it. And we're going to do the same thing for the y-axis. Now, this has nothing to do with our evaluation. It's all we're doing is we're creating a grid of data. And so we're creating a set of points between 0 and the x limit. We're creating 30 points, and the same thing with the y. And then the mesh grid loops those all together so it forms a nice grid. So if we were going to do this, say, between the limit 0 and 10 and do 10 points, we would have a 0, 0, 1, 1, 0, 1, 0, 2, 0, 3, 0, 4 to 10, and so on. You can just imagine a point at each corner of one of those boxes. And the mesh grid combines them all, so we take the YY and the XX we created and creates the full grid. And we've set that grid into the YY coordinates and the XX coordinates. Now remember, when we're working with NumPy and Python, we like to separate those. We like to have, instead of it being x comma 1, x comma y, and then x2 comma y2, and in the next set of data, it would be a column of x's and a column of y's. And that's what we have here, is we have a column of y's, and we put it as a capital YY, and a column of x's, capital XX, with all those different points being listed. And finally, we get down to the NumPy VStack. Just as we created those in the mesh grid, we're now going to put them all into one array, XY array. Now that we've created the stack of data points, we're going to do something interesting here. We're going to create a value z, and the z equals the CLF. That's our support vector machine we created, and we've already trained. And we have a dot decision function, and we're going to put the xy in there. So here we have all this data. We're going to put that xy in there, that data, and we're going to reshape it. And you'll see that we have the xx.shape in here. This literally takes the xx, resets it up connected to the y, and the z value lets us know whether it is the left-hand side. It's going to generate 3 different values, the z value does. And it'll tell us whether that data is a support vector to the left, the hyperplane in the middle, or the support vector to the right. So it generates 3 different values for each of those points. And those points have been reshaped so that they're right on a line, on those 3 different lines. So we've set all of our data up. We've labeled it to 3 different areas, and we've reshaped it. And we've just taken 30 points in each direction. If you do the math, you have 30 times 30, so that's 900 points of data. And we separated it between the 3 lines and reshaped it to fit those 3 lines. We can then go back to our matplot library, where we've created the AX, and we're going to create a contour. And you'll see here where we have contour, capital XX, capital YY. These have been reshaped to fit those lines. Z is the labels. So now we have the 3 different points with the labels in there, and we can set the colors equals K. And I told you we had 3 different labels, but we have 3 levels of data. The alpha just makes it kind of see-through, so it's only 0.5 of the value in there. So when we graph it, the data will show up from behind it, wherever the lines go. And finally, the line styles. This is where we set the 2 support vectors to be dash lines, and then a single one is just a straight line. That's what all of that setup does. And then finally, we take our ax.scatter. We're going to go ahead and plot the support vectors, but we've programmed it in there so that they look nice, like the dash line and the dash line on that grid. And you can see here, when we do the CLF dot support vectors, we are looking at column 0 and column 1. And then again, we have the S equals 100, so we're going to make them larger. And the line width equals 1, face colors equals none. Let's take a look and see what that looks like when we show it. And you can see when we get down to our end result, it creates a really nice graph we have our two support vectors in dashed lines, and they have the near data. So you can see those 2 points, or in this case the 4 points, where those lines nicely cleave the data. And then you have your hyperplane down the middle, which is as far from the 2 different points as possible, creating the maximum distance. So you can see that we have our nice output for the size of the body and the width of the snout, and we've easily separated the 2 groups of crocodile and alligator. Congratulations! You've done it. We've made it. Of course, these are pretend data for our crocodiles and alligators, but this hands-on example will help you to encounter any support vector machine projects in the future, and you can see how easy they are to set up and look at in depth. We're going to cover the k nearest neighbors, a lot referred to as KNN. And KNN is really a fundamental place to start in the machine learning. It's a basis of a lot of other things, and just the logic behind it is easy to understand and incorporated in other forms of machine learning. So today, what's in it for you? Why do we need KNN? What is KNN? How do we choose the factor k? When do we use KNN? How does KNN algorithm work? And then we'll dive into my favorite part, the use case. Predict whether a person will have diabetes or not. That is a very common and popular used data set as far as testing out models and learning how to use the different models in machine learning. By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values, our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws, how sharp are their claws, and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those two characteristics. Now tell me if it is a cat or a dog. An odd question, usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats. It must be a cat. Sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or it's not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we've gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put k equals 5. We'll talk about k in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose k? How do we know k equals 5? I mean, that was the value we put in there, so we're going to talk about it. How do we choose the factor k? KNN algorithm is based on feature similarity. Choosing the right value of k is a process called parameter tuning, and is important for better accuracy. So at k equals 3, we can classify, we have a question mark in the middle, as either as a square or not. Is it a square, or is it, in this case, a triangle? And so if we set k equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put k equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the k changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of k? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right k? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other. And in terms of KNN, the number of k, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things, and it's going to pick those things, and you might get a skewed answer. And if your k is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing k, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your k value odd. That helps it select better. So in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the k value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where you might get into a gig of data if it's really clean, it doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work? Consider a data set having two variables, height in centimeters and weight in kilograms. And each point is classified as normal or underweight. So we can see right here we have two variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the two edges of a triangle. We're computing the third edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point, and we placed it there in red, and we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13. And distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer. And it's not a really complicated math, so you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the three closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal. Hence, as per KNN algorithm, the class of 57170 should be normal. So a recap of KNN. Positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, you know if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine learning packages, but for a very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. You know, at 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly you can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up here and click on Cell. Actually, we want to go ahead and first insert a cell below, and then I'm going to go back up to the top cell, and I'm going to change the cell type to Markdown. That means this is not going to run as Python. It's a Markdown language. So if I run this first one, it comes up in nice big letters, which is kind of nice. Remind us what we're working on. And by now, you should be familiar with doing all of our imports. We're going to import the Pandas as PD, import NumPy as NP. Pandas is the Pandas data frame, and NumPy is a number array. Very powerful tools to use in here. So we have our imports. So we've brought in our Pandas, our NumPy, our two general Python tools. And then you can see over here we have our train test split. By now you should be familiar with splitting the data. We want to split part of it for training our thing and then training our particular model. And then we want to go ahead and test the remaining data just to see how good it is. Preprocessing, a standard scalar preprocessor, so we don't have a bias of really large numbers. Remember in the data we had like number of pregnancies isn't going to get very large, where the amount of insulin they take can get up to 256. So 256 versus 6. That will skew results. So we want to go ahead and change that so that they're all uniform between -1 and 1. And then the actual tool. This is the K-neighbors classifier we're going to use. And finally, the last three are 3 tools to test, all about testing our model. How good is it? We just put down test on there. And we have our confusion matrix, our F1 score, and our accuracy. So we have our 2 general Python modules we're importing, and then we have our 6 modules specific from the Scikit-learn setup. And then we do need to go ahead and run this so that these are actually imported. There we go. And then move on to the next step. And so in this set, we're going to go ahead and load the database. We're going to use Pandas. Remember, Pandas is PD. And we'll take a look at the data in Python. We looked at it in a simple spreadsheet, but usually I like to also pull it up so that we can see what we're doing. So here's our data set equals pd.readcsv. That's a Pandas command. And the diabetes folder I just put in the same folder where my IPython script is. If you put it in a different folder, you'd need the full length on there. We can also do a quick length of the data set. That is a simple Python command, len for length. We might even, let's go ahead and print that. We'll go print. And if you do it on its own line, length.dataset in the Jupyter Notebook, it'll automatically print it. But when you're in most of your different setups, you want to do the print in front of there. And then we want to take a look at the actual data set. And since we're in Pandas, we can simply do dataset head. And again, let's go ahead and add the print in there. If you put a bunch of these in a row, you know, the dataset 1 head, dataset 2 head, it only prints out the last one. So I usually always like to keep the print statement in there. But because most projects only use one data frame, Pandas data frame, doing it this way doesn't really matter. The other way works just fine. And you can see when we hit the run button, we have the 768 lines, which we knew, and we have our pregnancies. It's automatically given a label on the left. Remember, the head only shows the first 5 lines. So we have 0 through 4. And just a quick look at the data, you can see it matches what we looked at before. We have pregnancy, glucose, blood pressure, all the way to age, and then the outcome on the end. And we're going to do a couple things in this next step. We're going to create a list of columns where we can't have 0. There's no such thing as 0 skin thickness or 0 blood pressure, 0 glucose. Any of those, you'd be dead. So not a really good factor if they have a 0 in there because they didn't have the data. And we'll take a look at that because we're going to start replacing that information with a couple of different things. And let's see what that looks like. So first we create a nice list. As you can see, we have the values we talked about: glucose, blood pressure, skin thickness. And this is a nice way when you're working with columns is to list the columns you need to do some kind of transformation on. Very common thing to do. And then for this particular setup, we certainly could use there's some Panda tools that will do a lot of this where we can replace the NA. But we're going to go ahead and do it as a dataset column equals dataset column.replace. This is still Pandas. You can do a direct. There's also one that you look for your NAN. A lot of different options in here. But the NAN, NumPy NAN is what that stands for, is none. It doesn't exist. So the first thing we're doing here is we're replacing the 0 with a NumPy none. There's no data there. That's what that says. That's what this is saying right here. So put the 0 in, and we're going to replace zeros with no data. So if it's a 0, that means the person's, well, hopefully not dead. Hopefully they just didn't get the data. The next thing we want to do is we're going to create the mean, which is the integer from the data set from the column .mean, where we skip NAs. We can do that. That is a Pandas command there, the skip NA. So we're going to figure out the mean of that data set. And then we're going to take that data set column and we're going to replace all the NP-NAN with the means. Why did we do that? And we could have actually just taken this step and gone right down here and just replaced 0 and skip anything where, except you could actually, there's a way to skip zeros and then just replace all the zeros. But in this case, we want to go ahead and do it this way. So you can see that we're switching this to a non-existent value. Then we're going to create the mean. Well, this is the average person. So if we don't know what it is, if they did not get the data and the data is missing, one of the tricks is you replace it with the average. What is the most common data for that? This way, you can still use the rest of those values to do your computation, and it kind of just brings that particular value or those missing values out of the equation. Let's go ahead and take this and we'll go ahead and run it. Doesn't actually do anything, so we're still preparing our data. If you want to see what that looks like, we don't have anything in the first few lines, so it's not going to show up. But we certainly could look at a row. Let's do that. Let's go into our data set. Let's print a data set. And let's pick, in this case, let's just do glucose. And if I run this, this is going to print all the different glucose levels going down. And we thankfully don't see anything in here that looks like missing data, at least on the ones it shows. You can see it skipped a bunch in the middle. Because that's what it does. If you have too many lines in Jupyter Notebook, it'll skip a few and go on to the next in a data set. Let me go and remove this, and we'll just zero out that. And of course, before we do any processing, before proceeding any further, we need to split the data set into our train and testing data. That way we have something to train it with and something to test it on. And you're going to notice we did a little something here with the Pandas database code. There we go, my drawing tool. We've added in this right here off the data set. And what this says is that the first one in Pandas, this is from the PD Pandas, it's going to say within the data set, we want to look at the I location and it is all rows. That's what that says. So we're going to keep all the rows, but we're only looking at column 0 to 8. Remember column 9, here it is right up here, we printed it in here, is outcome. Well, that's not part of the training data, that's part of the answer. Yes, column 9, but it's listed as 8, number 8. So 0 to 8 is 9 columns. So 8 is the value. And when you see it in here, 0, this is actually 0 to 7. It doesn't include the last one. And then we go down here to Y, which is our answer, and we want just the last one, just column 8. And you can do it this way with this particular notation. And then if you remember, we imported the train test split. That's part of the Scikit-learn right there. And we simply put in our X and our Y. We're going to do random state equals 0. You don't have to necessarily seed it. That's a seed number. I think the default is 1 when you seed it. I'd have to look that up. And then the test size. Test size is 0.2. That simply means we're going to take 20% of the data and put it aside so that we can test it later. That's all that is. And again, we're going to run it. Not very exciting. So far we haven't had any printout other than to look at the data. But that is, a lot of this is prepping this data. Once you prep it, the actual lines of code are quick and easy. And we're almost there, but the actual running of our KNN, we need to go ahead and scale the data. If you remember correctly, we're fitting the data in a standard scaler, which means instead of the data being from 5 to 303 in one column, and the next column is 1 to 6, we're going to set that all so that all the data is between -1 and 1. That's what that standard scaler does. Keeps it standardized. And we only want to fit the scaler with the training set, but we want to make sure the testing set is, the X test going in is also transformed, so it's processing it the same. So here we go with our standard scaler. We're going to call it sc_x for the scaler, and we're going to import the standard scaler into this variable, and then our X train equals sc_x dot fit transform. So we're creating the scaler on the X train variable, and then our X test, we're also going to transform it. So we've trained and transformed the X train, and then the X test isn't part of that training. It isn't part of training the transformer. It just gets transformed. That's all it does. And again, we're going to go ahead and run this. And if you look at this, we've now gone through these steps, all 3 of them. We've taken care of replacing our zeros for key columns that shouldn't be 0, and we replace that with the means of those columns. That way that they fit right in with our data models. We've come down here and we split the data. So now we have our test data and our training data. And then we've taken and we've scaled the data. So all of our data going in. Now, no, we don't train the Y part, the Y train and Y test. That never has to be trained. It's only the data going in. That's what we want to train in there. Then define the model using k-neighbors classifier and fit the train data in the model. So we do all that data prep. And you can see down here we're only going to have a couple lines of code where we're actually building our model and training it. That's one of the cool things about Python and how far we've come. It's such an exciting time to be in machine learning because there's so many automated tools. Let's see, before we do this, let's do a quick length of, and let's do Y. Let's just do length of Y. And we get 768. And if we import math, we do math dot square root. Let's do Y train. There we go. It's actually supposed to be X train. Before we do this, let's go ahead and do import math and do math square root length of Y test. And when I run that, we get 12.409. I wanted to show you where this number comes from we're about to use. 12 is an even number. So if you're ever voting on things, remember the neighbors all vote, don't want to have an even number of neighbors voting. So we want to do something odd. And let's just take one away and we'll make it 11. Let me delete this out of here. That's one of the reasons I love Jupyter Notebook, because you can flip around and do all kinds of things on the fly. So we'll go ahead and put in our classifier. We're creating our classifier now. And it's going to be the k-neighbors classifier. N neighbors equal 11. Remember we did 12 minus 1 for 11, so we have an odd number of neighbors. P equals 2, because we're looking for are they diabetic or not. And we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of measure this, but the Euclidean is the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll jump into the F1 score. And finally, accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, Y test, Y predict. So those are the two values we're going to put in there. And let me go ahead and run that and print it out. And the way you interpret this is you have the Y predicted, which would be your title up here. We could do, let's just do PRED. Predicted across the top, and actual going down. Actual. It's always hard to write in here, actual. That means that this column here down the middle, that's the important column. And it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like three different, if you're looking at this across three different variables instead of just two, you'd end up with the third row down here and the column going down the middle. So in the first case we have the and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an Scikit-learn and running the KNN, the K nearest neighbor on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and we can pretty much round that off and just say we have an accuracy of 80%. Tells us it is a pretty fair fit in the model.
So what is K-means clustering? K-means clustering is an unsupervised learning algorithm. In this case, you don't have labeled data, unlike in supervised learning. So you have a set of data and you want to group them. And as the name suggests, you want to put them into clusters, which means objects that are similar in nature, similar in characteristics, need to be put together. So that's what K-means clustering is all about. The term K is basically a number. So we need to tell the system how many clusters we need to perform. So if K is equal to 2, there will be 2 clusters. If K is equal to 3, it's 3 clusters, and so on and so forth. That's what the K stands for. And of course, there is a way of finding out what is the best or optimum value of K for a given data. We will look at that. So that is K-means clustering. So let's take an example. K-means clustering is used in many scenarios, but let's take an example of cricket, the game of cricket. Let's say you received data of a lot of players from maybe all over the country or all over the world, and this data has information about the runs scored by the people or by the player and the wickets taken by the player. And based on this information, we need to cluster this data into 2 clusters, batsmen and bowlers. So this is an interesting example. Let's see how we can perform this. So we have the data which consists of primarily 2 characteristics, which is the runs and the wickets. So the bowlers basically take wickets and the batsmen score runs. There will be, of course, a few bowlers who can score some runs, and similarly there will be some batsmen who would have taken a few wickets. But with this information, we want to cluster those players into batsmen and bowlers. So how does this work? Let's say this is how the data is. So there is information on the y-axis about the runs scored, and on the x-axis about the wickets taken by the players. So if we do a quick plot, this is how it would look. And when we do the clustering, we need to have the clusters like shown in the third diagram out here. So we need to have a cluster which consists of people who have scored high runs, which is basically the batsmen, and then we need a cluster with people who have taken a lot of wickets, which is typically the bowlers. There may be a certain amount of overlap, but we will not talk about it right now. So with k-means clustering, we will have here, that means k is equal to 2, and we will have two clusters, which is batsmen and bowlers. So how does this work? The way it works is, the first step in k-means clustering is the allocation of two centroids randomly. So 2 points are assigned as so-called centroids. So in this case, we want 2 clusters, which means k is equal to 2. So 2 points have been randomly assigned as centroids. Keep in mind, these points can be anywhere. They are random points. They are not really the centroids. Centroid means it's a central point of a given data set, but in this case, when it starts off, it's not really the centroid. Okay, so these points, though in our presentation here we have shown them 1 point closer to these data points and another closer to these data points, they can be assigned randomly anywhere. Okay, so that's the first step. The next step is to determine the distance of each of the data points from each of the randomly assigned centroids. So for example, we take this point and find the distance from this centroid and the distance from this centroid. This point is taken and the distance is found from this centroid and this centroid, and so on and so forth. So for every point, the distance is measured from both the centroids, and then whichever distance is less, that point is assigned to that centroid. So for example, in this case, visually it is very obvious that all these data points are assigned to this centroid and all these data points are assigned to this centroid. And that's what is represented here in blue color and in this yellow color. The next step is to actually determine the central point or the actual centroid for these two clusters. So we have this one initial cluster, this one initial cluster, but as you can see, these points are not really the centroid. Centroid means it should be the central position of this data set, central position of this data set. So that is what needs to be determined as the next step. So the central point or the actual centroid is determined and the original randomly allocated centroid is repositioned to the actual centroid of this new clusters. And this process is actually repeated. Now what might happen is some of these points may get reallocated. In our example, that is not happening probably, but it may so happen that the distance is found between each of these data points once again with these centroids. And if it is required, some points may be reallocated. We will see that in a later example, but for now we will keep it simple. So this process is continued till the centroid repositioning stops, and that is our final cluster. So this is so after iteration, we come to this position, this situation where the centroid doesn't need any more repositioning, and that means our algorithm has converged. Convergence has occurred, and we have the cluster, two clusters, we have the clusters with a centroid. So this process is repeated. The process of calculating the distance and repositioning the centroid is repeated till the repositioning stops, which means that the algorithm has converged and we have the final cluster with the data points and the centroids. So this is what you're going to learn from this session. We will talk about the types of clustering, what is k-means clustering, application of k-means clustering. K-means clustering is done using distance measure, so we will talk about the common distance measures. And then we will talk about how k-means clustering works and go into the details of k-means clustering algorithm. And then we will end with a demo and a use case for k-means clustering. So let's begin. First of all, what are the types of clustering? There are primarily two categories of clustering: hierarchical clustering and then partitional clustering. And each of these categories are further subdivided into agglomerative and divisive clustering and k-means and fuzzy c-means clustering. Let's take a quick look at what each of these types of clustering are. In hierarchical clustering, the clusters have a tree-like structure, and hierarchical clustering is further divided into agglomerative and divisive. Agglomerative clustering is a bottom-up approach. We begin with each element as a separate cluster and merge them into successively larger clusters. So for example, we have A, B, C, D, E, F. We start by combining B and C, form one cluster, D, E, and E, form one more. Then we combine D, E, and F, one more bigger cluster, and then add B, C to that, and then finally A to it. Compared to that, divisive clustering or divisive clustering is a top-down approach. We begin with the whole set and proceed to divide it into successively smaller clusters. So we have A, B, C, D, E, F. We first take that as a single cluster and then break it down into A, B, C, D, E, and F. Then we have partitional clustering split into two subtypes, k-means clustering and fuzzy c-means. In k-means clustering, the objects are divided into the number of clusters mentioned by the number k. That's where the k comes from. So if we say k is equal to 2, the objects are divided into two clusters, C1 and C2. And the way it is done is the features or characteristics are compared, and all objects having similar characteristics are clubbed together. So that's how k-means clustering is done. We will see it in more detail as we move forward. And fuzzy c-means is very similar to k-means in the sense that it clubs objects that have similar characteristics together. But while in k-means clustering, two objects cannot belong to, or any object, a single object cannot belong to two different clusters, in c-means objects can belong to more than one cluster. So that is the primary difference between k-means and fuzzy c-means. So what are some of the applications of k-means clustering? K-means clustering is used in a variety of examples or variety of business cases in real life, starting from academic performance, diagnostic systems, search engines, and wireless sensor networks, and many more. So let us take a little deeper look at each of these examples. Academic performance. So based on the scores of the students are categorized into A, B, C, and so on. Clustering forms a backbone of search engines. When a search is performed, the search results need to be grouped together. The search engines very often use clustering to do this. And similarly, in case of wireless sensor networks, the clustering algorithm plays the role of finding the cluster heads, which collects all the data in its respective cluster. So clustering, especially k-means clustering, uses distance measure. So let's take a look at what is distance measure. So while these are the different types of clustering, in this video we will focus on k-means clustering. So distance measure tells how similar some objects are. So the similarity is measured using what is known as distance measure. And what are the various types of distance measures? There is Euclidean distance, there is Manhattan distance, then we have squared Euclidean distance measure and cosine distance measure. These are some of the distance measures supported by k-means clustering. Let's take a look at each of these. What is Euclidean distance measure? This is nothing but the distance between 2 points. So we have learnt in high school how to find the distance between 2 points. This is a little sophisticated formula for that, but we know a simpler one is square root of y2 minus y1 whole square plus x2 minus x1 whole square. So this is an extension of that formula. So that is the Euclidean distance between 2 points. What is the squared Euclidean distance measure? It's nothing but the square of the Euclidean distance, as the name suggests. So instead of taking the square root, we leave the square as it is. And then we have Manhattan distance measure. In case of Manhattan distance, it is the sum of the distances across the x-axis and the y-axis. And note that we are taking the absolute value so that the negative values don't come into play. So that is the Manhattan distance measure. Then we have cosine distance measure. In this case, we take the angle between the two vectors formed by joining the points from the origin. So that is the cosine distance measure. Okay, so that was a quick overview about the various distance measures that are supported by k-means. Now let's go and check how exactly k-means clustering works. Okay, so this is how k-means clustering works. This is like a flowchart of the whole process. There is a starting point, and then we specify the number of clusters that we want. Now there are a couple of ways of doing this. We can do by trial and error. So we specify a certain number, maybe k is equal to 3 or 4 or 5 to start with, and then as we progress we keep changing until we get the best clusters. Or there is a technique called elbow technique whereby we can determine the value of k. What should be the best value of k? How many clusters should be formed? So once we have the value of k, we specify that, and then the system will assign that many centroids. So it picks randomly that to start with randomly that many points that are considered to be the centroids of these clusters. And then it measures the distance of each of the data points from these centroids and assigns those points to the corresponding centroid from which the distance is minimum. So each data point will be assigned to the centroid which is closest to it. And thereby we have k number of initial clusters. However, this is not the final clusters. The next step it does is for the new groups, for the clusters that have been formed, it calculates the mean position, thereby calculates the new centroid position. The position of the centroid moves compared to the randomly allocated one. So it's an iterative process. Once again, the distance of each point is measured from this new centroid point, and if required, the data points are reallocated to the new centroids, and the mean position or the new centroid is calculated once again. If the centroid moves, then the iteration continues, which means the convergence has not happened. The clustering has not converged. So as long as there is a movement of the centroid, this iteration keeps happening. But once the centroid stops moving, which means that the cluster has converged or the clustering process has converged, that will be the end result. So now we have the final position of the centroid, and the data points are allocated accordingly to the closest centroid. I know it's a little difficult to understand from this simple flowchart, so let's do a little bit of visualization and see if we can explain it better. Let's take an example. If we have a data set for a grocery shop. So let's say we have a data set for a grocery shop, and now we want to find out how many clusters this has to be spread across. So how do we find the optimum number of clusters? There is a technique called the elbow method. So when these clusters are formed, there is a parameter called within sum of squares, and the lower this value is, the better the cluster is. That means all these points are very close to each other. So we use this within sum of squares as a measure to find the optimum number of clusters that can be formed for a given data set. So we create clusters, or we let the system create clusters of a variety of numbers, maybe of 10 clusters, and for each value of k, the within SS is measured, and the value of k which has the least amount of within SS or WSS, that is taken as the optimum value of k. So this is the diagrammatic representation. So we have on the y-axis the within sum of squares or WSS, and on the x-axis we have the number of clusters. So as you can imagine, if you have k is equal to 1, which means all the data points are in a single cluster, the within SS value will be very high because they are probably scattered all over. The moment you split it into 2, there will be a drastic fall in the within SS value. And that's what is represented here. But then as the value of k increases, the rate of decrease will not be so high. It will continue to decrease, but probably the rate of decrease will not be high. So that gives us an idea. So from here, we get an idea, for example, the optimum value of k should be either 2 or 3 or at the most 4. But beyond that, increasing the number of clusters is not dramatically changing the value in WSS because that pretty much gets stabilized. Okay, now that we have got the value of k, and let's assume that these are our delivery points, the next step is basically to assign two centroids randomly. So let's say C1 and C2 are the centroids assigned randomly. Now the distance of each location from the centroid is measured, and each point is assigned to the centroid which is closest to it. So for example, these points are very obvious that these are closest to C1, whereas this point is far away from C2. So these points will be assigned, which are close to C1 will be assigned to C1, and these points or locations which are close to C2 will be assigned to C2. And then, so this is how the initial grouping is done. This is part of C1 and this is part of C2. Then the next step is to calculate the actual centroid of this data, because remember, C1 and C2 are not the centroids. They've been randomly assigned points, and only thing that has been done was the data points which are closest to them have been assigned to them. But now in this step, the actual centroid will be calculated, which may be for each of these data sets somewhere in the middle. So that's like the mean point that will be calculated. And the centroid will actually be positioned or repositioned there. Same with C2. So the new centroid for this group is C2 in this new position, and C1 is in this new position. Once again, the distance of each of the data points is calculated from these centroids. Now remember, it's not necessary that the distance still remains or each of these data points still remain in the same group. By recalculating the distance, it may be possible that some points get reallocated. Like so. You see this? So this point earlier was closer to C2 because C2 was here. But after recalculating, repositioning, it is observed that this is closer to C1 than C2. So this is the new grouping. So some points will be reassigned. And again, the centroid will be calculated, and if the centroid doesn't change, so that is a repetitive process, iterative process. And if the centroid doesn't change, once the centroid stops changing, that means the algorithm has converged. And this is our final cluster with this as the centroid, C1 and C2 as the centroids, these data points as a part of each cluster. So I hope this helps in understanding the whole process, iterative process of k-means clustering. So let's take a look at the k-means clustering algorithm. Let's say we have x1, x2, x3, n number of points as our inputs, and we want to split this into k clusters, or we want to create k clusters. So the first step is to randomly pick k points and call them centroids. They are not real centroids because centroid is supposed to be a center point, but they are just called centroids. And we calculate the distance of each and every input point from each of the centroids. So the distance of x1 from C1, from C2, C3, each of the distances we calculate. And then find out which distance is the lowest and assign x1 to that particular random centroid. Repeat that process for x2. Calculate its distance from each of the centroids C1, C2, C3 up to Ck, and find which is the lowest distance and assign x2 to that particular centroid. Same with x3 and so on. So that is the first round of assignment that is done. Now we have k groups because we have assigned a value of k. So there are k centroids, and so there are k groups. All these inputs have been split into k groups. However, remember, we picked the centroids randomly, so they are not real centroids. So now what we have to do? We have to calculate the actual centroids for each of these groups, which is like the mean position. which means that the position of the randomly selected centroids will now change, and they will be the mean positions of these newly formed K groups. And once that is done, we once again repeat this process of calculating the distance, right? So this is what we are doing as a part of step 4. We repeat step 2 and 3. So we again calculate the distance of x1 from the centroid C1, C2, C3, and then see which is the lowest value and assign x1 to that. Calculate the distance of x2 from C1, C2, C3 or whatever up to ck, and find whichever is the lowest distance and assign x2 to that centroid, and so on. In this process, there may be some reassignment. X1 was probably assigned to cluster C2, and after doing this calculation, maybe now x1 is assigned to C1. So that kind of reallocation may happen. So we repeat the steps 2 and 3 till the position of the centroids don't change or stop changing. And that's when we have convergence. So let's take a detailed look at each of these steps. So we randomly pick K cluster centers. We call them centroids because they are not really the centroids. So let us name them C1, C2 up to CK. And then step 2, we assign each data point to the closest center. So what we do, we calculate the distance of each X value from each C value. So the distance between x1, c1, distance between x1, c2, x1, c3, and then we find which is the lowest value, right? That's the minimum value we find, and assign x1 to that particular centroid. Then we go next to x2, find the distance of x2 from c1, x2 from c2, x2 from c3, and so on up to ck, and then assign it to the point or to the centroid which has the lowest value, and so on. So that is step number 2. In step number 3, we now find the actual centroid for each group. So what has happened? As a part of step number 2, we now have all the points, all the data points grouped into K groups because we wanted to create K clusters, right? So we have K groups. Each one may be having a certain number of input values. They need not be equally distributed, by the way. Based on the distance, we will have K groups. But remember, the initial values of the C1, C2 were not really the centroids of these groups, right? We assigned them randomly. So now in step 3, we actually calculate the centroid of each group, which means the original point which we thought was the centroid will shift to the new position which is the actual centroid for each of these groups. Okay? And we again calculate the distance. So we go back to step 2, which is what? We calculate again the distance of each of these points from the newly positioned centroids. And if required, we reassign these points to the new centroids. So as I said earlier, there may be a reallocation. So we now have a new set or a new group. We still have K groups, but the number of items and the actual assignment may be different from what was in step 2 here. Okay, so that might change. Then we perform step 3 once again to find the new centroid of this new group. So we have again a new set of clusters, new centroids, and new assignments. We repeat this step 2 again. Once again we find, and then it is possible that after iterating through 3 or 4 or 5 times, the centroid will stop moving, in the sense that when you calculate the new value of the centroid, that will be same as the original value, or there will be very marginal change. So that is when we say convergence has occurred, and that is our final cluster. That's the formation of the final cluster. Alright, so let's see a couple of demos of K-means clustering. We will actually see some live demos in Python Notebook using Python Notebook. But before that, let's find out what's the problem that we are trying to solve. The problem statement is, let's say Walmart wants to open a chain of stores across the state of Florida.
and it wants to find the optimal store locations. Now the issue here is if they open too many stores close to each other, obviously they will not make profit. But if the stores are too far apart, then they will not have enough sales. So how do they optimize this? Now, for an organization like Walmart, which is an e-commerce giant, they already have the addresses of their customers in their database. So they can actually use this information or this data and use k-means clustering to find the optimal location. Now, before we go into the Python notebook and show you the live code, I wanted to take you through very quickly a summary of the code in the slides, and then we will go into the Python notebook. So in this block, we are basically importing all the required libraries like NumPy, Matplotlib, and so on. And we are loading the data that is available in the form of, let's say, the addresses. For simplicity's sake, we will just take them as some data points. Then the next thing we do is quickly do a scatter plot to see how they are related to each other with respect to each other. So in the scatter plot, we see that there are a few distinct groups already being formed. So you can actually get an idea about how the cluster would look and how many clusters, what is the optimal number of clusters. And then starts the actual k-means clustering process. So we will assign each of these points to the centroids and then check whether they are the optimal distance, which is the shortest distance, and assign each of the points, data points, to the centroids, and then go through this iterative process till the whole process converges. And finally, we get an output like this. So we have 4 distinct clusters, and which is, we can say that this is how the population is probably distributed across Florida state, and the centroids are like the location where the store should be, the optimum location where the store should be. So that's the way we determine the best locations for the store, and that's how we can help Walmart find the best locations for their stores in Florida. So now let's take this into Python notebook. Let's see how this looks when we are running the code live. Alright, so this is the code for k-means clustering in Jupyter Notebook. We have a few examples here which we will demonstrate how k-means clustering is used, and even there is a small implementation of k-means clustering as well. Okay, so let's get started. Okay, so this block is basically importing the various libraries that are required, like Matplotlib and NumPy and so on and so forth, which would be used as a part of the code. Then we are going and creating blobs which are similar to clusters. Now this is a very neat feature which is available in Scikit-learn. Make blobs is a nice feature which creates clusters of data sets. So that's a wonderful functionality that is readily available for us to create some test data kind of thing. Okay, so that's exactly what we are doing here. We are using make blobs, and we can specify how many clusters we want. So centers we are mentioning here. So it will go ahead, and so we just mentioned 4. So it will go ahead and create some test data for us. And this is how it looks. As you can see visually, also we can figure out that there are 4 distinct classes or clusters in this data set, and that is what make blobs actually provides. Now from here onwards, we will basically run the standard k-means functionality that is readily available. So we really don't have to implement k-means itself. The k-means functionality or the function is readily available. You just need to feed the data and we'll create the clusters. So this is the code for that. We import k-means, and then we create an instance of k-means, and we specify the value of k. This n underscore clusters is the value of k. Remember, k-means, in k-means, k is basically the number of clusters that you want to create, and it is a integer value. So this is where we are specifying that. So we have k is equal to 4, and so that instance is created. We take that instance, and as with any other machine learning functionality. Fit is what we use, the function or the method rather, fit is what we use to train the model. Here there is no real training kind of thing, but that's the call. Okay, so we are calling fit, and what we are doing here, we are just passing the data. So X has these values, the data that has been created, right? So that is what we are passing here. And this will go ahead and create the clusters, and then we are using, after doing fit, we run a predict, which basically assigns for each of these observations which cluster it belongs to. All right, so it will name the clusters. Maybe this is cluster 1, this is 2, 3, and so on, or I will actually start from 0, cluster 0, 1, 2, and 3 maybe, and then for each of the observations it will assign based on which cluster it belongs to, it will assign a value. So that is stored in y_k-means. When we call predict, that is what it does. And we can take a quick look at these y_k-means, or the cluster numbers that have been assigned for each observation. So this is the cluster number assigned for observation 1, maybe this is for observation 2, observation 3, and so on. So we have how many? About, I think, 300 samples, right? So all the 300 samples, there are 300 values here. Each of them, the cluster number is given, and the cluster number goes from 0 to 3. So there are 4 clusters, so the numbers go from 0, 1, 2, 3. So that's what is seen here. Okay, now, so this was a quick example of generating some dummy data and then clustering that. Okay, and this can be applied if you have proper data. You can just load it up into X, for example, here, and then run the k-means. So this is the central part of the k-means clustering program example. So you basically create an instance, and you mention how many clusters you want by specifying this parameter n_clusters, and that is also the value of k, and then pass the data to get the values. Now, the next section of this code is the implementation of a k-means. Now, this is kind of a rough implementation of the k-means algorithm. So we will just walk you through, I will walk you through the code at each step what it is doing, and then we will see a couple of more examples of how k-means clustering can be used in maybe some real life examples, real life use cases. All right. So in this case here, what we are doing is basically implementing the k-means clustering, and there is a function or a library calculates for a given 2 pairs of points. It will calculate the distance between them and see which one is the closest and so on. So this is pretty much like what k-means does, right? So it calculates the distance of each point or each data set from predefined centroid, and then based on whichever is the lowest, this particular data point is assigned to that centroid. So that is basically available as a standard function, and we will be using that here. So as explained in the slides, the first step that is done in case of k-means clustering is to randomly assign some centroids. So as a first step, we randomly allocate a couple of centroids, which we call here, we are calling as centers. And then we put this in a loop and we take it through an iterative process. For each of the data points, we first find out using this function pairwise distance argument. For each of the points, we find out which center or which randomly selected centroid is the closest. And accordingly, we assign that data or the data point to that particular centroid or cluster. And once that is done for all the data points, we calculate the new centroid by finding out the mean position with the center position, right? So we calculate the new centroid, and then we check if the new centroid is the coordinates or the position is the same as the previous centroid. The positions we will compare, and if it is the same, that means the process has converged. So remember, we do this process till the centroids or the centroid doesn't move anymore, right? So the centroid gets relocated each time this reallocation is done. So the moment it doesn't change anymore, the position of the centroid doesn't change anymore, we know that convergence has occurred. So till then, so you see here, this is like an infinite loop. While true is an infinite loop, it only breaks when the centers are the same. The new center and the old center positions are the same. And once that is done, we return the centers and the labels. Now, of course, as explained, this is not a very sophisticated and advanced implementation, very basic implementation, because one of the flaws in this is that sometimes what happens is the centroid, the position will keep moving, but in the change will be very minor. So in that case, also that is actually convergence. Right? So for example, the change is 0.0001. We can consider that as convergence. Otherwise, what will happen is this will either take forever or it will be never ending. So that's a small flaw here. So that is something, additional checks may have to be added here. But again, as mentioned, this is not the most sophisticated implementation. This is like a kind of a rough implementation of the k-means clustering. Okay, so if we execute this code, this is what we get as the output. So this is the definition of this particular function, and then we call that find underscore clusters, and we pass our data x and the number of clusters, which is 4. And if we run that and plot it, this is the output that we get. So this is, of course, each cluster is represented by a different color. So we have a cluster in green color, yellow color, and so on and so forth. And these big points here, these are the centroids. This is the final position of the centroids. And as you can see visually also, this appears like a kind of a center of all these points here, right? Similarly, this is like the center of all these points here, and so on. So this is the example, or this is an example of an implementation of k-means clustering. And next we will move on to see a couple of examples of how k-means clustering is used in maybe some real life scenarios or use cases. In the next example or demo, we are going to see how we can use k-means clustering to perform color compression. We will take a couple of images, so there will be 2 examples, and we will try to use k-means clustering to compress the colors. This is a common situation in image processing when you have an image with millions of colors, but then you cannot render it on some devices which may not have enough memory. So that is the scenario where something like this can be used. So before again we go into the Python notebook, let's take a look at quickly the code. As usual, we import the libraries and then we import the image, and then we will flatten it. So the reshaping is basically, we have the image information is stored in the form of pixels, and if the image is like, for example, 427 by 640 and it has 3 colors, so that's the overall dimension of the initial image. We just reshape it and then feed this to our algorithm, and this will then create clusters of only 16 clusters. So these colors, there are millions of colors, and now we need to bring it down to 16 colors. So we use k is equal to 16, and this is how, when we visualize, this is how it looks. These are all about 16 million possible colors. The input color space has 16 million possible colors, and we just compress it to 16 colors. So this is how it would look when we compress it to 16 colors, and this is how the original image looks, and after compression to 16 colors, this is how the new image looks. As you can see, there is not a lot of information that has been lost, though the image quality is definitely reduced a little bit. So this is an example which we are going to now see in Python notebook. Let's go into the Python notebook. And once again, as always, we will import some libraries and load this image called flower.jpg. Okay, so we'll load that, and this is how it looks. This is the original image, which has, I think, 16 million colors, and this is the shape of this image, which is basically, what is the shape is nothing but the overall size, right? So this is 427 pixel by 640 pixel, and then there are 3 layers, which is this 3 basically is for RGB, which is red, green, blue. So color image will have that, right? So that is the shape of this. Now what we need to do is data. Let's take a look at how data is looking. So let me just create a new cell and show you what is in data. Basically, we have captured this information. So data is what, let me just show you here. All right, so let's take a look at China. What are the values in China? And if we see here, this is how the data is stored. This is nothing but the pixel values. Okay, so this is like a matrix, and each one has about for this 427 by 640 pixels. All right, so this is how it looks. Now the issue here is these values are large, the numbers are large, so we need to normalize them to between 0 and 1. Right, so that's why we will basically create one more variable, which is data, which will contain the values between 0 and 1, and the way to do that is divide by 255. So we divide China by 255 and we get the new values in data. So let's just run this piece of code, and this is the shape. So we now have also, what we have done is we changed using reshape, we converted into the 3-dimensional into a 2-dimensional data set. And let us also take a look at how, let me just insert probably a cell here and take a look at how data is looking. All right, so this is how data is looking, and now you see this is the values are between 0 and 1. Right, so if you earlier noticed, in case of China, the values were large numbers. Now everything is between 0 and 1. This is one of the things we need to do. All right, so after that, the next thing that we need to do is to visualize this, and we can take random set of maybe 10,000 points and plot it and check and see how this looks. So let us just plot this. And so this is how the original, the color, the pixel distribution is. These are two plots. One is red against green and another is red against blue. And this is the original distribution of the color. So then what we will do is we will use k-means clustering to create just 16 clusters for the various colors and then apply that to the image. Now, what will happen is, since the data is large because there are millions of colors, using regular k-means may be a little time consuming. So there is another version of k-means which is called mini batch k-means. So we will use that, which processes in the overall concept remains the same, but this basically processes it in smaller batches. That's the only thing. Okay, so the results will pretty much be the same. So let's go ahead and execute this piece of code and also visualize this so that we can see that there are this is how the 16 colors would look. So this is red against green and this is red against blue. There is quite a bit of similarity between this original color schema and the new one, right? So it doesn't look very completely different or anything like that. Now we apply the newly created colors to the image, and we can take a look how this is looking now. We can compare both the images. So this is our original image and this is our new image. So as you can see, there is not a lot of information that has been lost. It pretty much looks like the original image. Yes, we can see that, for example, here there is a little bit, it appears a little dullish compared to this one, right? Because we kind of took off some of the finer details of the color, but overall the high level information has been maintained. At the same time, the main advantage is that now this is an image which can be rendered on a device which may not be that very sophisticated. Now let's take one more example with a different image. In the second example, we will take an image of the summer palace in China, and we repeat the same process. This is a high definition color image with millions of colors and also 3-dimensional. Now we will reduce that to 16 colors using k-means clustering, and we do the same process like before. We reshape it and then we cluster the colors to 16, and then we render the image once again, and we will see that the quality of the image slightly deteriorates. As you can see here, this has much finer details in this which are probably missing here, but then that's the compromise because there are some devices which may not be able to handle
this kind of high density images. So let's run this code in Python notebook. Alright, so let's apply the same technique for another picture, which is even more intricate and has probably much complicated color schema. So this is the image. Now once again, we can take a look at the shape, which is 427 by 640 by 3. And this is the new data would look somewhat like this compared to the flower image. So we have some new values here. And we will also bring this, as you can see, the numbers are much big, so we will much bigger, so we will now have to scale them down to values between 0 and 1, and that is done by dividing by 255. So let's go ahead and do that and reshape it. Okay, so we get a two-dimensional matrix. And we will then, as a next step, we will go ahead and visualize this, how it looks, the 16 colors. And this is basically how it would look, 16 million colors. And now we can create the clusters out of this. The 16 k-means clusters we will create. So this is how the distribution of the pixels would look with 16 colors. And then we go ahead and apply this and visualize how it is looking for with the new just the 16 colors. So once again, as you can see, this looks much richer in color, but at the same time, and this probably doesn't have, as we can see, it doesn't look as rich as this one, but nevertheless the information is not lost, the shape and all that stuff. And this can be also rendered on a slightly a device which is probably not that sophisticated. Okay, so that's pretty much it. So we have seen two examples of how color compression can be done using k-means clustering, and we have also seen in the previous examples of how to implement k-means, the code to roughly how to implement k-means clustering, and we use some sample data using blob to just execute the k-means clustering.
Ever wondered how hands-on projects can land you your dream job in machine learning? Whether you're eyeing internships or full-time positions, recruiters are always on the lookout for one real thing: real experience. And the best way to showcase that? Machine learning projects. In today's video, we'll dive into 5 amazing machine learning project ideas that will not only sharpen your skills, but will also make your portfolio shine. Each project brings a unique challenge, and mastering them will set you apart in the competitive machine learning job market. So let's get started and explore how these projects can transform your career. And remember, for each project, you can find all the resources and starter code in the description below. Let's kick things off with something really practical and highly relevant: real-time face mask detection. Now you must be thinking, why focus on this? Well, imagine a world where AI helps us ensure safety in public spaces, especially during health crises like pandemics. With the rise of computer vision, we can make that happen. In this project, you will work with tools like OpenCV and TensorFlow to create a model that detects whether people are wearing face masks in real time or using live camera feeds. You'll learn how to process images on the fly and handle real-time data, which is crucial in many industries like security, healthcare, and public safety. This project will also give you a solid foundation in computer vision, something every machine learning enthusiast will be comfortable with. Check the description below for all the resources and starter code to build the project. Now that you've got a hang on the computer vision part, you're probably curious on how to build something that feels more personal. That's where our second project comes in: movie recommendation system. You've probably used Netflix or YouTube's recommendation engine, right? It's a great example of machine learning in action, giving you a personalized suggestion based on your tastes. In this project, you will build your own recommendation system using Python, Pandas, and Scikit-learn. You'll explore 2 powerful techniques, that is content-based filtering and collaborative filtering, where content-based filtering uses movie details and collaborative filtering leverages user behavior. This is the perfect way to practice working with large data sets, learning about recommendation algorithms, and fine-tuning models to deliver the best results. Find the resources and starter code for the project in the description below. Next, let's tackle something that could really level up your skills for the job market itself. How about an AI resume matcher? Have you ever wondered how companies sit through hundreds of resumes to find the perfect candidate? Well, now you'll learn how to build that system. You'll use powerful natural language processing tools like Spacey and BERT to match job descriptions with the best fitting resumes. By deploying the system with Streamlit, you'll also get the hands-on experience with web deployment. This project is great for practicing NLP, learning about the intricacies of text processing, and giving you a tool that HR systems could actually use in their hiring process. Plus, it's a fantastic addition to your portfolio. Check out the description for all the resources and starter code for this project. Now let's move on to something that's both timely and impactful: fake news detection. In a world flooded with information, distinguishing fact from fiction has never been more important. With this project, you will dive into text classification, training a model that detects fake news articles based on patterns in language. By using NLP pipelines and tools like Logistic regression and BERT, you'll learn how to clean and process datasets, a vital skill when working with unstructured text. Not only will you gain expertise in handling text data, but you will also understand how to evaluate models using metrics like accuracy, precision, and recall, which are critical skills for any machine learning practitioner. You'll find all the relevant resources and starter code for this project in the description below. Finally, let's get into something that's a bit more advanced but super exciting: stock price prediction using LSTM. You've probably heard about financial models predicting stock prices, but what does it really take to build one? In this project, you will use LSTM, which is long short-term memory networks, a type of deep learning model specifically designed for time series forecasting. Using TensorFlow and financial APIs, you'll build a model that predicts future stock prices based on historical data. You will also know how to handle both real-time and historical data, perform scaling, and evaluate the model's performance. This project will give you an in-depth knowledge of deep learning as well as how it applies to financial forecasting, a field that's booming with opportunities. All the resources and starter code for the project are linked in the description below. Here are some bonus tips and project deployment. Now that you've built your project, you're probably wondering, how do I show them off? Don't worry, we've got you covered. It's time to talk about the deployment and presentation. Once your projects are polished, hosting them onto GitHub is a great way to showcase your work to potential employers. You can also deploy your models with platforms like Streamlit, Flask, or even Heroku, turning them into interactive web applications so that others can try them out. And don't forget to highlight these projects on your resume and LinkedIn profile. This is your opportunity to show off your practical skills, and when interviewers ask you about your experience, you'll be able to talk about real, live projects that you've worked on. For all the deployment tools and resources, make sure to check out the links in the description. And that's a wrap. We've explored 5 amazing machine learning projects that not only sharpen your skills, but also boost your employability. Whether you're interested in computer vision, natural language processing, or time series forecasting, there's a project for you. Now it's time to get you building. Which project are you excited to tackle first? Let us know in the comments below.
So let's start with beginner level questions, and number 1 is, what is machine learning? So machine learning is a subset of artificial intelligence that involves the use of algorithms and statistical models to enable computers to perform tasks without explicit instructions, that is by relying on patterns and interference. And now moving to number 2nd question, that is, what are the different types of machine learning? So the 3 main types of machine learning are, number 1 is supervised learning, and then comes unsupervised learning, and then there is reinforcement learning. Now moving to next question, that is 3rd, that is, what is supervised learning? So supervised learning involves training a model on a labeled dataset, which means each training example is paired with an output label. The model learns to predict the output from the input data. Now moving to the 4th question, that is, what is unsupervised learning? So unsupervised involves training a model on data that does not have labeled responses. The model tries to learn the patterns and the structure from the input data. So guys, these are the beginner level questions, and now we'll move to the 5th question, that is, what is reinforcement learning? So reinforcement learning is a type of machine learning where an agent learns to make decisions by performing actions and receiving rewards or penalties. The goal is to maximize the cumulative reward. So now moving to the 6th question, that is, what is a model in machine learning? So a model in machine learning is a mathematical representation of a real-world process. It is trained on data to recognize patterns and make predictions or decisions based on new data. So now moving to 7th question, that is, what is overfitting? So overfitting occurs when a machine learning model performs well on the training data, but poorly on new unseen data. It indicates that the model has learned the noise and details in the training data instead of the actual patterns. So now coming to question number 8, that is what is underfitting. So underfitting occurs when a machine learning model is too simple to capture the underlying patterns in the data. It performs poorly on both the training data and new data. Now move to the next question, that is ninth question, and the question is what is a confusion matrix? So confusion matrix is a table used to evaluate the performance of a classification model. It summarizes the number of correct and incorrect predictions made by the model, and that is categorized by each class. Now moving to the 10th question, that is what is cross validation. So cross validation is a technique for assessing how the results of a statistical analysis will generalize to an independent dataset. It involves partitioning the data into subsets, training the model on some subsets and validating it on the remaining subsets. So this was all about, that is the 10th question or the overall 1 to 10 questions for beginner level. Now we'll move to intermediate level, and here we'll cover 10 questions. So we'll start with 11th question, that is what is a ROC curve. So ROC, that is receiver operating characteristic curve. It is a graphical representation of a classifier's performance across different thresholds. It plots the true positive rate, that is TPR, against a false positive rate, that is FPR. Now moving to 12th question, that is what is precision and recall. So precision is the ratio of correctly predicted positive observations to the total predicted positives. And recall is the ratio of correctly predicted positive observations to all actual positives. So the formula is precision equal to TP slash TP plus FP, and the recall is TP slash TP plus FN. So now we'll move to the 13th question, that is what is the F1 score. So the F1 score is the harmonic mean of precision and recall. It provides a balance between the two metrics and is useful when you need to balance precision and recall. F1 score is equal to twice into precision into recall, and that is divided by precision plus recall. Now we'll move to 14th question, and here we will cover regularization. So the question is, what is regularization? So it is a technique used to prevent overfitting by adding a penalty to the model's complexity. And the common types of regularization include L1, that is lasso, and L2, ridge regularization. Now we'll move to the 15th question, that is what is the bias variance trade-off? So the bias variance trade-off is a fundamental issue in machine learning that involves balancing the error introduced by the model's assumptions and the error due to model complexity. So a good model should have low bias and low variance. Now we'll move to the question number 16, that is what is feature engineering. So feature engineering is the process of creating new features or modifying existing ones to improve the performance of a machine learning model. It involves techniques like normalization, encoding categorical variables, and creating interaction terms. So now we'll move to question number 17, and that is about gradient descent. So the question is, what is gradient descent? And your answer is, gradient descent is an optimization algorithm used to minimize the cost function in machine learning models, and it iteratively adjusts the model parameters in the direction of the steepest descent of the cost function. So with this, we'll move to the 18th question, and that will cover with the difference between bagging and boosting. So the question is, what is difference between bagging and boosting? And you could answer this with starting with bagging, that is bootstrap aggregating. That involves training multiple models on different subsets of the data and averaging their predictions. Then comes boosting, that involves training models sequentially with each new model focusing on correcting the errors of the previous ones. And then we have the question number 19, that is what is a decision tree? So a decision tree is a non-parametric supervised learning algorithm used for classification and regression. It splits the data into subsets based on the value of input features, resulting in a tree-like structure of decisions. Now we'll move to question number 20, that is what is a random forest. So random forest is an ensemble learning method that combines multiple decision trees to improve the accuracy and robustness of the model. It builds each tree using a random subset of features and data points, and then averages their predictions. So these were the questions that are for the intermediate level, and these are just the basic questions, or I will just say the theoretical questions that can be asked in an interview. So be prepared for that. Now we'll move to the advanced level interview questions, and we'll start with question number 21, and here also we'll cover the 10 questions. So number one question, or that is 21st question, and the question is, what is a support vector machine? So support vector machine is a supervised learning algorithm used for classification and regression. It finds the optimal hyperplane that maximizes the margin between different classes in the feature space. And then comes question number 22, that is, what is principal component analysis? So principal component analysis is a dimensionality reduction technique that transforms high dimensional data into a lower dimensional space by finding the directions, that is, principal components that maximize the variance in the data. And then comes the question number 23, that is, what is a neural network? So a neural network is a series of algorithms that attempt to recognize underlying relationships in a set of data through a process that mimics the way the human brain operates. It consists of layer of interconnected nodes or neurons. And then comes the question number 24, that is, what is deep learning? So deep learning is a subset of machine learning that involves neural networks with many layers, that is, deep neural networks, and it is particularly effective for tasks like image and speech recognition. Now I'll move to question number 25, that is, what is convolutional neural network, that is CNN. So we will start the answer by answering the interviewer that a convolutional neural network is a type of deep learning model specifically designed for processing structured grid data like images. It uses convolutional layers to extract spatial features or the spatial features and patterns from the input data. Now we'll move to the question number 26, that is, what is a recurrent neural network or RNN? So a recurrent neural network is a type of neural network designed for sequential data, and it has connections that form directed cycles, allowing it to maintain a memory of previous inputs and process sequences of data. So this was all about question number 26, and now we will cover the question number 27, that is, what is the difference between batch gradient descent and stochastic gradient descent. So batch gradient descent computes the gradient of the cost function using the entire training dataset, while stochastic gradient descent, that is SGD, computes the gradient using only one training example at a time. So SGD is faster but noisier. Now we'll move to question number 28, that is, what is dropout in neural networks. So dropout is a regularization technique used in neural networks to prevent overfitting, and it involves randomly setting a fraction of the neurons to zero during training, forcing the network to learn more robust features. And now we'll move to question number 29, and that will be about transfer learning. And your question is, what is transfer learning? So we'll answer this to the interviewer by starting that transfer learning is a technique in machine learning where a model developed for one task is reused as the starting point for a model on a second related task. It is particularly useful when there is limited data available for the second task. Now we'll move to the last question and the 30th question. So that is, what is a generative adversarial network, that is GAN? So you can start answering this. So generative adversarial network is a type of deep learning model consisting of two neural networks, a generator and a discriminator, that are trained simultaneously. The generator creates fake data while the discriminator tries to distinguish between real and fake data, leading to the generator producing increasingly realistic data. And these questions and answers are over, and these covers a wide range of topics in machine learning and should help prepare for interviews at various levels.
And with that, we have reached the end of this session on Machine Learning Engineer full course for beginners. Should you need any assistance or any other resources used in these sessions like PPTs, templates, GitHub links, project resource files, and others, then please let us know in the comment section below, and a team of experts will be happy to help you as soon as possible. Until next time, thank you and keep learning. Stay tuned for more from Simplilearn.